This is every single algebra lesson from start to finish. You'll also get to see how bad my lighting quality was when I started making videos. But anyway, I hope you enjoy. This is the Algebra full course. Before you start learning all sorts of complicated math, you first need to learn how to take a sentence in words and turn it into an equation that you can actually do math with. So we'll start with this example, which is 3 times the sum of 6 and a number. Now, we can point out some of the basic math operations, which are addition, subtraction, multiplication, and division, right? So immediately I'm seeing the word times here, which is going to mean multiplication, and I'm seeing sum, which is plus. Now, one thing that should stick out to you is the sum of. Whenever you see things like the sum of, or the difference of, or the product of, it's talking about one thing, right? So whenever you see the something of, that usually means parentheses. So we'll do that part first. So 6 plus, and now a number. Whenever it doesn't tell you what the number is in algebra, that means it's going to be a letter, a variable. You can use whatever letter you want. Most of the time in algebra, when we don't know a number, we use the letter x, but we can also use the letter n, because n for number, but you can literally use any letter. We'll just use the letter n for this. And then we have the last part, which is 3 times, and that will be 3 times everything else. So we'll do 3 times. Now this could just be the answer, but another way to write this in algebra is just without the multiplication sign. The reason for this being is in algebra, if you have two things next to each other without any sign in between, it just means multiplication, and it just kind of makes everything look nice and cleaner. So we're gonna go ahead and not put a sign here, and that will be our answer for this problem. All right, now here's another example for you. The quotient of 4 less than a number and 7. Now, the word quotient means division. And the important thing to remember is whenever you see the quotient of, or the sum of, or the difference of, you're usually going to have the word and in there somewhere, because there are 2 parts to it, and our 2 parts are 4 less than a number and 7. Those are our 2 parts. Now, we could use this division sign, but in algebra we usually just write it as a fraction. So we're going to have our fraction symbol, and the top of it is going to be the first part, which is 4 less than a number. Now, less than, you probably know, is subtraction. But this gets a little tricky, because you might be tempted to just say, okay, well, 4 less than a number, well, that's 4 minus n. But that's actually not the case. For example, let's say that your friend has $20, and you want to say that you have 4 less dollars than him. Find out how much money you have. You wouldn't say, all right, well, let's do 4 minus 20. You actually flip it around. You would say 20 minus 4, which is 16. And you would say, I have $16. So the word less than, you could call it a turnaround word or whatever. Basically, it just means that whenever you have less than, you need to flip the 2 numbers around. And you can just, this isn't something you have to memorize. You can just think of it logically in how you speak in real life, just like this situation here. So in this case, we're not going to put 4 minus n. We're actually going to put n minus 4. It's 4 less than n. And the bottom is easy. It's just the other part, the other side of the and, which is just 7. And there you go. Our answer in this case is n minus 4 over 7. Here's another problem. The product of the cube of a number and 3. Now what I'd like you to do, if you want to, is go ahead and pause the video and try this problem out for yourself, and then unpause and see how you did. Alright, so the product of the cube of a number and 3. Well, immediately I'm seeing the product of, which is a very common phrasing, the something of, right? So that immediately tells me that there's going to be an and, which there is, and there's going to be 2 parts to it. The cube of a number and 3. Those are our 2 parts. And the product means multiplication. So we are multiplying these 2 parts together. So the first part is the cube of a number. Well, we have a number, right? And then the cube of a number means to the 3rd power, because squared means to the 2nd power, cube means to the 3rd power. So whenever you see the cube of a number, that means to the 3rd power. So we write that with a little 3 here. And now we have the second part, and 3. It's just 3, right? So we can do times 3. Now, this can be our final answer. That is totally valid and fine. There are other ways we can write it. If you ever see problems with a dot, that's also a multiplication sign, and usually we use that in algebra instead of the x for the multiplication sign because the letter x is used so much anyway, and it can get things kind of confusing. So that's why we usually use a dot. Also, as I said before, if you just use no sign, like this, that's also acceptable because that means multiplication without a sign there. We usually put the number in front before the letter, but any of these answers are acceptable. Don't think that you have to do it a specific way unless your teacher says you have to for some reason. So now what if you have to do it the other way? What if you have to take an equation like this and turn it into a sentence? So let's look at this example, 5x equals 40. Well, if you couldn't tell just by me reading the question to you, I kind of just said the answer. 5 times x equals 40. That's it. This can be your answer. That's fine. That's totally acceptable. Of course, there are other ways you can write it. A lot of the times, if you look in your textbook, instead of the word equals, they'll put the word is. So in this case, we could say 5 times x is 40. That's the same thing as equals. Or if you want to sound really fancy and impress your teacher, you could put the product of 5 and we can even say like a number is 40. And now all of a sudden, you sound really fancy and you're so good at math. But yeah, all of these are acceptable. All right, here's another example of this, and what I'd like you to do is pause the video and try this one out for yourself. All right, so we have x plus 17 equals 34. Again, I basically just read the answer to you. X plus 17 equals 34. And that's it. That can be your answer. Or if you'd like the fancy, super smart sounding way of doing it, you can put our favorite phrase, the sum of x and 17 is 34. Two ways to write it. They're both fine. It's the first week of school and your teacher starts going over the properties of equality like reflexive, transitive, substitution. And you're probably asking yourself, what does this have to do with math? Well, I'm wondering the same thing, but let's do it anyway. So our first property of equality is the reflexive property. And the reflexive property is so obvious that it can be confusing. Reflexive says A equals A. So in other words, if you have the number 7, the reflexive property tells you that it is equal to 7. I didn't know this needed a name, but it does. It's called the reflexive property. So if you ever see something equal to itself, it's the reflexive property is the name for the rule that says you can do that. Next property of equality is the symmetric property, which is almost as obvious as the reflexive one. It says that if A equals B, then B equals A. So for example, let's say that we have x equals 7. Well, the symmetric property tells us that we can also write this as 7 equals x. It doesn't matter which side of the equal sign each one is on, it's just saying that they're equal. So in this case, both of these equations are correct. So now we get into the less obvious ones, which are transitive and substitution. So transitive basically says that if A equals B and B equals C, then A equals C. So if the first thing and the second thing are equal, and the second thing and the third thing are equal, then the first and the third thing must be the same, right? For example, let's say that we know that 5 is equal to x. So we know that 5 and x are the same. We also know that x and y are the same. X and y are equal. X equals y. In that case, we can combine these two statements and say that 5 is the same as y. Because 5 and x are the same, x and y are the same, so 5 and y must be the same. We're connecting the two equations together. And finally, we have the substitution property of equality. This basically says that if you have a and b and they're equal, then in any equation, a and b can replace each other because they're the same. So for example, let's say that we know that x and 5 are equal to each other. And then let's say we had some sort of complicated equation like x squared minus y cubed equals 4z. The equation's not important, but basically what the substitution property says is that we can replace x with 5 and 5 with x. So if we replaced x with 5 in this equation, we now have 5 squared minus y cubed equals 4 times z. These two equations right here are the same because you can replace x with 5 and 5 with x. So let's look at our first example of putting this to use. We're going to identify in each of these problems what property of equality we're dealing with. So here's the first one. I want you to think about those 4 different properties of equalities we talked about and come up with which one you think this represents. So go ahead and pause the video and try it yourself. All right, so 12 equals 12. And again, this should remind you of the very obvious one at the beginning, which says that a equals a, and that was called the reflexive property, which says that a equals a. That seems to fit this. 12 equals 12, a equals a. You know, they're the same thing, right? So this is dealing with the reflexive property. Here's another example that I'd like you to pause the video and try it yourself, and I'll warn you, it is a little tricky. So this is a more complicated one, so it's probably going to be one of the last two, which were transitive and substitution. And if you remember the transitive property, it said that if a equals b and b equals c, then a has to equal c. So does that fit this equation? Well, let's see. We have a minus 3 equals b, and we have b equals 8. We have our first thing, a minus 3, equaling our second thing, b. And the second thing, b, equals the third thing, 8. So in that case, we should be able to say that a minus 3 equals 8, because they're the same. And that fits this problem. So therefore, it's the transitive property, except that a lot of you might have said substitution. And this is where I start having problems with textbooks. You see, your textbook probably had a problem very similar to this, and it said, oh, it's the transitive property. But you might have also noticed, well, hey, we have a minus 3 equals b, and b is equal to 8, so they just replaced b with 8, and it works. Yeah, it represents 2 different properties of equality, so substitution would also be correct. And if you did something like this and your teacher marked you off for it, I would explain this to your teacher, because this does represent 2 different properties of equality. Here's another example. Go ahead and pause the video and try this. So we see here if 2x plus y equals 5 and y equals 7, then 2x plus 7 equals 5. This is going to be another one of those complicated ones, so we're going to probably pick from the last two, transitive and substitution. And if you look at it closely, you'll notice that the transitive property doesn't actually work here. We have 2x plus y equals 5, so 2x plus y is our first thing, and 5 is our second thing. But then our second equation, y equals 7. Well, yeah, 7 is our third thing or whatever, but y, that's a part of our first thing. So that's not really going to work with that specific formula. Instead, let's go ahead and look at the substitution property. The substitution property says that if we have 2 things equal to each other, then they can replace each other in equations. And if you see here, 2x plus 7 equals 5, what's the difference between this first equation and this new equation? Well, all we've done is we've replaced y with 7, and our second equation says that y equals 7. So what we've done is we've substituted y with 7. So therefore, we have the substitution property in this equation. Just the substitution property, nothing else. There's no tricks here. It's time to start solving algebra equations, but not this kind of equation. No, that's too complicated. You'll be able to do those eventually, but we need to start with the basics. So let's say you have this equation, x plus 3 equals 5, and you're told that you need to solve for x. Well, solving for a variable in algebra can be kind of scary, But the way you should think about an algebra problem is it's literally just a fill in the blank problem. So if I phrase the question as blank plus 3 equals 5, and I told you you need to fill in the blank with a number to make it true, you might be able to figure out in your head that the number that should go in this blank is 2, because 2 plus 3 is 5. So you might be able to just do this in your head, and yes, that's the answer, x equals 2. However, once we get into more complicated algebra equations, you're not going to be able to just do it in your head like that, right? So we need to have some sort of system to figure out these algebra problems. And luckily, we do have a system, and it's called isolating the variable, which is just a fancy way of saying we need to get x, the variable, by itself. We need to get the letter by itself. And by that we mean on by itself on this side of the equation. So x should be on the left side, or the right side, but either side is fine, and everything else should be on the other side. Now, how do we do that? Well, we can do anything we want to this equation. We can add, subtract, multiply, whatever, as long as you do it to both sides of the equation. So in this case, we want to do something to the left side of equation that's going to cancel out this plus 3. So let's do the opposite of plus 3. The opposite of adding 3 would be subtracting 3. So if we subtract 3, then we cancel out these two things. Because if I gave you $3 and then took it away, well, your total amount of money didn't change. And your feelings would probably hurt. But we have x on the left side of the equation. And now on the right side, we have to do the same thing to the right side of the equation, or else this equation is not true anymore, it doesn't work. So we're going to subtract 3 here as well. 5 minus 3 is 2. And so we have our final answer of x equals 2. Let's look at another example, 5x equals 15. Now, you may remember that in algebra, whenever we don't have a sign here, it's just a number and a letter next to each other, that means multiplication. So we can imagine a little multiplication sign here in between, because it's 5 times x when we don't have a sign. So we need to get x by itself on the left side of the equation and move everything to the right. So how can we get rid of this 5 and leave x by itself? No, we're not going to subtract 5 from both sides, because subtraction is not the opposite of multiplication. Before that worked with the addition, but in this case 5 is being multiplied by x, so we need to do the opposite of multiplication, which is division. Now remember, we need to do the division by 5 on both sides of the equation. So in this case, these 5's cancel out, and all we're left with is x. Well, that's great, but remember, the other side of the equation needs to get divided by 5 as well. So 15 divided by 5 is 3. And now we have x equals 3, and that's our answer. Here's another problem. What I'd like you to do is go ahead and pause the video and try this out for yourself, and then unpause and see how you did. Alright, so this is basically the same as our other problems, except we have a negative number in here, which might make things a little more complicated, but you'll see. So x minus 17 equals negative 5. We need to get x by itself. We need to isolate the variable. So in this case, we need to get rid of this 17, this minus 17 actually, and we'll do the opposite of minus, which is plus. So we're going to add 17, these cancel, and you're left with just x. Well, that's great and all, but on the other side, we have to do the same thing. We need to add 17. And now we have negative 5 plus 17, which if you might be kind of confused on how negative numbers work, but in reality it's just subtraction. So if you want, you can think of this as 17 minus 5. You're taking away 5 and then adding 17, which in that case is 12. And my pro tip would be, if you're ever stuck on one of these negative problems and it's confusing you, you can just put it into a calculator if your teacher allows you, of course, and that'll give you the answer. So in this case, our final answer is x equals 12. Here's our final problem for today, and it has fractions. So go ahead and try this out for yourself and see how you do. Okay, so fractions can seem complicated, but remember, fractions are just division. They're the same thing. So x is being divided by 3 here, and we need to get x by itself. So what's the opposite of division? Multiplication. So we are going to multiply this by 3. These cancel out, and you're just left with x. But remember, you need to do the same thing on the other side. So we're going to multiply this by 3. And if you don't know, basically whenever you multiply or divide a fraction by a number like this, you need to do it to the top of the fraction. The bottom stays the same. So 7 times 3 is 21, and the bottom stays the same, which is 2. This is different from if you were adding or subtracting, in which case you have to get a common denominator. It's a little more confusing. It's time to dive deeper into the forest of algebra with multiple step equations. But as you'll see, it's really just a bunch of one-step equations in disguise. Now here's our first example, and if you don't think you're quite ready for this yet, you can watch the one-step equations video on the card on the screen right now. So you'll see that this looks pretty similar to our one-step equations, just that we have two numbers here next to x. But the goal stays the same. We need to isolate the variable, a fancy way of saying we need to get x by itself. And the way we do that is by doing anything we want to the equation, as long as we do it to both sides. So before, what we would do is, let's say this was just x plus 7, we'd probably subtract 7. Or if we just had 3x, we would probably divide by 3. But what do we do here, since we have both a 3x and a plus 7? Does it matter which one we do first? Well, actually it does. If we divide by 3, remember we have to do it to both sides, but we also have to do it to the entire side. So if we divided by 3 on both sides, yes, that gets rid of these 3's, and we just left with x. But now we're left with 7 divided by 3, and then we just have fractions, and it's really complicated. So the easiest thing to do would just be to subtract 7. That cancels these out, because plus 7 and minus 7 cancel each other out. And you're left with 3x. We don't have to do anything to the 3x, because the plus 7 is its own separate term. 3x, the 3 is more attached to the x, so we want to get rid of that last. So as always, we need to subtract 7 on the other side as well, because we have to do it to both sides. 19 minus 7 is 12, and so right now we have 3x minus 12. And now you'll recognize this is just a one-step equation, and now we only have one thing next to x to get rid of. So now it just becomes, what do we need to do to get x by itself? How do we get rid of this 3? Well, this 3 is being multiplied, because if you have a number and a letter next to each other and there's no sign there, then that means multiplication in algebra. So the opposite of multiplication is division. So we are going to divide 3. And what that will do is that will get rid of these 3's and just leave us with x. But remember, when you do something to one side of the equation, you have to do it to the other side. So we're going to divide the 12 by 3. And 12 divided by 3 is 4. So our answer is x equals 4. I'm actually going to show you one more thing we can do. Because yeah, with these more complicated equations, you can be like, all right, x equals 4. I think I did that right. But you can be sure that you did it right by checking your work. Now, this isn't required to complete the problem, but some teachers actually require you to check your work. And even if they don't, it's a good habit to get into. Basically, an algebra problem is just a fill in the blank problem, right? What number goes in the blank here to make the answer correct? So what we can do to make sure we did the problem correctly is put this number in the blank and see if we get 19. So we're going to replace x with 4. We're going to fill in the blank. Plus 7 equals 19. And we're basically going to just do this to see if we get 19. We have to do multiplication first because, PEMDAS. So 3 times 4 is 12. And then we're going to add 7. And 12 plus 7 is 19. And yep, that matches up with the 19 over here. So that means we did the problem correctly. Here's another problem, and I know this one looks kind of scary. It's a little bit more than 2 steps, but remember, a multiple step algebra equation is just a bunch of one-step equations in disguise. So first off, what I'm seeing is there is this little plus x at the end here, but if we moved this to the other side, then we're just going to put an x on both sides and we're going to confuse everything. But look at this here. 2 times a thing in parentheses. What I'm noticing is that we can use something called the distributive property. And the distributive property says that if you have a number outside of these parentheses, then you can multiply it by each thing, by each term in the parentheses. So we have to multiply 4x times 2 and negative 3 times 2. And it's important that this negative sign stays. So first we have 2 times 4x. Well, that's just 2 times 4, which is 8. And then the x stays there. And then the second term is going to be 2 times 3, or actually 2 times negative 3, because this minus sign has to stay. So we have 2 times negative 3, which is negative 6. And now this plus x, we're just going to bring it down. We're not going to do anything fancy with it. And it equals 12. So what do we do now? Well, you might notice that we still have 2 x's in the problem, and we're going to want to bring it down to 1 before we can isolate it by itself. But there's an easy way to do that, and this is called combining like terms. Basically, whenever you see you have 2 things with an x in it on the same side, we can combine them. So in this case, we have 8x, and then we're adding another x. So in that case, we now have 9x. We're combining 8x plus x. And now this minus 6 is just going to stay the same. We didn't do anything with it. And you'll notice now that this just looks like one of our two-step equations, like the one from before. So we want to do the addition or subtraction first because we don't want to deal with fractions. That's dumb. So we're going to add 6 because that's the opposite of subtraction, addition. These cancel out, and you're left with just 9x on the left side. But remember, we have to do the same thing on the right side. We have to add 6. 12 plus 6 is 18. And now we just have a one-step equation. And we have 9 times x. Remember, this is multiplication. So we're going to do the opposite of multiplication, which is division. So we're going to divide by 9 on both sides. So these 9's cancel out. And now we finally just have x on the left side. But on the right side, we have 18 divided by 9, which is 2. So our final answer is x equals 2. And if you want to challenge yourself, you can plug that 2 back into x. Remember, you have to do it on both of these. Both of these need to be replaced with 2, and see if you get 12. Here's an example problem that I'd like you to pause the video and try for yourself. And remember, take it one step at a time. So this is one of our two-step equations. And don't freak out about this fraction over here. Remember, fractions are just division. So we're just going to do the opposite of division when we get to that. But first, we need to worry about this addition because this is what's not attached to the x right now. So we are going to do the opposite of plus 3 to get rid of the plus 3. And in this case, the opposite of plus 3 is minus 3. So we are going to cross out the plus 3 and minus 3 because they cancel out. They just do the opposite of each other. And we're left with just x divided by 5. But remember, we have to do it to the other side as well. So we're going to put minus 3 on this side. 6 minus 3 is 3. So now we're left with x divided by 5 equals 3. And now this is just a one-step equation. So we're going to do, remember I said this was division, so we're going to do the opposite of division, which is multiplication. So we're going to multiply 5 because that's going to be what cancels out these 5's. And now we're just left with x. But we need to multiply by 5 on the other side as well. So we're going to go ahead and do that. And we're left with 3 times 5, which is 15. So our answer to this problem is x equals 15. Here's our final example, and I know it looks like a lot, but remember, one step at a time, and I'm sure you'll get it. Alright, so first of all, I'm not seeing anything like plus 3 or minus 7 that's sticking out that we can just immediately deal with. But what I am seeing is a lot of these things that look like the distributive property. Actually, 2 of them in this case. We have this one and this one. So remember, the distributive property says when you have a number on the outside and things in parentheses on the inside, you have to multiply it to each part. So we have to do 3 times x and 3 times 1. Well, 3 times x, I mean, you can't really multiply a number by a letter, so we're just going to leave it as 3 times x. And this one, 3 times 1, well, that's 3. But now we have the other distributive property here, and this is where people get tripped up, because we have a minus sign on the outside here. And this confuses people because they think we just, oh, we'll just put a minus sign here and then we'll just do the rest of the distributive property like normal. But you can't do that. And this is because this minus sign is applied to the 2. And we're applying the 2 to everything else in the parentheses. If you want to think of it like this, we can change this to a plus sign and then do this with -2 and multiply -2 to both sides. But there's a less confusing way to do it. All you have to do is put the minus sign like normal, and then big parentheses. And whatever you do to the distributive property here is going to go in the parentheses. This will remind you that the negative sign is going to apply to everything in the parentheses. So in this case, we have 2 times x, which is just 2 times x. There's nothing much we can do with that. And then 2 times 2, which is 4. But now what we should do right away is take this minus sign and attach it to each of these things. So in this case, this first one's really easy. Minus 2x is just minus 2x. And in this case, we have minus 4. We're just going to attach the minus sign to the 4. And that equals 2. Let's say that this sign right here was a minus sign. If it was, then attaching another minus sign to it is actually going to make it positive. 2 negatives make a positive in algebra. So now what can we do to make this equation a little bit simpler? Well, I'm noticing that we have 2 terms here that have an x in them, and we can combine these. So 3x minus 2x, we have 3, and then we took away 2, we're only left with 1x, or in this case, just the letter x, where we don't have to put the 1 in. Here we have plus 3, and then minus 4. So 3 minus 4, gain 3, take away 4, and then you're left with 1 less than before, so minus 1. And on the right side, we have 2. And you'll notice that in just one step, we've gone from this to just a one-step equation. And that means the final step here is to get x by itself by getting rid of the minus 1. So we'll do the opposite of minus 1, which is plus 1. These cancel, and we're just left with x. But we have to do the same thing to the other side. Add 1, and 2 plus 1 is 3. So our final answer was x equals 3. Remember, it was a lot of steps to get here, but each one was just one step at a time. When you see this big pile of algebra stuff at the top here, it can be easy to go, I don't know what to do. But remember, just think of one thing you can do to make this a little bit simpler. As you can see, we did the distributive property, because that's what this looks like. And immediately we came up with more things that we can do to make it simpler. Sometimes there's only one thing you can do here that will lead to more things you can do. If you've made it this far in the video, go ahead and comment your favorite flavor of ice cream, because why not? Solving for a variable seems impossible because it's like there's 6 different letters in the equation. You're like, what am I supposed to do? But as you'll see, solving for a variable can actually be even easier than just doing a multi-step or one-step equation. So here's our first example. Our equation here is y equals x minus 2. So we've got 2 letters, and it says we need to solve for x. So like, what does that even mean? Well, solving for x just means make x by itself, isolate the variable. You don't have to actually figure out what number it's worth, and actually it's impossible to do because we don't know what y is either. So your answer is going to have y in it. In this case, what can we do to get x by itself on this side of the equation? Well, we can get rid of this minus 2. And if you know from one-step equations, we need to do the opposite of subtraction, which is addition. If we add 2, then we will be canceling out this minus 2, because taking away 2 and then adding 2 just does nothing. So we'll cross these out, and we're just left with x. But we have to do the same thing on the other side. So this plus 2 is going to go over here as well. Now, the only difference here between this and one-step equations is now we have a letter plus a number. And, well, you can't do that. So we're literally just going to leave it as y plus 2. And that's it. We've solved for x. Now, if you want your answer to look a little bit nicer, we can actually flip this around and put x on the left side, because that's probably what you're used to, is putting x on the other side. But either of these are fine. You could leave it on the right. You've technically solved for x. So our answer is x equals y plus 2. Now, by the way, fun fact, you can actually check your answer here the same way you would check your answer for multi-step equations. If you replace x with y plus 2, like it's a fill in the blank problem, it'll actually work the same way. So here we have y, And instead of x, I'm going to put y plus 2 because it's the same thing, right? And then minus 2. Well, plus 2 and minus 2, that's just 0. Those cancel out. And you're left with y equals y. And that's true. Y, it does equal y. So in this case, we know that we've done the problem correctly. This example is a little bit more complicated, but as you'll see, we're just going to take it one step at a time and do basically the same thing we've already been doing. So in this case, we want to solve for b. And we have negative 2b here. We can deal with that later. But the thing we should probably try to get rid of first is the 8a, because it's not attached to the 2b part. It's going to be easier to get rid of first and avoids us doing a bunch of weird fraction stuff. So we're going to get rid of this 8a. And since this is positive 8a, we need to do the opposite of addition, which is subtraction. We are going to get rid of the 8a by subtracting it from the equation. So we are going to cancel these out. And on this side, we're left with not 2b, negative 2b. This is one of the most common mistakes in algebra is forgetting these minus signs. They carry over. So we have negative 2b equals, and now we have to do the same thing to the other side, minus 8a. And you'll notice that this doesn't have the letter A and this does. So we can't actually subtract these together. If, for example, this was 4a, well, then we can do something with these. We can subtract 4 minus 8 and then put the A or whatever. But we can't do that. So we're just going to leave it as 4 minus 8a. So now we just have one step left, which is to get rid of this minus 2. And remember, the minus 2 is being multiplied by b, because when there's not a sign, it means multiplication. So we're going to do the opposite of multiplication, which is division. We're going to divide both sides by negative 2. So in this case, the negative 2's cancel out, and we're just left with b. But now this can look a little scary on the other side because we're dividing all of this by minus 2. Now, we have to divide both of these by minus 2, so we're going to do 4 divided by minus 2 and negative 8a divided by minus 2. So in this case, let's do 4 divided by minus 2. Well, 4 divided by 2 is just 2. But because there's a minus sign on one of them, then it's going to actually be minus 2. That's always the case if one of them has a minus sign. If it was negative 4 divided by negative 2, so if they both had a minus sign, remember, two negatives make a positive. And then in that case, this would be a positive 2. So now we need to divide negative 8a divided by negative 2. And if it makes you feel better, we have two negatives, so let's just make these a positive and forget about it. So we have 8a divided by 2. Well, 8 divided by 2 is 4, so we're going to put 4, and the a just carries over. And in that case, we have negative 2 plus 4a. So b equals negative 2 plus 4a, and that's our final answer. Once the variable that you're solving for is on its own on one side of the equation, that's it. You don't have to worry about anything else. Here's a practice problem that I'd like you to pause the video and try for yourself, and then unpause and see how you did. So in this case, we need to solve for y. It's important to know what letter you're solving for, and if you don't, then this equation doesn't mean much anything. So we're solving for y. So first we're going to get this other part that doesn't have y in it off of this side of the equation. So we are going to subtract 2x because we have a positive 2x here, right? And there's a little plus sign technically there. So we need to subtract it to get rid of it. So these cancel out, and we're left with negative 2y, not just 2y. Remember the sign. Then we need to subtract 2x from the other side because we have to do the same thing to both sides. Remember, when we're adding and subtracting, this doesn't have an x and this does. These are not like terms. So that basically just means we can't add or subtract them. So in this case, we just need to leave it as 16 minus 2x. So now we're left with one more step. To get this to just y by itself, we need to do one more thing, and that is get rid of this minus 2. And remember, it's being multiplied. There's no sign. So we need to do the opposite of multiplication, which is division. So we will divide minus 2 by both sides. These cancel out, and we're just left with y. But on the right side, we have the weird division fraction thing again. But remember, one step at a time. First, we're going to do 16 divided by negative 2. Well, 16 divided by 2 is 8. but we also have one negative sign here. We don't have two negative signs, so they don't make a positive. We just have one negative sign, so we're going to put the negative right there. And now on this side, we have negative 2x divided by negative 2. Well, actually, there's a way to make this way easier, which is the fact that, remember here, when we divided by negative 2 to cancel it out? Well, the problem has actually already done that for us. We can just cross these out. Here's another common mistake that people make in algebra. We cross these out, which we can do because they cancel each other out and we're just left with x. But just because we cross them out on this side does not affect this side. Because we cross these out does not mean that this is also crossed out for the 16 divided by negative 2. That is its own separate thing. So actually, a better way to write this would have been to split this up into 16 divided by negative 2 and negative 2x divided by negative 2. In this case, the negative 2's cross each other out, and we just have x, but on this side, the negative 2 stays the same. So we are left with our final answer of y equals negative 8 plus x. And you'll see that y is by itself, so there's nothing else we have to do. Remember when I said that some problems are going to have like 6 variables? Well, this is that problem. ABC equals DEF. I know it looks really weird and complicated, but in reality, it might actually be even easier than the problems that we did before. I don't know, you find out, because go ahead and pause the video and try it out for yourself. So remember, the goal stays the same. We need to get D by itself on this side of the equation. And remember, these are letters next to each other with no sign, which means that we're really just multiplying. So how can we get D by itself? Well, we have D times E times F. So we can literally just do this in one step by doing the opposite of multiplication, which is division. If we divide by E times F, then we're getting rid of everything next to D. So on the right side of the equation, we're just left with D because the E and F cancel out. But now we need to do the same thing to the left side of the equation. So we're going to divide by E times F. And we can't do any sort of weird like math, but we don't even have numbers. So we're just going to leave it as A, B, C divided by E, F. And that's it. That's our answer right there. D is equal to ABC over EF. Have you ever felt like your little brother or sister was getting in less trouble than you for doing the same thing or something else unfair like that? Well, I can't really help you out with that because this is a math channel. Oh, you want help with algebra inequalities? Well, why didn't you say that the first time? So what is an algebra inequality? Well, as you can see, it's literally just the same thing as an equation, except with a different sign. Instead of telling you that both sides are equal, like an equal sign does, in this case, the sign is telling you which side is bigger. So in this case, this is the greater than sign because it is saying that this side is bigger than this side. X plus 7 in this case, in this inequality, is greater than 10. It's a bigger number. And if you're not sure if this is the greater than sign or the less than sign, just remember what like your third grade teacher probably told you. The crocodile eats the bigger side. Or the alligator. I don't know my animals. So we're going to solve this literally the same way as a one-step equation. We're just going to keep the sign throughout the entire thing. So in this case, we need to isolate the variable. We need to get x by itself. And if you don't quite remember how to solve one-step equations, then I'll have the card on the screen that you can go watch that video first. So we need to isolate the variable. We need to get x by itself. And the way we do that is by getting rid of this plus 7. So we're going to do the opposite of addition, which is subtraction. We're going to subtract 7 from both sides. On this side, we're just left with x because the 7's cancel out. And on this side, we're left with 3. And we're going to keep that greater than sign. It's going to stay the same throughout the whole thing. And that's our answer. X is greater than 3. So you're probably wondering how this is any different from just a regular equation. Well, how you do it is actually no different. The difference comes with how you interpret it, I guess. Basically, what this is saying is any number greater than 3 will make this equation true. So we can check our work that way. Let's say we put in 4 for x, like for this fill-in-the-blank problem, right? 4 plus 7 is greater than 10. Well, 4 plus 7 is 11. And last time I checked, 11 is bigger than 10. This doesn't necessarily mean we did it right. It just means that this is true. And it should be true in every case if we did this correctly. So just to make sure, let's put in 2 for x. 2 plus 7 is greater than 10. Well, 9 is not greater than 10. So in this case, 2 does not work, which means we did it right because 2 is not greater than 3. So this is saying that 2 shouldn't work, which it doesn't. So we did it right. Now here's a two-step version of the same thing. However, this problem actually has one step that's different from doing a normal multi-step equation, and we'll talk about that when we get there. You may notice that this less than sign here has a little line under it. And that basically just means that it can be less than or equal to. That's the name of the symbol. It's less than or equal to. In this case, we're just going to keep the sign the same, less than or equal to. We'll just keep putting that line underneath each step, so you don't have to do anything different. So we need to isolate the variable. We need to get x by itself. So let's get rid of this plus 1 by doing minus 1, the opposite of plus 1. These cancel out, and we're just left with negative 2x on this side. We'll keep the sign and then subtract 1 on the other side. 7 minus 1 is 6. But now here's where it gets interesting. We need to get x by itself, so we're going to do the opposite of multiplication. Remember, this is multiplication, which is division. So we're going to divide both sides by negative 2. So these cancel out, negative 2. And on this side, we're just left with x. And on this side, we have 6 divided by negative 2, which 6 divided by 2 is 3. And we have one negative sign, so we're going to carry over the negative. But there's one interesting thing about this. When you're doing an inequality, whenever you multiply or divide by a negative number, you have to flip the sign. So in this case, it's going to become greater than or equal to negative 3. This is really important because it's the only thing that makes this different from normal multi-step equations. You need to flip the sign when you multiply or divide by a negative number. Now, one more thing that you might have to do in your homework is to graph the answer on a number line, which is actually pretty simple. Now remember, just graphing a number on a number line, like for example, if this was just negative 3, we would graph it by putting a dot here on minus 3 on the number line. But since this is an inequality, this represents all the numbers that are negative 3 and are greater than negative 3. This line here means negative 3 is included, and then all numbers bigger than negative 3 are included. So the way we'll represent this on a number line is we're just going to shade in all of the numbers that are greater than negative 3. And at the end, we'll go ahead and put an arrow because this arrow represents that this goes on infinitely. 4, 5, 6, 100, 1,000, they all are bigger than negative 3. So they are going to be included in this too. Now what about this one? X is less than 1. You will notice that in this case, we don't have a line underneath, which means that all the numbers that are less than 1 count. But 1 exactly doesn't because we don't have the equals part underneath. So we're going to graph 1 on our number line, but because 1 isn't included, we have to draw an open circle instead of a filled-in circle. The filled-in circle says that 1 is included, but in this case, 1 is not included, so we have to draw an open circle, or just a circle that's not filled in. And same way that we did before, we're just going to shade in all of the numbers that count. So all the numbers less than 1 are going to count. And we're going to go ahead and put an arrow at the end because this means that it goes on infinitely. Negative 100, negative 1,000, they would all be less than 1. So they should all be included. And that's what this arrow represents. So here's an example that I'd like you to pause the video and try for yourself. And then go ahead and unpause and see if you got it right. So this one is just a simple one-step inequality. We're going to do this the same way that we would do a one-step equation. We need to isolate the variable x, and we are multiplying right here. So we're going to do the opposite of multiplication, division. We're going to divide by negative 3, which cancels out these negative 3's, and we're just left with x. And on the other side, we divide by negative 3 as well. 6 divided by 3 is 2, but because we have a negative sign here, we're going to go ahead and put the negative sign. But remember, the one thing that makes inequality solving different from equation solving is that the sign needs to be flipped whenever you multiply or divide by a negative number. In this case, we divided by negative 3. So we need to flip the sign. So in this case, it's going to become greater than. So our answer is x is greater than -2. Here's another inequality. This one's going to take a couple steps. And for this one, I'd like you to try graphing it on a number line as well once you're done. So we need to isolate the variable x, and we're going to go ahead and do that by getting rid of this +2 first because it's not attached to the x. So we're going to subtract 2 because that will cancel this out, +2 minus 2. And we're just left with 3x. On the other side, we need to do the same thing. We're going to subtract 2. 8 minus 2 is 6, and we're just going to carry the sign over. And now we just have a one-step inequality. And we're going to solve that by getting rid of this multiplication by doing the opposite, division. We're going to divide by 3 on both sides. On this side, we have x, and on this side, we have 2. So now what do we do with the sign? Are we going to flip it or keep it the same? Well, we divided by a positive number. And remember, you need to flip the sign if you multiply or divide by a negative number. We divided, but by a positive number. So we don't have to flip the sign. We don't have to worry about any of that. So our final answer is x is greater than 2. So to finish things off, let's go ahead and graph this on a number line. We see we have all numbers greater than 2 count. But does 2 itself count? No, because we don't have the line underneath here, right? That would say equal to, as in 2 counts. But in this case, it's only one's bigger than 2. So we're going to put 2 on the number line, but as an open circle, which means that it's not part of it. But anything bigger than 2 is part of it. So we're going to go ahead and shade in all the numbers bigger than 2, and we're going to draw an arrow at the end to show that it goes infinitely. All numbers bigger than 2, like a million, would count. It's time for everyone's favorite kind of algebra problem, word problems. Yeah. But as you'll see, word problems don't actually have to be that bad. All right, so the first inequality word problem for today is about Bob the Builder. So Bob the Builder earns $100 for each building he builds, plus $20 for each room the building has. What is the least number of rooms a building needs for Bob to earn at least $300 from a building? So the first step of these kinds of word problems is to write out an equation or an inequality that represents this so that we can actually do math with it. So first of all, I'm noticing the different numbers we have in here. He earns $100 for each building, and that's $100 no matter what, right? Plus $20. So we already have the word plus, that means addition. And $20 for each room the building has. And he wants to earn $300. That's like the target amount. So on the left side of this inequality, we're going to go ahead and write how much he makes for each building. So in this case, he gets $100 no matter what, right? But he also gets plus $20 for each room the building has. Well, in this case, we don't have a specific building. We don't know how many rooms the building has. That's actually what we have to find out. The least number of rooms that the building needs. So that's going to be our unknown amount. So we're going to put plus 20 because he earns plus 20 for each room. So if he earns $20 for each room, then that means we need to multiply 20 by the amount of rooms. So you can use any letter for this. We'll just use the letter R for rooms because why not? Then on the other side, we need to put his goal. How much money does he want to get from this building? In this case, it's $300. We need to figure out what sign to put here. In this case, I'm seeing at least $300. What sign do you think we would put for at least? Well, first of all, I know that this would be greater than because he wants to earn more than $300, not less than $300. But do you think 300 is also included in this? Yes, because if he earns exactly $300, then he'll be happy. He earned at least $300. So this isn't just greater than, we also have to put the line underneath, which means or equal to. If he earns exactly $300, he'll be happy. If he earns more than $300, he'll also be happy. So now we have ourselves an inequality that we can solve using our normal math stuff. So we need to get R, the variable, by itself. So the way we do that is by getting rid of this 100 first. We don't want to get rid of the 20 yet because that's more attached to the R. It's easiest for us to get the 100 out first. So we're going to go ahead and subtract 100 from both sides because that will cancel these out. And on this side, we're just left with 20R. But we have to do the same thing on the other side. So we're going to subtract 100 from the other side of the equation as well. 300 minus 100 is 200, and we'll just carry the sign down. So now we just have a one-step inequality. 20r is greater than or equal to 200. So to get rid of this 20, remember this is being multiplied because whenever there's not a sign and they're just next to each other, that's multiplication. We need to do the opposite of multiplication, which is division. We're going to divide both sides by 20. On the left side, we're just left with r, and that is greater than or equal to 200 divided by 20, which is 10. So in this case, r is greater than or equal to 10. So what does this answer mean? Well, r is the amount of rooms, right? So in other words, if a building has greater than or equal to 10 rooms, then Bob the Builder will earn at least $300 from this building. So the question's asking, what is the least number of rooms the building needs? Well, 10 rooms. So the answer to this problem is 10 rooms. All right, here's another example problem. What I'd like you to do is go ahead and pause the video and try this one out for yourself. All right, so Mrs. Teacher is trying to manage the behavior of her kindergarten class. Whenever a student misbehaves, Mrs. Teacher gives them 5 sad face points. A student will have to go to the principal's office if they reach 30 points. How many times can Jeffrey, one of Mrs. Teacher's students, misbehave without having to see the principal? Well, let's write an inequality to represent this situation. The numbers I'm seeing here is 5 points for each time the student misbehaves. And we also have the number 30 here, which represents the total amount of points that a student doesn't want to reach. So on the left side, we'll put 5 times the amount of times that a student misbehaves. We'll go ahead and put M for misbehaviors. I don't know. And then we're going to put 30 because that's the total amount of points that a student doesn't want to receive. So in this case, would you say we would use less than or greater than? Well, I think they would use less than because they don't want to reach 30 points. As long as you have less than 30, you're fine. You don't have to go to the principal's office. So we're going to go ahead and say that 5m needs to be less than 30. But will we put a line under this? We actually wouldn't in this case, because if a student reaches exactly 30 points, well, they have to go see the principal, and they don't want to do that. So the number 30 is not acceptable here. It needs to be less than 30. So let's go ahead and solve this inequality. In this case, it's actually only one step. We need to get m by itself, so we're going to divide both sides by 5 because that is the opposite of multiplication. The 5's cancel out, and we're just left with m on the left side. The sign stays, and on the right side we have 30 divided by 5, which is 6. So the final answer of this inequality is m is less than 6. But what does that mean in the context of this problem? The question's asking how many times can Jeffrey misbehave without having to see the principal? Well, can he misbehave 6 times? No, because 6 is not included in this. And since you can't misbehave a half of a time, the maximum amount of times that he can misbehave is 5. And if he misbehaves any less amount of times, then that's fine. So if you wanted to write this out as an answer, you could say that he can misbehave 5 or less times, because 6 doesn't count. Here's a more businessy type of problem. Go ahead and pause the video and see if you can solve it yourself. Alright, so Susan is selling a plushie on her website. She earns $2 on each sale plus $50 per week. What is the least amount of plushies that Susan needs to sell this week to make at least $200? Well, I see 2 ways that Susan's making money. First of all, she earns $2 on each sale. So that's probably going to be 2 times, a letter like before. She also earns $50 per week. So $50 flat. And right here, I'm seeing least amount of plushies. That's probably going to inform us of what kind of sign we need to use. And then her goal is to make $200. That'll probably go on the other side of the equation. So let's go ahead and write this as an inequality. $2 on each sale. So we're going to put the number 2 times however many sales she has, which we don't know yet. That's what we're trying to find out. So we'll just put the letter S for sales. She also earns $50 per week, and that 50 stays the same every week. So we're just going to put 50. And on the other side, we're going to have 200 because that's her goal. Now, does she want to make more or less than $200? Probably more. So we're going to put the greater than sign because we want the amount of money that she makes to be bigger than 200. Now, do we put a line underneath this greater than sign or no? Well, she wants to make at least $200. So if she made exactly $200, yes, that counts. So we will put a line underneath this greater than sign because 200 is included in the amount of money that Susan can make to reach her goal. So now we have a two-step inequality right here. We want to get rid of this 50 first, right? Because this 2 is being multiplied by s. We want to get rid of the one that's not attached to the s first. So we're going to go ahead and subtract 50 from both sides. These cancel. And on the left side, we're just left with 2s. On the right side, we have to do the same thing. So we're going to subtract 50 from the right side as well. 200 minus 50 is 150, and the sign stays the same. So now we just need to get rid of this 2, and it's being multiplied by s, so we need to do the opposite of multiplication. We will divide by 2. These cancel, and we're just left with s. On the other side, we need to do the same thing. So we're going to divide 2 on the other side. 150 divided by 2 is 75. And if you didn't know that, you can just put that into a calculator. And we'll just put the sign back here. And that's our answer. S is greater than or equal to 75. However, what does that mean in the context of a problem? Well, the question's asking, what is the least amount of plushies that Susan needs to sell this week? Well, S is the amount of sales, or the amount of plushies. We could have used the letter P for plushies, it doesn't matter. But in this case, this is saying that she needs to either sell more than 75 plushies or exactly 75 plushies. So if we wanted to word out this answer, we would just say 75 or more plushies. And that's our answer. Time to start looking at some tables and graphs. I know you're so excited to start looking at those. But in just a few minutes, you're going to be able to find rate of change of both a table and a graph. Let's go ahead and get started. So here's our first table, and our goal here is to find the rate of change of this table. But what even is rate of change? Well, first I'll give you the math definition, and then I'll give you the actual definition. So in math, rate of change is usually written probably in your textbooks as delta y over delta x. Those little triangle things are the Greek letter delta. What does that even mean? Well, first of all, whenever you see this little delta triangle thingy, it usually means change in. So in other words, you would read this as change in y over change in x. But that still doesn't totally explain it, right? Well, it's still just a math equation. What does that mean? Well, rate of change is basically asking how fast is y moving in relation to how fast x is moving. So a good example of rate of change would be a car that drives at, let's say, 50 miles per hour. Well, that's actually rate of change. Your miles is changing by 50 for every time your hours are changing by 1. Let's say you increased the length of your trip to 100 miles, but you did that in 2 hours. Well, you were still driving at the same speed, so your rate of change didn't change. But if your distance went up to 100 miles, but the time stayed the same at just 1 hour, well, your rate of change now went up. It's now at 100 miles per hour, and you're going way too fast. So how do we find the change in y and the change in x in this case? Well, there's actually another way that we can write this math fraction thing here. And the most common way to write it is y2 minus y1 over x2 minus x1. This is something that we're going to be using, but basically what this means is you take your final y, which like 19, and your initial y, or the y at the beginning, which in this case was 3. And this is how you find how much it changed. So 19 minus 3 would be 16. So y went up by 16 from 3 to 19. That's pretty much all that this is saying. This is just the mathematical way to write it. So we're going to use this mathematical way to solve this problem. And in this case, to find the rate of change, you can actually just use any 2 points. You could use this one and this one. You could use this one and this one. It really doesn't matter. In this case, I think it would be easiest to just use these 2 because they have the smallest numbers and that makes the math easier. So let's go ahead and replace all of these letters with the actual numbers from this table. Well, y2, the second y. What is the second y in this table? Well, the bottom row of this table is y's, and the second one is 7. So we're going to go ahead and put 7 minus, because the minus here, and then y1. What is y1? Well, that's the first y. In this case, we look at y, and the first one is 3. Now we need to find x2, the second x. In this case, we're going to look at the top row, which is x, and the second one is 3. So we're going to put 3. And now we just need to find x1. The first x in this case is 0. So we're going to put 0. So now we're going to find out how fast y is changing in relation to x. So 7 minus 3 is 4, and 3 minus 0 is 3. So in that case, that's our answer right there, 4 over 3. So in this case, every time x goes up by 1, y is going to go up by 4/3, 4 over 3. As you can see for this problem, we now have our graph background on, and that's because we're going to be finding the rate of change of this graph. So how do we find the rate of change of this graph? How do we find out how fast y is going up compared to x? Well, the first important thing to remember is that on a graph, y is always the direction of going up, and x is always the direction of going to the right, left and right. So as before with the table, we only need to pick 2 points. Any 2 points will do. The easiest thing to do would be to pick 2 points that are perfectly in like the corners of these squares, like right here. Because if you don't, then you're going to start getting like fractions and stuff. So I see that one, and then also right here, that's perfectly in the corner of these squares. So we have our 2 points. So how do we figure out what these points are? Well, a point is always written as x, y. So we need to figure out how far to the right this point is, and then how far up this point is. So it is 0 to the right because it's perfectly right here. It hasn't gone any far to the right. So in this case, x is going to be 0. Now, how far up has this point gone? Well, from here, the 0 point, it has gone up 1 space. So in this case, y is 1. So we're going to put 1 for y. So our first point is 0, 1. Now, what about this point over here? How far to the right has it gone? Well, it's from here, the starting point, it's gone 1, 2, 3, 4. So x in this case is 4. But now how high up has it gone? Well, starting from here at the bottom, it's gone 1, 2, 3. It's gone 3 spaces up. So we're going to go ahead and put 3 for y. So now we have our 2 sets of coordinates. We have x and y, x and y. So how do we do rate of change with this? Well, remember that rate of change is y2 minus y1 over x2 minus x1. So in this case, we need to figure out y2. Well, that's the second y. So here's the second pair of points, and which one's y? Well, y is the one to the right, so 3. Now y1 is the first point, so 0, 1, and which one's y? The one to the right, 1. So we're going to put minus 1. Now what's the second x? Well, the second point is here, and x is the one to the left, so 4. And then x1, the first x. Here's the first point, and x is the one to the left, so 0. So now it's just subtraction. 3 minus 1 is 2, and 4 minus 0 is 4. Now 2 over 4 is a fraction, but we can simplify it because we can divide both of these numbers by 2. 2 divided by 2 is 1, and 4 divided by 2 is 2, which is 1/2. So 1/2 is our final answer. So every time x goes up by 1, y goes up by 1/2. And if you look at that, that makes sense. X has gone over 1, but the line has only gone up half of a square. So that fits with our answer. Here's another example of a table. And what I'd like you to do is pause the video and try this one out for yourself, and then unpause and see how you did. So the first thing to remember that's important is this here, time and distance. You don't need to worry about these labels. It's not going to change how you do the problem. It's just giving you some context as to what this is. So we still need to figure out how fast y is changing in relation to x. So we're still going to use that formula that we talked about before, which is y2 minus y1 over x2 minus x1. So we'll use 2 points. I would say let's just use the first 2 again, like before. You could have used any 2 points. So in this case, y2, the second y, well, y is the bottom row, right? And the second one is 45. So we're going to put 45. y1, the first y, would be 60. Now we need to find the x's. x2, the second x is the top row, so the second one is 5, and the first one is 0. So now we just need to do the subtraction. 45 minus 60 is negative 15, and 5 minus 0 is 5. So now we just need to do the division. 15 divided by 5 is 3, and we have one negative sign, so the negative sign carries over. So in this case, our rate of change is negative 3. So that's our answer. So what does it mean if rate of change is negative? Well, it means that every time seconds go up, the distance is going down, as you can see. Every second, we are getting less and less distance. So maybe this was like distance from your house or something, and you were like walking home or something. In that case, then your distance from your house would be going lower and lower every second because you're walking home. So the rate of change would be negative in this situation. And if your teacher were to require you to have units, well, you would say that your distance, your feet, is going down every second. So you would write that as feet per second. It's kind of like a car that runs in miles per hour. It is just feet per second this time. They're just different units. The graph is back for our final problem, and in this case, it's pretty flat. Go ahead and pause the video and try it out for yourself. So remember, rate of change is still y2 minus y1 over x2 minus x1. And because this is flat, you can see that as x goes by, y isn't really changing that much. So you would probably expect rate of change to be pretty low for this one. So to start out, we need to find 2 points that we want to use. The starting one is usually pretty good because it's right in the corner of these squares. And this one right here is also in the corner of these squares, so we're going to get some nice even numbers here. This first point here, we need to find the x and y for. Well, we need to figure out the x first, so how far to the right has it gone? Well, from the starting point here, it hasn't really gone anywhere, so in that case, x is going to be 0. But how high up has it gone? Well, here's the starting point, 1, 2, 3. It's gone up 3 squares, so in that case, our first point is 0, 3. But what about our second point? How far to the right has it gone? 1, 2, 3, 4, 5. So in that case, 5 is going to be our x. But now how high up has it gone? Well, 1, 2, 3, 4. So our y is going to be 4. So now we have our 2 points here, 0, 3, and 5, 4. So now we need to figure out the rate of change. So first of all, what is y2? Well, that's the second y, which in this case is the second point. The one to the right is y4. And what is y1? Well, here's the first point, and then the y of this point is 3. Now x2. Well, here's the second point, and x is the one on the left, so 5. And x1 is the first point. The one to the left right now is 0. So now we just need to do the subtraction. 4 minus 3 is 1, and 5 minus 0 is 5. So the rate of change of this graph is 1/5, which is really close to 0. It's far less than 1, and that fits with what we were saying before about how the rate of change would probably be pretty low, because this is very flat. It's not really changing in height much at all, and 1/5 is pretty low. So yes, that fits, and our answer makes sense. Time to start slope, which is one of the most commonly struggled on topics in Algebra 2. But don't worry, once you get the hang of it, it'll be easy peasy. So here's our first example. Find the slope of the line that passes through 2, 5, and 7, 8. Well, these are 2 points on a line, and we can't actually see this line, but in this case, you don't actually have to graph the line. We can just find the slope just using these numbers. But what even is slope? So right here, I have a terribly drawn graph for you. This graph shows a pretty low slope. Well, how do you know that? Well, slope is just the steepness of a graph. So if you want to think of this as like a mountain that someone's climbing up, this would not be too difficult to climb up because it's pretty flat. It's not very steep. So the slope of this would be probably a low number. And this graph would be an example of a high slope. I would not recommend trying to walk up this unless you can like defy gravity or something. But we actually don't need to draw a graph for this problem. If you have 2 points, you can figure out the slope. And that's because we have a formula for slope. Formula for slope is y2 minus y1 over x2 minus x1. But why? Well, In this case, y2 minus y1. We want to find out how much y is changing, and y is how high up a graph is. So we need to find out how much the height of our mountain is going up. And if we subtract the ending height from the beginning height, we find out how much the height changed. It's the same with x. This is how we find out how far to the right our graph has gone. So x2 is our ending x, and then x1 is our beginning x. So that's how we find out how far to the right the graph goes. So in this case, we can just plug these numbers from these points into this fraction. So for example, we have y2. Well, that's the y of the second point, the ending point. 7, 8 is our second point, and the y of this point is the second number because a point is always written with x first, then y. So 7, 8, 8 is y, so we're going to put 8. Now we're going to put the minus sign, and now we need to figure out y1. Well, that's the y of the first point. Our first point is 2, 5, and y is the second number, which is 5. So next we need to find x2. Well, x2 is the x of the second point. This is our second point, and x is the one to the left, which is 7. And now we just need to find x1, the x of the first point. The first point is 2, 5. So the x of this point is 2. So now we just need to do the subtraction. 8 minus 5 is 3, and 7 minus 2 is 5. So in this case, 3 over 5 is our slope. So what does this look like on a graph? Well, right here, this is a slope of 1. A 1 slope means it's perfectly diagonal. So anything steeper than that would be bigger than 1, and anything less steep than that would be less than 1. So 3 over 5 is less than 1, so it would probably look something like this. So here's another example. We're going to do this literally the same way as the last one, except in this case we have some negative numbers. So even though we're going to do it the same way, it might be a little bit more confusing, but don't worry, we'll get through it. So we're going to go ahead and use our slope formula that we used last time, which is y2 minus y1 over x2 minus x1. So what is y2? Well, y2 is the y of the second point. Here's the second point, and the y is the one on the right, negative 5. y1 is the y of the first point. Here's the first point, and y is the one on the right. So the one right here is 3. Now x2. x2 is the x of the second point. Here's the second point, x is the one on the left, so 2. And now the x of the first point. Here's the first point, the x is negative 2. So how do we write this? Well, remember, we already have a minus sign, so it's going to be minus negative 2. And if it helps, you can put negative 2 in parentheses to make sure you understand that these are two different negative signs. So now we just need to do the subtraction. Negative 5 minus 3. You might not immediately be able to do this in your head, but just think about it like this. You lost $5, and then you lost another $3. So how much money did you lose? $8. So we're going to put minus 8 for losing $8. Now what about this one here? We have negative, negative, so minus, minus. Whenever you have two minuses next to each other like this, they cancel each other out and make a positive. So you can just kind of like make these positive signs. In this case, we have 2 plus 2, which is 4. Now we have negative 8 over 4. Remember, this is just division. A fraction is just division. 8 divided by 4 is 2. And we have one negative sign. So the negative sign is going to carry over. So our final slope is negative 2. But what is a negative slope? Here's my terribly drawn graph once again. And this time in blue, I have a slope of 0. 0 slope means it's completely flat. It's just flat ground. It's not steep at all. So what is a negative steepness? Well, that would mean that it's actually going down. So this would be a downhill walk and pretty much equally as dangerous. It's pretty steep. Minus 2 would probably look like this as a slope. Here's another example. What I'd like you to do is go ahead and pause the video, try it for yourself, and see how you do. So we're going to use the same slope formula as before. y2 minus y1 over x2 minus x1. So what is y2? Well, y2 is the y of the second point, so 3. And y1 is the y of the first point, which is negative 3. Remember, we already have a minus sign here from this, so negative 3 means we're putting yet another negative sign. And we're just going to go ahead and put it in parentheses to make sure that we understand that these are two negative signs. Now we need to find x2, the x of the second point. Here's the second point, and x of this point is the one on the left, so 4. And now the x of the first point, x1. Here's the first point, And the x of this point is -4. And again, we have another negative sign, so we're going to go ahead and put it in parentheses to make sure we understand that. So now we have two cases where we have double minus signs. Remember, two minus signs make a plus sign. So we're going to go ahead and make these pluses. So now we just have 3 plus 3 and 4 plus 4. 3 plus 3 is 6, and 4 plus 4 is 8. So our slope is 6 over 8. But you might notice that we can actually simplify this fraction down. We have two numbers here that can both be divided by 2. So 6 divided by 2 is 3, and 8 divided by 2 is 4. So our final slope is 3 over 4. Now, you might have not immediately seen that we can simplify this fraction down. So here's a pro tip. You don't have to immediately know what number you can divide both of these by. Always look for like small numbers like 2 and 3. You can easily see if both of these numbers are divisible by 2 just by noticing if it's an even number. So we have an even number on the top and even number on the bottom. If they're both even, that means you can simplify the fraction by dividing by 2. And if you want to see if both of these are divisible by other numbers, you can just try them in a calculator and see for yourself. So in this case, our final slope is 3 over 4. Here's another example that I'd like you to pause the video and try yourself. So I've got our slope formula here that we're going to be using just like the other problems. We need to find y2, which is the second point, y is -4. Now we need to find y1. Here's the first point. Y is the one on the right, so -3. And remember, we already have a minus sign. So we're adding another minus sign. So minus -3. On the bottom, we need x2, the x of the second point, which is 7. And now the x of the first point. Here's the first point, x is 0. We have two negatives here. Two negatives make a positive, so we'll go ahead and make these plus signs. So -4 plus 3. If this confuses you, again, you can use the money example from before. You lost $4, but then you earned $3 back. Well, you haven't regained all your money. You still lost money in total. And how much money have you lost? $1. You lost 4 and then gained 3 back. You still are missing $1. So we're going to make this -1. On the bottom here, 7 minus 0 is 7. And that's our answer here. There's nothing else we can do with this. -1 over 7. So because this is pretty close to 0 on a graph, this would probably be pretty flat. Not exactly flat. It would be sloping down a little bit because it's negative. And as always, you can leave a comment if you're confused about anything in this video, and I'll be sure to help. Thanks for watching. How am I supposed to find the slope of the graph? There's no numbers here. What am I supposed to do? Well, let me show you. Slope is just the steepness of a graph. So in this case, this graph is really steep, right? If you were thinking of this like a mountain, this would be pretty tough to climb up. So this would have a high slope. And this would be an example of a low slope. This is relatively flat. It's pretty easy to climb up, so this would be a low slope. And finally, this would be a slope of 1. So if you have a perfectly diagonal line like this, that would be a slope of 1. Anything that's less steep than that would be less than 1, and anything more steep would be more than 1. So how do we find the slope of a graph like this? How do we find the exact number for the slope? Well, in past videos, I've talked about the slope formula, which you can use. This formula works to find slope in any case, even if you can't see the graph. But when you can see the graph like this and you need to find the slope, there's actually a faster way than we can do it. It's the same thing as the y2 minus y1 thing, but it's a little bit easier to understand. And you've probably heard of it before. Slope is equal to rise over run. So what does that even mean? Well, here's our graph, right? We want to figure out how much it rises and how much it runs, and then we put those into this fraction, and you'll get the slope. So first we need to pick any 2 points on this graph. I would recommend picking points that are in the corners of these little boxes, like right here, because if you pick something like over here, then you're going to be getting like fractions or decimals or whatever, and that's really complicated. So this one is a nice even number. It's in the corner of these boxes. And another great point to pick is the one right here in the middle, because that's going to be 0 and 0 right in the middle. So now we need to figure out how much it rises and how much it runs. Well, to get from this point to this point, it needs to rise 2 squares. So the rise is 2, and it needs to run 3 squares. So the run is 3. So to find our slope, we just need to plug in rise and run. The rise in this case was 2, and the run in this case was 3. So that's it. Our final slope is 2 over 3. What about this graph? How do we find the slope of this graph? You may notice that in this case, it's actually going down. And whenever the slope is going down, the slope is going to be a negative number. So let's pick 2 points that are nice even numbers. I like this one and this one. It really doesn't matter which ones you pick. You could have picked this one or this one. It doesn't matter. So let's find out how much it rises and how much it runs. The rise, or in this case, it's actually going to be falling, 1, 2. So when it's falling, that means it rose a negative amount. So this went 2 boxes, but the rise is going to be -2 because it went down. And the graph runs 1, 2 squares. So the run is going to be 2. So let's go ahead and plug this into our equation. Slope is -2 for the rise over 2 for the run. So now all we need to do is divide. 2 divided by 2 is 1. And we have a negative sign, so we'll put the negative sign here. And that's it. Our slope in this case is -1. So what about this graph? What I'd like you to do is pause the video, try to figure out the slope yourself, and then unpause and see if you got it right. So we're going to do this the same way as before. We're going to pick out 2 points that are nice even numbers. Let's go with right here and right here. So now we need to figure out how much it rises and runs. In this case, it's falling instead of rising again, so we're going to have a negative rise. So it only falls down 1 square. So that's going to be -1 for the rise. And now how much does it run? Well, 1, 2, 3, 4. So our run is going to be 4. So now we just plug this into our equation. Slope is rise -1 over run, which is 4. And that's it. Our final answer is -1/4. Here's one more example. Go ahead and pause the video and try it yourself. All right, so let's pick out 2 points. I like this one and this one. Why not? First, we need to figure out the rise. The rise in this case is going to be 1, 2, 3. So our rise is 3. And our run is just 1. So we're going to put 1. So now we need to figure out rise over run. Our rise is 3, and our run is 1. And 3 divided by 1 is 3. So our final slope is 3. And that makes sense because this is a pretty steep graph. First, slope-intercept form can seem really confusing. You just have like a line and suddenly you're supposed to come up with a bunch of numbers and letters and stuff. There's nothing there to work with. Slope-intercept form doesn't actually have to be that confusing. So how do we write the equation of a line like this? Well, to start, we need to go over what slope-intercept form even is. Slope-intercept form is, you've probably heard this equation before, y equals mx plus b. But by itself, this doesn't really mean much anything, right? It's just a bunch of letters. Well, x and y are just going to stay as x and y. You don't need to put any numbers in for these because every equation of a line has an x and a y that you plug in. But we need to figure out what m and b are. So what do these stand for? Well, first of all, m stands for slope. Don't ask me why m stands for slope. I didn't choose this. But let's see what b stands for, right? That's got to be something better. B in math stands for y-intercept. Yeah, I don't know. But the letter doesn't matter. The point is we need to find the slope and the y-intercept of this graph. Then we put those numbers in for m and b. We leave x and y as they are, and we'll have the final equation for our graph. So first, the slope. How do we find the slope? Well, to do this, we're going to go ahead and use rise over run. Well, if you're not quite familiar with rise over run, I actually just made a video on it that you can watch on the card on the screen right now. But just as a quick review, to find the slope of this graph, we need to figure out the rise and the run. So we're going to go ahead and pick 2 points. I'm going to go with this point and this point because they're on nice corners of the squares. We're not going to get any fractions or decimals or anything. So then we need to figure out the rise and the run. Well, the rise in this case is going to be 1, 2. We need to go up 2 squares to get to this point. And the run is going to be 1. We need to go over to the right 1 square. So rise over run is 2 over 1. 2 divided by 1 is 2. So our slope is going to be 2. So in our final equation, we're going to be replacing m with 2. So what about b? B is that mysterious y-intercept that I've been talking about. Well, the y-intercept is just where the graph intercepts y. A better way of putting it would be it's where it crosses over the y-axis. The y-axis is this up and down line here, because this is how you figure out y. This other line is called the x-axis. So we need to figure out where this line crosses the y-axis. Well, it looks like it's doing it right here. It's crossing this line right here. And what is the y value at this point? Well, from the beginning here, which is 0, it's up 1. So the y value of this point is 1. So our y-intercept is going to be 1. So we're going to replace b with 1. So now it's time to write our final equation. Y and x stay the same, and we replace m and b with the numbers that we just figured out. So y stays the same, equals m we're going to replace with 2, x plus, and then the b value that we just figured out, 1. So our final answer is y equals 2x plus 1. That is the equation of this line. So what about this line? Well, we're going to do it the same exact way. We're going to find the slope and the y-intercept, m and b. So let's go ahead and pick 2 points. I'm going to go with this one here and this one here. So now we need to find the rise and run. In this case, we're not actually rising, we're falling. So it's going to be a negative rise. So let's see how many squares we go down. 1, 2, 3, 4. We've gone down 4 squares. So the rise is going to be negative 4. Remember, it's negative because we're going down. And now we need to figure out the run. In this case, the run is 1, 2, 3. We've gone to the right 3 squares, so our run is 3. So our rise is negative 4, and our run is 3. So our final slope is negative 4 over 3. So that's what we're going to go ahead and put in for m once we're done. But now we need to find b. Remember, b stands for y-intercept. So we need to figure out the y-intercept of this graph. Where does the graph cross the y-axis? Well, in this case, it crosses the y-axis right here. This is where it crosses. So what is the y value of this point? Well, it's how high up it is from 0. Here's 0. 1, 2, 3. The y value in this case is 3. So our y-intercept is going to be 3. So let's go ahead and write our final equation. Our final equation is y equals, and remember m is now negative 4 over 3, x plus, and our b is 3. So our final equation is y equals negative 4/3 x plus 3. Here's another line to write the equation for, and what I'd like you to do is go ahead and pause the video, try to find the equation for this line, and then unpause and see how you did. Alright, so we're going to go ahead and find m first. Remember, m is slope, and that is rise over run. So we're going to pick out 2 points. Let's go with this one and this one. In this case, we're falling again, so our rise is going to be negative. So we go down 1 square. So our rise is going to be negative 1. But we're going to have a much bigger run, so let's find out. 1, 2, 3, 4. In this case, our run is 4. So our final slope is going to be negative 1 over 4. So now we just need to find our y-intercept. Where does it cross the y-axis? Well, it looks like it does it right here. It crosses that vertical line right here. So what y value is this? Well, it's how high up it is from 0. And in this case, it's actually lower than 0. So it's going to be a negative number. So our y value is going to be 1, 2. It's 2 below 0, so it's going to be negative 2. So our b is negative 2. So let's go ahead and write our final equation. Y equals, m in this case is negative 1 over 4, x, and then you could put plus negative 2, but that's the same thing as just saying minus 2. So we're just going to go ahead and put minus 2. So that's our final equation. Y equals negative 1/4 x minus 2. Here's one more line. Go ahead and pause the video and try to figure out the equation. So we need to figure out the equation of this line. We have a pretty steep slope here, so I would expect the slope to be pretty high. Let's go ahead and do rise over run to figure it out. So I'm going to pick this point and this point. We need to figure out how much it rises and runs. So it is rising 1, 2, 3. So the rise is going to be 3. And the run is just 1. So our rise over run is 3 over 1, which is just 3. So 3 is going to be what we put in for m once we're done. And now we just need to figure out the bool y-intercept. So where does it cross the y-axis? In this case, it looks like it does that right here. And it is below 0, so we're probably going to have a negative number. It goes 1 square below 0. So our y-intercept is going to be negative 1. So let's go ahead and write our final equation. Y equals, remember our m in this case is 3, x, and then we have minus 1. So we're just going to put minus 1. So our final equation in this case is y equals 3x minus 1. Oh yeah, finding the equation of a line. Oh yeah, that's easy. Where's the line? We need to find the equation of a line with just this information. We know that the line goes through 1, 3, and that the slope of the line is 2. Well, if you're familiar with slope-intercept form, then you'll know that the equation for a line is y equals mx plus b. If that doesn't sound familiar to you, I have a video on slope-intercept form that you can watch in the card on the corner of the screen right now. So in this case, we know what m is, right? We already know that m is 2. But what is b? Remember, b stands for y-intercept. So we need to figure out what b is, but we have no way of figuring out b. We can't even see the graph. So in this case, we need to use a new form of equation, and it's called point-slope form. So point-slope form is y minus y1 equals m times x minus x1. So what does this mean? Well, y and x are the same, right? And we know what m is. But instead of b, we're instead using x1 and y1, which basically you would put in a point into those letters. And we have a point right here, 1 and 3. So we would put in 1 for x1 because x is the number to the left, and 3 is y, it's the number to the right. So we would put that in for y1. Remember, we're still not putting anything in for x and y. They're going to stay x and y in the final equation. x1 and y1 is where we put in our point here. So we're going to go ahead and put in the numbers that we know. X and y stay the same, remember. So we have y minus, and now y1. The y of this point is 3. So 3 equals, we know that m, because which stands for slope, is 2. So we're going to put in 2. X stays x. And then x1 is the x of this point, which is 1. So here we have an equation for the line, but obviously this can be simplified, and our goal is eventually to make this, which is in point-slope form, into slope-intercept form. And we can do that just using algebra. So the first thing I'm saying is that this looks like the distributive property. So let's go ahead and do it. Remember, we need to multiply the 2 to both parts of what's in the parentheses. So to the x and to the minus 1. So 2 times x is, well, 2 times x. And 2 times 1 is 2. But remember, the negative sign has to go with it. So now, the last thing we need to do to get this to slope-intercept form, you notice that y is by itself. So just like solving a normal algebra equation, we need to isolate y to get it into this form. So we're going to add 3 to both sides. The minus 3 and plus 3 here cancel, and on this side, we're just left with y. But on the other side, we needed to do the same thing, add 3. The 2x stays the same, and in this case, we have minus 2 and then plus 3. That's the same thing as saying 3 minus 2, or you can think of it as you lost $2 and then earned $3. So in that case, you earned a total of $1. So our final equation is y equals 2x plus 1. Here's another example. We know that the line passes through the point minus 2, and that it has a slope of 1 over 2, or 1/2. We need to find the equation of the line. Well, remember, we know what the slope is already, 1/2, that's going to go for m, but we don't know what b is, so we're going to use point-slope form instead. So let's go ahead and replace the letters with what we know. Remember, y stays as y, and y1 is going to be the y of this point, which is minus 2. Now, because we have 2 minus signs here, what I would recommend is just put parentheses around this minus 2 so that you can tell that these are 2 separate minus signs. M we know is 1/2, x stays the same, and x1 is the x of this point, which is minus 2 as well. And we're going to go ahead and put parentheses around that. And there we go. We have our point-slope form equation, but we can simplify this down, and we're going to try to get it to this form. And we're going to do that by isolating the variable, y. So first of all, to make our lives easier, we have two negatives in a lot of cases. And remember, two negatives make a positive. So let's go ahead and replace all these with positives. Y minus minus 2 now becomes y plus 2. And x minus minus 2 becomes x plus 2. So now we can do the distributive property here. 1/2 times x plus 2. We're going to multiply on both sides. So in this case, we're going to have 1/2 times x, which is just 1/2 x, and 1/2 times 2. If you want, you can write this out for multiplying fractions. 1/2 times 2 over 1. Remember that a whole number like this, when it's not a fraction, it's just over 1. So this would be 1 times 2 is 2, 2 times 1 is 2, and 2 divided by 2 is 1. So it's going to be plus 1. So now our final step is to get rid of this plus 2 to get y by itself. So we're going to go ahead and subtract 2. This is going to cancel these out and leave us with y, because plus 2 and minus 2 cancel out. We have to do the same thing on the other side though. Minus 2 on the other side. 1/2 x stays the same. And on this side, we have plus 1 minus 2, which is minus 1. You gained $1 and then lost $2. So in total, you lost $1. So our final equation is y equals 1/2 x minus 1. All right, here's another example. What I'd like you to do is pause the video, try to do as much as you can, and then unpause and see how you did. So we know that the line goes through 3, 1, and that the slope is negative 1/3, or negative 1 over 3. So let's go ahead and write the point slope form. So y and x stay the same, remember, so we're just going to put y. And then we need to find y1. y1 is the y of this point, and the y is the one to the right. So y is 1. M is our slope. So remember, our slope is negative 1 over 3. We already know that from the problem. So we're going to put negative 1 over 3. And then we need to figure out x1. Well, that's the x of the point. In this case, that's 3. So now let's go ahead and do our distributive property here. Negative 1/3 times x is just negative 1/3 times x. And in this case, we have negative 1/3 times negative 3. We have two negatives, and remember, two negatives make a positive. So this is going to be a plus. You always got to remember those negative signs. That's one of the most common mistakes in algebra. So 1/3 times 3, if you wanted to write it out, you would do 1/3 times 3 over 1. And this would be 3 over 3. And 3 over 3 is 1. So it's going to be plus 1. And finally, we just need to get y by itself. We need to get rid of this minus 1. So we'll do the opposite, which is plus 1. That cancels these out, leaving you with just y. But you have to do the same thing on the other side. So we're going to add 1 to the other side. Negative 1 over 3x stays the same. And on this side, we have 1 plus 1, which is 2. So our final equation is y equals negative 1 over 3x plus 2. Here's another problem. Go ahead and pause the video and see if you can write the equation yourself. So here we have a line that goes through negative 5, 2, and the slope is 1/5. We're going to use point slope form again for this one. So here's our point slope formula, and we're going to go ahead and plug in what we know. Y and x stay the same, so we're going to leave it as y. y1 is the y of this point, which is 2, because y is the number to the right. We already know what m is. M is slope, and slope is 1/5. X stays the same, and then we need to find x1. x1 is the x of this point, which in this case is negative 5. But remember, we already have a minus sign here from the formula, and we're adding another minus sign. So now let's go ahead and clean up this, make this a positive, because two negatives make a positive. So this becomes x plus 5. And now let's go ahead and do our distributive property. Multiply 1/5 on both the x and the 5. So 1/5 times x becomes 1/5 x. Then 1/5 times 5, well, that's 1/5 times 5 over 1, which is going to be 5 over 5. And 5 over 5 is 1. So it's going to be plus 1. So now we just need to get rid of this minus 2 to get y by itself. And to do that, we'll add 2 to both sides. These cancel out, and you're just left with y on this side. And on the right, we'll have this 1/5 x stay, and 1 plus 2 is 3. So our final equation is y equals 1 over 5x plus 3. How do we write the whole equation of a line with just 2 points? So here's our first example. We need to figure out the equation of the line that goes through 0, 1, and 1, 3. Well, to solve this, we're going to be using something called point-slope form. So point-slope form is y minus y1 equals mx minus x1. If that doesn't sound familiar to you, I've actually already made a video on point-slope form that you can watch on the card, but I'll also quickly review it right here. So there's two important things that we need to find to be able to do point-slope form. We have m. M is the slope because for some reason they decided the letter m means slope. And we have x1 and y1. So the problem actually already gives us a lot of the information we need. X1 and Y1 can either be 0 and 1, or they can be 1 and 3. It doesn't matter. You can choose either one. Any point on the line is fine. So we're going to find the slope using the slope formula. And I've actually also already made a video on the slope formula. So if you're not quite familiar with that, you can watch the video on the card, but I'll quickly review it here as well. So the slope formula lets us find the slope of any line just as long as we have 2 points, which we do. They're right here, 0, 1, and 1, 3. So y2 means the y of the second point. Well, the second point is right here, 1, 3, and y is the number to the right because x is the number to the left. So in this case, that would be 3. So we're going to put 3 here for y2. Now y1 is the y of the first point. Well, here's the first point. 0, 1 is the first point. And the y of that point is 1 because it's the number to the right. So we're going to put in 1. Now we need to find the x of the second point. Here's the second point. The x is 1. And now the x of the first point. The first point's right here. And x is the one to the left, which is 0. So now we just need to do the subtraction. 3 minus 1 is 2, and 1 minus 0 is 1. And then 2 divided by 1 is just 2. So now we know that m is going to be 2 when we replace it in our equation. And since we already have x1 and y1 because they're a point, then we can just start our point-slope form. So let's start writing our point-slope form, replacing everything that we know. Remember that x and y just stay the same. They're going to stay as x and y in the equation. So we have y minus, and then y1. We know what y1 is. I'm going to choose this point to use just because they're smaller numbers and it'll make it easier. So y1 is the y, so that's 1. We know what m is. We just figured it out that m is 2. X stays the same. And then x1 is going to be the x of this point. And the x is 0, so we're going to put 0. So normally here you would have to do distributive property because, you have to multiply by both parts in the parentheses. But I feel like an easier way to do this would just be to see that this is x minus 0, and x minus 0 was just x. The minus 0 wasn't doing anything. So let's go ahead and change x minus 0 to just x. So now we have a nice equation, and our last step is to get this into slope-intercept form. Slope-intercept form is y equals mx plus b. So basically all we have to do is get y by itself. We have to isolate y, and we'll automatically have it in this format. So how can we get y by itself? Well, we have a minus 1 here, so we should do the opposite of minus 1, which is plus 1. So we add 1 to both sides. On this side, we are just left with y. And on this side, we are left with 2x plus 1. So our final equation is y equals 2x plus 1. All right, here's another example. We've got some negative numbers in this one. We need to figure out the equation of the line that passes through -2, -2, and 4, 1. So we're going to do this the same way. We're going to use point-slope form. And to do that, we need to figure out m, because we already have x1 and y1 there right here. So we're going to use our handy-dandy slope formula. So first, y2. y2 is the y of the second point. Our second point is here, 4, 1. So the y of this point is going to be 1, because it's the number to the right. Now y1, the y of the first point. Here's the first point. The y is -2. And notice how we have two negative signs here. Remember, this has a negative sign, but there's already a negative sign in the slope formula. So we need to have two negative signs. And I'm going to go ahead and put this in parentheses, just so that we remember that these are two separate negative signs. x2 is the x of the second point. Here's the second point. The x is the one to the left, so 4. And x1 is the x of the first point. Here's the first point, and the x is -2. And we'll go ahead and put this in parentheses as well, just to remember the same thing. So now remember, we have two negative signs here, and that can be confusing, but remember, two negatives just make a positive. So let's go ahead and change all these to positives. So right now we have 1 plus 2 and 4 plus 2. Well, 1 plus 2 is 3, and 4 plus 2 is 6. Now, 3 over 6 can be simplified. If we divide both the top and the bottom by 3, then it will simplify to 3 divided by 3 is 1, and 6 divided by 3 is 2. If you didn't immediately see that, then I think the good way to think about it is 3 is half of 6. So like, 6 slices of pizza, 3 slices would be half the pizza. If you see something like this, then you immediately know that it's going to simplify to 1/2. So our slope here is 1/2, and that's going to be what goes in for m. So we have all the information we need. Let's go ahead and do point slope form. So y minus y1. y1 is the y of, you can actually choose either point. I'm actually going to go with this point because there's no negative numbers in it, so that'll probably make our lives easier. So y1 is going to be 1, the one to the right. Now m, we just figured out that m is 1/2, so let's do 1/2. X minus and then x1. Remember, we're doing this point. You can't, this is a big mistake. You cannot switch points in between. You can't say, oh, well, y1, I like this y, so I'm going to go with this one. But then when you get to x1, you're like, oh, but I want to do this point now. You have to stay consistent with which point you're using. So we have to use this x right here, 4. So remember, our goal now is to try to get this into slope-intercept form. So we need to get y by itself on the side of the equation. And our first step in simplifying this down is to do the distributive property right here. Remember, when there's a number on the outside of parentheses like this, you have to multiply to each part of the parentheses. So 1/2 times x is just 1/2 times x. That doesn't change, right? Because you can't multiply a number and a letter. They just stay like this. And 1/2 times -4. Don't forget the negative, right? Well, 1/2 times 4, if you expanded it out as a fraction, you could do that. Remember, 4 is just 4 over 1. 1 times 4 is 4, and 2 times 1 is 2. And 4 over 2 is 2, 4 divided by 2. But you didn't even actually have to do this. You could have just looked here and seen 1/2 times 4. Remember, fractions are just division. So 1/2 times 4 literally just means 4 over 2. So remember, we need to keep the minus sign. So it's going to be minus 2, like we figured out here. So our final step in getting y by itself is to get rid of this minus 1. And we'll do that by doing the opposite of minus, which is plus. So y is now by itself because these cancel out. And on this side, we have 1 over 2x, and then minus 2 plus 1. So you lost $2, and then you gained $1. So you still are down $1, so that would be minus 1. So our final equation is y equals 1/2 x minus 1. Here's another example. What I'd like you to do is go ahead and pause the video, try to solve it yourself, and then unpause and see how you did. All right, so we need to figure out the equation of the line that passes through -1, 6, and 1, 0. We'll still be using point slope form, so we need to figure out m, which is slope. Slope. So we'll use our slope formula, y2 minus y1 over x2 minus x1. So y2 is the y of the second point. Here's the second point. The y is 0. y1 is the y of the first point. Here's the first point, and the y is 6. x2, the x of the second point. Here's the x of the second point, which is 1. And x1, the x of the first point. Here's the first point. The x is -1. And we're going to go ahead and put parentheses around this because these are two different negative signs. I mean, you don't have to, but it helps you realize that these are two different signs. So let's go ahead and do the subtraction. 0 minus 6 is -6. And two negative signs here. Remember, these make a positive. So we're left with 1 plus 1, which is 2. So now 6 divided by 2 is 3. But we do have a negative sign here, so that we have to put that here in the answer as well. And our final m is -3. So we have everything that we need to do point slope form. So let's go ahead and plug in what we know. Y minus y1 is the y of a point. I'm going to choose this point because there's no negative numbers in it and they're smaller, just makes things easier. So the y of this point is 0. Now m is -3. That's what we just figured out. X stays the same. Remember, x and y are going to stay the same in every equation. And then x1, we have to do the same point we used last time. So remember this one. We'll do the x of that point, which is 1. So you may notice that this -0 here isn't doing anything, so we can actually just cross this out. And we now have y by itself. But we still need to simplify this down with the distributive property. Remember, we need to multiply this -3 to both parts of the parentheses. minus 3 times x is just minus 3x. And now we have negative 3 times negative 1. Remember, when you're multiplying or dividing, two negatives make a positive. So negative 3 and negative 1, you can just act like these are positive. 3 times 1 is 3. And that's actually our final equation. There aren't any more steps to do because y is already by itself. This is already in the form y equals mx plus b. Here's one more example. Go ahead and pause the video, try to solve it yourself, and then unpause and see how you did. So we're going to figure out m using our slope formula like before. So y2 is the y of the second point. The y is 1. y1 is the y of the first point. Here's the first point, and the y is 3. x2 is the x of the second point. Here's the second point, and the x is 4. And x1 is the x of the first point. Here's the first point, and the x is 3. So now we just need to do the subtraction. 1 minus 3 is negative 2. Remember, you earned $1 and then lost $3, so you were down $2. 4 minus 3 is 1, and anything over 1 is just itself. So negative 2 divided by 1 is just negative 2. So our final m is negative 2. So let's go ahead and plug what we know into point slope form and see what we get. So y1, I'll go ahead and use this point because why not? The y of this point is 3. And now m, we've already figured out m, which is negative 2. X stays the same. And now the x of this point that we used before, x is 3. So now we just need to do distributive property. So negative 2 times x is just going to be negative 2 times x. And we have two negative signs here. So remember, these are a positive. So 2 times 3 is 6. So it's going to be plus 6. So now our final step is to get y by itself so that we can get the y equals mx plus b equation. So we're going to get rid of this minus 3 by doing the opposite of minus, which is plus. So on this side, we just have y because these cancel out. And on this side, we have negative 2x, and then we have 6 plus 3, which is 9. So our final equation is y equals negative 2x plus 9. It's time to start writing the equation of a line using parallel and perpendicular lines. And this is the point where you realize that you've probably heard those words in 4th grade and have never heard them ever since, and your math knowledge from elementary school is failing you. But don't worry, once you get the hang of it, writing an equation this way can actually be one of the easier ways of doing it. So here's our first example. We need to write the equation of a line that passes through 1, 2, and is parallel to y equals 2x minus 3. So remember, to write the equation of a line, we always need to figure out the slope. But how can we figure out the slope? It doesn't tell us the slope. We only have 1 point, so we can't use the slope formula. Like what do we even do? Well, for this, we need to go over what parallel and perpendicular lines are. So first is parallel lines. Parallel lines are just lines that perfectly line up with each other like this. They will never cross each other if they go on infinitely. Or at least these would be parallel if I could draw straight lines. So one thing to notice here is that parallel lines have the same slope. That's what makes them parallel. Perpendicular lines, on the other hand, are like the opposite of parallel lines. These would be an example of perpendicular lines. They perfectly intersect each other at these 90-degree angles. So if you want to think of this as like a road, parallel lines would be like two lanes on the same road. And perpendicular lines would be like an intersection. So in this case, we have parallel lines. Now, you may notice that we don't have the y-intercept anywhere here, and we can't figure that out. So we're going to use our handy-dandy point slope form. If this doesn't look quite familiar to you, I've actually made a video on point slope form before that you can watch on the card on the screen right now. But just as a quick review, point slope form requires you to know m, which is the slope, and requires us to know x1 and y1, which are just x and y of any point, which we do have a point right here, 1, 2. But how do we figure out the slope? Well, remember what I said earlier about parallel lines having the same slope? In this case, we can look at this equation of the line that it's parallel to. This minus 3 doesn't help us at all, so just ignore it. What we care about is right here, the 2x. Remember, 2 is the slope, that's m in y equals mx plus b. And parallel lines always have the same slope. So the slope of this new line is also going to have a slope of 2. So we actually already have all the information we need to do point slope form. So let's replace these letters with what we know. Remember, x and y always stay the same in these equations. So y minus. Now y1 is the y of this point, which is 2. Now m we just figured out is 2. X stays the same. And now x1 is the x of this point, which is 1, because x is the number to the left, y is the one to the right. So we already figured out point slope form. Here it is. So now our final step is to get this into slope-intercept form, which is y equals mx plus b. And basically to get into slope-intercept form, we just need to get y by itself. You see how y is by itself in this form? So first, I see this distributive property thing here. Remember, when there's a number on the outside of parentheses, you have to multiply it to both parts of the parentheses. So y minus 2 stays the same. And then we're going to multiply this out. 2 times x is just 2 times x. And 2 times negative 1, well, 2 times 1 is 2. But remember, the negative sign has to stay. So now our final step in getting y by itself is to get rid of this minus 2. So we can do that by doing the opposite of minus 2, which is plus 2. So these cancel out, and you're just left with y. And on this side, we have 2x. And you'll notice here, this is minus 2 plus 2, which also cancels each other out. So our final equation is just y equals 2x. I know we don't have the plus b here, but in reality, this is actually plus 0. It still follows this form. It's just we don't have to include the plus 0 because there's no point. A plus 0 doesn't do anything. So how do we do this if we have a perpendicular line instead of a parallel line? Well, we'll do the same thing. We'll use point slope form. But now how do we figure out m? Because we don't have a parallel line that just tells us m. Well, we can actually figure out the slope still this way. And again, we're going to be ignoring this plus 4 because that doesn't help us. We just care about this. So here's how you figure out the slope with a perpendicular line. The slopes of perpendicular lines are always negative reciprocals. What does that mean? Well, we have 3 over 2, right? To figure out the slope of this new line, you need to figure out the negative reciprocal. So the reciprocal of a fraction just means flipping the fraction. So the reciprocal of 3 over 2 just means 2 over 3. Just flip the two numbers. But the negative reciprocal means you flip it and you have to change the sign. So we have to make this negative 2 over 3. If this was negative 3 over 2, then this would become positive 2 over 3. You basically just flip whatever the sign is. So the m of our new line is going to be negative 2 over 3. So now we already have all the information we need to do point slope form. So let's go ahead and do that. Y stays the same. Y1 is the y of this point. Y is the one on the right, which is 1. And now m, we figured out the m of this new line is negative 2 over 3. X stays the same. And now x1 is the x of this point. X is negative 3. Now you may notice we have 2 minus signs here. 2 minuses make a positive, but for now, we'll just go ahead and put parentheses around this so that we know that these are 2 different negative signs, and we'll deal with it later. So now we need to do the same thing as we did before. We need to get this into y equals mx plus b. So first we need to simplify this. We need to make this distributive property by multiplying to both parts. And now we'll just deal with this right now. We'll go and turn these into positive signs because 2 negatives make a positive. So negative 2 over 3 times x is just negative 2 over 3 times x. And now we have 2 over 3 times 3. Well, we can multiply this out as fractions. So 2 over 3 times 3, remember 3 would just be 3 over 1. And we'll go ahead and multiply these out. So 2 times 3 is 6. And 3 times 1 is 3. And 6 divided by 3 is 2. So our final multiplication is 2. But remember, we have a minus sign here. We can't forget the minus sign. The minus sign has to carry over. So we're going to have minus 2. So now our final step is to get y by itself. Because y equals mx plus b, y is by itself. So we need to do the opposite of minus 1, which is plus 1. These cancel, and you're just left with y on this side. But on the other side, we have minus 2 over 3x and minus 2 plus 1, lose $2, get $1 back. You still are missing $1, so minus 1. So our final equation is y equals negative 2 over 3x minus 1. So here's our next example. What I'd like you to do is go ahead and pause the video, try to figure out the equation of this for yourself, and then unpause and see how you did. All right, so we know that our line passes through negative 2, negative 1, 2 negative numbers. Always so fun. And then we have parallel to y equals negative 1 over 2x minus 2. Well, whenever I see the word parallel, I breathe a sigh of relief because that's easier than perpendicular. So let's go ahead and do our point slope form. So we need to figure out m. Well, remember, parallel lines always have the same slope. So we're going to ditch this minus 2, no one cares. And we have our m right here, negative 1 over 2. So that's going to go in for m. So let's go ahead and do our point slope form. Y minus, and then y1 is the y of this point, which is negative 1. And we'll go ahead and put parentheses around this because we have two negative signs. M is negative 1 over 2. X stays the same. And then x1 is negative 2. And we'll do parentheses again. You don't have to do parentheses, but it's easier for me to see that these are two different minus signs. So we have a bunch of double negatives here, so we can turn those into positives. So we'll do it right here, and we'll do it right here. So this is y plus 1, and on this side we need to do distributive property. Multiply to both parts of this parentheses. So negative 1 over 2x is just negative 1 over 2x. And negative 1 over 2 times 2. Well, we can multiply this out with fractions if you want. 1 over 2 times 2, remember 2 is just 2 over 1. This is 1 times 2 is 2, 2 times 1 is 2, and 2 over 2 is 1. But remember, we have one negative sign here, so the negative sign has to follow through. So minus 1. So our final step is to get y by itself, so that we have y equals mx plus b. So we need to do the opposite of plus 1, which is minus 1. On this side, we're left with y because these cancel out. Then on this side, we have negative 1 over 2x, and then minus 1. You have to do it to both sides of the equation. So then minus 1 is minus 2. So our final equation is y equals negative 1 over 2x minus 2. So here's another example problem, and it's another perpendicular line example problem. So go ahead and pause the video, try to find the equation yourself, and then unpause it and see if you got it right. So it passes through 4, 0, and it's perpendicular to y equals negative 4x minus 7. So we're going to do point slope form again. So we need to figure out m. Remember, it's not so easy with a perpendicular line. We have to do the negative reciprocal. So how do you find the reciprocal with an m that isn't even a fraction? Well, remember, any number that's not a fraction is really just over 1. So we have negative 4 over 1. So we need to find the negative reciprocal. So the reciprocal means flipping the fraction. So 4 over 1 becomes 1 over 4. But now we need to do the negative reciprocal, and that means changing the sign. Well, there's already a minus here, so it's going to become a plus. Plus 1 over 4 is going to be our m. So let's go ahead and plug in what we know. Y and x stay the same, remember that. So y minus y1 is going to be the y of our point. Here's our point. The y is the one to the right, which is 0. M we just figured out is 1 over 4. X stays the same. And then x1, the x of this point is 4. So minus 0, remember, minus 0 doesn't do much of anything, so we can just get rid of this, and we're just going to have y here. But now we need to do the distributive property. Multiply on both of these sides. So 1 over 4 times x is 1 over 4 times x. And now we have 1 over 4 times negative 4. Well, let's go ahead and multiply this out. 1 times 4 is 4. 4 times 1 is 4. And 4 over 4 is 1. 4 divided by 4. It's a lot of 4s. But now we need to take this negative sign because we have one negative sign. It carries over. So it's minus 1. And that's actually it. We don't have to do anything else because y is already by itself. So our final equation is y equals 1 over 4x minus 1. It's time to start graphing lines, one of the most mysterious parts of algebra that people seem to struggle with all the time. But soon you'll be able to graph an equation in just a few seconds. So right now we have our favorite background on, the graph background. And we need to figure out the equation of y equals 3x plus 1. How do we graph that? Well, if you remember Slope-Intercept Form, which is y equals mx plus b. If you're not quite familiar with Slope-Intercept Form, I actually have a video on it that you can watch on the card on the screen right now. But just as a quick review, m means slope, and b equals y-intercept. I didn't choose those letters, okay? So if you look at these two equations, I mean, this seems to fit this format really well. It's just that m is replaced with 3, and b is replaced by 1. So we need to graph the equation where the slope is 3 and the y-intercept is 1. Well, y-intercept is just where it crosses the y-axis. Remember, the y-axis is this big vertical line here on our graph. The x-axis would be this horizontal line. So it needs to cross the y-axis at 1. So we're going to start here at 0 and go up 1. So right here is where it crosses the y-axis. So now we just need to figure out a slope of 3. Well, remember, slope is rise over run. So we don't have a fraction here, but remember that if you just have a number, then it's over 1. So the rise and run is going to be 3 over 1. So we need to get another point that rises 3 and runs 1. So we're going to rise 1, 2, 3. And then we're going to run 1. And that'll give us our next point. So now we just need to draw a line that connects these two. If you were doing this on paper, normally you would have a ruler of some sort, but I don't. So I'm going to do a terrible attempt to draw a straight line. Oh, this is going to go so bad. Here we go. We're drawing the line. Okay, now we got to do it the other way. Okay. Okay. That's actually not as bad as I thought it would be. We don't talk about how this is my second take. I'm trying. I'm trying. I can't. I'm doing it. So we can just erase all of these random rise over run marks, whatever they're not necessary. So we have our final line here. This is the line of y equals 3x plus 1. Of course, a little more straight than that. So here we have another equation that we need to graph. But you may notice problem with this. It's not in y equals mx plus b. You see here that we have y plus 3 equals 1 over 2x. It's like b is over here or something for some reason. So how do we get this equation into y equals mx plus b? Well, y equals mx plus b, y is by itself. So in this equation, we need to try to get y by itself as well. So we can get rid of this plus 3 by doing the opposite of that, which is minus 3. So we subtract 3 from both sides. These cancel out. And on this side, we're just left with y. And on this side, we need to do the same thing. So minus 3. This has an x and this doesn't, so you can't actually subtract these, but we'll just leave it as 1 over 2x minus 3. And now you'll see that this actually fits y equals mx plus b. The b is right here, and the m is right here. So you might say, oh, okay, so let's start graphing, right? 3. Y-intercept is 3, so let's go to 3. No, stop. You have to remember this negative sign. This is like the most common mistake in graphing on the face of the planet, is forgetting this minus sign. The minuses have to stay. So our b is actually minus 3. So we need to go down 3. 1, 2, 3. So our dot is going to be right here. So now we need to figure out a second point. And we have our m here, our slope of 1 over 2. So remember that slope is rise over run. So 1 over 2. Our rise is going to be 1, and our run is going to be 2. So let's go ahead and rise 1. And then we can run 2. And here's our second point. Now, you could just draw a line through this. Yeah, that works, and you can try that. If you want to make a little bit more accurate straight line, then you can actually just do the rise over run again if you wanted. So we can rise another 1 and then run another 2, and then that'll give us another point. So then that can help you draw a straight line, but you only need 2 points. That's not necessary. So now we have to draw a straight line. Oh, it's so bad. Oh, here we go. Oh, that's okay. That's actually not too terrible. So this is the final line of our equation. Y plus 3 equals 1 half x. We just had to do a little extra algebra to get there. So here's another example. What I'd like you to do is go ahead and try to graph this yourself by pausing the video and unpausing when you're done and see if you got it right. So remember, we need to follow the form y equals mx plus b. And it looks like it already follows that, right? We have our m here, and we have our b. So let's go ahead and graph. Our b in this case is 3 plus 3. So we need to go up 3 from the middle. 1, 2, 3. And we'll put our dot right here. So that's our first point. But we need to figure out a second point. So we'll find our slope, which is rise over run. So our slope is not 2, negative 2. And because this is a whole number, not a fraction, remember whole numbers are always just over 1. So our rise is going to be -2 and run is 1. But how do we do a negative rise? Well, remember, a negative rise just means we're falling. So we are going to go down 1, 2. And then we are going to run 1. So here's our second point. And if we wanted to make this a little more accurate, we could just do that again. So fall 2, go over 1. And now here comes the part of trying to draw a straight line on this thing. What's that? Oh. Okay, it's not good, but it's not bad. So this is our final line here. Y equals -2x plus 3. Here's our final example. Go ahead and pause the video, try to solve it yourself, and unpause and see how you did. You may have to do a little algebra. I'm sorry. So, as you can see here, this looks nothing like y equals mx plus b. But remember, we just need to get y by itself. So let's get rid of this minus x so that we can leave 2y by itself. We won't get rid of the 2 yet because the 2 is more attached to the y. So we can get rid of minus x by doing the opposite of minus, which is plus. We'll go ahead and add x to both sides. So these cancel, and on this side we just have 2y. And on the other side we have 4 plus x, which is just 4 plus x. So now to get y by itself, remember these are being multiplied together. Whenever there's a number and a letter next to each other, it's multiplication. So we need to do the opposite, which is division. We will divide both sides by 2. So these cancel, and on this side, we're just left with y. And on this side, we have to divide both of these by 2. So 4 divided by 2 is 2, and x divided by 2 is just x over 2. Now, this actually is y equals mx plus b, but you see the x is actually on the right side. So what we can do is we can just go ahead and flip these around. So x over 2 plus 2. That's fine. We can do that. And then that'll look more like y equals mx plus b. So let's go ahead and put our y-intercept down, which is plus 2. So we will go up 2 from the middle and put our dot there. But now we need to figure out the slope. And I know a lot of people can be confused because we're used to having a number and then x, but in this case we have x over a number. Well, x over 2 literally just means 1 over 2 times x. Those mean the same thing. So don't worry about having the x on the inside, just write it as 1 over 2x. So we can figure out our rise over run. Our rise is going to be 1, and our run is going to be 2. So let's go ahead and do our rise over run. It's going to rise 1 and run 1, 2. So our point is here. And we could do that again if we wanted. So now let's go ahead and try to draw a straight line. So here's our line, and we're done. 2y minus x equals 4. This is the line for that graph. There are two main differences between graphing a line and graphing an inequality. So let's go over how to do it. So here's our first example. We need to graph the inequality of y is greater than 1/2 x plus 1. So you may notice that this looks like slope-intercept form. Slope-intercept form is y equals mx plus b, and that's how you would graph a line. And this looks exactly like a line that we would graph. The only difference is that we have a different sign than equals. So our first step here is going to be to graph this as if it was a line. So if you're not quite familiar with how to graph a line, I have a video on it that you can watch on the card on the screen right now, but I'm also going to quickly review it here. So basically, m here is the slope, right? So in this case, m is going to be 1/2. And b is our y-intercept, so that's going to be 1. So first, let's go ahead and graph the point that has a y-intercept of 1. That's where it crosses the y-axis being this big vertical line here. So we're going to go ahead and plot the point where this crosses 1. 0 is right here, and we're going to go up 1. So our y-intercept is going to be right here. And now we just need to graph the slope. Remember that slope is rise over run, and our slope here is 1/2. So in this case, the rise is going to be 1, and the run is going to be 2. So let's go ahead and graph that. We're going to rise 1, and then we're going to run 1, 2. And here's our point. And now if you wanted it to be a little more accurate to help you draw a straight line, we can do it one more time. So we can rise 1, and then run 2. So we have our points here to graph the line. And normally when you're graphing a line, you would just go ahead and draw this right away. But because this is an inequality, you need to ask yourself one more question. Does this sign here have a line under it or not? If it did have a line under it, then it would look like this, and that would be greater than or equal to, which means that all the numbers greater than are in the answer, but also equal to is in the answer. So that means that this line would be a part of the answer. But in this case, this sign does not have a line under it, which means that everything above the line is going to be correct. But exactly on the line is not correct. So instead of just drawing a regular line, we have to draw a dashed line. So here is our extremely terrible dashed line drawn across these dots. It's a dashed line because it is not part of the answer. So our final step here for inequalities is we have to shade in the part of the graph that's correct. Now in this case, we have a greater than sign. So everything that is higher up than this line is going to be correct. So we're going to shade in everything that's higher than this line. So here it is shaded in. Everything that is higher up than this line is correct because it's greater than. If it was less than, we would have shaded in below the line. So this is the final graph of y is greater than 1/2 x plus 1. Here's our next example. Now we're going to do this the same way as we did last time, except you may notice that this time the equation is not in slope-intercept form. In slope-intercept form, y is by itself on the left side of the equation. But in this case, y is not by itself, it's got a plus 2. So we need to rearrange this equation so that it looks like slope-intercept form. So we need to get y by itself. We can get rid of this plus 2 by doing the opposite of plus 2, which is minus 2. So these cancel out, and on this side, we're just left with y. And on the other side, we have 2x minus 2, which we can't subtract, so we're just going to leave it the same. And this sign is just going to carry over. So now we have a line in slope-intercept form that we can graph. So let's go ahead and graph it. Remember that the number next to x is m, the slope. So our slope is going to be 2. And our y-intercept is going to be not 2, negative 2. We've got to remember that sign. So this is going to be negative 2. So let's go ahead and graph our line to start off. We're going to start with the y-intercept, which is minus 2. So we're going to start in the middle and go down 1, 2. This is where the line is going to cross the y-axis. And now we just need to graph our slope. Remember that slope is rise over run. In this case, our slope is 2, and anything that's not a fraction is just over 1. So our rise is going to be 2, and our run is going to be 1. So let's go ahead and plot this slope. We're going to rise 1, 2, and we're going to run 1. So this is our new point. And if we wanted to, we could do that again to make it a straighter line. We could go 1, 2, and then 1. You don't actually have to do this. This is just a way to make it a straight line. If you could just take a ruler and draw through these 2 points, that would be fine as well. So now we need to ask ourselves, do we have to draw a dashed line or a regular line? Well, if you look at the sign here, this sign has a line under it. The line means or equal to, which means that this line is going to be part of our answer. So we can just draw a normal, not dashed line. Wow, that was a terrible line, but you can see here that it's somewhat straight, and it is indeed part of the equation. So we are going to leave it a solid line, not a dashed line. So now we just need to figure out which side of this line to shade in. Over here, you can see that the sign here is less than, which means everything that's lower than the line, we need to shade in. So in this case, that's going to be this area. So here is the shaded in area, and this is our final graph of y plus 2 is less than or equal to 2x. Okay, here's another example. What I'd like you to do is go ahead and pause the video, try to graph this yourself, and then unpause and see how you did. Alright, so we have y is greater than or equal to 3 over 2x minus 3. So this is already in slope-intercept form, so we can just go straight to graphing it. So remember, m is our slope, so our slope is going to be 3 over 2. And b is our y-intercept, so that's going to be not 3, negative 3. Don't forget those minus signs. So we're going to go ahead and graph our points. First, we need to do the y-intercept, which is where it crosses the y-axis. Negative 3 means we need to go down 3. So here's where we're starting, right in the middle. 1, 2, 3, right here. And now let's plot our slope. Remember, slope is rise over run. So our rise is going to be 3, and our run is going to be 2, because this is our slope, 3 over 2. So let's go ahead and do that. Our rise is going to be 1, 2, 3, and the run is 1, 2. So now we need to figure out what kind of line we need to draw. Is it going to be dashed or solid? Well, here we have a line underneath our sign here. That means equal to, which means the line is going to be part of the answer. So we need to draw a solid line. So here's my, wow, the lines just get worse and worse every equation. This is our line, I guess. And now we need to figure out which side of the line we need to shade. In this case, this is greater than, not less than, right? So greater than means everything that's above the line needs to be shaded in. So here is our shaded in area, and we're done. This is the graph of y is greater than or equal to 3 over 2x minus 3. Here's another example. Go ahead and pause the video, try to solve this for yourself, and then unpause and see how you did. All right, so this is not in slope-intercept form, unfortunately. So we need to get this into slope-intercept form by getting y by itself. So how can we get y by itself? We've got two different things on y's side of the equation. The best thing to get rid of would be this plus 4 first, because the 2 is more attached to the y, and then we're going to deal with fractions and stuff, and we don't want that. So let's go ahead and get rid of this 4 first. So we've subtracted 4 from both sides so that these cancel out, right? The opposite of plus 4, minus 4. And on this side, we're just left with 2y. The sign stays the same. And on the other side, we have x minus 4. You can't really subtract a letter and a number, so it's just going to stay as x minus 4. And now the final step of getting y by itself is to get rid of this 2. Remember, this is multiplication whenever a number and a letter are next to each other. So we need to do the opposite of multiplication, which is division. We're going to divide both sides by 2. So this side, these cancel out, and we're just left with y. And on the other side, you see that we have two different things here divided by 2. So we need to divide 2 on both of them. So in this case, we just have x divided by 2. And on the other side, remember the sign, we got to keep the minus sign. And then 4 divided by 2 is 2. Now this is in slope-intercept form. We have y by itself, and then we have our x, and then plus b. You may be wondering how we're supposed to find the slope when x is like inside of the fraction. Remember that if we have x over 2, that's the same thing as just saying 1 over 2x. So let's go ahead and graph this. Remember, our y-intercept is going to be minus 2. We have to keep the minus sign. And our slope is going to be 1/2. So let's go ahead and graph our y-intercept. We're going to start in the middle and go down 1, 2. This is going to be where it crosses the y-axis. This is our y-intercept. And now we need to figure out the slope. Remember, slope is rise over run. So our rise is going to be 1, and our run is going to be 2. So let's go ahead and graph that. Our rise is 1, and our run is 1, 2. And if you want, we can do that one more time. Rise 1, run 2. So now we need to figure out if we have a solid line or a dotted line. In this case, the sign here does not have an underline under it. So that means we need to draw a dotted line. So here is our dotted line, a little bit better than last time, but still not good. So now we need to figure out which side of the line to shade. Well, this is less than, and less than means everything below the line. So we're going to go ahead and shade everything that's below the line. So there we go. This is the final graph of 2y plus 4 is less than x. It's time to start learning how to solve systems of equations, which is two equations at once. And the first way that you're going to learn how to solve them is a table. You will literally never do it this way ever again after today. But yeah, you're here anyway, so let's learn how to do it. So here's our first example. We need to solve for both x and y. And we can do that because we have two equations. As long as you have the same number or more equations as you do the number of letters, you can solve for any amount of letters. So to solve using a table, what we need to do is guess and check. So we need to pick a number for x, and then we're going to plug it into both of these equations and see what we get for y. And if we get the same number for y on both equations, then that means we found our answer. So here's the table we're going to be using. We're going to put in a number for x, get something for the first equation and the second equation. So let's go ahead and start by using 0 for x. We'll start with some simple numbers. We'll start with the first equation, y equals x plus 1. So if we plug in 0 for x, that just means we're replacing x with 0. So let's go ahead and do that. In this case, we have y equals 0 plus 1. Now, 0 plus 1 is 1. So in this case, y is going to be equal to 1. So we're going to go ahead and put 1 here in our table. So now let's do the same thing on the other equation. Y equals 2x minus 2. Let's go ahead and replace x with 0. And you'll notice here that the x is next to a number. We're going to go ahead and put 0 in parentheses, just so that we can tell that these are two different numbers. If we had just put this without parentheses, then it would say 20, and we don't want that. So remember that if you have two numbers next to each other like this, or a number next to a letter, that means multiplication. So 2 times 0 is 0. And we're just going to carry the minus 2 down. and 0 minus 2 is negative 2. So our y of the second equation is negative 2. So we're going to go ahead and put that in our table. So we have not found the correct answer because 1 and negative 2 are different numbers. So let's go ahead and try 1 for x. So let's go ahead and plug in 1. Y equals 1 plus 1. 1 plus 1 is 2. So y is equal to 2. So we're going to go ahead and put in 2 on our line right here. Now let's go ahead and try the other equation. Y is equal to 2 times 1 minus 2. Well, 2 times 1 is 2, and then minus 2. And 2 minus 2 is 0. So the second one is going to be 0. So 1 is not correct either. So we need to figure out what number to guess next. You could always use any number, but what I'm noticing here is, you see how these two numbers here, they are 3 apart from each other. And these numbers here, they're only 2 apart from each other. So what that tells me is we want them to be 0 apart from each other. So if we keep guessing higher numbers, they're going to get closer and closer together. So let's go ahead and try 2. Y equals, we change x for 2. 2 plus 1. 2 plus 1 is 3. So y is going to be equal to 3. And we'll go ahead and put that in our table. Now let's do the same thing for the other equation. Y equals, we're going to plug in 2, and the minus 2 carries over. So 2 times 2 is 4, and then minus 2 carries over again. 4 minus 2 is 2. So we're going to go ahead and put in 2 in our equation. And you'll notice here we're even closer now. 3 and 2 are only 1 apart. So I have a feeling that if we keep going higher and try plugging in 3, that's going to end up being our answer. So let's go ahead and put 3 in our table. And now I'm realizing that we're running out of room here. You see 3, it's right there. Y equals, in this case, it's going to be 3 plus 1. 3 plus 1 is 4. So y is 4. So we're going to go ahead and put in 4 into our table. And now let's do the same thing on the other equation. Y equals 2 times 3 minus 2. 2 times 3 is 6 minus 2. 6 minus 2 is 4. So we're going to put in 4. And as you'll see, here we have two numbers that are equal. So we figured out our answer. But what is it? Well, remember, we're solving for x and y. We know what x is. X is 3. And in both cases, y was 4. So y is 4. So there's two ways you can write your answer. I guess it just depends on what your teacher or professor prefers. You could write this as x equals 3 and y equals 4. That's true. We solved for x and y. Or you could write this as a point on a graph, which you would put the x on the left and the y on the right. So it would be 3, 4. So there we go. Our answer is x is 3 and y is 4. So here's another example. What I'd like you to do is go ahead and pause the video, try to solve this one for yourself, and then unpause it and see how you did. So you may notice here that these look a little different. Y is not by itself this time. Before, when we plugged something into x, it was super easy. We just solved everything and it was already equal to y. But in this case, y is not by itself. So there are two ways that we can do this, and either one is fine. You could just make a table immediately and go ahead and do it. You'll plug in something for x, and then you'll probably have to do a little one-step algebra equation or something to figure out what y is equal to. Your second option, and arguably the faster way to do it, is to solve these for y first, and then go ahead and do the table so that you don't have to keep doing it over and over and over again. So in this case, we have both equations not solved for y. So let's go ahead and solve these for y. So x plus y equals 5. To solve it for y, we need to get y by itself. And to do that, we'll get rid of this x. So we'll get rid of this x by subtracting it from the equation. So these cancel, and on this side, we're just left with y. We have to do the same thing on the other side. So 5 minus x is, well, 5 minus x. So this is our first equation, y equals 5 minus x. So now let's solve for y on the other equation. In this case, we need to get rid of this 2x to get y by itself. So we need to subtract 2x from both sides of the equation. On this side, these cancel out. And no, we're not left with just y. Remember, this minus sign is to say we're left with minus y. And on the other side, we're left with 1 minus 2x. So now how do we get rid of this minus sign on y? Well, there are two ways you can think about this. You can just add a negative sign to both sides of the equation. these two would turn into a positive, and we're just left with y. And on the other side, we have to apply the minus sign to both parts of this parentheses. So we have minus 1, and then we have minus 2x. Two minuses make a positive, so we're going to have plus 2x. The other way you could have thought about it, it's quite literally the same thing, but remember that if you have a minus sign, like minus y, this is really saying minus 1 times y. So if you want to think of that as a minus 1, you divide both sides by minus 1. It would do basically the same thing. So this is our final equation on the second side. So let's go ahead and do our table. I've gone ahead and changed the problem to our new equations just so that we avoid any confusion here. These are the equations we're going to be using because these are equal to the ones that we had before. So to make things easier, as always, we're going to go ahead and start with 0. And we're going to go ahead and plug in 0 into both of these equations. So y equals 5 minus, remember x is being replaced with 0, and 5 minus 0 is 5. So y is going to be equal to 5, and we'll go ahead and put 5 into our table here. So now let's plug in 0 into the other equation. Y is equal to negative 1 plus 2 times 0. And remember, we're putting in parentheses so that this doesn't look like a 20. So y is equal to negative 1 plus, and remember, 2 times 0 is just 0. And negative 1 plus 0, well, the 0 isn't doing anything, so y is equal to negative 1. So we're going to go ahead and put in negative 1 as our answer here. Now, 5 and negative 1 are pretty far apart, so I think we're kind of far from the answer, but let's go ahead and test out 1. So y is equal to 5 minus 1, and y is equal to 4, because 5 minus 1 is 4. So we're going to go ahead and put 4 into our table here. And now we're going to go ahead and plug in 1 on the other one as well. Y is equal to negative 1 plus 2 times 1. So y is equal to negative 1 plus 2 times 1 is 2. So we have negative 1 plus 2. That's the same thing as saying 2 minus 1. So 2 minus 1 is 1. So we're going to go ahead and put 1 into our table. So before, when we put in 0, these numbers were 6 apart. They were pretty far apart, right? But in this case, 4 and 1, they're only 3 apart from each other. So we're pretty quickly getting closer to the answer if we keep going this direction with our table. So let's go ahead and keep going this direction by trying out 2. Now let's say that these numbers were actually getting farther apart as we got bigger numbers. Then we would actually start testing out numbers the other way. So we would start testing out negative 1, negative 2, and so on. So let's go ahead and test out 2. Y is equal to 5 minus 2. So y is equal to 3. So we're going to go ahead and put in 3 in our table here. Now let's try out the other equation. So we're going to put in 2 for x here. 2 times 2 is 4. And negative 1 plus 4, that's the same thing as saying 4 minus 1. 4 minus 1 is 3. So we're going to put in 3 in our table here. And you'll see that these are the exact same number. So we found our answer. So how would you write our answer? Well, x is going to be 2, and y is going to be 3, right? Because it's 3 in both equations. So we're either going to write our answer as x equals 2 and y equals 3, or we could write it as a point on a graph, which would be 2, 3. So there you go. Our answer is x is 2 and y is 3. It's time to start solving systems of 2 equations using graphing. And if you're not a fan of graphing, then don't worry, you will never be solving systems of equations this way ever again. So here's our first example. We need to use this graph to solve this system of equations. Now, a system of equations basically is just a fancy way of saying we have 2 equations here, and we also have 2 letters. In a normal equation, you wouldn't be able to solve for 2 letters. That doesn't make sense. But you can always solve for any amount of letters as long as you have that many equations or more. So since we have 2 equations, we can solve 2 letters at once. So the basic idea of this is we're going to go ahead and plot both of these equations on the graph. And wherever they intersect each other, wherever they cross over each other, is going to be where our answer is. So you'll notice that both of these equations are in the form y equals mx plus b. This is the form that you need to graph a line. M is the slope, the slope, and b is the y-intercept. So we can graph both of these equations on the graph immediately. If you're not quite familiar with how to graph a line, I do have a video on it that you can watch on the card. You can watch that first and then come back here. Or you can just watch this, I'll quickly review it. So remember that if there's not a number next to x, if x is just by itself, then that means we have like an invisible 1 here. This is another number 1, And because we have minus x here, that actually also means minus 1x. So our slopes are going to be 1 and minus 1. So let's go ahead and graph this line first. We're going to graph the y-intercept first, the plus b. In that case, that's 1. That's going to be where it crosses the y-axis, this big vertical line here. So we need to plot where it crosses the y-axis at 1. So here's 0 right in the middle. We're going to go up 1. So our first point is going to be right here. Then we need to find the slope. Remember, the slope is 1, and slope is rise over run. A number by itself is just over 1. So both our rise and our run are going to be 1. So let's go ahead and plot that. We're going to rise 1 and run 1. So our point is going to be here. And we can do that again if we want to help us draw a straight line. We can rise 1, run 1. So let's go ahead and draw a line through these points from left to right, and we'll have our line. Now, the biggest issue with this is trying to draw a straight line. So that's going to be a challenge. So after like 3 attempts of trying to draw a straight line, here's our line, right? We have the line of y equals x plus 1. So now we need to draw the line of y equals negative x plus 3. So our y-intercept here is going to be 3. So let's go ahead and graph 3 as our y-intercept. We're going to start in the middle and go 1, 2, 3. Here's our point. That is our y-intercept. So now we need to graph the slope. In this case, it's minus 1, and it's not a fraction, so remember that would just be over 1. So in this case, our rise is actually going to be negative 1. A negative rise means we're falling. So we're going to go ahead and fall 1, and then we're going to run 1 also. So we have our point here. And we can do that one more time if we want to get a straight line. Down 1, over 1. So let's go ahead and make another sad attempt of drawing a straight line. Nice, it's even worse than before. So we have our 2 lines here. So the final question to ask is, where do these cross each other? Well, it looks like they cross each other right here. So we need to figure out what are the coordinates of this point. Remember, coordinates are written as x and y. So the x of this point is how far to the right it is. We'll start in the middle, it goes right 1. So the x is 1. And it goes up 1, 2. So the y is going to be 2. So our coordinates are 1, 2. And that's our answer. Our answer is 1, 2. Here's another example. What I'd like you to do is go ahead and pause the video and try this out for yourself, and then unpause and see if you got the right answer. Alright, so we need to graph both of these lines first. And you'll notice here, this equation here is in slope-intercept form, y equals mx plus b. And we can tell that because y in y equals mx plus b is by itself. And y is by itself here, everything else is to the right. But this equation here looks really weird. And that's because y is not by itself in this equation. So we're not going to be able to graph it. So what we're going to do before we do anything else is we are going to get y by itself in this equation so that we can graph it. So the first step of getting y by itself is to get rid of this plus 2. We could get rid of this 2, and that would be fine, but the easiest thing to do in this case would be to get rid of this plus 2, because the 2 is more attached to the y. We'll get rid of that last. So we're going to subtract both sides by 2. On this side, these cancel out, and we're just left with 2y. On the other side, 2x minus 2. This has an x and this doesn't, so you can't really subtract these. So we're just going to leave it as 2x minus 2. So the last step of getting y by itself, remember this is multiplication because there's not a sign in between. So we're going to do the opposite of multiplication, which is division. We're going to divide both sides by 2. So on this side, these 2's cancel out, and we're just left with y. And I'm going to move this over because my head is in the way. And on the other side, we are going to divide 2 on both of these parts of the equation. You see, we have a 2x and we have a minus 2. So 2x divided by 2, the 2's would cancel out, and we would just be left with x. And the other side, 2 divided by 2 is 1. But remember, this minus sign needs to stay. So we're going to put minus 1. So our equation is y equals x minus 1. So let's go ahead and replace this equation with our new one. So here's our new equation. Remember, this is equal to the old one, so we can do this. So let's go ahead and graph both of these. Remember that y equals mx plus b is slope-intercept form. So in this case, in our first equation, m, the slope, the slope, is going to be 2. And our y-intercept is going to be not 3, negative 3. You've always got to remember these signs. So let's go ahead and graph this. We're first going to start with our y-intercept. We're going to start in the middle, and because it's negative, we're going to go down. 1, 2, 3. And here is our first point. And now we're going to graph the slope. Remember that slope is rise over run. So this is just 2, and anything that's not over anything is just over 1. So we're going to rise 2, and we're going to run 1. So let's rise 1, 2, and then we're going to run 1. So here's our next point. And if you wanted to make this a straighter line, a little more accurate, we could actually do that one more time. So we can rise 2 and run 1. You don't have to do that. It just helps to make a straighter line. So now let's go ahead and fail to draw a straight line. Wow, that was terrible. But here's our line. This is the line of y equals 2x minus 3. So now let's plot the line of not that super confusing equation from before, but one that's equal to it. Y equals x minus 1. Remember that if we don't have a number in front of x, it just means 1. So our slope is going to be 1. And our y-intercept is going to be negative 1, not 1. So let's go ahead and plot our y-intercept first of all. We're going to be going down 1. And now we need to figure out our slope. Slope is rise over run. So our rise is going to be 1. And since it's over nothing, it's going to be over 1. So we're going to rise 1 and run 1. So we're going to rise 1 and run 1. And we can do that one more time if we want for a more accurate graph. Rise 1, run 1. So now let's go ahead and draw a line through this. So here is our line. This is the line of y equals x minus 1, and also the line of that confusing thing we had before. So our final question is, where do these graphs intersect each other? In this case, they seem to intersect right here. So what are the coordinates of this point? Well, remember coordinates are written as x, comma, y. X is how far to the right it is, and y is how high up it is. So in this case, x is 1, 2. It's 2 to the right, and we have to go 1 up. So x is 2, and y is 1. So remember, x always goes on the left, so it's 2, comma, 1. So that's our final answer. The answer to this system of equations is 2, 1. Normally in math class, you expect to do this thing called math, but instead we're doing things like consistent and inconsistent, dependent and independent. How is this math? So here's our first example. Instead of finding the answer to this, like 2 numbers for x and y, we instead need to figure out if this is consistent or inconsistent, and if it's dependent or independent. But what does that even mean? First of all, let me share with you what consistent and inconsistent mean. So if you wanted to find the actual math answer to this, you wanted to find x and y, you would plot both of these equations on this graph and draw the 2 lines, and then wherever they intersect, like right here, that would be the answer to x and y. But in this case, we don't have to do that. In this case, we just have to tell if it's consistent or inconsistent. Consistent basically just means that there's at least one answer. In this case, there is an answer. See, it's right there. So this would be consistent. So how can 2 lines not have an answer? How can it even be inconsistent? Well, this is an example of an inconsistent graph. You have 2 lines here, but you may notice that they're parallel, which means that they have the same slope and they are never going to cross each other, ever. So these will never have an answer, so this is inconsistent. Now, if the graph is inconsistent, that means that that's it. There is no dependent or independent. It would just be inconsistent. But if it is consistent, then you have to tell if it's dependent or independent. So going back to a graph like this, where they intersect at somewhere at one spot, this would be considered independent. This would be independent because they cross at exactly one point. So how can they not cross at exactly one point? Well, something like this would be an example of crossing at more than one point. And you might be asking yourself, wait, but there's only one line there. I thought this was having to do with 2 lines. Well, actually, this is 2 lines graphed right on top of each other, so that it's literally just one line. If you imagine this as 2 lines on top of each other, they cross each other at every single point here, as in an infinite amount of points. So in math, we would call this infinite solutions, or you would call this consistent and dependent. So here's a little chart here that will help you remember this, and you can always just take a picture of this or whatever and just reference it for when you're doing the problem. So let's go ahead and do this first example. We have y equals 2x minus 2 and y equals negative 2x plus 1. Well, to see if they cross and at how many points they cross, we need to first graph them. If you're not quite familiar with graphing lines, I have a video in it that you can watch on the card on the screen right now. And if you want, you can go watch that one first and then come back here. But I'll also quickly review what we're going to do. We need to use y equals mx plus b. So remember that these two equations are in y equals mx plus b because y is by itself, and we have a number for m and b. And m is the slope, and b is the y-intercept. So looking at our first equation here, y equals 2x, 2 is in the place of m, so 2 is going to be our slope. And here, negative 2 is b, not just 2. Remember, the negative sign has to stay when we're doing things like m and b. So b is going to be negative 2, our y-intercept. So let's do our y-intercept first. We have negative 2 here, so we're going to start in the middle and go down 1, 2. This will be where it crosses the y-axis, this big vertical line here. And now we need to do the slope. Remember that slope is rise over run. So in this case, our slope is 2, so we're going to put 2 for the rise. And since it's not over any number that isn't over anything is just over 1. So our run is going to be 1. So let's go ahead and do our slope. We are going to rise 1, 2, and we're going to run 1. So we're going to put another point here. And if you wanted, we could do that one more time just to help us draw a straight line. Rise 2, run 1. So now we just need to draw a straight line between these points, and that's going to be the hardest part. Well, there we go. Now we have a straight enough line, and that's the line of y equals 2x minus 2. But now we need to plot y equals negative 2x plus 1. So to do this, we'll do the plus 1 first, which is b, right? We're going to do the y-intercept. So plus 1, we're going to start in the middle and go up 1. And now we need to do the slope. In this case, the slope is negative 2. That's what's in front of m, but it's not just 2. We have to include the minus sign as well. So that means our rise is going to be negative 2, as in we're going to be falling because it's a negative number. And our run is just going to be 1 because there's still no number under this, so it's just over 1. So we're going to fall 1, 2, and run 1. Now let's draw a straight line, or at least try to. So there we go. We have our line of y equals negative 2x plus 1. So now our final part is we need to figure out, is this consistent or inconsistent, and is it dependent or independent? Well, first of all, we have to ask ourselves, do these lines cross at all? If they don't cross at all, then that's going to be inconsistent and we're done. But in this case, these lines do cross each other right here. So that's going to make this consistent. So if the graph is consistent, then we have to ask ourselves, is it dependent or independent? And remember, independent means 1, as in it's got one answer. In this case, it does have one answer. It would have been dependent if they had infinite answers. So this is going to also be independent. So that's it. Our final answer is consistent and independent. And if you wanted to also solve for x and y, you would just figure out the coordinates at this point here. But it looks like it's going to have a lot of fractions and stuff, and no one wants to deal with that. So here's another example. What I'd like you to do is go ahead and pause the video, try to graph these yourself, and then determine if it's consistent or inconsistent, and dependent or independent. And then go ahead and unpause the video and see how you did. Okay, so we need to graph these two lines. And the first thing I'm noticing here is that one of these lines doesn't follow y equals mx plus b. In y equals mx plus b, y is by itself here, right? And that seems to follow this equation. But this bottom one, x is by itself instead of y. So we need to fix this equation to be able to graph it. In this case, I see y has a minus 1 attached to it. So we can get rid of this minus 1 by doing the opposite of minus 1, which is plus 1. So we're going to add 1 to both sides. These cancel out, and on this right side, we're just left with y. And on the other side, we added 1 to x, which you can't add a letter in a number, so we're just going to leave it as x plus 1. And now you see this does follow y equals mx plus b because y is by itself. It's just kind of weird that y is on the right side. So what we can do is just flip these two sides around. That'll still be true. So we now have y on the left side and x plus 1 on the right side. You didn't have to do this, but it makes it look more like y equals mx plus b. So y equals x plus 1 is going to be our equation, our second equation that we're going to graph. So let's go ahead and graph these two lines. And you may already be noticing that these equations are very similar. So you might be going, oh, maybe this is going to not be just consistent and independent. We'll see. So first of all, let's graph the y-intercept. In this first equation, the y-intercept is negative 1 because the minus sign is involved. So we're going to start in the middle and go down 1. Now we're going to graph the slope. Remember, slope is rise over run. And in this case, we don't have a number in front of x. So we can imagine that there's a 1 in front of x. That's what you can always do when there's not a number in front of it. So our rise is going to be 1. And because there is no number under this, then it's just over 1. So our rise and run are both going to be 1. So we're going to rise 1 and run 1. And we can do that again if we wanted, rise 1, run 1. And now we can draw a line in between these. So let's try to do that. So there we go. We have our line of y equals x minus 1. But now we need to draw the line of y equals x plus 1. So our y-intercept is going to be positive 1, just 1. So we're going to start in the middle and go up 1. And now we need to figure out our slope. In this case, our slope is going to also be 1. So we don't even have to erase this. This is the same. Our rise is going to be 1, and our run is going to be 1. So we're going to rise 1 and run 1. And then we can do that again if we want. We can rise 1 and run 1. And now let's go ahead and draw a line between these, and you may already be noticing what our answer is probably going to be. So there we go. We have our line of our second equation. So now we need to ask ourselves, is this consistent or inconsistent? Well, in this case, we don't have any crossing of the lines. But you may be asking yourself, okay, well, maybe these just go on and they cross somewhere off of the graph. How can you tell that these aren't going to cross off like 100 squares away? Well, you can tell that because they have the same slope. If two lines have the same slope, they are never going to cross each other like this. So in this case, this is going to be inconsistent, because remember, inconsistent means that there are no answers to this problem if we were to try to figure out the numbered answers. So now, is it dependent or independent? Well, remember, if it's inconsistent and there are no answers, then it's neither. It's not dependent or independent. So in this case, our answer is just going to be inconsistent. We don't have to do anything else. How can you solve two equations at once with two different letters? Well, actually just much the same way as you would solve one equation. So here's our first example. We need to solve for both x and y in these two equations. Now, how you can tell that we are able to solve two different letters is because you always need to have as many equations as you do letters to solve. So in this case, we have two equations and two letters, so we can solve it. If we had 4 letters but only 3 equations, then we couldn't solve it. Now, in the past, you may have used other methods to solve these, like graphing them both on a graph or, oh no, a table. I hope you didn't have to do that. But basically, we're going to be using a better method. It's going to be faster and not use any graphing, just algebra. And it's called substitution. It's called that because we are going to be substituting one of these letters for something that has the other letter. And that will make an equation only have one letter. You'll see what I mean. So basically, we know that y is equal to x plus 4. So how can we use that to our advantage? Well, if we look at this equation, we have 2x plus y equals 7. What if we substituted y for x plus 4? We just replaced y with x plus 4 and get rid of y altogether. Well, in that case, we would have 2x plus, and then in this case, we have x plus 4 equals 7. And see, now suddenly our equation only has x in it. It doesn't have y. So we can solve this just like a normal algebra equation. So it looks like we have 2x plus x. If we have two terms with the same letter, we can do combining like terms, which just means add them together. Everything needs to have a complicated name. So 2x, we had 2x, and then we add one more x. That makes 3x. And this plus 4 is just going to stay, equals 7. And now we have a multiple step equation. So we need to get x by itself. And the way that we can do that is by getting rid of this plus 4 first. We could get rid of this 3, but it's more attached to the x, and then we're going to have a bunch of fractions and stuff, and that's no fun. So we're going to get rid of this plus 4 first, which is less attached to the x. So how can we get rid of this plus 4? Well, we'll do the opposite of plus 4, which is minus 4. We have to do it to both sides, remember that. Plus 4 and minus 4 cancel out. And in this case, we just have 3x. But now on the other side, we have 7 minus 4, which is 3. So now we just have a one-step equation. 3 times x, remember if there's no sign here, this is just going to be times. So 3 times x, we can get rid of this 3 times by doing the opposite of times, which is divided by. We will divide both sides by 3. That will make these cancel each other out, and we're just left with x. And on the other side, we have 3 divided by 3, which is just 1. So we figured out that x equals 1. So that's our answer for x. But if you remember, we need to solve for both x and y. So how can we solve for y now? Well, we can do more substituting. Remember here it says y equals x plus 4. And we can actually choose either equation, but this one looks a little simpler, so we're going to use this one. We can substitute in 1 for x. and then we'll only have y in this equation. So let's go ahead and do that. Y equals x plus 4 becomes y equals 1 plus 4, because remember that 1 and x are the same thing. So 1 plus 4 is 5. So in this case, we know that y is 5. And now we have our answer. So there are two ways you could write this. One way is to just put x equals 1 and y equals 5, which is already there underlined, so you can leave it like that. Or your teacher or professor might want you to write it as like a coordinates of a graph. In that case, you would put x on the left and y on the right. So you would put in parentheses 1, 5. This is just another way to write your answer, but they mean the same thing. So that's it. Our answer is 1, 5. Here's another example. What I'd like you to do is go ahead and pause the video, try to solve this for x and y for yourself, and then unpause and see how you did. Alright, so we need to figure out a letter that we can substitute so that we have the other letter just by itself in an equation. But that might be a little problematic for this problem. You see, we don't have any x equals or y equals that are just staring us in the face, right? So in this case, we're going to have to do a little extra algebra. So we need to pick either one of these equations and solve them for either letter. In this case, I'm seeing that x is by itself here. We don't have any number attached to it, so I feel like that's going to be the easiest to get by itself. So let's go ahead and try to get x by itself for this equation. So how can we get x by itself? Well, we can get rid of this minus 2y. That would leave x by itself. So we can do the opposite of minus, which is plus. We will add 2y to both sides. In this case, these cancel out because minus 2y and plus 2y just do the opposite of each other. And then on this left side, we're just left with x. And on this side, we have minus 7 plus 2y. Well, I mean, this has a letter and this doesn't. You can't really add those, so we'll just leave it as minus 7 plus 2y. So you'll see that we now have an equation that's x equals something. So now whenever we see x, we can replace it with this. So now to substitute, we need to substitute this for x on the other equation. You can't actually do it with this bottom equation since we use this bottom equation to get x. I'll just quickly show you what would happen if we tried to do it with the second equation. So we replace x with negative 7 plus 2y. Minus 2y equals negative 7. Plus 2y, negative 2y cancel out. And we now know that negative 7 is equal to negative 7. So to avoid y canceling itself out in the problem, we need to substitute this for x on the first equation. So let's go ahead and do that. So we have 2, and then instead of x, we're going to put negative 7 plus 2y. And I want you to notice that I put this in parentheses. If we just wrote it out, then it's going to be 2 minus 7 plus 2y. That's not exactly true. Remember, this is 2 times x. So we are doing 2 times this entire thing. And now we'll just write the rest of the equation. So now we need to solve for y. As you'll see, there's no x here, so we can just solve for y like normal. But it's a little more complicated than last time. The first thing I'm noticing is this pattern here, which should immediately say in your head, this is the distributive property. Okay, maybe you didn't know the exact name of it, but basically the distributive property, remember, says that if we have a number outside of parentheses, remember that's multiplication if there's no sign, we need to multiply it to both parts of what's in the parentheses. So in this case, we have 2 times negative 7 and 2 times 2y. So let's go ahead and do that. 2 times 7 is 14. And we have one negative sign, so the negative sign has to carry over. Then we have 2 times 2y. Well, in this case, we have 2 times 2, which is 4, and then the y stays. Remember, when we're adding and subtracting, you can't add or subtract ones that have a letter and don't have a letter, like a mixture, but you can multiply or divide. And now let's write the rest of the equation. Plus 2y equals 4. Well, this is quite simpler now, but there's still things to clean up. So I'm seeing that we have 4y and 2y. We can add these together because they both have y in them. We can combine like terms. So negative 14 stays, plus, and now we have 4y plus 2y. We have 4 y's, and then we add 2 more y's. So then we have a total of 6 y's, and then that just equals 4. So now we are going to try to get y by itself. We have a shorter equation than we did before. So we can get y by itself. We could get rid of the 6, but remember, that's more attached to the y, so we want to get the least attached number first. In this case, that's negative 14. So we can do the opposite of minus or negative, which is plus. we will add 14 to both sides. In this case, minus 14 plus 14 just do the opposite of each other, so they cancel out. And on this side, we have 6y. On the other side, 4 plus 14 is 18. And now we can get y by itself by noticing that this is multiplication because there's no sign. And we can do the opposite of multiplication, which is division. So we divide both sides by 6. These cancel, and you're just left with y. And on the other side, as I start to run out of room here, 18 divided by 6 is 3. So we found the answer to our first letter, which is y. Y is equal to 3. But now what about x? Well, we can substitute this 3 in for either of these equations to figure out what x is. In this case, I'm noticing that for the same reason as before, when we said that x looks like it's by itself here, and it would be nice and easy, we can use this equation for that same exact reason. But this equation would work as well. So let's go ahead and use this equation, x minus 2y equals negative 7. And we can substitute y in for 3, because y and 3 are the same. So we have x minus 2 times 3. And we'll put this in parentheses so that we know that this is going to be multiplication, equals negative 7. So now let's simplify what we have here. We have 2 times 3, which is 6. So we'll go ahead and put 6 there. And now we just have one thing to get rid of to get x by itself, this minus 6. So we can do the opposite of minus, which is plus. We can add 6 to both sides. These cancel out. And on this side, we're just left with x. Now on the other side, we have minus 7 plus 6. If this is a little confusing at first, you can either put it in your calculator or ask yourself, well, if I lost $7 and then gained 6 back, well, I'm still down $1, so minus 1. So in this case, x is minus 1. So our answer is x is minus 1 and y is 3. Or if you want to write it as coordinates, remember x always goes on the left. So we would put parentheses, minus 1 and then 3, because x always goes first. So this is our answer, minus 1, 3. Now finally, what if you were like doing this on the test or something where you don't have an answer key to look at and you're not sure if you did it right? Well, you can check your work on this. I won't go through the whole process of checking your work, but basically what you'll want to do is plug in the answers for x and y and see if the equation is true. And you'll want to do that for both of those equations. So for example, for the first equation, x is negative 1. So we would put 2 times negative 1 plus, and then 2 times y is 3. And then you do the multiplication. So 2 times negative 1 is 2, and 2 times 3 is 6, and 6 minus 2, or negative 2 plus 6, is 4. So that's true. And then you would do the same thing for the second equation, and if that is true as well, then you've done the problem correctly. If you're watching this video, you've probably learned some other ways to solve systems of equations, like substitution, which is pretty nice, graphing, which is not so nice, or maybe even a table. Not nice at all. But in this case, we'll be using another method of solving systems of equations called elimination. So here's our first example. We need to use elimination to solve for both x and y. And we can do this because we have 2 letters and 2 equations. As long as you have the same amount of equations as letters, or if you have more equations than letters, you can solve it for any amount. Now, if you do already know how to do substitution, you may notice that this is a little bit hard to do with substitution, because we would need to get a letter by itself. And it's kind of hard to get a letter by itself in either of these equations. It would be a lot of work. So because this would be kind of hard to do with substitution, we can try a different method called elimination. And elimination is all about adding both equations together. So just to demonstrate, let's go ahead and try doing that. If we add both equations together, we will get a third equation that is just as true as the other two. So let's add these one at a time. 2x plus 2x is 4x, because we had 2 x's and then added another 2. In this case, we have minus 3y, and these signs are very important. Make sure you don't forget these for elimination. We have minus 3y plus 3y. Minus 3 and then plus 3 are just 0, so these actually cancel each other out. And here we have 13 plus 7, which is 20. So we now have a new equation, and there's a giant gap here, so I'll go ahead and smoosh this together. Our new equation is 4x equals 20. This is a true equation because we added these 2 equations together to get a third one. And we only have one letter here. You see how we only have x, which means we can solve for it just like normal. So there's no sign in between this number and letter, which just means multiplication. So 4 times x, we need to get x by itself, so we'll do the opposite of times, which is divided by. We will divide both sides by 4. These 4's cancel out, and on the left side, we're just left with x. On the other side, we have 20 divided by 4, which is 5. So in this case, we figured out x. X is 5. But we still need to figure out y. So what we're going to do is we're going to take this 5 and plug it in for x on one of these equations, and then figure out y. This is the same way of figuring out the other letter as substitution. So it really doesn't matter which one we choose. Let's choose the second equation just because it doesn't have a minus in it. That'll make things easier, I hope. So let's go ahead and plug in 5 for x. So this becomes 2 times 5 plus 3y equals 7. So 2 times 5 is 10. And the rest of the equation stays the same. And now we need to get y by itself. Well, the 10 is less attached to the y than the 3, so let's get rid of the 10 first. We can get rid of the 10 by subtracting it from the equation. We will subtract 10 from both sides. On the left side, these just cancel out, and we're just left with 3y. On the right side, we have 7 minus 10, which means we gained $7 and then lost 10. So we're down 3, so that would be minus 3. So now we just have a one-step equation. This is still multiplication, remember, there's no sign. So we will do the opposite of multiplying, which is dividing. We will divide both sides by 3. On this left side, the 3's cancel out, and we're just left with y. On the other side, we have negative 3 divided by 3. Well, 3 divided by 3 is 1, but we still have a minus sign here. The minus sign carries over. So y is negative 1. So that's our final answer. X is 5 and y is negative 1. Now, your teacher or professor may actually want you to write this as like coordinates on a graph. So in that case, remember x always comes first in coordinates on a graph. So it would be 5 comma negative 1. That could also be your answer. You could either just put x equals 5 and y equals negative 1, or you could write it like this. Either one is fine. Now, what about this problem? This one's a little weirder because if we were to add these together, neither letter would cancel out. So it seems like we wouldn't accomplish anything. So we need to do something to one equation to make it so that they would cancel each other out. If you want to try this yourself, I would challenge you to go ahead and pause the video and try to figure out how you can make one of the letters cancel out by doing something to one equation. Then go ahead and try to solve it yourself and then unpause the video and see how you did. All right, now the question that I always ask people whenever I'm like tutoring people on this kind of thing is I would always ask them, and this seemed to help them get it. It would be really convenient if, like, let's say this number here was what number? And they would say, well, it would be really convenient if this number was 2, because then if we add these together, we have plus 2 and minus 2, and they cancel out. And I say, okay, well, how can you make this 2? Well, how would you make it 2? Well, remember, this is multiplication if there's no sign in between. So we can just multiply this by 2. But obviously, you can't just multiply some random number by 2, and that would make the equation not true. So what we're going to do is multiply the entire equation by 2. That is, we're multiplying both sides by 2, which is something we do in algebra all the time. We do something to both sides of the equation. So we just have to make sure that this 2 is being multiplied to every part of the equation on both sides, and then it's totally true. So our first equation is going to stay the same. And now our second equation is going to be 2 times x, which is just 2x. This minus sign has to stay, remember? And then we have 2 times y, which is 2y. And finally, we have minus 1 times 2 is minus 2. And now it looks like if we add these two equations together, they will very conveniently cancel each other out on the y side. So let's go ahead and do that. We're going to add both equations together. 4x plus 2x, 4 plus 2 is 6, so 6x. And remember, we made this conveniently a 2, so plus 2y and minus 2y, they cancel each other out. And here we have 8 minus 2, which is 6. So let's go ahead and smush this equation together. And you'll see we now have 6x equals 6, which is really easy to figure out. We just need to do the opposite of multiplication, which is division. We will divide both sides by 6. These 6's here cancel out, and on the left side, we're just left with x. On the other side, we have 6 divided by 6, which is 1. So x is 1. So now we just need to figure out what y is. Well, we can use this original equation here, because x and y are by themselves. It seems like it will be pretty simple math compared to if we use this other equation. So let's go ahead and do that. We will plug in 1 for x and see what we get for y. So instead of x minus y equals -1, this is going to be 1 minus y equals -1. So now we need to solve for y. Well, we can get y by itself by, well, let's get rid of this 1 first, right? This 1, we can get rid of it by subtracting it from the equation. We will subtract both sides by 1. So on this side, these cancel out, and we're just left with not y, negative y. The minus sign has to stay. You never forget those negative signs. That's the most common mistake in algebra, I would say. On this side, we have -1, -1. You lost $1, then lost another $1. You are down $2. So now we just need to get rid of this minus sign on y. There's two ways you can think about this. Remember that if there's not a number in front of y, then that makes it a 1 in front of it. So we can basically just say, okay, well, there's a -1 in front of y. So let's divide both sides by -1. In that case, these cancel out, and we're just left with y on the left side. On the right side, we have 2 divided by 1, which is 2. We have 2 minus signs. And remember, when you're multiplying or dividing, 2 minuses make a positive. So these would become a positive, and it stays as a positive. So y is equal to 2. Another way you could have thought about that is just applying a minus sign to both sides of the equation. This does the same exact thing. So then 2 minuses make a positive on both sides, and you're left with y equals 2. Those both do the same thing. It's just two ways to think about it. So there we go. We have our answer of x equals 1 and y equals 2. If you wanted to write this as a point, then you could do x first, so 1, 2, and put it in parentheses, and that would be your answer as well. Now, the last thing I want to mention is if you were doing this problem for like a test or somewhere where you don't have an answer key and you want to make sure you did the problem right before moving on, you can do this thing called checking your work. You would check your work the same way you would check it for substitution or for any sort of problem. We would just plug in our answers for x and y, and as long as both equations are true, then we did the problem correctly. So just as an example for our first equation here, we have 4 times, and for x, we're going to put our answer for x, which is 1, plus 2, and then for y, we got 2, equals 8. And then you would just do the math. So 4 times 1 is 4, plus 2 times 2 is 4 as well, and 4 plus 4 is indeed 8 last time I checked. So that means that we did the problem correctly, as long as you do the same thing for the second equation, and that's true as well. Do you remember back in kindergarten when the #1 rule in class was don't color outside the lines? Well, this is what your teacher was preparing you for, graphing inequalities. So here's our first example. We need to graph this system of inequalities, which basically just means we need to figure out where these two inequalities intersect. If you've done systems of equations before by graphing or some other method, you probably know that for solving two equations, you need to graph the two equations and figure out where they cross. In this case, for inequalities, we're going to be doing the same thing. But it seems kind of weird because with inequalities, you're like shading in like half of the graph with each one. So our answer isn't actually going to be a number, it's going to be an area of the graph. So first we need to graph these two inequalities. If you're not quite sure how to graph inequalities, then I have a video on it that you can watch on the card on the screen right now, but I'll also quickly review it here. So essentially we need to graph these just like a line and then color in the right part of the graph. So for this first one, we have y is greater than 2x minus 2. Well, let's graph it just as if this is an equal sign. We need to graph the slope and the y-intercept. Remember that the form of a graph is y equals mx plus b. M is the slope and b is the y-intercept. Yeah, don't question the letters, all right? So first of all, let's graph the y-intercept. In this case, the y-intercept is not 2, but it's -2. You always have to include the minus sign. So the y-intercept is where it crosses the y-axis. So we're going to start in the middle, and then along the y-axis, which is this big vertical line, we're going to go down 1, 2. This is going to be where it crosses. And now we just need to graph our slope. Our slope is right here, which is 2. And remember that slope is rise over run. So in this case, the rise is going to be 2 because our slope is 2. But because this isn't a fraction, we can just assume that it's over 1 because any number by itself is over 1. So our run is going to be 1. Rise 2, run 1. So let's go ahead and do that on our graph. We're going to rise 2 and run 1. So now we just need to draw a line between them. But because this is an inequality, not a regular line, we first need to ask ourselves, is this going to be a regular line, or are we going to have to draw a dashed line? Well, that's entirely based on if the line itself is going to be part of our answer. With something like this, the second equation, this sign has a line under it. And this little line under it means or equal to, meaning the line is part of the answer. But for this equation, we do not have a line underneath, which means that this line itself is not going to be part of the answer. So the way we show that it's not part of the answer is with a dashed line. So we're going to draw a dashed line in between these 2 points. So here's my horribly drawn dashed line. So now we just need to figure out which part we need to shade. Well, it says y is greater than this line. And if y is greater than, that means everything that's above this line. If it was less than, then we'd shade everything below. Now here's the thing, because we have another equation here coming up, not everything we shade might end up in the answer. Remember, it's where they both cross. So if you were actually doing this on paper, maybe you'd want to shade this in lightly, or just draw some lines or something, because it might not be part of the answer, but I'll just be doing it in blue. So I have now shaded in everything that is above the line, and this is going to be the answer for our first inequality. But remember, we're trying to find the answer to the system of inequalities, and that's only going to include what is an answer of both inequalities. So we need to do the second one now to figure out where that is. So let's go ahead and graph the second one now. In this case, our y-intercept is going to be 3. So we're going to start in the middle and go up 1, 2, 3. This is going to be where it crosses the y-axis. And now we just need to figure out our slope. Well, our slope is -2 over 3. Remember, the negative sign is included. So our rise is going to be -2, and our run is going to be 3. So a negative rise means we're going to be falling. So let's go to our point here. Our rise is -2, so we're going to fall 1, 2. And then we're going to run 1, 2, 3. And this will be our second point. So now we have to determine what kind of line we're drawing. Well, before we had the dashed line because we did not have the line under our sign. But in this case, we do have the line under our sign, which means the line is going to be part of the answer. So we can just draw a normal line in between these 2 points. So here is possibly the worst line you've ever seen, and this is going to be our line. But remember, this is an inequality, so we need to figure out which side of the line we need to shade. Well, in this case, it's less than, so everything below the line we're going to shade. So let's go ahead and do that in green. So there we go. We've graphed our 2 inequalities. So what is the answer to our inequality here? Well, it's going to be everywhere that is included in both answers. In this case, you see that this part of the green is a little bit darker than this part of the green because it also has blue in it. So this area here was shaded in both times. So that's going to be our answer. So there we go. This purplish blue area here is the answer to this inequality. Now here's another example. What I'd like you to do is go ahead and pause the video, try to graph this one for yourself, and then unpause and see if you did it right. Okay, so we're going to go ahead and do this the same way as we did before. We're going to graph these, and remember that the equation of the line is y equals mx plus b. So you may notice that we have one slight problem. This equation right here, this is not in the form y equals mx plus b, because we have this -2 next to the y. So before we get started on graphing, we should probably get rid of this -2. So remember that this is multiplication here. How can we get rid of this -2? We can do the opposite of multiplication, which is division. So we will divide both sides by -2. So in this case, these two cancel out, and on this side, we're just left with y. On the other side, we need to divide both of these, both the 6x and the 2, by -2. So 6x divided by -2, well, 6 divided by 2 is 3. And there's a negative sign here, so that has to carry over, and the x stays. Here we have 2 divided by 2, which is 1, and we have 1 minus sign, so the minus sign carries over. But remember, the one thing that makes solving inequalities different from just solving an equation is that whenever you multiply or divide by a negative number, you have to flip the sign. So in this case, the sign was less than, now it's going to be greater than or equal to. So we have our new equation here of y is greater than or equal to -3x minus 1. And I'll go ahead and write that up here. So we now have 2 good equations here that are both in y equals mx plus b. So we can go ahead and start graphing them. So let's graph this one first. Y is less than 1/4 x plus 3. The plus 3 is the b part of y equals mx plus b. So that's going to be our y-intercept. So we're going to start in the middle and go up 1, 2, 3. This is going to be where it crosses the y-axis. And now we need to graph the slope. Remember that slope is rise over run. So our slope is 1 over 4. Rise is 1, run is 4. So let's go ahead and do that on our graph. The rise is 1, so we're going to rise 1, and we're going to run 1, 2, 3, 4. So now what kind of line do we draw? Is it going to be dashed or solid? Well, we don't have a line underneath here, right? That means that the line is not going to be included in our answer. So we need to draw a dashed line. So here's our dashed line. I'm sure you could draw a much better one than me, but here it is. Now we need to figure out which part of the graph are we going to shade in. Is it going to be the top or the bottom? Y is less than this equation. So less than is below the line. If it was greater than, it would be above the line. So let's go ahead and shade in everything that's below this line. So there we go. This is everything below the line shaded in. But we now need to graph our second inequality. So how do we graph this one? Well, we're going to find the y-intercept first, which is -1, not 1, -1. So we're going to start in the middle, and we're going to go down 1. Now we need to graph the slope. The slope is -3, and anything that isn't over a number is just over 1. So this is going to be over 1. So our rise is -3, as in we're falling 3, and the run is going to be 1. So we're going to rise or fall 1, 2, 3, and we're going to run 1. So now are we going to draw a dashed line or a solid line? Well, this is a line underneath here. That means or equal to. So the line is going to be part of our answer. So we need to draw a solid line. So now we need to decide, are we going to shade in the bottom or the top? Well, we have a greater than sign here. Y is greater than this equation, and greater than means we're going to shade everything above the line. So in green, I'm going to go ahead and shade in everything that is above this line. So there we go. That is the graph of y is greater than or equal to -3x minus 1. But we still haven't figured out the answer to our system of inequalities. Well, it's just going to be where these two graphs overlap, in this case, in this darkish green area. So I'm going to go ahead and shade that in purple to show where the answer is. So there we go. This is going to be our answer to this system of inequality. All right, we are testing the audio. We're going to be doing some math. We're going to switch to the whiteboard cam, and we're going to start drawing some gibberish. Yo, 4 plus 4 is 9, haha. Be sure to subscribe if you enjoyed. Oh, we're recording. Hi, we're finding the vertices of a triangle. Watch. So here's the example that we'll be doing in this video. We need to graph these three inequalities, figure out the triangle that they make, and then find the vertices of that triangle. So first we need to go ahead and graph all of these inequalities. Remember that the form for graphing is y equals mx plus b. So remember that in this form, m is the slope and b is the y-intercept. So let's go ahead and graph this first inequality. Y is greater than minus x minus 1. If you're not quite sure how to graph an inequality, I actually have a video on it that you can watch on the card on the screen right now, but I'll also quickly review it here. So first, let's go ahead and graph the y-intercept of this first line. The y-intercept is b, but that's not 1, it's -1. The sign is always included in m and b. So we're going to start in the middle of our graph and go down 1. This is going to be where our graph crosses the y-axis, this big vertical line. So now we just need to graph the slope. Remember that slope is rise over run, and our slope in this case is, well, m. We don't have a number in front of x, so what do? Well, if we don't have a number in front, then we can just assume that it's 1. But in this case, it's actually -1 because we already had a negative sign here. So our slope is -1. And if you have a number that's not over anything, then it's just over 1. So our run is going to be 1. So our rise is -1, and a negative rise means we're falling, right? And then run is 1. So we're going to fall 1 and then run 1. So we're going to have another point right here. Now, if this was just a normal line, we would just go ahead and draw a straight line between these and be done with it. But in this case, because we have a greater than or less than sign, we need to ask ourselves, are we going to draw a solid line or a dashed line? A solid line is what you would draw if the line is part of the answer. In this case, we do not have a line underneath our sign here. The line would mean or equal to. So in this case, the line is not going to be part of our answer, so we need to draw a dashed line to show that. So I've gone ahead and drawn the worst dashed line you've ever seen, and now we need to figure out, finally, which part of the graph are we going to be shading in? Would it be above the line or below the line? Well, it says y is greater than this equation. And y being greater than means everything that's above, because the numbers go up as you go up. So I would go ahead and shade in this area. You would just color it in with pencil or whatever. But because we have like 3 different equations, that's going to get pretty hectic if we shade in everything. So instead, I'm going to go ahead and draw little arrows pointing up to show that this is going to be shaded in. Once we're done with this problem, we're going to only shade in the area that all 3 of them have in common. So now let's go ahead and graph our second inequality here. Y is less than or equal to 1 over 2x plus 2. Like before, we're going to go ahead and do our y-intercept first, so that is 2. So we're going to start in the middle and go up 1, 2. This is going to be where it crosses the y-axis. And now we need to graph our slope. Slope is rise over run, and our slope is 1 over 2. So our rise is 1, and our run is 2. So we're going to rise 1 and run 1, 2. So now are we going to draw a dashed line or a solid line? We have a line underneath our sign here. This means or equal to. Our line is part of the answer, so we're going to draw a solid line. So our final question is, which part of the graph are we going to shade in, above the line or below the line? Well, this is less than, y is less than, and all the numbers that are less than the line are the ones below it. So we're going to shade in below. And again, we'll go ahead and do arrows instead to avoid all the chaos. All right, now it's time to graph our final line. In this case, that's going to be y is greater than or equal to 2x minus 1. Well, our y-intercept is going to be b, which is minus 1. Remember, the minus sign is included. So we're going to start in the middle and go down 1. And in this case, there's already a dot there, so we'll just leave that there. Now we need to graph the slope. The slope in this case is 2. So we're going to put 2 for the rise. But because this isn't over anything, that means it's just over 1. So we're going to put 1 for the run. So let's start at that point from before, and we're going to rise 1, 2, and run 1, and put a point here. So now are we going to draw a solid line or a dashed line? Well, in this case, we have a line underneath our sign, which means our line is part of the answer. It's equal to. So we're going to draw a regular solid line. So now finally, where are we going to shade in? Is it going to be above the line or below the line? Well, in this case, we have a greater than sign. All the numbers that are greater than the line are the ones above it. So we're going to go ahead and put up arrows. So now, because this is a system of inequalities, we need to shade in our answer, which is where all 3 of them would be shaded in. You may notice that we have this little triangle shape here. And in this triangle shape, all of the arrows are pointing inside it. So this triangle shape is going to be our answer. So there we go. This is our triangle shape. And now the final part of this problem is to find the vertices of this triangle. What's a vertice? Well, vertices are just the corners of the triangle. So right here we have a corner. This is a vertice. I guess it's not a vertice. Vertices is the plural for vertex. So this is a vertex here. Our second vertice is going to be right here. And then our third vertex is going to be right here. These are the 3 corners of our triangle. So now we just need to figure out the coordinates of each of these vertices. Well, let's go ahead and do this one first. Remember that coordinates are x first and then y. X is going to be left and right, and y is up and down. So in this case, starting in the middle, we have to go back 1, 2 to get to this point. So our x is going to be -2. And now we have to go up 1. And then we're at this vertex. So our y is going to be +1 because we went up 1. Let's go ahead and do this one next, this one right here. In this case, our x is actually 0. We don't have to go left or right at all. Right from the middle, we are already lined up with this point. We just have to go down 1. If we have to go down 1, that's going to be -1 for the y, because y is up and down. So our y is -1. And we now have our second point, and this is our final point right here. To get to this point, we have to go to the right, 1, 2, which means our x for this point is going to be 2. And we have to go up 1, 2, 3, which means the y at this point is going to be 3. So that's it. These are the 3 vertices of our triangle. All right, class, today we're going to be starting linear programming. Ooh, we get to do programming, like doing like programming languages. Ooh, I can't. Maybe I'll even learn how to hack into my friend. So linear programming is just another name for graphing. Bruh. So here's the first example that we'll be doing, and wow, that is a lot of equations. Well, first of all, here's what the point of linear programming is. The point of linear programming is optimization. Okay, that doesn't really help you, does it? Basically, what we need to do is this equation here, this one that says f of x and y, we need to figure out where on this graph would be this equation's minimum and maximum values. What are its lowest and highest numbers? So like, for example, if we were to put a point here, this point is 1, 1, because we have to go to the right one and up one to get to it. So if you were to plug these numbers into this equation, you would get 3 times 1 for x, plus, and then 1 for y. 3 times 1 is 3, plus 1 is 4. So this point would give you a 4 on this equation. What we're basically trying to find out with linear programming is what point on this graph within these boundaries, these are just going to be lines that like make a shape. Within the shape that these make, what point is going to give us the highest number for this and the lowest number for this? So remember, these are going to be the boundaries of our shape. We're going to be making a shape out of these lines, and we're going to figure out what the minimum and maximum value are. So to be able to figure out what this shape is, we need to graph this. So let's go ahead and graph this first one. Y is less than or equal to 3. Now, graphing a line with just one letter can seem kind of confusing. I feel like people get confused about this all the time. It seems like it should be easier, but people get more confused over these than regular lines. Well, basically how you need to think about this is, where is y less than 3? Well, for y, here's 3, right? Because y is up and down. So y is less than 3 everywhere here. How do we represent that with a line? Well, it would actually be a horizontal line. And I think this is where people get confused. They say, well, why is it a horizontal line? It has the letter y. Well, it's because we are representing the y letters, but it can be any x value. So we have to draw a horizontal line. Now, normally when you're graphing inequalities, I would ask you now, are we going to draw a dashed line or a solid line? And that just depends on if or equal to is part of the sign. But with linear programming, you're pretty much only going to be using inequalities that have the or equal to part. So you can safely assume that we're going to be using solid lines with everything. But if you wanted to double check, just make sure that there's a line underneath the sign. If there wasn't a line, you would draw a dashed line. If you're still a little confused on graphing lines or graphing inequalities, I actually have a video on it that you can watch on the card on the screen right now. So as always with graphing inequalities, we now need to figure out if we're shading in the top or the bottom. Are we shading above or below the line? Well, in this case, y is less than 3. So everything less than 3 is below the line, like I was showing you before. So we would shade in this whole area, but because we have so many equations here, I'm just going to reduce the chaos and just draw little arrows here. And we'll shade in our final answer when we get there. So our next inequality is x is greater than or equal to -2. And in this case, we actually don't have a y, so this can seem a little confusing. But we're actually going to do the same thing, just the other way around. Here's what I mean. X is greater than -2. Well, here is -2 for x, right? So where is x greater than -2? Well, x is left and right, so it's greater than -2 everywhere here. How can we represent that with a line? Well, we're going to have to draw a vertical line. So let's go ahead and make that a little bit neater. So now which side of this graph are we going to shade in? Are we going to shade, we actually don't have an above and below this time because there's no y. So are we going to shade to the left or the right? Well, x is greater than -2 everywhere to the right because the numbers go higher as you go to the right. So we're going to go ahead and draw arrows here to represent that we're going to be shading in to the right. So now we get to our last line, and this looks a little bit more like what you're used to, which is probably y equals mx plus b. Remember that m is our slope and b is our y-intercept. So first we're going to go ahead and graph our y-intercept. In this case, that's going to be 1. So our y-intercept is where it crosses the y-axis, this big line here. So we're going to start in the middle and go up 1. This is going to be where it crosses the y-axis. And now let's go ahead and do our slope. Our slope in this case, m is slope for some reason. So our slope is going to be 2. And remember that slope is rise over run. So because our slope is 2, our rise is going to be 2. But what is our run? Well, remember that any number that isn't over anything is just over 1. So our run is going to be 1. So let's go ahead and graph that. Our rise is going to be 1, 2, and our run is going to be 1, and we can put a point here. So these 2 points here that we have now, we can draw a line in between them. And we will do a solid line because we have a line underneath here. So now we just need to ask ourselves, are we going to shade in above or below the line? Well, in this case, y is greater than this line. So greater than, the numbers get greater as we go up. So we're going to draw a bunch of up arrows here. So you may notice that we have this triangle shape here. It's got like a little triangle. And all of the arrows here are pointing inside this triangle. So this triangle is going to be the shape. Our boundaries make a triangle. So we have our triangle here. These are the boundaries. But how do we figure out the maximum and minimum values? So this is the equation that we want to find the maximum and minimum values for. And here's the thing with linear programming that is going to make your life a lot easier. We're not going to be able to test every point in this triangle because there's infinite points. You will literally be doing this for an infinite amount of time. But here's the thing with linear programming. Because we can figure out these vertices, these corners, the maximum and minimum values will always be in these little corners. And in this case, a triangle only has 3 corners. So our maximum and minimum values are going to be on these 3 corners. So we're going to go ahead and find the coordinates of each of these vertices, which is the plural for vertex. A vertex is just a corner of the graph. So this first one right here, what is it? What are the coordinates of this point here? Well, remember, x is left and right, and y is up and down. So we need to go to the left, 1, 2. So our x is going to be -2 because we're going to the left, and the left is negative numbers. And now we need to go up 1, 2, 3, which means our y, which is up and down, is going to be 3. What about this one over here? In this case, we need to go to the right 1. So our x is going to be 1. And we also have to go up 1, 2, 3, just like the last one. So our y is still going to be 3. And now we just need to figure out this last point. Well, we need to go to the left 1, 2. And we have to go down 1, 2, 3. So our x is going to be -2 because we went to the left. And our y is going to be -3 because we went down. And the numbers go down as you go down. So these are our 3 points. We figured out the 3 vertices of our graph. So the final question is, which one is the minimum value and which one is the maximum value? Well, for this, we're going to be using our favorite thing ever, a table. Yay! So we're going to plug in each of these points into this equation here and figure out which one gives us the biggest number and which one gives us the smallest number. So let's go ahead and do this one first, -2, 3. So in this case, we're going to plug in -2 for x and 3 for y. We'll just replace the letters with these numbers. So we're going to have 3 and then times -2 plus, and then y is 3. So let's go ahead and solve this. 3 times -2, well, 3 times 2 is 6, and we have a negative sign, so it carries over, plus 3, and -6 plus 3, well, we lost $6 and then gained 3. You're still down $3. So -3. We still don't know if this is our biggest or smallest yet because we have to do the rest of the vertices. So let's go ahead and try the other ones. Let's try 1 and 3. In this case, we're going to have 3 times 1 plus, and then y is still 3. 3 times 1 is 3, plus 3 is 6. So this is a bigger number here. So this is going to be 6 for this point. So now let's go ahead and do the last point that we haven't done yet, -2 and -3. Let's go ahead and plug those numbers in. And because these are pretty big negative numbers, I have a feeling this is going to be our minimum value, but let's find out. 3 times -2, and then we have plus -3, which is just -3. So we'll just put -3. 3 times 2 is 6, but we have a negative sign, so the negative sign has to carry over. And then we have -3. So -6 minus 3. We lost $6 and then lost another $3. So we have lost $9. So what are our maximum and minimum values? Well, what is the maximum value here? The maximum is the biggest value. In this case, our biggest number here is 6. So our maximum value, and if you were to write this into words, you would say it is 6 at 1, 3. So now what's our minimum value? Well, our minimum is the smallest number. In this case, the smallest of these numbers is -9. So this is going to be our minimum value. So you would write this as our minimum value is -9 at -2, -3. So there you go. This is our answer. We found our maximum value and our minimum value and what point they're at. You know that feeling when you're doing an algebra problem and you've run out of space on the page and you're still on problem 1? Well, the problem that you were doing was probably a system of 3 equations. So here's our first and only example. We need to solve for x, y, and z in these equations. Now for 3 equations, the best way to solve this is using a method called elimination. Elimination is something you can do with 2 equations as well, and it will help if you already know how to do that for this video. If you don't already know how to do elimination with 2 equations, then I have a video on it that you can watch on the card on the screen right now. So you can watch that first and then come back here. So basically our goal here is to reduce this into 2 equations with 2 variables, because we already know how to do that, and that will just make our lives easier. But how do we do that? Well, we can just turn this into multiple 2 equation problems. So like, for example, let's say that I did elimination on these 2 equations, and from these 2 equations, we eliminated the letter y. Then let's say that I did more elimination, but I did it on these 2 equations. And from there, I also eliminated the letter y. Well, from there, I have just made us 2 new equations. And both of these equations only have x and z. And then we can use these 2 equations to eliminate, like, for example, let's say x. And then we're only left with z. So let's go ahead and do that first step that I was talking about. We need to get ourselves 2 equations that don't have a letter. So we'll use these first 2 equations first. So remember, elimination is all about adding these 2 equations together. So first we need to ask ourselves, if we added these together right now, would we eliminate a variable? And in this case, I'm saying we would. We have a plus 2y and a minus 2y. If we add these 2 together, y will be eliminated from the equation, and that's what we want. So let's just go ahead and add these together right now. 2x plus 3x is 5x, plus 2y minus 2y, that just makes 0, they cancel out, so we'll go ahead and cross those out. And then minus 3z plus z. We lost 3 z's, but then we got 1 back, so we're still down 2 z's. And then 14 minus 5 is 9. So we now have ourselves one equation that doesn't have y in it. So what I'm going to do is I'm going to have the problem over here, and then over here I'm just going to put some of the new equations that we come up with. So here I'm going to put 5x minus 2z equals 9. So now we need to get ourselves another equation that has no y in it. Well, let's go ahead and use these 2 equations. So this one's going to be a little trickier, because if we add these together immediately, it's not going to get rid of a letter. And just a reminder, this time we want to get rid of y. We can't get rid of some other letter because we need 2 equations that don't have y in it. So the question that I always ask is, it would be really convenient if the number right here was what number? And I think you would probably say that it would be convenient if this was a 2, because then these would cancel out and we would just add them together. So the question I usually ask next is, what do we have to do to make this number a 2? Well, remember, we don't have a number here, so we just pretend that it's a 1. So how can we make that a 2? Well, if we multiply it by 2, then it will become 2, because 1 times 2 is 2. But remember, in algebra, we have to do something to both sides of the equation. So what we're going to do is we're going to multiply this entire equation by 2. That will make this a 2, but we have to do it to every other part too, so that the equation stays true. So let's go ahead and rewrite these equations, but with our new multiplication. So there we go. Now if we add these 2 equations together, these y's will cancel out just like before. So let's go ahead and add them together. So we have 3x minus 8x, that's negative 5x. These cancel out because we have minus 2y plus 2y, those do the opposite things. And then z plus 6z, 6z's plus another one is 7. And then negative 5 plus negative 14. Lost $5, lost another $14, we've lost 19. So there we go. We've got another equation that doesn't have y in it. So let's go ahead and put it in our little bank up here. So now we have 2 equations that don't have y in it. And you'll notice here, this actually just looks like a 2 equations, 2 unknowns problem. We have 2 equations and 2 unknown letters. So we can solve this for one of those letters. So let's go ahead and do that. So now let's go ahead and ask ourselves, if we added these together right now, would we eliminate a variable? In this case, actually, we would. We would eliminate x, because 5x minus 5x, that just does nothing. So these would cancel out. And look at that, we're just down to one letter, and we can solve it for a number. So negative 2z plus 7z, that's just a subtraction problem, flip the other way around. So 7 minus 2 is 5. And 9 minus 19, gain $9, lose $19, you were down $10. And now we're down to a nice one-step algebra problem. What a relief. This is multiplication because there's no sign in between. You assume it's multiplication. So we'll do the opposite, which is division. We will divide both sides by 5. These cancel out. And on this side, you're left with z. But on the other side, we have 10 divided by 5, which is 2. and we have one negative sign, so the negative sign has to stay. So we now know that z is -2, but now we have to solve for the other two letters. So how are we going to solve for another letter? Well, normally, when you do these kinds of problems, you would plug the number back into one of the equations and see what letter you get. But if you plug this number back into one of these equations, you're still going to have an x and a y that you don't know. That's two unknowns, so we can't do that. So instead, what we're going to do is plug this into one of these equations, because if we plug it into z, all that's left is x, and we'll know what x is. So I've put that z is -2 over here so we don't forget. And which one do we want to do? I'm going to say, let's do this top one. It really doesn't matter. And what we're going to do is we're going to replace z with -2 because they're the same. And we'll see what we get for x. So 5x minus 2 times -2 equals 9. Now let's go ahead and clean this up a little bit. 5x, and then we have -2 times -2. Remember, every minus sign has to stay. And we have two of them, so they actually become positives because two negatives make a positive. So 2 times 2 is 4, so that'll be +4, and then equals 9. So now we have a two-step algebra problem. And in this case, we can get rid of the 5 or the 4 to get x by itself. Let's get rid of the 4 first, because the 5 is more attached to the x, and we'd have to divide everything by 5, and we have a bunch of fractions, and no one wants that. So let's get rid of the 4 first by doing the opposite of addition, which is subtraction. We will subtract both sides by 4. These cancel out, and on this side, you're just left with 5x. And on the other side, 9 minus 4 is 5. So now we have 5x equals 5. This is multiplication, so we have to do the opposite of multiplication, which is division. So we will divide both sides by 5. These cancel out, and you're left with x. And as I run out of room here, on the other side, we have 5 divided by 5, which is 1. So x is equal to 1. So our last letter to figure out is y. How can we figure out y? Well, we have a lot of equations with y in it here, and we couldn't use these before because we didn't know what x was either, so we would have two letters that we don't know. But we know what x is now. So we can replace x with 1 and z with -2, and all we'd be left with is y, and we could solve it for y. So we can choose any of these equations. It really doesn't matter which one you pick, but I feel like I'm going to go for this one because y is already by itself in this part of the equation, and then that's going to save us a step compared to if we did these other ones. So let's go ahead and use this bottom equation. All right, so let's go ahead and replace these letters with what we know. So -4 times, and x is 1. We don't know what y is yet. That's what we're trying to solve for. And then 3 times z is -2. And that's equal to -7. So let's go ahead and clean this up. -4 times 1, anything times 1 is itself, so that's -4, plus y. And then 3 times -2. 3 times 2 is 6, but the minus sign has to stay, so this is going to become -6. And then that's equal to -7 still. And now I'm seeing we have two numbers on this left side, so let's just go ahead and combine them. We have -4 minus 6. We've lost $4 and then lost another 6, so that's -10. You'll notice that it doesn't matter if these two numbers are next to each other. I know they have a y in between them, but we can still add them together. So now we just need to get y by itself. We need to get rid of this -10. So we'll do the opposite of minus, which is plus. We will add 10 to both sides. These cancel, and on this side, we're just left with plus y, or just y. And on the other side, we have -7 plus 10, which is just the same as saying 10 minus 7. 10 minus 7 is 3. So y is equal to 3. So there you go. We have our answer here. These are the three letters that we've solved for. But there's one other way to write your answer, and your teacher or professor might want you to write these as like coordinates on a graph or something. In that case, you would write this in parentheses, and you would always go x, y, z. Just like in a graph, you would do x then y. It's just this time we have a z. So we do x first, which is 1, comma, and then we have y, which is 3, comma, and then we have z, which is -2, and then close the parentheses. So our answer is 1, 3, -2. There's a car outside. Possibly one of the most common algebra subjects that I've tutored people in is domain and range. And that's because it just seems like it should be so simple, and it's explained like it's so simple, but somehow it's not. Well, let me explain domain and range in a way that actually makes sense. So the four examples that we're going to be going over in this video are each going to be a different kind of relation. We're also going to look at a graph with a bunch of points on it. We're going to look at a table, and we're just going to look at a big set of points, which is just a bunch of numbers. So for this first one, we need to figure out what the domain and range are. What do those even mean? Well, first we need to understand what these two boxes are even talking about. On the left here, we have all of our x values, and on the right, we have all of our y values. But that still sort of doesn't help, right? So instead, I want you to think of this as like a machine. So here we have a really amazing drawing of a machine. It's not amazing. So basically, we need to put something into this machine, and we will get something out. So like, let's say that this is a food machine. Let's say that if we put potatoes into this machine, here's my amazing drawing of potatoes, right? Let's say we put potatoes into here, and then whenever we put potatoes in, we get out French fries. Then this potato is our input, but in math, we just call it x. The French fries would be our output, and that would be just called y. So what are domain and range? Well, domain is basically a list of everything we can put into the machine. So basically, if we could put potatoes and get French fries, but let's say we could also put in tomatoes and get ketchup, and we can put in sugar and get chocolate. In that case, sugar, potatoes, and tomatoes would be our domain. Our range would be everything that we can get out of the machine. So French fries, ketchup, and chocolate would be our range. So something like a peanut butter and jelly sandwich would not be part of our range, even though that is a food. There's nothing that we can put into this machine to get that out of the machine. So that would not be part of the range. So let's go ahead and figure out our domain and range for this relation, is the fancy word for this. So the way we write a domain is with these fancy little bracket looking thingies with like the little things sticking out. And then we usually write the numbers in order from smallest to largest. But other than that, it's quite literally just everything we can put into the machine. Well, it looks like we can put 1, 3, and 5 into the machine. So our domain is going to be 1, 3, and 5. Now, what about our range? Well, the range is everything that we can get out of the machine. So it looks like it's going to be -2, 0, and 7, right? Not quite. You notice how there are no arrows pointing to 0. And that's because if we put 1 into the machine, we get -2. If we put 3 in, we get 7. And if we put 5 in, we get 7. There's nothing we can put into this machine to get us 0. So in this case, 0 is actually not part of our range. It is impossible for the machine to make a 0. So our range is only going to be -2 and 7. So there you go. We found the domain and range of this relation. Now, what about this one? This is a weird one. We've got a graph here because we've got the graph background on. And we have 4 points, and we need to figure out the domain and range. Well, even though we don't have our weird table thing with arrows pointing to things, this still works the same way. It's about what can you put into the machine and what can you get out of the machine. But what's in and out in this case? Well, on a graph, left and right is x, and up and down is y. And remember, x is what you put in, and y is what you get out. So for the domain, we're going to see all the different things we can put in based on these points. So in this case, let's see all the different numbers we can put in to the graph and get something out. Well, let's look at this point first. Remember, x is left and right. So to see the x value of this point, we need to figure out how far to the left or right we need to go. In this case, we need to go to the left, 1. And left is where all the negative numbers are. Right is where all the positive numbers are. So in this case, we need to go to the left 1, so that's -1. So -1 is part of our domain. Let's see what else we can put in. Oh, well, here it looks like we have 2 points that are on the same x value. You see, we have to go to the right 1 to get to both of these points. So do we put the number 1 twice? No, because they are the same number. It is the same number that you put into the machine, and you can get 2 different things. So that would be like putting potatoes into the machine and getting fries and chips at the same time. And if you're not from the US, that's chips are the fries, and then the chips that I'm talking about are I think like the fries are called chips, and then the chips are crisps. There we go. All right, that's what I'm talking about. I totally didn't just confuse you more. Now, what about this point all the way over here? We have to go to the right 1, 2, 3, 4 to get to this one. So 4 is going to be part of our domain as well. Oh, I'm just now noticing the x is off the screen. All right, so now we need to figure out the range. Remember, range is all of the numbers that we can get out of our machine, in this case, the y values. So let's go ahead and take a look at those. We'll start with the smallest numbers, which are the ones the lowest down. So let's look at this point. For this one, we have to go down 1, 2 to get lined up with this point. So that would be a -2. Now let's look at this point here. For this one, we only have to go down 1 to be lined up with it. So that's -1. This one here is actually already on the line. We don't have to go up or down. So that's a 0. And then finally, this point up here, you have to go 1, 2, 3 up. And since the number's going up, the numbers go up as you go up, then that would be a 3 because we have to go 3 up. That's a +3. So notice how we only have 3 numbers in the domain, but 4 in the range. And that's because this number in the domain, 1, can get you 2 different things. All right, here's another example, and this time we have a table. So what I would like you to do is go ahead and pause the video, try to figure out the domain and range for yourself, and then unpause and see how you did. All right, so we have our x values here. These are the things we put into the machine, and this is why these are the things we get out. So what is the domain in this case? Well, remember, the domain is the collection, the list of things that we can put into the machine. In this case, we can put -3, we can put -1, and it looks like we have 2 -1s, so -1 gives us both 2 and 3. We're not going to list it twice. And then we have 2. And now for the range, that is the list of things that we get out. So we're going to start with the smallest number first to the largest. So it looks like we can get 2. And we actually get 2 from 2 different things, but we're just going to put 2 once. Then we have a 3, and we have a 4. So there you go. That's our domain and range. Here's our last example. And yes, it looks kind of weird, I know, but go ahead and pause the video, try it yourself, and then unpause and see if you got it right. All right, so the first thing I'm noticing here is that there are a lot of repeating numbers. We've got a lot of 2s, -3s. Looks like everything's repeating, but we'll see how this goes. So first, our domain. Our domain is the collection of things that we can put into the machine. And in this case, we have coordinates, and coordinates are always written as x first, then y. So these first numbers of each of these pairs are the things that we can put into the machine. So we can put -3 into the machine. We can put 2 into the machine, and that's it. We have a 2, we have a -3 here. These are all repeats. So these are the only 2 things we can put into the machine. But what can we get out? That will be our range. Well, we can get -4 out, right? We can get 5 out, and that's also it. We have a -4 and a 5 here. We've already written those. So that's it. We have 2 numbers for the domain and 2 for the range. So that's our answer. Hi, I'm blurry. It's time to start talking about onto and one-to-one functions. It's already confusing in itself, but it's even worse by the fact that you have not done anything related to this whatsoever before suddenly having to do this. All right, so here's our first example. First, we need to figure out if this is a function, and then if it is, we have to figure out if it's one-to-one, onto, both, or neither. Well, first we need to figure out if this is a function. What even is that? Well, the way I want you to think about functions is it is basically a machine, a food-making machine. Now, I used this food-making machine example in my last video, which was about domain and range, and if you haven't watched that and you're curious about domain and range, then the card on the screen, you might want to watch that. So whatever we put into the machine is going to be our input, and that is also known as x in math. And what you get out of the machine is our output. I know, shocking. And in math, that would be called a y. So we put something into the machine, like, for example, a potato. Please don't judge my drawing of a potato. I actually judge it all you want. I don't care. And now, let's say that this potato, when we put it into the magic food machine, I just realized this machine doesn't have a name. So when we put a potato into this magic food machine, we get fries. So whenever we put potatoes into the machine, it's expected that we will get fries out. So what would make this not a function? Well, let's say that when we put a potato in, sometimes we get out fries and sometimes we get mac and cheese. First of all, that makes no sense. I don't know why you would get mac and cheese from a potato. But second of all, this is not a function, because for a function to be a function, whenever you put in an item, you need to get the same thing out every time. So in this case, let's ask ourselves, is this a function? Well, remember the ones on the left are x and the ones on the right are y. So whenever we put in -1 into our magic number machine, which is not as exciting as the magic food machine, but still sort of exciting, we get -2. When we put in 3, we get 0 every time. When we put in 3, we get 0. And when we put in 6, we also get 0. to me, that sounds like a function, right? You can get two things that give you the same thing. So like, for example, if there was something else we could put into this machine to get us fries, that would be fine. Because we know that when we put that item into the machine, we're going to get fries. So in this case, this would be a function. But now we need to ask ourselves, is it one-to-one and is it onto? What do those mean? Well, let's say that there was something else that we could put in to get fries. Let's say if we put in bread, then we would also get fries. In this case, this would be a function because if we put in potatoes or bread, we can expect to get fries out. But this would not be one-to-one because there are multiple things we can put in to get the same thing. For this to be one-to-one, fries need to be exclusive to one certain item. So there can only be potatoes that make fries, and there can be nothing else that make fries. So is this one here one-to-one? Well, no, because 0 is a thing that the machine can make, but 3 and 6 can both make it. So in this case, this is not one-to-one. But what about onto? Well, onto is a weird one because like 95% of the time it is going to be onto because it seems really weird. But basically, onto means the big list, as you could say, the menu of things that can come out of the machine need to actually be possible to get out of the machine. What? Well, basically, let's say that this machine said that it makes fries, ketchup, and chocolate. If the machine says it makes these three things, it should be possible to put something in and get each of these items. So, like, for example, we could put a tomato in and get ketchup, or we could put, what would we put in for chocolate? Like cocoa beans and get chocolate. You can tell I've played Minecraft. So what about this? Is this onto? Well, this is one of those rare cases where it's actually not onto. You see how it's promising that 4 is one of the y values here, but there's no way to make 4. There's nothing you can put in to get 4. 4 is just sitting here all lonely and you will never make 4. So in this case, onto is, this is not onto. All right, what about this one? First of all, we need to decide if this is a function. Remember, every item has to make one item. You can't put in something and then have maybe it makes this thing, maybe it makes another thing. It needs to make only one thing. So let's see, -3 makes 2, 1 makes 4, 2 makes -2, and 5 makes 4. There isn't any x value that can make two different things. So in this case, yes, this is a function. But what about one-to-one? Remember, for it to be one-to-one, each of these things that the machine can make needs to be exclusive to one thing that you put in. So in this case, it looks like 2 can only be made by -3, so that's good. But look at this. 4 can be made by either putting in 1 or by putting in 5. So you can put in 1 or 5 to get the same thing. In that case, 4 is not an exclusive item. So one-to-one, nope. But what about onto? Remember I said onto is that one that's going to be true like 99% of the time. And in this case, it is, because it basically just means everything that's on the menu, or however you want to say it, is possible to make. And yeah, it's possible to make all of these by putting the thing that's next to it in. This is why onto is one of those things that's almost always true, but it wasn't in that last case. So in this case, we do have a function and it is onto, but it is not one-to-one. Okay, here's another example, and it's a weird one. We've got a graph, but you would do it the same way. Go ahead and pause the video if you'd like, try to solve it for yourself, and then unpause and see how you did. All right, so the first question is this a function? Remember, for it to be a function, you need to only get one thing out of each number that you put in. But where are the numbers that we're putting in? Well, remember, x is the things you put in, and y is what you get out. For a graph, x is the numbers from left to right, and y is the numbers from top to bottom. And immediately, without doing any sort of like complex math or anything, I'm noticing that here we have x equals -1. Because you have to go to the left one to get to it. And there are 2 dots here. There are 2 dots on -1, which means that if you put in -1, you can get 2 different things. That automatically breaks the rules of a function, which means that it is not a function. And we don't even have to answer the other ones, like one-to-one or onto. We're just done, because it can't be one-to-one or onto if it's not a function. All right, everyone, don't panic. The graph background is gone, but we still have graph points here, so enjoy those. Go ahead and pause the video, try this out for yourself, and then unpause and see if you got it right. All right, so first question. Is this a function? For it to be a function, we have to make sure that we don't have a number we're putting in giving us 2 or more things. So let's see, -3 gives us 1, -2 gives us 2, 1 gives us -4, and 5 gives us 6. Yeah, I don't see the same input giving us 2 outputs. I mean, each one of these is different. So yeah, that's a function. Is it 1-to-1? Remember, for it to be 1-to-1, each of these items here on the right, this is our output, needs to be exclusive to one item. We can't have multiple ways to get the same number. Well, it looks like we have a unique number for each of these, and each of these only has one way to get it. So in this case, yes, this is 1-to-1. And now is it onto? Basically, everything that is promised to be able to make is actually possible to make. Yeah, seems true to me. We have 4 of these numbers here that we can make, and we have a way to make them. So yes. So yes, this is a function, and it is both 1-to-1 and onto. Here's how to figure out if an equation is linear in just 5 minutes. All right, here's our first example. We have an equation here, and we need to figure out if this is linear or not linear. Linear basically just means that if we were to graph this equation, it would be a straight line. If it would like make a curve or something, then that means not linear. If you're taking algebra class right now, you might know that the equation for a straight line is y equals mx plus b. This is the equation that all straight lines are in. But this equation actually doesn't apply if you have like a curved line or something else that's not a straight line. Which means if we want to figure out if this equation is a straight line, all we need to do is try to make it y equals mx plus b. If it turns into y equals mx plus b, then we have a straight line. If it's impossible to turn it into y equals mx plus b, then it's not a straight line. So in this equation, y is by itself. So let's try to get y by itself in this equation and see if it turns into this form. So we can get y by itself by getting rid of this -5. And we can do the opposite of minus, which is plus, to get rid of it. So we will add 5 to both sides. These cancel out. And on this side, we're just left with y. On the other side, we have 3x plus 5. This has the letter and this doesn't, so you can't add these together, so we'll just leave it as 3x plus 5. And already we can see, yep, that's y equals mx plus b, right? M would be 3 and b would be 5. So our final answer is yes, this is a linear equation. All right, here's another example. We have xy equals 7. Well, whenever we have 2 letters or a number and a letter next to each other and there's no sign, that means it's multiplication, right? So we'll get y by itself like before and see if it turns into y equals mx plus b. So this is multiplication, so we need to do the opposite of multiplication, which is division. We need to get rid of this x to leave y by itself, so we will divide both sides by x. These cancel out, x divided by x is just 1, and we're left with y. On the other side, we have 7 divided by x. You can't divide a number and a letter, so it just stays like that. So this does not look like y equals mx plus b, right? Because we have something divided by x. And the only way to fix that would be to move x back over to this side again. So this is not going to ever turn into y equals mx plus b. So basically, whenever you see 2 letters being multiplied by each other, or whenever you see something being divided by a letter, those are both signs that it's not linear, because you will never be able to turn those into y equals mx plus b. So our final answer is that this is non-linear. It will probably be like a curved line of some kind. All right, here's another example. What I'd like you to do is go ahead and pause the video, try to figure out if this is linear or non-linear, and then unpause and see how you did. All right, so we'll do what we did before. We'll try to get y by itself and see if it becomes y equals mx plus b. So we can get rid of this 2 next to the y, but that's more attached to the y right now, so we probably don't want to get rid of that now. We don't want to deal with fractions. So let's get rid of this 2x first. So we can get rid of this 2x by subtracting it from the equation. These cancel out, and on this side, we're just left with 2y. On the other side, we have 4 minus 2x, which you can't subtract a number and another number with a letter in it, so we'll just leave it as that. And now we can get y by itself by noticing that this is multiplication, and do the opposite of multiplication, which is division. So we can get rid of this 2 by dividing both sides by 2. These cancel out, and on this side, we're left with y. But on the other side, we are dividing this by 2, and we have to divide both of these terms by 2. So we'll start with 4 divided by 2, which is 2, and then negative 2x divided by 2. Well, the negative sign is going to stay, and then 2 divided by 2 is 1, and we do have an x here, so the x has to carry over, but we don't have to put 1x. If you have 1x, that's just x. If you don't have the number here, you assume it's 1, so we'll leave it like that. So is this y equals mx plus b? Well, at first glance, you might say, no, it doesn't look like that because we have the number first and then we have x. But in reality, that's the same thing because we can just switch the order of these. Now, if we were to switch the order of these, we can't just turn it into x minus 2. You can't switch the order of subtraction. But as long as you keep the minus sign on the x, we can switch the order. So you can say that this is minus x plus 2. And in this case, this actually is y equals mx plus b. The m is just 1 because we don't have a number here, so you assume it's 1. And then we have plus b, and our b is 2. So yes, this is a straight line. So this would be a linear equation. All right, here's another example. Go ahead and pause the video, see if you can figure out if this is linear or nonlinear, and then unpause and see how you did. So here we're dividing by x, and we can't do that, so this is nonlinear. Okay, maybe we could have taken that a little slower, but yes, that's absolutely true. If you see that it's being divided by x, it's probably nonlinear. We could also reason this through by saying, well, y is already by itself. So anything we do to both sides is just going to add it to the y and like reverse what we're already trying to do, which is to get y by itself. So there's nothing that we can do to turn this into y equals mx plus b. So in this case, it is nonlinear. Here's how to solve for f of x, or g of x, or h of x, or whatever letter you have. So here's our first example. We have here f of x, that's how you say it, with the x in parentheses, f of x, and we need to solve for f of 3. Well, what does that mean? Well, basically, x, remember, for a function is what you put in, and y, or in this case, f of x, is what you get out. So here you may notice that this is f of x, but this is f of 3. So what we've done is we've replaced x with 3. Which means in this x plus 2 part, we're going to do the same thing. We need to replace x with 3. So let's go ahead and do that. We're going to rewrite this top line, but whenever we see an x, we're going to put 3 instead. So we're going to have f of 3 equals, and then x is going to be replaced with 3 plus 2. 3 plus 2 is 5. So in this case, f of 3 is equal to 5. Here's another example. We have g of x is equal to x squared minus 2x plus 1, and we have to solve for g of 5. So you might be asking yourself, well, why is it a g now instead of an f? Does that change anything that we do? Nope, it doesn't change anything at all. Basically, the reason that we use the letter g is because it's the letter after f. So if you have two different equations going on in the same problem, then you would use f and g to not mix them up. But literally g is the same thing as f. Don't get confused over this. So we're going to do the same thing as before. We have x being replaced with 5 here. So whenever we see x in the other side of the equation, we also have to replace it with 5. So g of x is going to become g of 5 equals, and then we have an x here. X becomes 5 squared minus 2 times, and we have an x here, so that's also going to become 5, and then plus 1. So now we just need to solve this, and you may be confused about what we're going to do first, but we're just going to use that thing that you learned in elementary school and then never used again, PEMDAS. So the first step in PEMDAS is P, or parentheses, and we do have parentheses here, but it just has 5 in it. There's nothing to do in the parentheses. So we're going to move on to the second step, which is E, exponents. Do we have an exponent? Yes, we do. We have one right here, 5 squared. And 5 squared is 5 times 5, which is 25. All right, we don't have any more exponents, so we're going to move on to this step, and this step can kind of confuse people. Remember, multiplication and division are the same step. You just have to do all of it from left to right. But in this case, we don't have any division, so that's not going to confuse us. So we do have a multiplication here, though. 2 times 5 is 10, so we're going to go ahead and do that. And then the final step is addition and subtraction from left to right. These are also the same step. So we have 25 minus 10 plus 1. All we have left is addition and subtraction, so we'll just do it from left to right. So 25 minus 10 is 15, plus 1, and that is 16. So g of 5 is equal to 16. That's our answer. All right, here's another example. What I'd like you to do is go ahead and pause the video, try to solve this one for yourself, and then unpause and see if you did it right. All right, so we're going to do this exactly the same way, except this time we have a negative number. So it might get a little more confusing, but we'll do it the same way. So we have f of x equals 3x minus 6, and x is being replaced with minus 2. So let's do the same thing with this. So 3 times x becomes negative 2 minus 6. And now in PEMDAS, we don't have anything to do in parentheses. We don't have exponents. So we're going to move on to multiplication and division, which we have right here. We have a multiplication. So 3 times 2 is 6, but we do have one minus sign, so the minus sign has to carry over. and then minus 6 again. And then all that's left is minus 6. So we lost $6 and then lost another $6. So we've lost $12. So there you go. Our final answer is f of -2 equals minus 12. All right, here's another example. Go ahead and pause the video, try to solve this one yourself, and then unpause and see how you did. All right, so we've got another negative number here, so we'll see how this goes. We are replacing x with -3. So we'll go ahead and do that on this side as well. So we have -3 squared. Now you may notice that I'm putting the -3 in parentheses, and the reason for that is because all of x needs to be squared. You'll see why that makes a difference in a second. So now we have -3 squared. Well, that's -3 times -3. 3 times 3 is 9. And then -3 times -3, well, that's two negatives, and two negatives make a positive. So this is going to stay positive 9. And here's how that would be different if I didn't put parentheses around this. If I had written it as -3 squared, then that would actually be -3 squared. And 3 squared is 9. So it would have become -9. That's why it helps to put x in parentheses so that you know that all of this is being squared. And then that's just plus 2. And 9 plus 2 is 11. So in this case, our final answer is g of -3 is equal to 11. You may have first learned symmetry back in kindergarten when you learned that a butterfly is like an example of symmetry. So is this any different? Not really. Well, actually, it's a little different. Let me explain. So basically, in algebra, graphs can have two types of symmetry. There's line symmetry and point symmetry. When you think about a butterfly having symmetry, that's called line symmetry. A butterfly has line symmetry because you can draw a line through it, and it is the same whenever you reflect across it. So like a butterfly is like a mirror image of itself across the line. Point symmetry is a little bit different. You can think of point symmetry as being like a snake. If you were to draw a line through this, no, this is not a mirror image of itself, so it does not have line symmetry. But it does have point symmetry, because if you put a little dot right in the middle of it, and you rotate everything 180 degrees, you basically just flip it upside down, it would look exactly the same. So let's look at this graph here. Does this graph have any kind of symmetry? Well, let's look at line symmetry first. Can you draw a line somewhere in this graph that will make it a mirror image? In this case, we can actually draw a line right through here, because now everything on this side is a mirror image on this side. This is a mirror image of this. This is a mirror image of this. It works all the way around. Does it have point symmetry? Well, let's try putting a point here and see if it works. This part of the graph right here, if we rotate it 180 degrees, it would probably look something like this. This does not line up with this part of the graph, so no, this does not have point symmetry. But it does have line symmetry, and in a lot of cases, if you see that it does have symmetry, your homework or whatever is probably going to ask you to write the equation of the line. So how do we find the equation of this red line? Well, if it's a straight up and down line or a straight left and right line, it's probably just going to be x equals or y equals. And I can see that at this line right here, this is where x is always 0. Because here's x equals 0, right? X is left and right. X is always 0 right in the center on this line. So in this case, our equation for the line is going to be x equals 0. So there we go. We've figured out that this graph has line symmetry at x equals 0, but it does not have point symmetry. What about this graph? Can we figure out if this has line symmetry and point symmetry? Well, let's see if it has line symmetry. Is there anywhere that we can draw a line that will be a mirror image of both sides of the graph? Well, if I draw a line right here, then no, this is not a mirror image, right? This does not reflect over here. But maybe you're thinking we could draw a line like maybe right here, and then this would be line symmetry. Well, if you just like tilt your head a little bit, or, if I just use the magic of editing, we can see that this is not a mirror image of this, because it's dipping upward this way, but downward this way. So no, this graph does not have line symmetry. But does it have point symmetry? Well, let's go ahead and draw a point right here in the middle of our graph and see if it does. If we take this part of the graph here and we rotate it 180 degrees, it's going to go right here, which is exactly on this line. So yes, this does have point symmetry. But now we have to figure out the point that the point symmetry is at. Well, this is a little easier, hopefully. Here's the point here. We need to figure out the coordinates of this point. But in this case, this point is actually right in the middle of the graph. It has not moved from the middle. So it's gone 0 left and right and 0 up and down. The middle of the graph is always 0, 0. So we can say that this graph has point symmetry at 0, 0. All right, here's another example. What I'd like you to do is go ahead and pause the video, see if you could figure out what kind of symmetry this has, if any, and then unpause and see how you did. All right, first of all, does this have line symmetry? Remember, line symmetry is like the mirror image symmetry that a butterfly has. So it looks like there's nowhere that we can draw an up and down line to get a mirror image. However, we can also draw other kinds of lines. We can draw a horizontal line, and it looks like we can draw it right here. Here we have a mirror image. So this is a mirror image of this. This is a mirror image of this. This line acts as a mirror. So this is the line where there is line symmetry. But what is the equation of this line? Well, remember that the letters are usually the opposite of what you might think. So we have a left and right line here, but because x means left and right, the equation is actually going to have y in it. And that's because on this line, we have all sorts of x amounts. Like here it's -5, here it's 2. But everything on this line has the same up and down value. And that up and down value is -1 because we have to go down 1 to get to this line. So our equation of this line is y equals -1. Now, does this have point symmetry? Well, let's go ahead and put our point right here, and we'll take this part of the graph, and if we rotate it 180 degrees, we get this. Does not line up with this line at all. So in this case, no, we do not have point symmetry. So our final answer is that we have line symmetry at y equals -1. All right, here's another example. Go ahead and pause the video, see if you can figure this one out, and then unpause and see how you did. All right, so we need to determine first if this has line symmetry. Is there a place that we can draw a line and have a mirror image? Well, it seems like the most probable place we can do it is right here. So is this a mirror image? Well, yeah, here, this is a mirror image of this. Here, this looks like a mirror image of this. But look down here. Down here, this actually extends farther than this other part. So this is not a mirror image. And it has to be a mirror image all the way. So in this case, no, this does not have line symmetry. And this probably looks like it's also not going to have point symmetry, but let's test it out. We can put a point here in the middle, or just, somewhere that seems like the most probable to have point symmetry, right? And this part here, if we were to rotate it, then it would look like this. See, because we have this, and it continues on and goes down. This has nothing to do with this part of the graph, so this does not have either kind of symmetry. So that's our final answer, that this does not have any kind of symmetry. It's time to start talking about end behavior. And no, this is not how you acted as a kid after having to sit in the timeout chair for 10 minutes. So here's our first example. We need to figure out what the end behavior is of this graph. What does that mean? Well, end behavior is basically the behavior of the graph as it ends. But you say that doesn't make sense. The graph doesn't end. See, it goes on infinitely. That's what this arrow means. Exactly, which is why end behavior is going to have a bunch of infinity symbols in it. Infinity is not a number, but basically when this graph goes on infinitely, we can say that it is approaching infinity, as in it's going to keep going until it reaches infinity. Which is it's never going to, but it's going to keep going on. It's also approaching negative infinity in this direction because the numbers get smaller and smaller as you go to the left, and eventually they will get infinitely small. So the goal of end behavior is to say, what is the graph doing as it goes towards infinity and as it goes towards negative infinity? So the way we'll write this is we'll say, as x approaches, and this little arrow means approaches, as x approaches infinity, y is going to do something. And then we'll do the same thing for this. As x approaches negative infinity, y is going to do something as well. And I just realized this infinity is off the screen. That's nice. So let's first ask ourselves, what is y doing as x approaches infinity? Well, as you'll see, the graph is going up as it goes to the right. And as it goes up, what does going up mean? That means the numbers are also going up because the higher you go, the numbers get higher. In this case, y is actually also approaching infinity. It's going to keep going up, 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 up until it just can't go up numbers anymore. So in this case, y is also approaching infinity. But what about over here? It says that in this case, x is approaching negative infinity. What is y doing here? Well, the graph, as you can see, is going lower and lower. And as you go lower and lower, the numbers get smaller and smaller. And they are going to keep going smaller and smaller and smaller and smaller and smaller until, we run out of numbers, which will never happen. So y is also approaching negative infinity as x approaches negative infinity. So this is what you would write as your end behavior. As x approaches infinity, y approaches infinity. And as x approaches negative infinity, y approaches negative infinity. Not all graphs are like that. In this case, we have a graph that has a slightly different end behavior, so let's figure out how to find this one. This may look like it's eventually going in a straight line upwards, but that's actually not true. This kind of graph is called a parabola, and basically what this is saying is you are going to be going straighter and straighter upwards as you go up, but you're never going to be going completely straight upwards. This is always going to be slightly going to the left. So in this case, x is still approaching negative infinity here. It's going to keep going farther and farther to the left until it goes through all the numbers. And this way, it's going infinitely to the right. These amounts are going to keep going to the right, to the right, to the right, until you hit the end of numbers. So we need to figure out what y is doing in this case for all of these. So first, let's look as x approaches infinity, as x goes towards the right. It looks like as x goes towards the right, the y, which is the up and down value, is going up, because you can see this graph is going up very fast, actually. So this is going to keep going up and up and up and up and up until we're out of numbers. So in this case, as x approaches infinity, y approaches infinity. But what about this side? As x goes to the left and left, which means the numbers get smaller, what is y doing? Well, y is the up and down value, and y is still going up. It's going up just like this side. So it doesn't matter which way you go, left or right, it's always going to be going up. So in this case, as x approaches negative infinity, y is going to approach positive infinity. It goes up no matter which way you go. It's never going to go down. So in this case, this is our final end behavior. All right, here's another example. What I'd like you to do is go ahead and pause the video, try to figure out the end behavior of this graph, and then unpause and see how you did. All right, so first let's go ahead and label our x like before. Here on this side, it's going infinitely to the left, right? So this is going to be approaching negative infinity. And here it's approaching to the right. So this is approaching positive infinity. So for each of these things that x is approaching, let's find out what y is approaching. So first, as x approaches infinity, which is here, what is y doing? Is it going up or down? Because remember, y means up and down, x means left and right. So in this case, as the graph is going to the right, the y value, which is up and down, is going down. So in this case, as x approaches infinity, y approaches negative infinity. Now what about over here? This is where the graph goes farther and farther to the left. And as it goes to the left and left and left, the graph is also going up and up and up. So in this case, y is approaching positive infinity. So this is our final end behavior. All right, here's one more example. Go ahead and pause the video, see if you can solve this for yourself, and then unpause and see how you did. All right, so let's find out where it's going to the left and right. Here, this is going to the left, and it's going to keep going to the left, so this is approaching negative infinity. And here, this is going to the right. It's going to keep going to the right this way, so this is approaching positive infinity. So let's find out what y, the up and down value, is doing in both of these cases. Over here, where it's approaching positive infinity, what is y doing? Well, the graph is going down and down and down and down, and down is negative for y. So in this case, as x approaches infinity, y is approaching negative infinity. Now what about here? X is approaching negative infinity here because it's going to the left and left. And as it goes to the left and left, it's also going down and down and down. And the numbers down here keep getting smaller and smaller. So in this case, they're getting infinitely small. So y is going to be approaching negative infinity here as well. So this is our final end behavior. What are the zeros of a graph? What are relative minima and maxima? What are extrema? Are any of those even different from each other, or are they all the same thing? Well, here's the answer to all of those questions in just one video. All right, here's our first example. We need to estimate the zeros and relative maxima and minima of this graph. What do any of those mean? Well, first let's talk about zeros. Zeros are the x values where y is equal to 0. I know that's kind of confusing, but basically the way we can figure that out is where it crosses the x-axis, this left and right line here. Because see, this is x and this is y. So for example, this would be a 0, this would be a 0, and this would be a 0. These are all places where it crosses the x-axis. The reason why that we have to figure out where it crosses the x-axis is because the x-axis is where y is 0. It hasn't gone anywhere up or down. So to find the zeros, we just need to figure out what the x values are of each of these points. And they're probably not going to be exact, partially because I drew this graph pretty terribly, but also it says to estimate the zeros. So we don't need to find the exact amount, just kind of where it's close to. So let's look at this one first. How far to the left or right do we have to go to get to this point? Well, if we start in the middle, you have to go to the left 1, 2, 3 to get to this. And remember, as you go to the left, the numbers get smaller. If you were to go to the right, the numbers would get bigger. So this would be -3 because we started at 0 and went down 3. Now, what about this point here? This one, you need to go to the left 1. So in this case, -1 would be another 0. And this one all the way over here, we're going to have to go to the right. So it's going to be a positive number. So we have to start in the middle and go 1, 2, 3 to the right. So that's going to be +3. So there you go. Those are our 3 zeros. And remember that these are estimates. I mean, they're pretty close, but some of them, the line doesn't quite exactly hit that number, but it's pretty close. So these are our estimates. All right, now we need to figure out the relative maxima and minima. Well, first of all, let's clear up something in case you were confused. Maxima and minima are just the plurals for maximum and minimum, which are probably words that you've heard before. Remember, minimum is the smallest amount, and maximum is the biggest amount. So maxima is just multiple maximums. Yeah, that's the plural form. Now, what are relative maxima and minima? What does this word mean? Well, the opposite of a relative maximum or minimum is an absolute maximum or minimum. An absolute is basically the highest number that you can get for y in the entire graph. In this case, what is that? Well, I mean, this goes up infinitely. So there is no absolute maximum. It's just going to go to infinity. But a relative maximum is basically the highest point on like a hill of the graph. In this case, we do have a hill of the graph right here, see? So the relative maximum would be right here. And it is possible to have multiple relative maxima. That's why we have the plural form here, because you can have a bunch of hills on the same graph. And relative minima are basically just the opposite of that. It's the lowest points in these like valleys here, right? So here's one right here. Now, I did talk about some other words that you might see. For example, the word extrema. Extrema are literally the same thing. Extrema are just relative minima and maxima. And occasionally you might also see the term turning points. Those also mean the same thing because turning points are basically where the graph changes direction. So let's see, it's going up, and now it's going down. So this is a turning point. So we've found our relative maxima and minima right here, right? Here are the two of them. But we need to tell the coordinates of these. It doesn't help to just circle it. So let's find the maxima first. Here's our maximum, and we'll call it a maximum because we only have one of them. Maxima would be multiple maximums. So we need to figure out the coordinates of this, and remember, we're estimating. So this is not exactly on a coordinate, but we'll just pick out the nearest one. So the nearest one is this one right here. So when you write coordinates, you have to do x first and then y. So x is left and right. So we start in the middle and we have to go left 1, 2 to line up with this point. And left is negative numbers. So our x is going to be -2. And now we have to figure out how high up we have to go. We have to go up 1, 2, 3. And that's positive because as you go up, the numbers go up. So 1, 2, 3, we have to put 3 for y. So we found our maximum. Our relative maximum is -2, 3. But now let's find our minimum. That seems to be right around this point. And to get to this point, we have to go to the right 1. The right is positive numbers, so that's going to be a 1. And now we need to figure out y. Well, in this case, we're not going up, we're actually going down. So we're going to go down 1, 2, 3, 4. When you go down, those numbers are negative. So this is going to be -4 for y. So there you go. This is our answer. We have found the zeros and then the maximum and minimum for this problem. Here's another example, and yes, this is a very weird looking graph, but go ahead and pause the video, see if you can find the zeros and relative maxima and minima, and then unpause and see if you got it right. All right, so first let's look for zeros. And remember, zeros is where it crosses this x-axis, the left and right line here. Whenever it crosses that, that is a 0. And in this case, that's actually going to make our lives easier because we only have one of them, and it's right here. This is the only place where it crosses this line. So now we need to figure out what the x value is of this point. How far left or right do we have to go? Well, Not at all. We just stay here, which means that our 0 is going to be 0. Now we need to find the relative maxima and minima. Remember, those are the hills and valleys of our graph. And as you can see, we have more of them than last time. So this time I'm going to write maxima because we have multiple of them, because that's plural. So where do we see the tips of hills on our graph? Well, I see one right here, and I see one right here. These are the two hills of our graph. So we need to figure out the points of these, or at least estimate them. We have one like right about here. So x is going to be how far left or right we have to go. So to get to this point, we have to go left 1, 2, 3, 4. And left is all of our negative numbers. So our x is going to be -4. And now we have to figure out y. How far up or down do we have to go? Well, we have to go down 1, 2. So that's going to be -2. So in the last problem, that would mean that we're done. But in this case, we actually have another hill over here. So this is also going to become a maximum, a relative maximum. So we have to go to the right 1, 2 to get to it. The right is positive numbers. So this is going to be 2 for x. And we have to go up 1, 2, 3. And up is positive numbers as well. So that's going to be 3 for y. So we found our two relative maxima, but now we have to find our minima. So where can we find our minima? Remember that minima are valleys, these bottoms of valleys here, like this one, and this one right here as well. So let's figure out the coordinates of these. This one is right about here, and to get to here, we have to go to the left 1, 2 to be lined up with it. So our x in this case is going to be -2. But now we have to figure out y. That's up and down. We have to go down 1, 2, 3, 4, 5. And that's going to be negative because down is negative. So we have to go down 5, -5. And now finally this one. This is right about here. We have to go to the right 1, 2, 3. To the right is positive numbers. So that's going to be 3 for x. And then we have to figure out y. Y is up and down. So we have to go up 1. 1 up is positive numbers, so our y is going to be 1. So there you go. We have found our 0, which is 0, and we found our two maxima and two minima. So there we go. One of the most confusing graphs that you'll have to graph in Algebra 2 is a piecewise function. Like, what on earth is this? Here's our first example, and in this case, we have this weird thing here. Like, what even is this? Well, this is called a piecewise function because it is in pieces. This is our first piece here on this line. And this is our second piece. So the main thing that we want to look at is right here. These are our actual graphs. So if you were to graph a normal line, this would be y equals x minus 2, and this would be y equals x plus 3. But these are just chunks of our graph. So these second amounts here, these ones here, these tell you how big the piece is. So this is saying the piece, this graph here, is going to keep going until we hit 1, and then it's going to stop. And this one here says x is greater than or equal to 1. So greater than means that starting at 1, it's going to continue on with this graph here. So the way that we're going to do this is we're going to start by graphing y equals x minus 2. And then we're going to only keep the part of the graph that is less than 1 on x. So let's go ahead and do that. If you're not quite familiar with graphing a line in general, then I have a video on it that you can watch on the card on the screen right now. So I would recommend that you watch that first and then come back here. So we're graphing y equals x minus 2, and we're going to use y equals mx plus b to graph this. So in this case, our m is going to be, well, we don't have a number here, but whenever there's not a number, we assume it's 1. So our m is going to be 1. And our b is going to be minus 2. We have to include the minus sign. So let's go ahead and graph our y-intercept first. Our y-intercept is minus 2, which means it's going to cross the y-axis at minus 2. So we're going to start in the middle and go down 1, 2, because down is negative numbers. So it's going to cross the y-axis right here. And now we need to graph our slope. Our slope is 1, and remember that slope is rise over run. In this case, our rise is 1, and it is not over a number, so you assume it's over 1. So our rise is 1 and our run is 1. So let's go ahead and graph that. We're going to rise 1 and run 1. And this is going to be our point right here. So let's go ahead and graph a line in between these. But remember, this is a piecewise function, which means that this is only going to be a piece of the graph. In this case, you'll see that it keeps going until x is 1. Whenever x is less than 1, this piece of the graph is true. So where is x 1? Well, remember, x is left and right. So x is 1 right here. So this is the cutoff point here for when this piece of the graph stops. Everything to the left of this will stay, but to the right of this is going to be a different piece. So we need to get rid of this part of our line. So I'm going to erase this part of our line. So there you go. This is our piece. And now the final thing we have to ask ourselves is, we are going to draw a point here, but we can draw a regular point or we can draw an open point. So how do we know which one to draw? Well, it depends on whether or not the point is included in the answer. In this case, x is less than 1. 1 is not less than 1. If there was a line under here, then that would mean less than or equal to, and then 1 would be included. But because we don't have a line underneath our sign, that means 1 is not included. So we have to draw an open circle to show that. So there you go. We have our first piece of the function. But remember, whenever it's 1 or greater, that means that we have this piece instead, x plus 3. So let's go ahead and graph x plus 3. So y is equal to x plus 3. And in this case, our slope is still 1. And our y-intercept is plus 3 instead of minus 2. So let's go ahead and graph plus 3 first. We're going to start in the middle and go up 1, 2, 3. This is going to be where it crosses the y-axis this time. And now our slope is going to be the same. It's going to be rise over run. The rise is 1, just like last time. And the run is going to be also 1 because it's over 1. So we're going to do the same thing. We're going to rise 1 and run 1. And we're going to put another point here. So now let's go ahead and draw a line in between these 2 points. But remember that this is just going to be a piece of our final graph. And remember, 1 is still the cutoff point right here. And it's x is greater than or equal to 1. So x has to be greater than 1, so on this side. So everything to the left, we're going to erase. So we're going to go ahead and erase all of this until we get to 1. There we go. So this is our second piece. And now we have to figure out which dot we're going to draw. Well, in this case, we do have a line underneath our sign here, right here, which means that 1 is included. So we're going to draw a filled in circle. So there you go. This is the final graph. And I know it looks weird, but basically it's x minus 2 up until 1, at which point it changes into x plus 3 and continues on. All right, here's another example. What I'd like you to do is go ahead and pause the video, see if you can graph this one for yourself, and then unpause and see how much you got right. So let's go ahead and graph our first piece here, 2x plus 1. So that's going to be y equals 2x plus 1. And to graph this, we're going to use slope-intercept form, y equals mx plus b. So in this case, our m, our slope, is going to be 2. And our b, our y-intercept, is going to be plus 1. So let's go ahead and do our y-intercept first. That's where it crosses this y-axis here. It's going to cross it at 1 right here. And now we need to graph our slope. Slope is rise over run. And our rise is going to be 2 because our slope is 2. And it's not over anything, so we assume it's over 1. So our run is going to be 1. So we're going to rise 2, and we're going to run 1. And this will be another point. So let's go ahead and draw a line in between these points. But remember, this is just a piece of the graph. Our cutoff point is negative 2. So this is x is less than negative 2. So everything to the left of negative 2 will be part of our graph, but everything to the right we need to erase. So we're going to erase everything up until negative 2 right here. Here's negative 2. So now what kind of dot are we going to draw? Is it going to be a full circle or an open circle? Well, in this case, we have a line underneath our sign, which means that negative 2 is included. So we're going to draw a filled in circle. So we finished our first piece of the graph. It's right here. But now let's go ahead and do our second graph. So y is equal to, in this case, negative x minus 1. Our slope is going to be, well, we don't have a number in front of x, so we assume it's 1. But we do have a negative sign, so our m is going to be minus 1. And our b, our y-intercept, is also going to be minus 1 right here. So first we're going to do our y-intercept. That's going to be where it crosses the y-axis. So it's going to cross at minus 1, which is down 1. So we'll draw a point here. And now we need to graph our slope. Slope is rise over run. Our rise is just going to be negative 1. And our run, well, we don't have a number under here. And as always, you assume it's over 1. So our run is going to be 1. So our rise is negative 1. A negative rise means that we're falling. So we're going to go down 1. And then we're going to run 1, just like the other ones. So we'll have another point here. So let's go ahead and draw a line in between these 2 points. But remember, this is only a piece of the graph. So x is greater than -2. So everything greater than to the right of -2 is going to be included. So everything to the left we need to erase. So we're going to erase this part here up until -2. Here's -2. So that will be where it stops. And now we have to figure out what kind of point to draw here. Is it going to be a filled in circle or an open circle? Well, we do not have a line underneath our sign, which means that -2 is not included. So we're going to have to draw an open circle. So there you go. This is our final graph. You see that the line goes like this, and then at -2, it stops and becomes this graph, and then it continues on infinitely. Transforming graphs is possibly the most common topic that algebra students get confused about. But here's how you can do all three types of transformations in just one video. So here's our first example. We need to first describe the transformation that's happening for this equation and then graph it on our graph here. Well, to be able to do this, we need to do two main steps. The first step that we need to do is figure out what the parent graph is. What's a parent graph? Well, basically, when you're transforming functions, there are three main types of parent graphs that you're going to be using. The first one is just y equals x. Y equals x is basically just your standard straight line. It goes diagonally like this, and it has a slope of 1 because there's no number in front, so we assume it's 1. Another common parent graph is y equals x squared, and this is called a parabola. And the way you figure out how to draw this parabola is you would say, well, 0 squared is 0. So we would put a point at 0, 0. 1 squared is 1, so you put in 1, you get out 1. So 1, 1 is going to be another point. But if you put in 2, 2 squared is 4. So if you put in 2, you go up 1, 2, 3, 4. And this is actually the same on the other side, because if you put in a negative number and square it, you get a positive number. So ultimately, you end up getting this kind of bowl shape like this. This is the graph of y equals x squared. And lastly, you might see y equals, what is that? Well, these lines to the left and right of x, those are the absolute value signs. This is the absolute value of x, which basically just means whatever number you put in, make it positive. So if it's already positive, it's not going to make a difference. So it's just going to be like y equals x, and it's going to go up like this. But instead of going down like this, they're going to stay positive numbers. So it's going to go back up like this. So if you ever see the absolute value of x, this is going to be a V shape like this. And you may notice that all of these parent graphs have started in the middle. They will always start at 0, 0 and then stem out from there. So which parent graph do you think we're using in this case? Well, I see y equals x squared here. So our parent graph is going to be y equals x squared. And remember, that's the bowl shape, the parabola. But now we need to do step 2, which is apply the transformation. And just like before, there are three types of this as well. There are translations, there are reflections, and there are dilations. I know this is already like pretty confusing, but you actually don't even need to know these names. We're going to go over each of these one at a time, and I'll explain to you what they mean. So we're going to be doing them in order. So in this case, this first one is going to be a translation. And the way you would know this is a translation is this. Translations always involve adding or subtracting to the equation. So in this case, we are adding 1 to the equation. Whenever you add to the equation, the graph goes up. And whenever you subtract from the equation, the graph goes down. There is one exception to this that I'll talk about in the next example. But in this case, all we care about is it is plus 1. And whenever you add 1 to a parent graph, that means you move it up 1. So we're going to graph the same exact thing, but 1 square higher. So there you go. You'll notice that at each part here, we have moved it up 1 square. So in this case, this black line is our final graph. Now this green part, our parent graph, isn't actually part of our answer. If your homework says that you need to graph the parent graph, then just go ahead and leave it. If it doesn't, then if you want, you can just go ahead and erase the parent graph. So there you go. This is the graph of y equals x squared plus 1. And if your homework says you also need to describe the translation, then all we need to do is say that the graph went up 1. There you go. We've described it. It went up 1. Now you may remember me saying that there is one exception to adding and subtracting, meaning up and down. And this is that exception. You may notice we are doing the same thing. We are adding 1 to our equation. But in this case, we are doing it inside the parentheses. Before, only x was getting squared. But in this case, the plus 1 is also getting squared with the x. So what do we do about this? Well, first let's figure out our parent graph. We can choose between y equals x, y equals x squared, or y equals the absolute value of x. But don't get too confused about this. We have a squared here still, so it's still going to be y equals x squared, even though the squared is not right next to the x. So we are going to draw the same parent graph as before. But what do we do now? Are we going to go up 1 like before? No, actually we're not. Whenever you add or subtract inside the parentheses, you have to move it left or right. Now you may be asking yourself, well, which way do we move it, left or right? And if you were to take a guess, you might say, well, I think we'd move it right, because right is positive numbers and left is negative numbers. But here's the weird thing about moving left and right, is that it's actually the opposite of what you think. If that confuses you, then maybe this will make sense. Let's think of this equation without the squared. Let's say it was just y equals x plus 1. If you wanted to solve for x, you would subtract 1 from both sides. And in this case, x would be y minus 1. When we're talking about x by itself, we are actually taking what x already was, which is y, and subtracting 1, which means to the left. So in this case, we are actually going to be moving left 1. And if you have to describe the translation, you would just say left 1. So let's go ahead and graph this same parent graph, but we're going to move everything to the left 1. So there you go. We have moved everything to the left. As you'll see, everything has been moved to the left 1 square. So let's go ahead and erase the parent graph. And there you go. This is the final graph of y equals x plus 1 squared. Now, I did say that there were 2 other types of transformations you have to do, and this is an example of one of those. So first, we need to figure out the parent graph. Well, the parent graph is going to be y equals the absolute value of x. Remember, that was one of our choices from the beginning of the video. And this graph is in the shape of a V, but we have this negative sign here, and this is actually going to be our transformation for this problem. Whenever you have a negative sign on it, that means that everything of the graph is going to become negative, which means we are going to flip everything upside down. And this is called a reflection. So if you had to describe this transformation, you would literally just say it's a reflection. Or if you wanted to be a little more technical, you would say it's a reflection across the x-axis, because this line here is the x-axis. This one up and down is the y-axis. And in this case, we're going to be flipping everything upside down. So there you go. This is the same exact graph, except everything is upside down. Everything became negative. So we can go ahead and erase the parent graph now. And there you go. This is the final graph of y equals negative the absolute value of x. All right, so here's our final example. Before we did translations, which is adding or subtracting from the equation, and we did reflections, which is putting a negative sign. But in this case, we are putting a number in front of it, or in other words, we are multiplying here. And in this case, we're going to be doing dilation. So first, let's go ahead and graph our parent graph as before. It's the same one as last time. We have y equals the absolute value of x. But now, what do we do with this 2? Well, if we think about this logically, we have 2 times the entire graph. So everything is going to get multiplied by 2. So for example, here, this point here is above the ground, above the x-axis here, by 1 square. So if we multiply that by 2, it will now be above 2 squares. And this one here, this is 2 squares above the ground. It is now going to be 4 squares above the ground because we are multiplying it by 2. So if we do that to the entire graph, this is what it's going to look like. Here is our graph of y equals 2 times the absolute value of x. You'll notice it was actually squished together. The bigger the number here, the more we are going to squish and squish this graph until it's really skinny. This is called compressing the graph. So if you were going to describe this, you would say you are compressing the graph. Or if you wanted to give a more technical answer, you would say compressed by a factor of 2. Now, you will always compress the graph for any number here that is bigger than 1. But let's say that it was less than 1. Let's say this was actually 1/2. In that case, you would multiply everything by 1/2. So here it was 2 above the ground. Now it's only 1 above the ground. This one was here 4 above the ground. Now it's only 2. And you'll notice that we're now going to have a stretched out V shape. And I'll go ahead and draw it for you. Here we are actually stretching it out. And that is true for any number you put in front that's less than 1. But in this case, we are compressing it. So this is the final graph of y equals 2 times the absolute value of x. Here's how to find the x and y intercepts of any graph, like this one. So here's our first example. We need to figure out the x and y intercepts of this graph. Well, first of all, remember that x and y mean left and right and up and down. So in this case, all these numbers left and right here are x, and all these numbers up and down here are y. X and y intercepts basically just mean where does this graph cross those lines. So first of all, x intercepts X-intercepts are wherever the graph crosses the x-axis. So it seems to cross it right here and right here. So how do we figure out the x values of these points? Well, it's how far to the left or right they are on the graph. So in this case, this first one here, this one you have to go to the right 1 to get to it. And remember, numbers to the left are negative numbers, but numbers to the right are positive numbers. They go up as you go to the right. So in this case, 1 is an x-intercept. That's not the only x-intercept. We also have one here. And to get to this one, you have to go to the right 1, 2, 3 to get to it. So in this case, 3 is also an x-intercept. So there we go. We now have 1 and 3 as our x-intercepts. But what about y-intercepts? Well, y-intercepts work the exact same way, but for the y-axis, this up and down line. Wherever the graph crosses the y-axis is a y-intercept. So it looks like it only does that in one point this time. Right here is our y-intercept here. And we have to count how far up or down it has to go. Numbers get bigger as you go up the graph. So this is going to be positive numbers up here and negative numbers down here. So to get to this point, we have to go up 1, 2, 3. So in this case, our y-intercept is going to be 3, and that is our only y-intercept. And the last thing to note here is that if you ever have to find the roots of a graph, or the zeros of a graph, or the solutions of a graph, any of these words refer to the x-intercepts. So there you go. Our final answer is that 1 and 3 are x-intercepts, and that 3 is the y-intercept. All right, here's another example. What I'd like you to do is go ahead and pause the video, see if you can figure out the x and y intercepts on your own, and then unpause and see how you did. All right, so first let's find our x-intercepts. Remember, x is the left and right line. Y is the up and down line. So where does this graph cross the x-axis? Well, it looks like it crosses it right here, and then goes around here and crosses it again right here, and then it crosses it again right here. So let's go ahead and figure out the amounts for each of these. For this one, we actually have to go to the left. And remember, to the left, these are negative numbers. So starting from the middle, we have to go to the left. 1, 2. So in this case, negative 2 is going to be an x-intercept because the left is negative numbers. What about this one here? This one we need to go to the right, and we need to go to the right 1. So 1 is going to be an x-intercept. And finally, this one right here. For this one, we also need to go to the right. We need to go to the right 1, 2, 3. So 3 is an x-intercept. So now let's figure out y-intercepts. In this case, we only cross the y-axis once, and it's right here. Now we need to count how far up or down we need to go. In this case, starting from the middle, we need to go up 1, 2. So 2 is going to be a y-intercept. And that is our only y-intercept in this case. So there you go. Our final answer is that negative 2, 1, and 3 are x-intercepts, and 2 is our y-intercept. It's time to start graphing quadratic equations, which also requires you to find the y-intercept and the axis of symmetry, and requires you to plug in numbers into equations. Yeah, there's a lot of stuff, but don't worry, it'll be all broken down in this video. All right, here's our first example. We need to graph this quadratic equation. Well, if you've done a straight line graphing before, you might know that the equation for a straight line is y equals mx plus b. For that, m is the slope and b is the y-intercept. So essentially, if you were graphing a straight line, you would see what numbers are in each of these letters and then use them accordingly. Well, we're going to be doing the same thing for a quadratic equation. We're going to be using a different form, and that is y equals ax squared plus bx plus c. So what do these letters mean? Well, A and B don't necessarily have names, but they're going to be used in something called the axis of symmetry. And in this case, C is our y-intercept. First, let's find out what our y-intercept is. Well, what is here for C? Well, in place of C in this equation, we have 2. So our y-intercept is going to be 2, which means that's where it crosses the y-axis here. So we can plot 2 right here. There's going to be a point right here because you have to go up 1, 2 to get to where it crosses the y-axis. But now we're going to find probably the most important part of graphing a parabola, which is the axis of symmetry. Now the equation for the axis of symmetry is negative b over 2a. So in this case, what is b? Well, b is where it replaces b. So you might say, oh, b is 4. No, b is negative 4. You always have to include the sign in the numbers. So in this case, b is negative 4, so this is going to become negative 4, which is just positive 4. So we'll just make these positive. And 2a, well, 2 times what is a? Well, in this case, we don't even have a number here. And whenever you don't have a number in front of a letter, then you just assume it's 1. So it's going to be 2 times 1. And 2 times 1 is 2, so it'll be 4 divided by 2. And 4 divided by 2 is 2. So the number for our axis of symmetry is 2. Well, but the axis of symmetry is actually a line. It's going to be an up and down line. So technically the equation of that line is x equals 2. So if you have to write the axis of symmetry, it would be x equals whatever number you get. So how do we graph our axis of symmetry here? Well, the axis of symmetry, like I said, is an up and down line. And it's going to be where the graph is symmetrical. Because remember, our goal for a parabola is to get this kind of bowl shape. And the bowl shape is symmetrical right here, because this line acts as a mirror. It's a mirror image on both sides of the mirror. So the axis of symmetry basically just told us where that mirror is. It's at x equals 2. So we're going to start in the middle and go 1, 2. It's going to be right here that our mirror is. So let's go ahead and graph that. So we now know what our axis of symmetry is, but we don't know where to put a point on this axis of symmetry. Where is going to be that bottom of the bowl shape? Well, to do that, we need to plug in 2 back into this equation and find out what we get for y. So in this case, we're finding f of 2 because we are plugging in 2 to find out what we get for y, and then we'll know where to put our point. So whenever we see an x, we're going to replace it with a 2. So x squared is now 2 squared. And then we have minus, and then 4 times, and x becomes 2, like before, plus 2. 2 squared is 4. 4 times 2 is 8, and then plus 2. 4 minus 8 is negative 4, because we had $4, and then we spent $8, so now we are down $4, and then plus 2. And for the same dollar example, if you want to use it again, we lost $4, gained 2 back, we are just still down $2. So whenever x is 2, our y value is negative 2. So how do we graph that on our axis of symmetry? Well, it says that y is negative 2. So we're going to start here on this line and go down 1, 2. This is going to be our point here. And this is actually going to be called our vertex. Because when we draw our bowl shape, this is going to be the bottom of the bowl, the very bottom. Now, if we were graphing an upside down bowl, because sometimes they can be upside down, then it would be the top of the bowl. That's the vertex. Now, to draw an accurate graph, we need to have 5 points to draw our parabola. So we have 2 right now. We have 1 here and we have 1 here. But we can utilize this fancy red line here, because remember when I said this is a mirror, that means we can use that to our advantage to get more points. So we have a point right here. It is 2 away from the mirror. So we know that we're going to have another point on the other side of the mirror, also 2 away. So if we go 1, 2, we have another point here. We didn't even have to do any extra math to figure out this point. We've got it right here. So we now need to figure out 2 more points. So at this point, you can kind of just pick whatever. I think if we start picking out points this way, we're going to get off the graph. So let's go ahead and pick here where x is equal to 1 because you are 1 to the right of the middle. So let's go ahead and plug in 1 into this graph and figure out where our point is right here, just like we did for the axis of symmetry. So it's going to be f of 1 because we are plugging in 1 into the equation. We have x, that's going to be replaced with 1, so 1 squared, minus 4 times, and this is going to be 1, plus 2. And now let's go ahead and simplify this down. So 1 squared, 1 times 1, that's just 1, minus, and then 4 times 1, anything times 1 is itself, so that's 4, and then plus 2. 1 minus 4, gain $1, lose $4, you're down $3, and negative 3 plus 2 is negative 1. So in this case, on this x equals 1 part here, y is negative 1. So we're going to go where we wanted to find our point, and because it's negative 1, we have to go down 1. So it's going to go down 1, and here's a point right here. Now we need 1 more point. So can you think of how we can figure out this last point? If you said the mirror image or the axis of symmetry or that red line or anything like that, you're right. We can use this red line as a mirror image. So this is 1 away from the mirror. So on the other side of the mirror, we're also going to be 1 away. So right here, there's going to be a point here as well. And look at that, we already have 5 points. We only did math for a couple of those points, but we figured out all 5. So now we just need to draw the bowl shape between these points. So I'll do the best I can. So there we go. We have our parabola here, and this is the final graph of f of x equals x squared minus 4x plus 2. It's time to start solving quadratic equations, and the first way you'll learn how to do it is with graphing. All right, here's the problem that we'll be doing in this video. We have the equation x squared minus x minus 6 equals 0, and we need to solve for x. Now, we can't solve for x the normal way, because normally in an algebra equation, you would try to get x by itself, and then see what x is. But in this case, not only do we have two x's, but we have one that's squared and one that's not squared, and we can't combine these. There's no way to combine them. So we're never going to get x by itself. But there's another way to figure out what x is equal to. And that is if we graph this equation, anytime it crosses the x-axis, that's this vertical line here, then we can figure out what x is equal to. And the reason that we can do that is this equals 0 here. You see how this is normally y equals x squared minus x minus 6, but in this case it's equals 0. So that means y is 0. And along the x-axis, that's where y is 0. We're not going up or down at all. So how do we graph this? Well, the form for every quadratic equation is ax squared plus bx plus c. Now, if you have no idea how to graph one of these quadratic equations, I do already have a video on it that you can watch on the card on the screen right now, but I'll also review how to do it here. So what do each of these letters mean? Well, c is the y-intercept. This is going to be where it crosses the y-axis here. And A and B are both going to be used to help us find our axis of symmetry, which we'll get to later. So what is C? Well, C, you might be going, oh, well, C is 6, right? Because 6 is where C is. But you always have to include the sign. So it's actually going to be minus 6. So that's where it crosses the y-axis. So we're going to start in the middle, and we're going to go down 1, 2, 3, 4, 5, 6. There's going to be a point right here. That's where it crosses the y-axis. So now let's find our axis of symmetry. The axis of symmetry is basically where the graph is symmetrical. It's like a mirror, and I'll show you what that means in a second. So the equation for the axis of symmetry is always negative b over 2a. So what is b? Well, b, you'll see we don't have a number in front of x, but remember that if we don't have a number in front of a letter, then that means it's 1. So in this case, b is not 1, negative 1. Remember, we have a negative sign here. So in this case, it's going to be negative, negative 1. Or in that case, two negatives make a positive. So we'll just write positive 1. And now 2a, well, that's going to be 2. And then what's a? Well, a, there's also not a number in front of here, so it's just going to be 1. So a is 1. So we have 1 over 2 times 1, which is 1/2. So this means that our axis of symmetry, 1/2 here, is going to be where the mirror is. And remember, that mirror is going to be like an up and down line. If we start in the middle and we're going to go to the right, because x means left and right, we're going to go to the right 1/2 of a box. So right here, we're going to draw an up and down line here. So let's go ahead and do that. So now we know where our mirror is. It's right here. And we also know that the vertex is going to be on this line. The vertex is basically just like the bottom of the bowl shape that we're going to be graphing. So to be able to figure out where our vertex is, we need to plug 1/2 into this equation and figure out what we get for y. And in this case, there is no y, but that's because we replaced y with 0. So we're going to put y instead of 0 for this equation. So we're going to put 1/2 for each of these x's. So x squared is now going to be 1/2 squared. And then we have minus 1/2 minus 6 is equal to y. And we're going to figure out what y is. So 1/2 squared, well, that's 1/2 times 1/2. And whenever you are multiplying two fractions, you multiply the tops and the bottoms. So 1/2 times 1/2, that's 1 times 1 is 1, and 2 times 2 is 4. So 1/4. And now minus 1/2 minus 6. And now we have 1/4 minus 1/2. Well, we're going to have to get a common denominator here, right? So we will multiply 1/2, we'll multiply the top and the bottom by 2. So we get, instead of 1, we'll get 2, and instead of 2, we'll get 4. So now we have a common denominator. And when you're adding or subtracting fractions, you have to make sure the denominators are the same, and then the denominator just stays the same, and you add or subtract the tops. So 1 minus 2 is negative 1, and then over 4. So we're going to have negative 1 over 4 minus 6. Now, we could figure out the improper fraction for this and all of that, but if you want to make your life easier just because we're graphing, all you have to do is just say, okay, well, this is minus 6, so we've lost 6, and then we've lost another 1/4. So we've lost a total of 6 and 1/4. So that is going to be the y value for this mirror, this axis of symmetry. So we're going to start in the middle at the axis of symmetry, and we're going to go down 1, 2, 3, 4, 5, 6, and a 4th. So that's going to be about here. All right, so now if we were just graphing the parabola, we would say we need 5 points to make it the most accurate for graphing. But in this case, we're just going to use however many points we need to figure out exactly where it crosses this line. Because wherever it crosses this line is going to be what x is equal to. So first of all, I know that because this is a mirror image, because we have a point here, remember from the beginning, we know that there has to also be a point right here, because this red line is a mirror and the points are mirror images of each other. So now let's go ahead and plot some more points. Let's go ahead and do it like right here. So here would be x equals 2 because it's 2 squares from the middle. So let's figure out where we would plot a point here. And the way we do that is basically by doing what we did before. We're going to plug in 2 into this equation and see what we get. So instead of x, we're going to have 2 squared minus, instead of x, we're going to have 2, and then minus 6. So 2 squared, that's 2 times 2, which is 4, minus 2, minus 6. And now 4 minus 2 is 2. And then 2 minus 6, we had $2, and we lost $6, so we're down $4. So we know that here, y is going to be equal to negative 4 on x equals 2. So we're going to go at x equals 2, and we're going to go down 1, 2, 3, 4. And we're going to plot a point here. And now because we know that this is a mirror image, we can plot a point exactly on the other side of the mirror, which would be right here. And the way that you would know that it goes right here is because the distance between the mirror and this point here is 1.5 squares. So you would go 1.5 squares the other way as well. So now this would be enough points to just graph our parabola, but because we want to get the exact numbers if possible, we'll go ahead and graph a couple more points just to make sure. So let's go ahead and plot a point on right here. This is x equals 3 because it's 3 from the middle. So let's see what we get for 3. So we have 3 squared minus 3 minus 6. 3 squared, that's 3 times 3, which is 9. 9 minus 3 is 6. And then 6 minus 6 is 0. So y is going to be equal to 0. So at x equals 3, that's 3 to the right from the middle, we're going to have y equals 0. And y equals 0 means we're not going up or down at all. So we're just going to plot it right here. So you'll notice this is actually going to be one of our answers because it crosses the x-axis here. But remember, we do have a mirror image. So this is 2.5 squares from the mirror. So we're going to have to go 2.5 squares this way as well. So there's going to be a point right here. So it looks like we found our 2 answers. And yes, whenever you have a quadratic equation, it is normal to have 2 answers. You won't always have 2 answers, but most of the time you will. So let's go ahead and draw our bowl shape. All right, well, this is probably the worst bowl-shaped graph I've ever drawn, but it's fine because it doesn't matter. We're just trying to figure out where it crosses the y-axis. So it does it right here and right here. So the last thing to do is to figure out the x values of these points. Well, this one we already know because we just did it, right? You start in the middle and go 1, 2, 3. So x equals 3 is going to be an answer. But we also have this one right here. So where's this one? Well, if you start in the middle, you have to go to the left, 1, 2. And remember, to the left is negative numbers. So this is going to be negative 2. So there you go. Our answers to this problem are negative 2 and 3. And if you wanted to check your work to make sure you did that right, all you'd have to do is plug in these numbers back into the equation and see if you get 0. All of your life, you've been doing math with real numbers. So boring, isn't it? Well, it's time to start doing math with fake numbers. What does that even mean? Well, this is an example of a fake number, or as we'll call them, imaginary numbers. You know how all of your teachers have told you that you cannot take the square root of a negative number? Well, it's kind of true. Like, no, you can't. And the reason for that is because whenever you multiply the same number by itself, then you're going to always get a positive number. So like, for example, if I had 5 times 5, that's 25. But if I did negative 5 times negative 5, well, 2 negatives make a positive, that's still 25. So there's no way to multiply a number by itself and get a positive number. That is until you enter the world of imaginary numbers. So basically, what is the square root of negative 1? Well, I mean, you can't do that, right? But the square root of negative 1 is going to be a new unit, and we're going to call it I. Now, the letter I always means the square root of negative 1. Always. It's not going to mean anything else. And the reason that we even have imaginary numbers, it might seem weird that we even have these if they don't exist. Well, when you're solving equations, you might come across imaginary numbers, numbers that don't exist. But you can combine imaginary numbers in some ways to actually get real numbers from them. So for example, what if we had I squared? What if we had I times I? Well, in that case, I is the square root of -1, right? So we're going to have the square root of -1 times the square root of -1. Well, if you're multiplying a square rooted number by itself, that actually cancels out the square roots, because that's like saying you have a square root and then you're squaring it. They cancel out. So you're just going to end up with -1. Now, what about I cubed? Well, I cubed is going to be the square root of -1 times the square root of -1 times the square root of -1. And we know that two square roots of -1 make -1. So we have -1 times the square root of -1. And the square root of -1 is I. So in this case, we're going to have -1 times I. And -1 times something just means the same thing as putting a negative sign on it. So we're going to have -I. And finally, what is I to the fourth? Well, I to the fourth is, well, you know what it's going to be. 2 square root of -1s make -1. So we have -1 times -1. And -1 times -1 is 1. That means if you get I to the fourth, it just turns into 1. So it basically cancels itself out. So here's our first example problem. We need to figure out I to the 11th. Well, we don't want to write out 11 square roots of -1s, but there's actually a simpler way we can do this. And all we have to do is remember that I to the fourth means nothing, it just means 1. We can actually take I to the fourth out of this. Remember, this would be I times I times I times I, and then it's like 11 times. So we can split this up as I to the fourth times I to the seventh, because we have 4 i's times 7 more i's. And we know that I to the fourth is equal to 1. So we're going to have 1 times I to the seventh. And anything times 1 is itself. So this 1 is doing absolutely nothing here. So we can just cross it out. And now we only have I to the seventh. So what is I to the seventh? Well, we can actually do the same thing here. We can split this up into I to the fourth times I to the third. And again, I to the fourth is the same thing as 1, so it's doing absolutely nothing here, so we can cross it out. And now we just have I to the third here. And if you don't quite remember what I to the third was, we'll just work it out again. So remember, that is the square root of -1 times the square root of -1 times the square root of -1. And 2 square roots of -1 make -1. And then times, and then the square root of -1 is I. And -1 times I is just -I. So in this case, I to the 11th is equal to -I. So you can see how, because we just keep taking out I to the fourths, you could have some ridiculous number here like I to the 583rd, and it would end up just being one of these simple answers like -I or -1 or something like that. All right, here's another example. We need to figure out the square root of -36. Well, if you know your square numbers, you might be able to say, well, the square root of 36, like positive 36, that's 6, because 6 times 6 is 36. But we do have a negative sign here, and normally you can't take the square root of a negative number, but we have imaginary numbers. So to do this, you need to remember that if you multiply two numbers in square roots, then you just multiply them together and keep them in a square root. So we can actually split this up into the square root of -1 times the square root of 36, because if you multiply these two numbers, you just multiply the inside, so it would be -36. And remember that the square root of -1 is I, and the square root of 36, well, that's 6. So we just have I times 6, and we'll treat I like a variable in this case, and when you have variables, it's just neater to put the number before the variable, so we'll put 6i. So there we go, our final answer is 6i, that is the square root of -36. And we can do the same thing even for square roots that aren't nice perfect squares. So what I'd like you to do is go ahead and pause the video, see if you can figure out how to solve the square root of -20, and then unpause and see how you did. Alright, so we're going to split this up just the same way as before. So we're going to do the square root of -1 times the square root of 20. And the square root of -1 is I. So we have I times the square root of 20. But the square root of 20 is not a nice perfect square. But we can actually use the same method to pull out a perfect square from this. So if you know your perfect squares, we have 4, because that's 2 times 2. We have 9, because that's 3 times 3, and so on. So we can actually divide 4 out of this. So if we were to do I times, and then we're going to split this up into 4 and some other number. And if you weren't sure what other number we would use, then you could put it in your calculator. 20 divided by 4 is 5. So we can split this up into the square root of 4 times the square root of 5. So we have I times And then the square root of 4 is 2. And then we just have the square root of 5, which we can't simplify. So to keep this neater, we'll put the number before the letter, and then we'll put the square root at the end, just to make everything neater. But you don't necessarily have to do that. So there you go. This is our final answer. The square root of negative 20 is 2i times the square root of 5. All right, here's another example. We need to multiply these two imaginary numbers. And you might not be sure how to do this, but you can actually do it just with the information we've been talking about before. So go ahead and pause the video, try to see if you can do it yourself, and then unpause and see if you got it right. Alright, so you might realize that these are all being multiplied because if you have a letter next to a number, that means multiplication. So these are all being multiplied, and in this case, it doesn't matter what order we do this in. So we can multiply the numbers together, and we can multiply the i's together. So negative 4 times 3 is negative 12. And then we have I times I, which is I squared. And if you remember from before, I squared is the square root of negative 1 times the square root of negative 1, which is negative 1. So I squared is negative 1. So we're going to put negative 1. And now we have negative 12 times negative 1. Well, 12 times 1 is 12, because anything times 1 is itself. And we have two negatives, and two negatives make a positive. So in this case, our final answer is 12. Negative 4i times 3i is 12. All right, here's one more example. We need to multiply two square roots with negative numbers in them. So I'll give you a chance to go ahead and pause the video and try to solve it yourself, and then unpause and see how you did. All right, so this is a weird math thing. You might think to yourself, because we've been talking about how if you have two square roots, you can multiply them and get what's inside. So you might think that, okay, well, we'll do negative 5 times negative 10. 5 times 10 is 50, and two negatives make a positive. So we'll have the square root of 50, and we're done. But actually, you can't do that. When you have two square roots with negatives in both of them, you actually can't multiply them together, which may seem weird, but I'll show you why that is. So we're going to go ahead and turn these into i's. So remember that this can be split up into the square root of negative 1 times the square root of 5. And the square root of negative 1 is I. So we have I times the square root of 5, which is just I times the square root of 5. And then we can do the same thing for this. It's going to be the same thing. We're going to have I times the square root of 10. So now we can multiply the numbers together and the i's together. So we're going to have the square root of 5 times the square root of 10. That's the square root of 50. And we have I times I, which is I squared. But remember from before that I squared is actually negative 1. So we're going to have the square root of 50, which is what we thought we had before, but times negative 1. So this is actually going to be negative the square root of 50. So yeah, imaginary numbers have weird rules like that, but just remember to try to split it up into i's and see if it gives you the right answer. So in this case, our final answer is negative the square root of 50. In this video, I'm going to show you how to add, subtract, multiply, and divide complex numbers in just one video. And don't worry, this doesn't actually have to be that complex. Ha ha ha. Get it? Because yeah, it's because it's a complex number, and it's like complex. All right, so here's our first example. I'm first going to show you how to add complex numbers. But what even is a complex number? Well, a complex number is this right here. This is a complex number, and so is this one here. It basically just means a number that is part real, like the number 4. The number 4 is real, and then part imaginary. So 3i. 3i is a fake number. It's an imaginary number. If you're not sure what imaginary numbers are, then what I would recommend is go watch my video on imaginary numbers, which you can watch on the card on the screen right now, and then come back here. So basically, we need to add these two complex numbers. And the way that we're going to do that is we're going to add the real parts together, and we're going to add the imaginary parts together. So in this case, we have 4 plus 5, which is 9, and then 3i plus 2i, which might be confusing, but it's just the same thing. 3 plus 2 is 5, and then the I stays. So there you go. You've just added complex numbers. It's 9 plus 5i is your final answer. All right, now how do you subtract complex numbers? Well, in this case, we're going to do the same thing, right? So we have 2 minus 6. 2 minus 6 is negative 4. And then we have 3i, and then this can be confusing, but remember, this minus sign is in addition to this minus sign. So we have 3i minus minus I. Two negatives make a positive, so that's going to be 3i plus I, which is 4i. So there you go. Our final answer is negative 4 plus 4i. All right, so we just added and subtracted complex numbers, and those were pretty quick, but these are going to take a little bit longer, but they're actually not that bad. So first, we're going to multiply complex numbers. We have 3 plus 2i times 4 minus 5i. So you might think that we're just going to do the same thing we did before. We're going to multiply the real parts and multiply the imaginary parts. But we actually can't do that. And the reason for that is with real numbers, we have this thing called FOIL. FOIL basically says that when we're multiplying two binomials, which is just a fancy way of saying a number plus a number or a number minus a number, when you're multiplying two of them, you have to follow the steps of FOIL. So you multiply the two first numbers, and then the outer numbers, that's what O stands for, outer, and then the inner numbers, and then the two last numbers. So I know it seems like a lot, but we'll just take it one step at a time. So we're going to follow the steps of FOIL. We'll start with F, which is first. So we have 3 times 4. 3 times 4 is 12. Now we have to do outer. So that's going to be 3 times negative 5i. Don't forget the signs. The signs are important. So we have 3 times negative 5i. Well, 3 times 5 is 15. And then we have an I, so the I stays. And we do have a minus sign here. So one minus sign, that stays. Now we're going to do inner. That's the two inner numbers. So that's 2i times 4. And in this case, we don't have any negative numbers. So this is going to be plus. And then 2 times 4 is 8. And then we have an I, so the I stays. And finally, we have to do last. 2i times negative 5i. Well, 2 times 5 is 10. And then we have I times I, which is I squared. And then we have a negative sign, so the negative sign stays. So we have this kind of confusing mess, but we can go ahead and kind of clean this up. First of all, we can do combining like terms, which is just a fancy way of saying we have two terms with I in it, so we can combine them. So we have minus 15i plus 8i. We lost $15, and then we gain 8 back, but we're still down 7. So it's going to be negative 7i. So you might think that, well, we're done here. We don't have any more numbers that we can combine because they all have a different amount of i's in front of them. But I squared can actually be broken down into something simpler. If you watch the imaginary numbers video, you might know that I squared can be broken down into the square root of negative 1 times the square root of negative 1. Because remember, that's what I means. I just means the square root of negative 1. It doesn't mean anything else. And when you multiply something in a square root by itself, that basically cancels out the square root, because that's saying the square root of something squared. So this just becomes negative 1. So I squared is actually just negative 1. So we'll go ahead and replace it with a negative 1. So let's go ahead and simplify this down. We're going to have just the same thing as before, 12 minus 7i. And then we have negative 10 times negative 1. Well, 10 times 1 is still 10, but we have two negative signs, so that becomes a positive. And now we can combine 12 and 10. So we have 12 plus 10. 12 plus 10 is 22. And there we go. We now have a number that looks like our complex numbers from before. So that is our final answer, 22 minus 7i. All right, so the last thing that you need to know how to do with complex numbers is how to divide them. And this one might be the most confusing, but just like the other ones, you'll be doing the same thing every time. So just keep practicing it and make sure that you've got the steps down. Our ultimate goal of dividing these two complex numbers is to get the I, the imaginary part, out of the denominator. We want the denominator, the bottom of the fraction, to only be real numbers. All of the fake imaginary stuff needs to be at the top. And the way that we can do that is with complex conjugates. What? Well, the complex conjugate of an imaginary number is always just the same thing, but with the sign flipped. So the complex conjugate of 3 plus 5i is 3 minus 5i. And the thing about complex conjugates is if you multiply a number by its complex conjugate, I like saying that. That's a nice word. Complex conjugate. If you multiply them together, then it actually eliminates all of the fake numbers in it. It eliminates all the imaginary stuff. It leaves you with real numbers only. But we can't just multiply some random number by some other random number, right? Because then it's not going to be the same number anymore. We can't just do random stuff like that. So what we need to do is we need to multiply both the top and the bottom of the fraction by the complex conjugate. So we are going to multiply both the top and the bottom by 3 minus 5i. And we can do this because 3 minus 5i over 3 minus 5i is just 1. Anything over itself is 1. And if you multiply something by 1, it doesn't do anything. So in this case, we're going to have negative 2i times 3 minus 5i over 3 plus 5i times 3 minus 5i. And now we've turned division into a bunch of multiplication. So let's go ahead and do the multiplication. First of all, we have the distributive property here, right? We have something in front of parentheses, so we have to multiply it out to both parts. So we have negative 2i times 3. Well, 2 times 3 is 6. And then we have a minus sign, so the minus sign stays. And we have an I, so the I stays. And now we have negative 2i times negative 5i. Lots of things going on, but let's just take it one step at a time. 2 times 5 is 10. We have 2 negatives, and 2 negatives make a positive, so we're going to have plus. And we have 2 i's, so that's going to be I times I, or I squared. And now let's multiply out the complex conjugates right here, which we will do the same way as before when we were multiplying. We're going to use FOIL. So we're going to start with f, which is first. 3 times 3 is 9. Then we're going to do outer, so 3 times negative 5i. 3 times 5 is 15. And then we have a minus sign, so the minus sign stays. And we have an I, so the I stays. Now we're going to do inner. 5i times 3. 5 times 3 is 15. And then we have an I, so the I stays. And no negative signs this time, so it's going to be plus. And now we have last. So we're going to have 5i times negative 5i. 5 times 5 is 25. We have one minus sign, so the minus sign stays. And then we have I times I, which is I squared. So now you may notice that we have minus 15i plus 15i. Those just do the opposites of each other, so those cancel out. And actually, when you're doing complex conjugates, these actually cancel out every time. This is how it's always going to work. So let's go ahead and rewrite our fraction now with the simplified part. And I'm going to go ahead and move this back up to the top. So now what do we do here? I thought the whole point of this was to get the imaginary numbers out. Well, remember, I squared can actually turn into a real number. And if you remember from before, I squared is equal to negative 1. So let's go ahead and turn all these I squareds into negative 1s. So we have negative 6i plus, and then we have 10 times negative 1. And then that's over 9 minus 25 times, and then we have I squared, that's negative 1. So now let's go ahead and simplify these. So we have negative 6i, and then we have 10 times negative 1. And anything times 1 is itself, so it's still 10. But we have a negative sign, so it's going to be minus 10. And now down here, we have 9 minus, and then 25 times negative 1. We have two negative signs. Two negatives make a positive. So we're going to have 9 plus 25. And 9 plus 25 is 34. So let's go ahead and write that. All right, so the last thing we need to do, because we've gotten the imaginary stuff out of the bottom, is now we need to split this up into two fractions. So we have a real fraction and an imaginary fraction. So this is going to become negative 6i over 34 minus, because this minus sign has to stay, minus 10 over 34. And both of these fractions can be simplified. So let's go ahead and look at negative 6i over 34 first. We can divide both the top and the bottom by 2. And the way that I knew that we could do that is because these are both even numbers. So if we divide both by 2, then we'll have negative 3i instead of 6. Over 34 divided by 2, which if you put that in your calculator, it would give you 17. So there we go. We have negative 3i over 17. And now here we have negative 10 over 34, and we can actually divide both the top and the bottom by 2 on this as well. So we would have 10 divided by 2, which is 5, and 34 divided by 2, which is 17. So there you go. We have a complex number here, right? We have a part that has I and a part that doesn't. So that is our final answer, unless you want to make it a little bit neater, because complex numbers, you usually have the real part first and then the imaginary part. So we're going to have negative 5 over 17, which is the real part, minus, and then we have 3i over 17, or another way to write that would be 3 over 17 times I. So there you go. This is our final answer. This is the answer to negative 2i divided by 3 plus 5i. There are so many different ways to learn how to solve quadratic equations, but here's the first one, which is factoring. All right, here's our first example. We need to solve for x in this equation. In other words, we need to figure out what numbers we can put in for x to make the equation true. Now, if you've already solved quadratic equations using graphing, you probably already know that that takes a really long time and seems completely unnecessary. Factoring is basically a way of doing the exact same thing. We're figuring out what numbers we can put for x to make it true, but it's a lot faster than graphing. Well, you might be familiar with something called FOIL. And FOIL is basically when you have two things in parentheses here. These are technically called binomials because we have two things in them. We have an x and we have a 1. FOIL says that to multiply these two things, we need to follow the steps of FOIL. So F in FOIL means first. So we would multiply the things that are first in these parentheses. And then O means outer. So we multiply the ones on the outside. And then inner, and then last. And if you were to do FOIL on this, you would end up with something like this, x squared plus 3x plus 2. So basically, factoring is the opposite of doing FOIL. We have this equation here that's already fine, and we want to turn it into two binomials in parentheses. So basically what we want to do is get the equation in this format. But we need to figure out what numbers to put inside here. And these two numbers are going to be two numbers where if we add them together, we get this number. But if we multiply them together, we get this number. And you may notice how I'm kind of extending the underline to this plus sign here. And that's because if this was a minus sign, you would have to include the minus sign in that number. So it would be -5. But in this case, we have two positive numbers. So we always try to add to the number that's in front of the x, not in front of the x squared, just in front of the x. And then the number that doesn't have any letter next to it is the number we're trying to multiply to. So how do we figure out these two numbers? Well, I mean, you kind of just have to guess and check. But I would focus on the multiplying number first. So what are two numbers that multiply together to get 6? Well, we have 1 and 6, 1 times 6. But 1 plus 6 is 7. So we don't want that, right? We need it to be 5. Well, what about 2 times 3? 2 times 3 is 6, and if you add up 2 plus 3, you get 5. And that's our magic number, right? That's what we want. So we found our two numbers. Our two numbers are 2 and 3. So what we're going to do is we're going to put those numbers into these parentheses. So we're going to have plus 2 and plus 3. But what do we do from here? How do we solve for x now? We have like two different x's here, and it's pretty confusing. Well, with this, you can do this pretty neat thing where you split up the equation. Whenever you multiply anything by 0, you get 0, right? 5 times 0 is 0, 6 times 0 is 0. So what this means is if x plus 2 here is 0, then the whole thing is 0. And the same thing over here. If x plus 3 is 0, the whole thing is 0. So we can actually split this up into two equations. We can have x plus 2 equals 0. And we have x plus 3 equals 0. This is something that you can only do if it equals 0. So if this was like equals 6 or something, then you can't do this. So our final step here is to just solve for x in each of these equations. So we have x plus 2 equals 0. We need to get x by itself. So we're going to do the opposite of plus 2, which is minus 2. These cancel out, and on this side we just have x. And on the other side, we have 0 minus 2. Well, the 0 isn't doing anything, so it's just minus 2. So we found one of our answers. One of our answers is minus 2. And we can do the same thing over here on this equation. So we have x plus 3. We get x by itself by doing minus 3. These cancel out like last time, and we just have x equals, and then 0 minus 3, which is -3. So there you go. We found our two answers, and you can put your answers in these little fancy bracket-looking thingies if you want. This is kind of like the fancy way of doing it. But yeah, our answers are -2 and -3. All right, here's another example. We need to solve for x in this case, just like before. We need to figure out what we put in for x to make this true. And we'll use factoring for it, but you may notice that there's one thing that's different about this equation. Before, we were only paying attention to this number and this number, but we have another number right here. So here I have the last equation that we just did, and before we didn't have a number in front of x. Now, it's important to note that this doesn't mean that there was no number. If there is no number shown, then that just means it's 1. But in this case, we have a number that's not 1 in front. So to do this, we're going to have to do it a slightly different way. It's going to be a little bit harder, but I'm going to show you a way that most people don't teach, and it's called the x method. So here's our x here, and what we're going to do is we are going to multiply this number here, the one in front, with the number that is normally our multiplying number. And remember that we have a minus sign here, so we need to include the minus sign. So we have 3 times 8, which is 24, but we do have a minus sign, so the minus sign carries over. And then we're going to take this number here in the middle, minus 10, remember the minus sign stays, and we're going to put it in the bottom of our x. So this number in the top of our x is our new multiplying number, and the one at the bottom is our adding number. So we need to come up with two numbers that add up to -10, but multiply to get -24. And I know because we have negatives, this is going to get a little confusing, but we're going to do it the same way. So let's figure out numbers that multiply to, well, let's ignore the minus sign for now. Let's go with 24. So we have 1 times 24. 1 times 24 is 24. But remember, this is minus 24. And to get a negative number when multiplying, one of these numbers has to be negative. And because we know that we're adding to a negative number, That means that the bigger number is always going to be the one that's negative, because if the smaller number was negative, then they would add up to a positive number, and we know that that's not going to be the case. So if we have 1 times negative 24, if you add these together, you get negative 23. And that's not even close to negative 10. So we're going to try again. To get 24, you could also do 2 times 12. And remember that it's the bigger number that's going to be a minus because we're adding to a negative number. And if you were to add these two numbers together, you would get 2 minus 12. So 12 less than 2 is minus 10, which is the number we're trying to get. So we found our two numbers, 2 and minus 12. Now, normally we would just take these numbers and put them straight into our factored equation, but we actually can't do that in this case. What we need to do for our final step is bring back this 3 here. And what we need to do is divide either one of these numbers by 3. Now, we can divide either one of these by 3, but if we divide the left one by 3, then we're going to have 2 over 3, and we're going to be dealing with fractions. No one wants to do fractions. So we're going to divide the negative 12 by 3, because 12 divided by 3 is 4. And remember that if you have one minus sign, we have to carry the minus sign over. So the two numbers that we're going to be putting in our parentheses are 2 and minus 4. But we're going to do it a slightly different way, and I'll show you. So we're going to have 2 and minus 4. But we're not just going to put x plus 2 and x minus 4, because this is a 3x squared in the front, not just x squared. So what we're going to do is, instead of x, we're going to put 3x, but for the opposite parentheses that we divided by 3. I know that sounds confusing, but let me show you. We divided this by 3 to get minus 4. So we need to put the 3x on the other one, which is the 2. So we're going to put 3x plus 2. And then this one is just going to stay as x. And you might say, well, why is that? Well, if you think of this as FOIL, we have first, outer. Well, look at outer. 3x is being multiplied by minus 4. And 3 times minus 4 is minus 12. So it's still being applied in the outer stage of FOIL. And if you want to check your work and you're not sure if you did it right, just go ahead and do FOIL on this and see if you get back to 3x squared minus 10x minus 8 equals 0. So now we can split this up into two different equations like normal because it equals 0. So we'll have 3x plus 2 equals 0, and we'll have x minus 4 equals 0. So on this side, we need to get x by itself. So we're going to subtract 2 from both sides. These cancel out, and we just have 3x equals, and then 0 minus 2 is minus 2. But now we have another step here because we have 3x and not just x. And this is multiplication because there's no sign. So we have to do the opposite of multiplication, which is division. We will divide both sides by 3. These cancel out, and on this side we just have x. And on the other side, well, I mean, you can't really divide this, so it's just going to stay minus 2 over 3. So this is one of our answers. X equals negative 2 over 3. And now we just have x minus 4 equals 0, which is much easier because all we have was a minus 4. So we have to do the opposite of minus, which is plus. These cancel out, and you just have x equals 0 plus 4, which is 4. So there we go. We have our two answers, and if you want to write it the fancy way, we would have x equals, and then these fancy little bracket things, negative 2/3 and 4. So there you go. This is our final answer. It's time to learn how to solve quadratic equations by completing the square. Well, that was really easy. Well, thanks for watching. If you have any... Okay, yeah, that's not what completing the square is. Let me explain. So for this equation, our goal is to figure out what x is equal to. We need to figure out what numbers we can put in for x to make this equation true. So what is this square that we're supposed to be completing? Well, this equation here, this part right here, is considered a perfect square. And the reason that we call it a perfect square is because of factoring. Now, if you don't already know how to factor equations, then I have a video on it that you can watch on the card on the screen right now, but I'll also quickly review it here. So basically, we need to figure out two numbers that add up to 6 and multiply to get 9. Well, we have 1 times 9. But if you add up 1 and 9, you get 10, which is not 6. But what about 3 times 3? 3 times 3 is 9, and if we add 3 and 3, we get 6, which applies to this. So if we were to factor this equation, we would have x plus 3 times x plus 3. But listing x plus 3 twice is redundant because they're the same thing. So we can actually list this as x plus 3 squared. And this squared here is why this is called a perfect square. A perfect square is an equation or a part of an equation where if you factor it, you get the same thing twice. So how would you solve it if you have this square here? Well, we can get rid of this squared by doing the opposite of squaring, which is square rooting. So we will square root both sides. So the square root and the squared cancel, and we just have x plus 3. And on the other side, we have the square root of 16. But actually, when you square root both sides, what you're really doing is the plus or minus square root. And the reason for that is if you have 4 times 4, because 4 is the square root of 16, 4 times 4 is 16. But negative 4 times negative 4 is also positive 16, because two negatives make a positive. So we're going to put plus or minus 4. And this makes sense because quadratic equations usually have two answers. They don't always have two answers, but most of the time they do. So this is actually two different answers, and we'll split this up into two equations. We'll have x plus 3 equals positive 4, and we'll have x plus 3 equals negative 4. So the last thing we need to do is solve for x on each of these equations. So we have plus 3 here on the x, so we need to do the opposite of plus, which is minus. We will subtract 3 from both sides. These cancel out, and on this side we just have x, and on the other side we have 4 minus 3, which is 1. So x is equal to 1. That's one of our answers. And on the other equation, we'll get another answer. So we'll subtract 3 from both sides. These cancel out, and we just have x. But on the other side, now we have minus 4 minus 3. Lost $4, lost another $3, you've lost $7. So if you want to write your answer the fancy way, we'll put it in these fancy little brackets, and we'll put our two answers here. So our final answer is x is 1 and negative 7. All right, so you may be noticing a slight problem with completing the square, and that is you need to have a perfect square in the first place. Like, what are the chances that you're just going to magically have a perfect square in a problem to be able to do this with? Well, it's called completing the square for a reason. And that's because we don't have a perfect square, but we need to complete it and turn it into a perfect square. So I want you to think about how you can do that. And if you want to give yourself a little bit of time, you can even pause the video right now and think about how you do this. So I want you to think about what this equation looks like. Well, first of all, we don't actually have to have this equal 0. And it will probably actually make our lives easier for completing the square if we don't have this minus 11 here that's blocking everything. So let's go ahead and move this minus 11 to the other side. So we will do the opposite of subtraction, which is addition. So we will add 11 to both sides. And if we do that, we'll have x squared plus 10x equals 11. So now all we need to do is figure out what number goes here that will give us a perfect square. And to do that, we need to take this number, divide it by 2, and then square it. Wait, what? What does that have to do with anything? Well, let's take a look at this equation that we just did in the last problem. If you take the middle number and then divide it by 2, 6 divided by 2 is 3, and then square it, 3 times 3, because 3 squared, is 9, which is this number. And this is actually going to be true for every single perfect square. So let's go ahead and do that with this middle number, which is 10. Divided by 2 is 5. And then if we square it, we get 5 times 5, which is 25. So this number right here needs to be 25. But you can't just add a plus 25 here and then just expect the equation to still work, right? You can't just add a random number. So we need to do it the algebra way, which is doing something to both sides of the equation. So we need to add 25 here, but because we added 25 to this side, we have to do it to the other side. So we have our new perfect square here that we just completed, but on this side we have 11 plus 25, which is 36. And now we can turn this into a perfect square. And we know that it's a perfect square, and we know the two numbers are going to be the same. So let's take 5 times 5, which is 25, and 5 plus 5 is 10. So because we knew that we're going to be dealing with two of the same number, you don't need to go through all the factors of this number here. Like, well, I mean, in this case, the only other one is 1 times 25. But if this was a number with a ton of factors, you don't have to go through all of them. We already know it's going to be 5 times 5. So we're going to have x plus 5 times x plus 5, or just x plus 5 squared, equals 36. And now we just need to solve for x. So we can get rid of this squared here by doing the opposite of squaring, which is square rooting. And remember, this is technically plus or minus square rooting, so we'll deal with that later. The square root and the squared cancel, and we just have x plus 5 equals, and then the square root of 36 is 6. So we're going to have plus or minus 6. And like before, we can split this into two equations because we have a plus and a minus. So this will be x plus 5 equals positive 6, and x plus 5 equals negative 6. So now we just need to solve for x in each one of these. So x plus 5, we do the opposite of plus, which is minus. So these cancel out, and we just have x equals 6 minus 5 is 1. So x equals 1 is one of our answers. On this side, we're going to do the same thing. We have plus 5 here. So to get x by itself, we need to subtract 5 from both sides. These cancel out, and we just have x equals negative 6 minus 5. We lost 6 and then lost another 5. So we lost 11. So there we go. These are our two answers. And if we want to write it the fancy way, then we're going to have x equals, fancy brackets, 1 comma negative 11. So there you go. This is our final answer, 1 and negative 11. In this video, I'm going to show you how to use the quadratic formula, how you can memorize it, and how to use it for problems that even have imaginary numbers. So let's go ahead and get started. All right, here's our first example. We need to solve for x using the quadratic formula. That means we need to figure out what numbers go into x to make the equation true. And unlike the other ways that you might have learned how to solve these, like factoring or completing the square or graphing, the quadratic formula can be used in every case. So those other ways, you could only do it in certain cases when it worked, or it was just really tedious to do it. But in this case, the quadratic formula works every time. So what is the quadratic formula? Well, it's this nice small formula. It's x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Yeah, see? Nice and small. Okay, that's not nice and small. So how are you supposed to memorize this? Well, my advice is always to keep using formulas, and the more that you use them, the more that you'll memorize them. But this is still kind of long, so I have this really great idea for you. All you have to do is go on YouTube and search quadratic formula song. And there you go. Just listen to any one of these, and I promise you it will be seared into your brain for the rest of your life. And you'll be like 50 years old, and the quadratic formula song will appear in your brain, and you'll never get rid of it. So enjoy. And no, I will not be singing the quadratic formula song for you in this video because copyright troubles. Yeah, I don't want to get copyright claimed. That's the real reason I'm not singing the. So anyways, how do we even use this equation? I mean, you have it memorized, but what do these letters even mean? Well, in other kinds of problems, we've actually labeled these as A, B, and C, and we're going to do it the exact same way. So whatever number is in front of the x squared is going to be A. The number that's in front of just the regular x is going to be B, and then the number that's by itself is C. So in this case, what are A, B, and C? Well, A is the number in front of x squared. There is no number in front of x squared, but if there's no number in front, that means it's 1. So in this case, A is equal to 1. And that's the same case for B. There's no number in front of x, so it's just 1. So B is equal to 1. But C, we do have a number. So C is 2, right? No, this might be like the most common mistake I see in quadratic formula. It's not 2, it's negative 2. Because the minus signs always stay with the number. So C is negative 2. All right, so all we need to do is plug in these numbers into these letters and see what we get for x. So we're going to have x equals, and now whenever we see a letter, we're going to replace it with its number. So negative, we already have a letter. We have the letter B, but we know that B is 1. So instead of B, we're going to put 1. Plus or minus, and then b squared, we know that b is 1, right? So it's going to be 1 squared minus 4, a is 1, and c is negative 2. And I'm putting these in parentheses because remember, these are being multiplied together because there's no sign in between. And now it's all over 2 times a. A is 1. So now let's just go ahead and simplify this. And we're going to simplify what's in the square root first, because that'll make things easier. So we're going to have negative 1 plus or minus the square root of 1 squared is just 1 minus, and then we have 4 times 1 times 2. Well, anything times 1 is itself, so this is literally doing nothing. And 4 times 2 is 8. But in this case, you'll see we have minus this, but we have another minus sign here. 2 negatives make a positive. So this is going to be 1 plus 8. And that's going to be over 2 times 1, which is 2. And 1 plus 8 is 9. So we're going to write this as negative 1 plus or minus the square root of 9 over 2. And now what's the square root of 9? Well, the square root of 9 is 3, because 3 times 3 is 9. So we're going to have negative 1 plus or minus 3 over 2. So now we just need to simplify this, but plus or minus, what do you do with this? Well, this is actually going to be plus and minus. So we're going to have -1 plus 3 and -1 minus 3. So let's go ahead and split this up into two equations. So we're going to have -1 plus 3 over 2. We're going to have -1 minus 3 over 2. So in this case, -1 plus 3, that's the same thing as saying 3 minus 1, which is 2 over 2. And 2 divided by 2 is 1. So 1 is one of our answers. Now here we have -1 minus 3. We lost $1 and then lost another $3. So that's -4 over 2. And now -4 over 2, 4 divided by 2 is 2, and we have 1 minus sign. So the minus sign carries over. So that's our second answer, -2. These are our two answers, and if you want to write it the fancy way, we'll do x equals these fancy little bracket things, 1 comma -2. So there you go. This is our final answer. X is equal to 1 and -2. And if you wanted to check your work, you can plug in 1 and -2 back into the equation and see if you get 0. All right, here's another example, and as promised, this one is going to have imaginary numbers, but you'll still do it the same way as before. So if you're feeling up to it, go ahead and pause the video, try to solve this one for yourself, and then unpause and see how you did. All right, so we're going to do this exactly the same way. We need to figure out a, b, and c. So a is going to be the one in front of x squared. So that's going to be 1 because we don't have a number in front, so you assume it's 1. So a is 1. B is the one right here, and b is +6. And c is the one right here that's by itself, without an x in front of it. So that will be 10. All right, so let's go ahead and plug in these numbers into our formula and see what happens. So we have x equals -b. b is 6, so that's going to be -6. Plus or minus the square root of b squared. b is 6, so we're going to have 6 squared. Minus 4 times a is 1, and c is 10. And then that's over 2a, which is 2 times 1. All right, so let's go ahead and simplify this down. We have -6 plus or minus the square root of 6 squared is 36, because 6 times 6 is 36. And then this 1 is doing nothing because it's 4 times 1 times 10. Anything times 1 is itself. So we will get rid of this 1. 4 times 10 is 40. And then that's over 2 times 1, which is 2. Now let's go ahead and simplify this more. We're going to have -6 plus or minus, and 36 minus 40 is -4 over 2. And I'm going to go ahead and move this back up here so that we have more room. So you may be noticing a problem here, and that's because we have a negative number inside our square root, which normally means, well, you can't do that. You can't take the square root of a negative number. But you may have learned about imaginary numbers. If you're not already familiar with imaginary numbers, I do have a video on it that you can watch on the card on the screen right now. But remember that we denote imaginary numbers with the letter I, which is the square root of -1. So what we can do is we can split this up into the square root of +4 times the square root of -1, because 4 times -1 is -4. And now we have the square root of 4, which is 2, and the square root of -1, which is I, and then that's over 2. So now our last thing that we need to do is divide this top part by 2. We can get rid of the denominator, and we're going to have to divide both parts by 2. Let's just go ahead and split this up into two fractions just to show you. We're going to have -6 over 2 plus or minus 2i over 2. So -6 over 2, 6 divided by 2 is 3, and we have 1 minus sign, so the minus sign carries over. So we have -3 plus or minus, and then 2i over 2. Well, 2 divided by 2 is 1, and then the I stays. So we have 1i, or in this case, the 1 isn't doing anything, so we just have I. So there you go. We have -3 plus or minus I. And you actually don't really have to split this up. You could just say that this is the answer. The answer is x equals -3 plus or minus I. But basically what you're saying by this is that we have two answers. We have -3 plus I and -3 minus I. So if you wanted, you could write this as your two answers as well in these fancy bracket thingies. So yeah, our final answer is x equals -3 plus or minus I. Here's how to solve quadratic inequalities with just algebra, no graphing required. All right, so here's the example problem that we'll be doing in this video. We need to solve x squared plus 2x minus 15 is greater than or equal to 0. So this is like one of those solve for x problems where we have to figure out what numbers can go into x to make the equation true. And normally with quadratic equations, we'll have like two answers, like two numbers could go into x. But in this case, any numbers that will make it greater than or equal to 0 are true. So we're going to have a ton of answers. Our final answer is going to be something like, x is greater than 4 or something like that. But it might actually be a little more complicated, and I'll show you why in a second. So the way that we solve this is actually pretty similar to a normal inequality that's not even a quadratic equation. So for example, if we had something like x plus 3 is less than 5, if we wanted to solve this, we'd first have to just treat this like an equal sign, and we'd solve x plus 3 is equal to 5. So here we'll do the same thing. We're going to solve what's called the related equation. We're going to solve x squared plus 2x minus 15 is equal to 0. And that will tell us our boundaries, which will make sense in a second. So how can we solve this? The three good ways to solve a quadratic equation are factoring, completing the square, and the quadratic formula. And you're free to use these however you want. You can try whichever ones you want first. For me personally, I always try to use factoring first because it's the easiest one. And if factoring doesn't work, then I just do the quadratic formula, which works every time. I don't really use completing the square that much, but this is all just a matter of preference and what you like. So if you're not sure how to factor, I do have a video on it that you can watch on the card on the screen right now, but I'm also going to show you how to do it here. And basically the goal of factoring is to figure out two numbers that add up to this middle number, the one that's next to x, and multiply together to get this number, the number that doesn't have a letter next to it. And that's going to give us our two numbers that go in these parentheses. We want it to be in this format. So let's go ahead and go through the factors of 15. It is negative 15, but we are just going to treat it like positive 15 for now, and we'll worry about the negative signs later. So 15 is 1 times 15. And now which one do we make negative? Because this is a negative number here, and a positive times a negative makes a negative. But we are adding up to a positive number, which means the bigger number is going to be the positive one. So we're going to be putting negative signs on the smaller numbers. So if we were to add these two numbers, we would get 15 minus 1, which is 14. That is not even close to 2. So we're going to disregard this one. The only other factors that make 15 are 3 times 5. And we have to make the smaller number negative because this is adding up to a positive number. And negative 3 times 5 is negative 15. And they add up to 5 minus 3, which is 2. And yeah, that's the number we're looking for. So we found our two numbers here that we're going to be putting in these blanks. So we have negative 3 and positive 5. So we're just going to continue solving this like normal. And with factoring, the step to recognize here next is we have two things here being multiplied and are making 0. And anything times 0 is 0. So if either of these becomes 0, if this is 0 or if this is 0, the whole thing is 0. So just because this is equal 0, we could split this up into two equations. So we'll have x minus 3 equals 0, and we'll have x plus 5 equals 0. And now we'll solve each equation individually. So x minus 3 equals 0. We have to get rid of this minus 3, so we'll add 3 to both sides. These cancel out, and we just have x equals, and then 0 plus 3 is 3. And now we have x plus 5 equals 0. We have to get rid of this plus 5 by doing the opposite of plus, which is minus. So we will subtract 5 from both sides. These cancel, and we just have x equals, and then 0 minus 5, this 0 doesn't do anything, so it's just minus 5. So we have our two answers to this equation here, the one with the equal sign. So how does that help us to solve this with the greater than or equal to sign? Well, here's what we're going to do. We're going to go ahead and draw a number line, because I think that'll help us visualize this. All right, so here's our number line. We have the numbers from negative 6 to 6. You could put whatever numbers you want, but I want to make sure we can fit these numbers. So these were our answers for the equation with the equal sign, but for the equation with the inequality sign, these numbers are actually just going to be boundaries. So we're going to go ahead and put dots on these two numbers, and you have to ask yourself what kind of dot we're going to put. If you know about how to solve regular inequalities, you might know that if you have this little line underneath, this means or equal to, then you're going to draw a filled in circle because the circle is part of the answer. If it's just this sign, then you would put an open circle like this that's not filled in because it's not part of the answer. But in this case, we do have a line underneath. So we're going to put filled in circles on 3, which is right here, and negative 5, which is right here. So we have boundaries, and now you may notice that we have 3 sections. we have a section right here that goes on infinitely this way, like in this direction. We have a big section here that goes in between these two circles, and we have a big section here that goes on infinitely this way. So what we need to do is we need to test out a number in each of these sections. And if a number works in that section, then the whole section is filled in. But if that number that you put in the section doesn't work, then the whole section doesn't work. So let's go ahead and test out a number in this section first, the one to the left. Anything less than -5 to the left of -5 will work. So let's try out -6 then. So what we're going to do is we're going to plug in -6 into this equation, and if the equation is true, then we're going to fill in this whole section. So we're going to replace x with -6. So x squared is going to become -6 squared plus 2 times -6, because that's x, minus 15 is greater than or equal to 0. So let's go ahead and simplify this down. -6 squared, that's -6 times -6. 6 times 6 is 36, and that's two negatives, and two negatives make a positive. So it's positive 36. Here we have 2 times 6, which is 12, and we have one negative sign, so the negative sign carries over. And then minus 15 is greater than or equal to 0. 36 minus 12 is 24, and I'm running out of room here, so we're going to move it over here. 24 minus 15 is 9. Our statement here is 9 is greater than or equal to 0. Is that true? Yeah, 9 is bigger than 0. So in this case, this section here is going to be true. So what we're going to do is we're going to fill in this whole section. And remember that this section goes on infinitely this way, so we're going to draw a little arrow at the end to show that it goes on infinitely. All right, we're good for that section. Let's look at this section now. We can pick out any number in this section. So I think the easiest one to pick will be 0, because 0 is in the section. So we're going to replace x with 0 whenever we see it. So x squared is going to become 0 squared plus 2 times 0 minus 15 is greater than or equal to 0. And now 0 squared, well, that's 0 times 0, which is 0, so that cancels out. 2 times 0, anything times 0 is 0, so that also cancels out. So all we're left with now is -15 is greater than or equal to 0. Is that true? Nope, this is not true. -15 is not bigger than 0, and it's not equal to 0. So in this case, this whole section here is not true. So we're not going to shade it in. We're going to leave it blank. So now we're just left with this final section here, 3 and everything bigger than 3. So we can pick any number in this section. The easiest thing to do would pick the smallest number, so let's go ahead and pick 4. I guess you technically could pick 3 as well, but when you have like open circles, you're not allowed to pick the same number. So just to keep things the least confusing as possible, I'm just going to pick 4. So whenever we see x, we're going to replace it with 4. So 4 squared plus 2 times 4 minus 15 is greater than or equal to 0. So 4 squared, that's 4 times 4, which is 16, plus, and then 2 times 4 is 8, minus 15 is greater than or equal to 0. 16 plus 8 is 24, minus 15 is greater than or equal to 0. And running out of room again, so we'll move it over here. 24 minus 15 is 9. So this is actually the same thing that we had before. Is 9 greater than 0 or equal to 0? Yeah, it's greater than 0, right? 9 is bigger than 0. So this whole section is going to be shaded in. So we're going to go ahead and color in this whole section. And we're going to put a little arrow at the end to show that it goes infinitely. So there you go. We have our answer, but it's a number line. Shouldn't the answer be in numbers? So there's actually 2 ways to write your answer. Whichever one you use is just going to be based on which one you like more, or which one your teacher likes more. So the first way is going to be using these little fancy bracket things that are technically called braces. Whenever you're writing something with multiple answers, like let's say 1, 2, and 3, you would put them in these fancy brackets, and these are called a set. So this shows that there is a set of numbers. So what you can do is you can say x such that, and this line here means such that. And basically what this means is you're saying that all the answers are x when x is within the boundaries that you set here. So all we have to do is basically just write what we see here. So if it is an answer, if it is less than or equal to 5, remember that -5 is part of the answer. So we have to include the or equal to. So if x is less than or equal to -5, it is an answer. And then we're going to go ahead and put or, because it doesn't have to be both of these, it just has to be one of these. X can also be, in this case, it can be 3 or bigger. So what we have to do is we have to put greater than or equal to 3. Because remember, the line underneath means or equal to, because 3 is part of our answer. So there you go. This is one way to write our answer. X such that x is less than or equal to -5, or x is greater than or equal to 3. Yeah, that was a mouthful, but here's the other way you can write your answer. The other way you can write your answer is using something called interval notation. What is that? Well, let's say you wanted to write all the numbers from 1 to 4, but you wanted to say that 1 is included in your answer, but 4 is not included in the answer. So what you would do is you would write 1, 4. But the signs that you encase them in are important. If the number is included in the answer, you're going to use brackets. In this case, 1 is included in the answer, so we're going to put a bracket. But if the number is not included in the answer, then you have to use parentheses. So 4 is not included, so we're going to put a parenthesis to close it. And I know this looks really cursed because we have a bracket and a parenthesis, but this is how you do it. So what we're going to do is we're going to show, remember, this goes on infinitely. So this is going to go all the way to negative infinity. So for our first interval, we're going to put negative infinity all the way to -5. So what signs do we use? Well, negative infinity, even though it goes all the way there, infinity itself is not actually a number. So we have to use a parenthesis. And now is -5 included? Well, yes it is. Remember, that's why we filled in the circle here. So we're going to use a bracket. Now we're going to do another interval. And the symbol that we use to show another interval is like this U shape here. This U shape means union, like we're bringing these two intervals together. So our second interval is going to be from 3 all the way infinitely this way, so positive infinity. 3 is included, so we're going to use a bracket. And infinity, even though it goes all the way there, infinity is not a number, so it's not included, so we're going to put a parenthesis. So there you go. This is the second way to write your answer, and that's this. Possibly one of the scariest words in algebra is simplify, because math is not simple. All right, so here's our first example. We need to simplify this. What is going on? Well, the word simplify literally just means to make something simple. We need to make this as simple as possible, because it doesn't actually need to be this long and confusing. Now, the most important thing to remember to simplify something is to know that usually when you have two of the same letter, then you can combine those in some way. So like, for example, you may be noticing that these parentheses aren't doing anything in this equation because everything's being multiplied and it doesn't matter what order you multiply things in. So let's go ahead and group up all of the things that we can combine. So 3 and 5, those are just normal numbers, so we can combine those. So let's go ahead and put 3 and 5 together. And then we have x to the -2 and x to the 4th. Well, those can be combined because they're both x, so let's put those together. And notice how I'm putting all these in parentheses, because when two things are next to each other in parentheses, that means you just multiply them. And then we have two y's here, so we'll combine those as well. So 3 times 5, well, that's 15. But now it gets a little more complicated. X to the -2 times x to the 4th. How do you even do that? Can you do that? I don't know. Well, you can multiply two of the same letter here with different exponents. And here's how you would do that. For example, let's say I had x to the 2 times x to the 3. Well, x to the 2 just means x times x. And x to the 3rd means x times x times x. So you end up with x times x times x times x times x, which is 5 x's, so x to the 5th. So basically, whenever you're multiplying two of the same letter with different exponents, you have to add the exponents together, because 2 plus 3 is 5. So we have x to the -2 times x to the 4th. Well, -2 plus 4, that's 4 minus 2, which is 2. So we're going to put x to the 2. And now finally here we have y to the 3rd times y to the -6. 3 minus 6. We earned $3 and then lost $6. We're down $3. So y to the -3. So you might think that, oh yeah, that's nice. We can't do anything else. We can't combine anything. But when you're simplifying, there's one more important thing you need to do. And you need to get rid of the negative exponents if it's possible, which can seem kind of confusing if you don't know what a negative exponent is. But let me show you. Let's say we had x to the -2. A negative exponent basically just means the same thing as putting it in the bottom of a fraction. So x to the -2 is actually just 1 over x to the +2. So what we can do is we can just put this y to the -3 in the bottom of a fraction. So we'll have 15x squared and then over y to the third. So there you go, our final answer, and this is our simplified version of this thing at the top. 15x squared over y to the third. All right, enough multiplying and dividing and stuff. Let's do some adding and subtracting. So here we have two polynomials, or a fancy way of saying stuff with multiple things in it. So how do we subtract these? Well, the difference between multiplying and adding and subtracting is you can only add and subtract if the two letters are not only the same, but have the same exponent. If they have different exponents, you can't add and subtract them. So there's multiple ways you could go about this. I think the easiest way to think of this would be to just line these two up. So we'll have 3x squared minus 4x plus 1, and then we'll be doing a minus 5x squared plus x minus 3. But it's important to remember that we're subtracting this whole bottom row. We're not just subtracting 5x squared. So let's go ahead and keep this in parentheses to show that. So here we have 3x squared minus 5x squared. Well, 3 minus 5 is negative 2, and then the x squared stays. And now here's the thing you need to remember. This is not negative 4x plus x. This is negative 4x minus x, because the minus is distributed to all three of these parts. So we're going to have minus 4x minus another x, which is minus 5x. And now here we have 1, so positive 1, minus 3. Well, two negatives make a positive, so this is actually 1 plus 3, which is 4. So there you go, our final simplified version of this top part is negative 2x squared minus 5x plus 4. All right, and now finally, this example. This one might be the scariest type of simplification for a lot of algebra students, but let me explain it to you in a way that makes sense, just step by step. So you might be thinking this actually looks pretty similar to another form that you might have done before called FOIL. And with FOIL, you follow the steps of FOIL. So that's when you have two things in parentheses, each one with two parts to them, and you have to follow the steps. So F is first, so you multiply the first ones together. Then outer, you multiply the outer ones together. And then the inner ones like this for I, and then L is last. But the reason that FOIL exists is essentially what you can do with this, even though there are more parts to this. So what we have to do here is basically just an extended version of the distributive property. We have to multiply this first part here, the x, to every part of the second set of parentheses. So like this, and then we'll get some set of numbers here. Then we're going to do the whole thing over again with the 2. So we're going to multiply the 2 to all three parts. And then that'll give us another set of 3 numbers. And then we'll just combine what we can combine. So let's go ahead and do this with the x first. So we have x times x squared. Remember that we add the exponents together. X times x, which is x squared, times another x is x to the third. Then we have x times negative 4x. Remember the minus sign has to stay. So we have minus 4, and then x times x, which is x squared. And then finally we have x times 5, which is, well, 5x. So now let's do the same thing, but with the 2 right here. So we have 2 times x squared. Well, there's nothing you can do about that except just write 2 times x squared. Then we have 2 times negative 4x. Well, 2 times 4 is 8, and then the x stays. And we also have a minus sign, so the minus sign stays. And then we have 2 times 5. 2 times 5 is 10. And this is slightly off center and it's bothering me, so let's move it. So can we combine anything in this mess of numbers? Well, I am seeing 2 parts with an x squared in it, so we can combine those. Well, first of all, x to the third we can't combine, right? But we have negative 4x squared and then plus 2x squared. Well, negative 4 plus 2, you lost $4 and then gained 2 back, but you're still down $2. So we're going to put minus 2x squared. And now we can actually also combine these two, the 5x and the minus 8x. So we gained $5 and then lost $8, we're down $3. So that's going to be minus 3x. And then this 10 that's all lonely and by itself doesn't have anything to combine with, so that's just going to stay plus 10. So there you go. Our final answer here is x to the third minus 2x squared minus 3x plus 10. There's nothing there that we can combine, because even though these are the same letters, to add and subtract, they have to have the same exponent as well. So this is our simplified version. Here's how to use Pascal's triangle to solve algebra problems. And don't worry, it's super simple. This is the triangle. Wait, am I supposed to memorize that? Well, actually, no, you don't have to memorize anything. Let me explain. Well, Pascal's triangle was, believe it or not, made by a guy named Pascal. And It's in the shape of a triangle. All right, thanks for watching. That's all you need to know. Okay, well, what is the triangle? Well, the triangle starts with a 1 at the top. Then it has two 1s. I know, crazy, right? So every row is going to have another number, and there are always going to be 1s on the outside. So we're going to have 1s going like this. But what numbers go on the inside of the triangle here? Well, for example, let's try to find this number. Well, to figure out this number, what we need to do is take the two numbers above it and add them together. So 1 plus 1 is 2. That's it. That's all you need to do. So for example, this number, what is this number? Well, 1 plus 2 is 3. So 3 goes here. And this one is 2 plus 1, which is also 3. This is 1 plus 3, which is 4. This is 3 plus 3, which is 6. And this is 3 plus 1, which is 4. And there you go. You now have 5 rows of Pascal's triangle. And this goes on infinitely. So you could have more rows and more rows. And it just keeps going. So how does this help us whatsoever with this problem here? What even is this problem? Basically, we need to expand this out so that we don't have parentheses with an exponent. We need to basically simplify it, but it's not going to be simple. It's going to be way more complicated than this. So you may be familiar with something called FOIL, and you would use FOIL if you have x minus 3 squared, for example, which is x minus 3 times x minus 3. And FOIL says that you need to follow the steps of FOIL. So you need to do the first, outer, inner, and last, and so on. But could you imagine having to do all of that multiplication 6 times? We would have to write x minus 3 times x minus 3, and it would get harder and harder every time. So that's why we have Pascal's triangle instead. So for Pascal's triangle, what we need to do is we need to use the same row as the exponent. So we have an exponent here of 6. That means we need to use the 6th row of Pascal's triangle. But actually, this first row here with just a 1 doesn't actually count. This is considered the 0th row. And starting here is the first row, the one with multiple numbers in it. So this would be the second, the third, and the fourth. So we need to go down all the way to the 6th row of Pascal's triangle. So let's go ahead and continue on the triangle. Remember, there's always 1s on the outside. And for the rest, we just use basic addition. So for this number here, we just take 1 plus 4. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. And 4 plus 1 is 5. And then for the 6th row, we have 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. 10 plus 5 is 15, and 5 plus 1 is 6. And you may notice that this is actually symmetrical. It's symmetrical every time, so that helps. So this is going to be the row of Pascal's triangle that we will be using right here. So we're going to erase everything else, and we're just going to hold on to this row because it's going to be important. So how are we going to use this row to help us? Well, when we expand this out, it's going to be in 7 different terms. So there's going to be something plus something plus something plus something, and there's going to be 7 somethings. And each one is going to start with this number. So the first term is going to be 1. And this 1 is going to be 1 something. Well, what goes here? Well, the exponents in each term are always going to add up to 6. In this first term, all 6 of them are going to be x. So we're going to have x to the 6th. And each term in our expansion, we're going to remove one of the x's and replace it with a 3. And this is going to keep going all the way until we get to the end, where the last term is just going to not even include x, and all the exponents are going to be on 3. So we're going to have 3 to the 6th. First of all, I'm going to erase this 1 because this 1 is not doing anything. Remember, you don't have to include the number 1 when it's in front of a letter. It's just implied that it's a 1 when you don't have a number. So our next term is going to be a 6. There's going to be a 6 in front. And remember, it's going to be x to the 6th, except we're taking away one of the x's and replacing it with a 3. So it's going to only be x to the 5th, and it's going to turn into a 3. And technically, it's 3 to the 1, but anything to the 1 is just itself, so we don't actually have to include the to the 1 part. And notice how I haven't put a sign here. Let's say this problem was x plus 3 to the 6th. If it's something plus something, then every sign in between is just going to be a plus sign. So it's going to be plus this, plus this, plus this. But because this is x minus 3, you actually have to alternate signs. So it's going to be minus 6x to the 5th times 3. And then it's going to be plus the next part, and then minus the next part, and then plus the next part, and then minus, and so on. So our next part is going to start with 15, because 15 is the next number in this row of Pascal's triangle. So we're going to have 15, and it's going to be the same thing as this, except we take away one of the x's and turn it into a 3. So we had 5 x's, now we only have 4, and it's getting turned into a 3. So instead of just a 3 here, we now have 2 3's, so we have 3 to the 2. Now we just did a plus sign, so we have to do a minus sign next, and we're going to use the next number in Pascal's triangle. In this case, that's 20. So we're going to have 20 times, and now we're turning one of the x's into a 3 again. So we had x to the 4th, now we have x to the 3rd. And we had 3 to the 2nd, now we have 3 to the 3rd. The next number in Pascal's triangle is 15. We're going to start moving down back to 1 again. So we just used a minus sign, so now we're going to have to use a plus sign. So plus 15, and we're turning another x into a 3. So we had 3 x's, now we only have 2. And we had 3 3's, now we have 4. We just used a plus, so now we have to use a minus, and we'll use the next number in Pascal's triangle, which is 6. And we had 2 x's here, now we're only going to have 1. And we had 4 3's here, now we're going to have 5 of them. And now the final part of our expansion here, we just used a minus, so we have to use a plus. And then we have 1, which remember, we don't have to actually include the 1 because 1 doesn't do anything. And we're getting rid of the final x, so we don't have any x's left, but now all of them are 3's. So we now have 3 to the 6. So we now have this big complicated mess. And you might be thinking, wow, like there must be so much to simplify here. Actually, there's not that much, because each of these have a different amount of x's. And remember, to add and subtract, you need to not only have the same letter, but you also need to have the same exponent on that letter. So first, let's go ahead and clean up these exponents. So here we have x to the 6th, minus, this doesn't have an exponent on 3, so we're going to leave it. But this one here, we have 15 x to the 4th, and then we have 3 squared. 3 squared, that's 3 times 3, which is 9. Then here we have minus 20 x to the 3rd, and then 3 to the power of 3. That's 3 times 3 times 3, which if you weren't sure about that, you could put in your calculator, you would get 27. Then we have plus 15x squared, and then 3 to the 4th. 3 to the power 4, that's 3 times 3 times 3 times 3, which is 81. Then we have minus 6x times 3 to the 5th, that's 3 times 3 times 3 times 3 times 3, which you could put in your calculator, you will get 243. And then finally, we have plus 3 to the 6th, which is, yeah, I'm not going to repeat it again, but if you put it in your calculator, you would get, what would you get? Oh, 729. So let's go ahead and get rid of this stuff at the top because we don't need it anymore and it's messy. All right, so the last thing we need to do is one more part of simplification, which you may notice we have numbers that we can multiply together that are just sitting around. So let's go ahead and do that. So you have x to the 6th minus, and then we have 6 times 3, which is 18. And then the x to the 5 is just going to stay because we can't do anything with that. Then we have 15 times 9, which if you put that in your calculator, you would get 135. X to the 4th. Then here we have 20 times 27, which if you were to put that in your calculator, you would get 540. X to the 3rd. Then here we have 15 times 81, which is 1215. Yeah, no cheating here. Plus 1215, x to the 2. Then we have here 6 times 243. I'm not even going to try to do that. I'm just going to put it in your calculator. Let's see, we get 1458. So this is going to be 1458 times x. And then 729, that's just by itself. So we're going to put 729. And that's it. Like I said before, we can't combine these because they have different exponents on them. So this is all we can do. And yeah, I know it seems like this is not simple whatsoever. I don't know how this is simplifying. That's why they use the word expand instead of simplify, because you're not making it simpler. But anyway, this is the answer. And I'm not even going to try to read all of this out loud, but yeah, that's your answer. Here's how to divide polynomials by monomials. What do those even mean? Well, a monomial, mono is in that, mono means one. So a monomial is basically just something like this, because there's only one term here. A term is basically just a clump of letters and numbers, like right here. But this part up here, this is a polynomial. And this is a polynomial because we have multiple clumps of numbers and letters. Actually, we have 2 of them. We have one right here, and then plus, and then we have one right here. So this is a polynomial. So how do we divide these? And yes, this is division. Just to clear up any confusion, fractions are the same thing as division. All we have to do is take what's at the bottom here and divide it to each term. So we would divide it from here and divide it from here. And we'll do that separately. So if you want to visualize it this way, we can go ahead and split this up into two different fractions. So we're going to have in our first fraction 24 x to the fourth, y to the third, over 3x squared. And then because we have a plus sign here, it's going to be plus. If it was a minus sign, it would be minus 6x to the third, y, over 3x squared. And now for each fraction, what we can do with a fraction is cross out the same thing if it's on the top and the bottom. So first of all, can we cross out any numbers here? Well, I mean, you might be able to say no because we have a 24 at the top and a 3 at the bottom. But we can just do division. 24 divided by 3 is 8. So we're going to have 8 at the top. Or another way you could have thought of that is 24 is the same as 3 times 8. And now we have a 3 at the top and a 3 at the bottom. So they cross out. And now can we cross out any letters here? Because we can cross out variables as well. Well, I'm noticing that we have x squared here. That's 2 x's. And we also have 4 x's up here. So what we can do is we can cross out to get rid of this bottom part. We can take out these 2 x's, and then we take out 2 of them from up here. So we had 4 of them, now we only have 2. So this is going to be 8x squared y to the third. The y to the third stays the same because we don't have any y's at the bottom here, so we don't have anything to cross out. So it just stays the same. And now let's go ahead and look at this other fraction here. Here we have 6 divided by 3. 6 divided by 3 is 2. So we're going to have plus 2. Or you could have thought of this as splitting this up between 3 and times 2, and the 3's cancel out, just leaving us with 2. And now we're going to do the same thing here. We have 2 x's at the bottom here, and we have 3 up here. So we can cross out 2 from the bottom and 2 from the top. So this 3 is going to become 1. So there's only one x left, so we're just going to put x. We don't have to put x to the 1 because to the 1 doesn't even do anything. We'll just leave it as x. And then we have y here, and there's nothing we can do with that. This is our final answer right here. We can't do anything with this because they're not like terms. You can't add them together if they don't have the same amount of letters and the same letters. So our final answer is 8x squared y to the third plus 2xy. All right, here's another example. If you'd like, go ahead and pause the video, try to solve this one for yourself, and then unpause and see how you did. All right, so it's going to be the same thing. We have 2 terms here at the top and just 1 at the bottom. So we can split this up into 2 different fractions and deal with them separately. So let's go ahead and do that. So we're going to have 28a squared b to the fifth, and it's going to be over 4a squared b. And then this time we're going to put a minus sign in between the fractions because we have a minus here. And then it's going to be 4a to the third b to the sixth, over 4a squared times b. All right, so let's look at this first fraction here. We have 28 divided by 4. 28 divided by 4 is 7. So we're going to have 7 here at the top of our fraction. And now let's go ahead and look at the letters. Well, if we look at the a's first, we have 2 a's at the bottom, and we have 2 a's at the top. Well, we can cross both of those out, because if they're at the top and the bottom of a fraction, they cancel out. So these are both going to cross out, and we're not left with any a's left. So we're not going to put any a's here. And then finally, we have 1b at the bottom. I know that there's not an exponent here, but when there's not an exponent, that means it's just 1. So this is 1b, and we have 5 up here. So we can cross out 1b from the top and the bottom. So we'll cross out 1 here, and then this one will become a 4. Now we only have 4 left, and that'll transfer down here. All right, the minus sign is going to carry over. And then we have 4 divided by 4. Well, that's just 1. So these cancel out, actually. And we're not going to write the number 1 because it's pointless to write the number 1 because anything times 1 is itself. Now let's look at the a's here. We have 2 at the bottom, just like before, but this time we have 3 at the top. So we're going to cross out the 2 at the bottom, and we had 3 of them. Now we're only going to have 1 of them because 3 minus 2 is 1. But a to the 1 doesn't mean anything, right? It just means a. So we're going to put just a. And now we have b to the sixth over b. So we're going to cross out the b at the bottom and cross out one of the b's from the top. We had 6, now we're only going to have 5. So we're going to have b to the fifth. And remember, we can't combine these because they don't have the same letters and the same exponents on them. So this is our final answer, 7b to the fourth minus a b to the fifth. It's time to go back to fourth grade and do some long division. All right, here's our first example. We've got a quadratic equation thing at the top, and we've got x minus 3 at the bottom, and we need to divide them using long division. And just to clear up any confusion, this is a fraction. Fractions are the same thing as division. So if this had a divided by sign, it would mean the same thing. So you may remember long division from like way back in elementary school. So for example, let's say we had to divide 68 divided by 4. We would put 68 in this weird like curvy box thing and then put 4 on the outside. And then you would do the steps of divide, multiply, and subtract. So first you'd see how many times 4 goes into 6. Well, only one time, because if you did 4 times 2, that would be 8, and that's too much. So we would have 1. Then you do step 2, which is multiplying. So we take 4 times 1, which is 4. And then finally we subtract. So 6 minus 4 is 2. And then we bring down another digit and then do it all over again. So 28 divided by 4 is 7. 4 times 7 is 28. And then we subtract 28 minus 28 is 0. And we're done. Our final answer is 17. So you might be asking yourself, why am I teaching you long division again from elementary school? Well, we're actually going to do exactly the same thing with polynomials. So what we're going to do is we're going to take this top part here, this first part, and we're going to write it out. And then we're going to put it in that weird box thing. And then we're going to take this second part here, x minus 3, and put it on the outside. And now we're going to do the same steps as before. We're going to divide, multiply, and subtract. So we're going to take this first x part here, and we're going to divide it to x squared. So x squared divided by x. Well, if we were to visualize this, x squared divided by x, we would cancel out an x from the top and the bottom. So we get rid of x, and then here we had 2 of them, now we only have 1. So our final answer would be x. So we're going to put x up here. Now we're going to do step 2, which is multiplying. So we're going to multiply the x to both the x and the minus 3. So first we're going to do x times x, which is x squared. Then we're going to do x times, not 3, minus 3. Remember, the minus signs always stay. So we're going to have x times minus 3, which is just minus 3x. We can't multiply a number and a letter, so it stays the same. And now our final step is to subtract. But in this case, if we were to just do this and add them together, that would be adding. So to subtract, all we have to do is change all the signs. So this is going to become minus, and this is going to become plus. So now we have x squared minus x squared. Well, those cancel each other out, right? That would be equal 0. And then we have 3x plus 3x, which is 6x. And now we're going to bring down, which in elementary school was just bringing down another digit. In this case, it's bringing down another term, another part of this. So we're going to bring down the minus 18, and we're going to do it again. So we're going to divide this first part by this first part. Well, the x's would cancel out, and we just have 6. So we're going to put plus 6. Now we're going to multiply. So we're going to multiply x times 6 and negative 3 times 6. So x times 6, well, you can't multiply a number to letter, so it's just going to stay as 6x. And then negative 3 times 6. Well, 3 times 6 is 18. And then the minus sign stays. And now we just go on to our final step, which is subtract. So we're going to go ahead and change all the signs here at the bottom. So 6x minus 6x, those cancel out. And minus 18 plus 18, those cancel out as well. So that just leaves us with 0. Now we've finished all of our terms here, so we're done with the problem. This number right here, this is going to be our remainder. But because it's 0, we don't have to do anything. If it wasn't 0, then we would have to use a remainder, which I'll talk about in the next problem. But because we don't have a remainder, that's our final answer. Our final answer is x plus 6. All right, here's another example. Go ahead and pause the video, see if you can solve this one yourself, and then unpause and see if you got it right. All right, we're going to do this the same way as before. So we're going to take this top part here, and we're going to put it in that weird box thing. And then on the outside of the box, we're going to put x plus 2. So remember, the steps to long division are divide, multiply, and subtract. So first we're going to divide. We're going to divide the first part of this by the first part of this. So we have 3x squared divided by x. Well, one of the x's is going to cancel out. So we had 2 x's here, now we're only going to have 1. So we're going to have 3x. And if you wanted to visualize that, let's go ahead and write it up here in the corner. 3x squared divided by x. the x crosses out, and one of the x's on the top crosses out. Nothing happens to the 3 because we don't have a number down here. So we're just left with 3x. Now we need to multiply. So we have 3x, and then we're multiplying by another x. So that's going to be 3x squared. And then 3x times 2. Well, nothing's happening to the x, so the x is going to stay the same. But we have 3 times 2, which is 6. So we're going to have 6x. And now our final step is to subtract. So we need to subtract by the bottom. So what we're going to do is just change all the signs. So this is going to be a minus, and this is also going to change to a minus. So 3x squared minus 3x squared, well, those cancel each other out, so that's 0. And then we have plus x minus 6x. We had 1, and then we lost 6 of them, so we're down 5. So it's going to be minus 5x. And now we bring down the minus 8, and we do the same thing again. So divide. We're going to divide the first part of this by the first part of this. So we have minus 5x divided by x. Well, dividing it by x cancels out the x's. So all we have left is the minus 5. So we're going to put minus 5. Now we just have multiplication. So we're going to multiply the minus 5 to both of these. Minus 5 times x is just, well, minus 5x. And then minus 5 times 2. Well, 5 times 2 is 10. And then we have one minus sign. So the minus sign carries over. And now our final step is to subtract. So we're going to go ahead and change these signs. They're both minuses, so now they're going to be both pluses. So minus 5x plus 5x, those cancel out. And then minus 8 plus 10. That's the same thing as saying 10 minus 8. 10 minus 8 is 2. So we're going to be left with 2 here. And we don't have any more terms to bring down, so we're done. We're done with the problem. But before we had a 0 here. Now we have a 2. So our remainder is 2. So what do we do with the remainder? Well, we're just going to take our remainder and we're going to add it as another term in our answer. But it's going to be 2 divided by whatever is here on the outside of our division problem. In this case, it's x plus 2. So it's going to be 2 divided by x plus 2. So there you go. Our final answer is 3x minus 5 plus 2 over x plus 2. When we're dividing polynomials, long division is cool and all, but there's one main problem with it. It's long. So here's an even faster way to do polynomial division, and it's called synthetic division. All right, here's our first example. We need to divide these two polynomials. We've got like a quadratic equation looking thing at the top, and then we've just got x minus 2 in the bottom. So synthetic division, which is the faster version of long division, only works when you have x plus something or x minus something at the bottom. So if you had like 2x minus 5, or if you had x squared plus 4x plus 3 or something at the bottom, then you can't do this. You'll have to use long division. And remember that fractions are the same thing as division. So if you had this and then a divided by sign and then x minus 2, then this would mean the same thing as a fraction. So here's what we're going to do. We're going to take this number right here that's next to x, and we're going to put it in a box. But we're going to use the opposite sign. So because this is minus 2, we're going to take positive 2 and put it in a box. If this was plus 2, then we would put minus 2 in the box. And now we're going to take the first number of each of these terms and lay them out here. So here we have 2 at the beginning, so we're going to put 2. Next we have, well, there's no number in front, right? But when there's not a number, it means 1. So this is going to be minus 1. Make sure you include the minus signs as well. So minus 1. And then here we have minus 6. Then we're going to go ahead and draw a line under here, leaving room for some numbers. And we're going to draw another line right here before our last number. And this is going to be where our remainder is. I know this seems more like a Bob Ross tutorial than a math tutorial right now, but trust me, the math is coming. So our first step here is to just bring this first number here down here. Easy. But then we have to do multiplication. So we're going to take this number and multiply it with the number in the box. 2 times 2 is 4. So we're going to put a 4 here in this empty space. And now we're going to add these numbers together. So minus 1 plus 4, that's the same thing as saying 4 minus 1. 4 minus 1 is 3. So that gives us 3. And that's going to give us our next number at the bottom. And then we repeat. So 3 times 2 is 6. And then negative 6 plus 6, well, that's the same thing as 6 minus 6, which is 0. These cancel out, right? So we figured out our answer, and it's going to be right here. But what does this even mean? Well, it's not quite our final answer yet until we interpret it into x's and stuff. So basically, this number right here in the box is our remainder. But because we have a 0 for the remainder, we don't actually have to do anything with this. So we're going to ignore it for this problem. The next problem, I'll show you what to do when the remainder isn't 0. So we're going to take this number here. This number is going to be by itself. And every number to the left, we add an x. So this is going to be our x term. If we had a number here, this would be our x squared term, and then our x to the third term, and so on. So we're going to have 3 by itself, and we have 2 times x. Then you just put a plus sign in between them, or a minus sign if they're negative numbers. So our final answer is 2x plus 3. All right, here's another example, and this one is going to have a remainder. So it's going to be a little bit harder, but if you want to try it yourself, go ahead and pause the video and attempt it, and then unpause and see how you did. All right, so we're going to set it up exactly the same way. We're going to take this number right here, and we see that it's plus 2, so we're going to take the opposite sign, so minus 2, and put it in a little box. And then we're going to take the beginning numbers of each of these and lay them out. So we're going to have 2 for x to the 4th, and then we're not going to put minus 3. You may notice that we have x to the 4th, and then x to the 2. We're missing an x to the 3rd, right? So whenever you're missing an x term, in this case we're missing an x to the 3rd, we will put a 0 as a placeholder. So we're going to have 0 for x to the 3rd, and then we just continue on. So we have minus 3, and then 2, and then minus 5. And then we're going to draw a line underneath here, and another line here for our remainder. So we're going to bring down the 2, and we're going to multiply. 2 times 2 is 4, and then we have 1 minus sign, so the minus sign stays. Then our next step is to add these together. So 0 minus 4, well, the 0 is not doing anything, so it's just minus 4. And then we repeat. So we have 2 times 4, which is 8, and then we have minus sign, 2 minus signs, so they turn into a positive. So we're just going to have positive 8. Then we add these together. Minus 3 plus 8, that's the same thing as 8 minus 3, which is 5. Then we have 2 times 5, which is 10. And we have 1 minus sign, so the minus sign stays. Then we have 2 minus 10. We had $2 and then lost 10, so we're down 8. And then we have 2 times 8, which is 16. And 2 minus signs, 2 minuses make a positive, so positive 16. And then finally we have minus 5 plus 16. That's the same thing as 16 minus 5, which is 11. So I know that was a lot, and if you need to, you can go ahead and slow down and look at each thing that I did, but it's basically repeating the same steps over again. So our final step is to interpret what we have at the bottom here, because this is just a mess of numbers right now. Well, remember that this number here is going to be by itself, and then every number after that to the left is adding another x. So this is going to be our x term. This is going to be our x squared term. This is going to be our x cubed term, or x to the 3rd. And if you had more, it would be x to the 4th, x to the 5th, and so on. So we're going to have 2x to the 3rd minus, because we have a minus sign here, 4x squared plus 5x, and then minus 8, and that one's by itself. So normally we're done here, right? But in this case, this number here is not 0. This is a remainder, and we're going to have to use this remainder at the end of our answer. So what we're going to do is we're going to attach it to the end. We're going to put plus 11. It would be minus if it was a negative number. So we're going to have plus 11, but then we have to divide it by what we were dividing by at the start. So that's x plus 2. So we're going to have 11 over x plus 2. So there you go. This is our final answer. And if you wanted to check your work, you could multiply it by x plus 2 and see if you get what's at the top here. It's time for the quickest math tutorial ever. Here's how to find degree and leading coefficient. So here's our first example. We have a polynomial here, and we can call this a univariate polynomial or a polynomial in one variable. Those are all basically just fancy ways of saying we only have one letter here, it's x. So for this example, we need to find the degree and the leading coefficient. Well, because this polynomial only has one letter, we can say that the degree is just the biggest exponent. So what is the biggest exponent here? Well, this one, right? This is a 3, and this is the biggest exponent out of all of these. So the degree is 3. Now what about leading coefficient? Well, that's just the number that's in front of the biggest exponent. So in this case, here is our term that has the biggest exponent, 3. So the number in front of it is 4. So our leading coefficient is 4. That's it. That's all you need to know. All right, well, there is one mistake that I feel like you might be likely to make. So here's another example. Go ahead and try this one on your own. Pause the video and then unpause and see how you did. Same thing, degree is the biggest exponent, and it looks like the biggest exponent is right here. This is an 8, and there's nothing else bigger than 8 for exponents, so the degree is 8. And now what about the leading coefficient? Well, that's just the number that's in front of the biggest exponent. So in that case, you might be saying, all right, well, here's the term, the leading coefficient is 6. But there's one thing you need to remember, and that is negative signs always stay. So in this case, the leading coefficient is actually negative 6. Because the minus sign is attached to the 6. But yeah, that's it. The degree is 8 and the leading coefficient is negative 6. You've learned how to graph this, and you've learned how to graph this. But now it's time to graph this. All right, here's the example that we'll be doing in this video. We need to graph this polynomial right here. And remember that the official scholarly definition for polynomial is stuff with multiple things in it. So before, with straight lines and with quadratic equations, we had like a fancy system we could use to graph these. But once we start getting to like x to the third and x to the fourth, it starts getting a little bit too complicated to just do some fancy system and graph something. So we're going to have to graph this using a table. And essentially what this means is we're going to plug in numbers for x, see what we get for y, and then we're just going to plot that on our graph. And once we do that enough times, we'll have a rough idea of what the graph's going to be. That's why your homework might say to sketch the graph instead of like graph it, because sketching means it doesn't necessarily have to be super accurate. And remember that this up and down line here, the up and down values, those are y. And left and right, that's x. So we're going to start over here on the left with the negative numbers, and we're just going to work our way to the right. So for my first number, I think I'm going to start here at -3. So we're going to put -3. You could start at somewhere farther to the left if you wanted, but I'm just going to start at -3 as a good starting point. Doesn't matter. So what we're going to do is we're going to plug in -3 every time we see x. So x is going to become -3. And whatever number we get is going to become y. So let's go ahead and rewrite this equation, but with -3 for x. So we're going to have -3 cubed plus 3 times, and then x is going to become -3 squared plus, and then -3 minus 2. So if you remember PEMDAS, which is like the order that you have to do these things in, the E is for exponents. We need to do exponents first before we do any multiplication, division, addition, or subtraction. So -3 cubed, let's go ahead and write that out. That's -3 times -3 times -3. So we have 3 times 3. 3 times 3 is 9. And then we have 2 negatives. 2 negatives make a positive, so we just have +9 times -3. 9 times 3 is 27. And we have 1 negative sign, so the negative sign stays. So this is equal to -27. But you may notice that here we have -3 cubed. So we're going to have -27, which is +27, because 2 negatives make a positive. Next we have +3 times -3 squared. Well, that's -3 times -3. 3 times 3 is 9, and 2 negatives make a positive. So we're going to have +3 times 9. And then here we have plus -3. That's just the same thing as saying -3 minus 2. So let's go ahead and continue on. We have 27 plus, and then 3 times 9 is 27. And then -3 minus 2, that's -5. And now I'm already noticing this is going to be way too big a number, but we'll just finish it off anyways. 27 plus 27, that's 54. Minus 5 is 49. So our final number for y is going to be 49. Now, there's no way we're going to be able to graph that on this little graph here. So what I'm going to do is actually, I'm probably going to skip over to -1, because I think that'll have a more reasonable number. So let's go ahead and put in -1 whenever we see x. So we're going to have negative, and then instead of x, we're going to put -1 cubed plus 3 times, and instead of x, we're going to put -1 squared plus -1 minus 2. -1 cubed, that's -1 times -1 times -1. 1 times 1 times 1 is just 1, so then the number is still going to be 1. But remember, we have 2 negatives here. 2 negatives make a positive, and we're left with 1 more negative. So the negative sign carries over, and it's going to be -1. But remember that we have one more negative here on the outside. So that's going to be -1, which is +1. So we had a total of 4 negative signs, and those turned into positive. Next, we have plus 3 times -1 squared. Well, that's -1 times a -1. Two negatives make a positive, so that's going to be 1. So we're going to have 3 times 1. Then we're going to have plus -1. That's the same thing as just saying -1. So we're going to put -1, -2. Then let's go ahead and clean this up. We're going to have 1 plus 3 times 1 is 3. And then -1, -2. That's, we lost $1 and then lost another $2, so that's -3. And then we're going to have 1 plus 3 minus 3. The plus 3 and minus 3 cancel each other out, actually. So we're only going to be left with 1. So our y value is going to be 1. So this is actually going to be the first point that we plot on our graph. So we're going to have x equals -1 and y equals +1. So remember, x is left and right. Negative numbers are on the left. So we need to start in the middle and go to the left 1 to get to the x value. And then it says that y is +1, which means we have to go up because y is up and down. We need to go up 1. And we're going to have a point right here. And now, even though this -349 thing seems like it's totally pointless because we can't graph it here, it actually tells us that because the point is all the way up here somewhere, the graph is going to be coming down to this point. Because it could have started down here and then gone up like this. But this tells us that it's coming from the top. So let's go ahead and graph 0 now. Let's go ahead and plug in 0 and see what we get. So we're going to have -0 cubed, plus 3 times, and then instead of x squared, it's going to be 0 squared, plus 0, minus 2. Now, 0 cubed, that's 0 times 0 times 0, which is just 0. And -0 is still 0. So this isn't doing anything. We have plus 3 times 0 squared. Well, anything times 0 is 0, so that cancels out as well. And this plus 0 is also not doing anything. So our final answer actually already is -2. So when x is 0, y is -2. So let's go ahead and plot this point on our graph. Where x is 0, that means we're not going to the left or right at all. We're staying in the middle. We are going down because y is up and down. We're going down 2. So we're going to go down 1, 2. And our point is going to be right here. We already did -1 and 0. Now let's go to +1. Let's go another one to the right. So we're going to have -1 cubed plus 3 times 1 squared plus 1 minus 2. 1 cubed, and remember that this negative sign is actually on the outside of what's being cubed. We have to do the cube first. 1 times 1 times 1 is just 1. So we're going to have -1 because the negative sign is still here. So -1 plus 3 times 1 squared. 1 squared is 1 times 1, which is 1. So we're going to have 3 times 1 plus 1 minus 2. Let's go ahead and clean this up. We're going to have -1 plus 3 times 1 is 3. And then plus 1 minus 2. We had $1 and lost $2, so we're down $1. And now we have -1 plus 3. That's the same as 3 minus 1. 3 minus 1 is 2. And then 2 minus 1 is 1. So when we plug in 1 for x, we get 1 for y. So let's go ahead and plot that on our graph. We have to go to the right 1 because x is left and right, and x is +1 in this case. And when we go to the right 1, we go up 1. So we're going to go up here. So now you may notice the graph is actually, because we started up here, we're going to be going down, but then we go back up. And I'll show you why that is in a second. But first, we need to plot some more points. So let's go with x equals 2. We're going to have -2 cubed instead of x cubed, plus 3 times 2 squared, plus 2 minus 2. And immediately I'm seeing that this plus 2 minus 2 are just canceling each other out. They're not going to be doing anything, so let's just cross those out now. Why not? So we're going to have 2 cubed, 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. So we're going to have -8 because that negative sign is here. Then we're going to have plus 3 times 2 squared. That's 2 times 2, which is 4. Now the -8 is going to stay, and we have 3 times 4 because we have to do multiplication first. 3 times 4 is 12. And then we have -8 plus 12. That's the same thing as saying 12 minus 8. 12 minus 8 is 4. So we get 4 for y. So let's go ahead and plot that on our graph. We go 2 to the right because x is 2, but we get 4 for y. So we're going to go up 1, 2, 3, 4. And we're going to have a point right here. Now you may be thinking that if we started up here, we're going to go down here and then go back up. It kind of looks like a parabola, right? But actually, I don't think it's going to. And just to show that, I'm going to do one more x value. We're going to go ahead and do 3. 3 cubed, that's 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. So we're going to have negative 27, and then plus 3 times, and then 3 squared. 3 squared is 3 times 3, which is 9. So we're going to have 3 times 9. Plus 3 minus 2. 3 times 9 is 27, so plus 27. And then plus 3 minus 2. 3 minus 2 is 1, so we're going to have plus 1. Negative 27 and plus 27, those cancel out, right? Those just equal 0. So we're going to have 0 plus 1, which is just 1. So 1 is our answer. So let's go ahead and put in 1 on our table and plot this point. So we're going to have 3 for x. That means we have to go to the right 3. So 1, 2, 3. And y is 1. So we need to go up 1. Well, this is a weirdly shaped graph. What is going on here, right? So it's actually not going to be a parabola. We're going to start up here, go down and back up like a parabola, and then go back down again. So let's go ahead and draw the line in between these. And remember, this is just a sketch, so it doesn't need to be totally accurate, which is just my excuse for drawing really terrible graphs. But here we go. This is our sketched graph. But you might be asking yourself 2 questions. First of all, how did I know that it was going to go back down like this and not just keep going like this? And second of all, how do I know that if I do 4 or 5, it's not going to go back up again? Why am I so confident that it's going to look like this? Well, for that, all we need to do is look for the biggest exponent in our equation. In that case, that's 3. And the 3 means that we're going to have a maximum of 3 directions that this graph is going in. So you can see that this graph is going down, and then it goes up, and then it goes down again. It changes direction twice, so we have a total of 3 directions for a 3 exponent. It doesn't necessarily have to have 3 unique directions. It could look something like this instead. This graph goes up the entire time, but you can see it goes fast and then it slows down and then it goes fast again. So you can think of it like that as well. But it's never going to have more than 3 directions. So if the exponent is 3, you're not going to go back up and then back down again. This is the maximum amount of directions that you can have. And also, because this is an odd number, you're always going to have an odd number of directions. So you're never going to have it go down and then up like this, because that's an even number of directions, down and then up. That's 2 directions. So there you go. This is our sketch of the graph of this polynomial. Here's how you can find the zeros and relative maxima and minima of a polynomial like this one without even having to graph it. Let's help you understand what it is that we're finding without graphing. I'm going to have to show you a graph. So first of all, we need to find the zeros of the polynomial. And that's basically wherever it crosses the x-axis. It's wherever y is 0. Remember, y is up and down. So where y is 0, that means we're not going up or down at all. So like, for example, right here. Here, we're just staying on the line. We're not going up, we're not going down. So this is a 0. And we represent zeros by where they are relative to x. So in this case, we started in the middle and went to the left, 1, 2, 3, 4. Remember, to the left is negative numbers, so we would say that we have a 0 about at x equals negative 4. What about this one here? This is also a 0 because it crosses the x-axis here. This is where we're not going up or down. And this is probably about x equals negative 1 because we went to the left 1. So this is about at x equals negative 1. And then this one's kind of in between 2 values. This is between x equals 2 because it's 2 to the right, and x equals 3. So we're just going to say between x equals 2 and x equals 3. And you'll see that once we start doing our table and we're solving this without a graph, we're probably just going to say, oh, it's between these 2 numbers, because that's basically as specific as we can get. Now, what about relative maxima, which is just the plural word? Maxima is the plural word for maximum, which is probably a word you've heard before. It's just the biggest value. But a relative maximum is basically the maximum value just within a little small space. So in that case, it would be right here. This is a relative maximum. It's the top of a little hill. It's not the biggest value in the graph because there are numbers way bigger than that over here, but it's the biggest relative to where it is. So this is going to be a relative maximum. It's actually the only one, and it's going to be between these two values. Here we have x equals -3 because we go to the left 3, and this is x equals -2 because we go to the left 2. So this is going to be between x equals -3 and x equals -2. And now finally we have relative minima, which is just the same thing, but it's the smallest numbers in a little area. In that case, we only have one here, and it's this one. This is the smallest number in this little valley here. And it looks like it's between x equals 0, which is just right on the line, and x equals 1, which is 1 to the right. So we're going to say that this is between x equals 0 and x equals 1. So this is how you find zeros and relative maxima and minima on a graph. But how do we do this without a graph? Well, here's the example that we'll be doing in this video. We need to figure out the zeros and relative maxima and minima of this graph right here, except we're not going to graph it. We're just going to figure those out without having to draw anything. So we're going to be doing this very similar to how you would sketch a graph of this, except we're just not going to do the plotting the points part. So when we're sketching a graph of something like this, we always do a table. So we plug in numbers for x, see what we get for y. We just do that a bunch of times, and then we have a rough idea of what the graph looks like. So we're going to have an x column and a y column. And for every number that we plug in for x, we'll get a number for y. And we'll do that multiple times and see what we get. So we're going to start as far to the left as possible without going too crazy. I think I'm going to try out -3 and see what happens. And then we'll do -2, -1, and so on. So we're going to rewrite this equation, except whenever we see x, we're going to put -3 instead. So we're going to have negative, and instead of x, we're going to put -3. So we're going to have -3 to the fourth plus -3 to the third plus 4 times -3 squared minus 3 times -3 plus 1. Now, -3 to the fourth, that might be a little hard to think of in your head, but we're going to have -3 4 times. So we're going to have -3 times -3 times -3 times -3. -3 times -3, well, that's 3 times 3, which is 9, and then 2 negatives make a positive. So it's going to be +9. So we're going to have +9 times +9, and 9 times 9 is 81. So we're going to have 81 for this. But remember, we actually have a negative sign here. We have another negative. We have negative what we just did. So this is actually going to be -81. Next, we have plus -3 cubed. Well, that's -3 times -3 times -3. And remember from before that -3 times -3 is 9 times -3. 9 times 3 is 27. And we have one negative sign, so the negative sign stays. So we're going to have plus -27, which is just the same thing as saying -27. Next, we're going to have plus 4 times -3 squared. That's -3 times -3, which is +9. So we're going to have +9. And then -3 times -3, that's showing up a lot in this problem, but it's the same thing. 3 times 3 is 9, 2 negatives make a positive, so +9. And then +1. All right, so next we're going to have -81 minus 27. That's going to be minus 108. You can put that in a calculator if you want, obviously. And then plus 4 times 9, which is 36. And then plus 9 plus 1. 9 plus 1 is 10. And now we can just do this in any order, but if you wanted to put this in your calculator, minus 108 plus 36, that would give you -72, and then that would give you -62. Again, this is very calculatorable. But yeah, our final number here is -62, which kind of makes me thankful that we're not actually graphing this because this would be literally impossible. All right, let's go ahead and do the same thing for -2. Let's go ahead and put -2 as our next number. So we're going to do the same thing, but instead of x, we're going to put -2. So -2 to the fourth plus -2 to the third plus 4 times -2 squared minus 3 times -2 plus 1. So -2 to the fourth, well, let's go ahead and write that out. -2 times -2, that's 2 times 2, which is 4, and 2 negatives make a positive. So we're going to have 4 times 4, and 4 times 4 is 16. So this is, remember, we have a negative sign here as well that we hadn't used. So it's going to be a -16. Then we have plus -2 to the third. That's -2 times -2 times -2. -2 times -2 is +4 times -2. 4 times 2 is 8. And we have a minus sign, so the minus sign stays. So we have plus -8, which is just -8. Then we have plus 4 times -2 times -2 which is positive 4. Then we have negative 3 times negative 2, a little bit different this time. Woo! 3 times 2 is 6, and then we have two negatives make a positive, so positive 6, and then plus 1. Negative 16 minus 8, we lost $16, lost another 8, that's minus 24. Then plus 4 times 4 times 4 is 16, plus, and 6 plus 1 is 7. And now, again, you can always put this in your calculator if you want. We have negative 24 plus 16. If you want to think about it like the dollar analogy as well, you lost $24, then gained 16 back, you're still down 8, and then you gain another 7 back, but you're still down 1, so negative 1. So already we've gone from negative 62 all the way to negative 1 in just one amount of x. So next, let's go ahead and try out negative 1, and it's the same thing over and over, so I'm going to go a little bit fast, but again, you're always free to pause the video and think about what it is I'm doing. But it's the same thing that I was doing before, just with a different number for x. So we're going to plug in negative 1 wherever we see x. So here we have negative 1 to the 4th. Well, 1 times 1 times 1 times 1 is still 1, so the 1's not going to change. But because we have an even numbered exponent here, that's negative times negative, which is positive, times another negative, which makes it negative, times one more negative, which makes it positive again. So this is actually going to be positive 1, but we have another negative right here, so that makes it negative. 5 negatives, not confusing at all. Then we have plus negative 1 to the 3rd, that's negative 1 times negative 1, which makes it positive 1, times another negative 1, which makes it negative. So that's going to be negative 1. Then we have plus 4 times negative 1 squared, that's negative 1 times negative 1, which is positive 1. Then we have negative 3 times negative 1. 3 times 1 is 3, and 2 negatives make a positive, so positive 3, and then plus 1. Minus 1, that's minus 2, plus 4 times 1 is 4, plus 3 plus 1 is 4. So here we have negative 2 plus 4, that's the same thing as 4 minus 2, which is 2, and then plus 4 is 6. So we're going to have 6 for y. And now let's keep going. So we're going to have 0 for x. This should be the easiest one. And this is quite easy because 0 to the 4th is 0, 0 to the 3rd is 0, 0 to the 2nd is 0, 3 times 0 is 0, and all we're left with is 1. So it's 1. Easy. But unfortunately, that was the only super easy one because we're back to more confusing ones. But at least we don't have negative numbers anymore. So I've plugged in 1, and let's go ahead and see what we get when we plug in 1. And then 1 plus 1, really hard, but it's 2. So we're going to put in 2 for y here. Let's keep going. We're going to plug in 2 for x, and you might be asking yourself, when are we going to stop? We're basically going to stop when we have something ridiculous like this again. Once we know that the graph isn't going to change again, like this, when we have negative 62, then that's how we know that we're going to stop. So let's go ahead and plug in 2, which is 8, minus 5 is 3, so 3 is our number here. Let's plug in 3. And this should give you negative 26. So we're going to put in negative 26 here. So this is our final table here. And with this, we can figure out our zeros and relative maxima and minima. So first, let's look for zeros. The only problem is zeros are where y is 0, but y is not 0 in any of these, right? Well, we can actually figure out where y is going to be 0. Like, for example, here. Here we went from negative 1 to 6. And 0 is in between here. So this means that if we were to graph this, between negative 2 and negative 1, we crossed 0. We went from the negative numbers to the positive numbers. So in this case, we know that one of the zeros has to be between x equals negative 2 and x equals negative 1. Where else do we see that happening? Well, it stays positive for this whole time, but then it becomes negative again here. We switch signs, which means that 0 is in between here. We crossed 0 at some point. So we crossed 0 at some point between x equals 2 and x equals 3. So let's write that down. So we have now found our zeros. Let's go ahead and find relative maxima and minima now. So remember that relative maxima are just like those hills where we have a big number that's the biggest number in a little group of numbers. So in this case, this number 6 is sticking out to me because we have a 6 here, and to the left and the right of it are both numbers that are smaller. So we had negative 1, we go up to 6, and then we go down to negative 1 again. So that suggests a hill. And here, x is negative 1. So we can say that there's going to be a relative maxima near negative 1. But remember, it might not be exactly negative 1 because there could be like a 7 or an 8 or something really close to this that we just don't know about. but in this case, it's going to be near -1. And do we see any others? Well, I see one right here. Here we have a 3, and to the left and the right of it are smaller numbers. We had a 2, we went up to 3, and then went back down to -26. So here we have another relative maximum, and this relative maximum is going to be at x equals 2, or near x equals 2. We don't know for sure, but it's going to be near x equals 2. Finally, we just need to find a relative minima, or the plural for minimum. It's the same thing, except we have a small number around bigger numbers. And I want to remind you that in this case, these two numbers here, -62 and -26, even though those are extremely small numbers, they are not going to be relative minima because they are not the valleys that we were talking about. For it to be a valley, it needs to have gone up on both sides. Well, the only one I'm seeing here is right here. And this is a relative minimum because it's a small number that's surrounded by numbers that are bigger than it. And in this case, we're going to have x equals 0. So our relative minimum, and our only relative minimum, is going to be near x equals 0. So there you go. We found the zeros, the relative maxima, and relative minima, or at least good estimates for where they are. Here's how to factor using sum and difference of cubes. So here's our first example. We need to factor this using the sum or difference of cubes. But what do those even mean? Well, first of all, to be able to use sum or difference of cubes, these two parts here in the problem, they have to be cubes for you to use the rules of cube. And a number is a cube basically if you can multiply 3 of the same thing to get to it. So like, for example, 64 here is a perfect cube because if you multiply 4 times 4 times 4, you will get 64. Also, like, for example, 2 times 2 times 2, that's a perfect cube because that gives you 8. And then 3 times 3 times 3 is 27. So 8, 27, 64, those are all perfect cubes. But it doesn't just have to be a number. For example, x cubed, x to the third, that is also a perfect cube, even though it's not a number, because x to the third just means x times x times x, which is a perfect cube. We're multiplying x 3 times to get x to the third. So because these are both perfect cubes, we can apply one of these rules. So first of all, I'll go over sum of cubes and then difference of cubes. So sum of cubes basically says that if you have a cube plus another cube, that's actually what we have in this case, a plus, then you can turn it into this. You can turn it into a plus b times a squared minus ab plus b squared. Now, difference of cubes is what you would use if you had two cubes with a minus sign in between. So we're going to call that a cubed minus b cubed. And that is going to equal exactly the same thing, except we're going to replace this with a minus and this with a plus. We're just swapping these two signs. So you would get a minus b times a squared plus ab plus b squared. So for this problem, x cubed plus 64, this is a sum of two cubes, because a sum means you're adding them together, right? So we're going to use sum of cubes in this case. But we need to figure out what a and b are, because we have a cubed plus b cubed. But a is not going to be x to the third, and b is not going to be 64, because we need to figure out a and b, and they're going to be the numbers that we multiplied to get these cubes. So for example, for 64 here on the right, we multiplied 4 times 4 times 4 to get to 64. That's why it's a perfect cube. So b is actually going to be 4. And for x cubed over here, this is a perfect cube because we multiplied x times x times x. So in this case, a is going to be x. So all we need to do is replace a and b with x and 4 in this formula. So we're going to have a plus b, that's going to be x plus 4. And then we have a squared, that's now x squared because a is x, minus a times b, that's x times 4. You can't multiply a letter and a number, so it's just going to stay x times 4. Or usually in algebra, we put the number first, so that would be 4x. And then plus b squared. B in this case is 4. 4 squared means 4 times 4, which is 16. And there we go. We have now successfully factored x cubed plus 64. And remember that factoring is the opposite of simplifying. So if you saw this and you were like, oh, wait, I need to simplify this, right? You would just get yourself right back to here. So we're basically doing the opposite of simplifying. All right, here's another example. What are we going to do in this case? Well, this minus sign might suggest to you that we're going to use difference of cubes, which makes sense, right? And we've got x cubed and y cubed here. So they're probably perfect cubes, right? But the numbers in front also need to be perfect cubes. In this case, 6 is not a perfect cube. And if you didn't already know that, there's an easy way to tell. You can just figure out what the actual perfect cubes are. So in this case, we have 1 times 1 times 1. That's a perfect cube. That gets you 1. And 2 times 2 times 2 gives you 8. 6 is in between these. So that means that it's not going to be a perfect cube because 1's a perfect cube and 8 is a perfect cube. And 4 is also not a perfect cube. It is a perfect square because 2 times 2 is 4. But a perfect cube means you have to multiply 3 times to get that number. And there's no number that you can multiply 3 times to get 4. I mean, it's probably like a decimal or something, but we're not doing decimals in this. So if they're not perfect cubes, what do? Nothing. Now, if you literally couldn't factor it any other way, then you would just say that this is prime. And that would be your final answer. If it's prime, that means you can't factor it. But we can actually factor this another way, and that is, I'm noticing that 6 and 4, they both have 2 in common as a factor. You can divide 2 out of both of these. So what I'm going to do is I'm going to put 2 on the outside, and then I'm going to divide both of these numbers by 2. So 6x to the third now becomes 3x to the third, and 4y to the third becomes 2y to the third. And this is called factoring using the greatest common factor, or GCF. That doesn't have to do with sum or difference of cubes, but it is a thing you can do. So if it says to factor using sum or difference of cubes, that's not what this is. This is basically the only way we can factor this. You cannot factor this using sum or difference of cubes. All right, here's another example. What I'd like you to do for this one is go ahead and pause the video, try to solve this one for yourself, and then unpause and then see how you did. And this one's a little bit tricky, but try your best. All right, so let's see if these are perfect cubes, right? So 2 times 2 times 2, that was 8, and 8 is a perfect cube. But 3 times 3 times 3, that's going to be our next perfect cube, is 27. And 16 is not there, right? So 16 is not a perfect cube. And if we were to go on with 4 times 4 times 4, that's going to give us 64, not 54. So 54 is not a perfect cube either. So it looks like we can't use sum or difference of cubes, right? Oh no, how unfortunate. So I guess in our sadness, let's go ahead and factor this using the GCF like we did before. We could divide 2 out of both of these, right? Because they're both even numbers. So I'm just going to factor out a 2 and just say that we're done, right? So we're going to divide this by 2. 16 divided by 2 is 8. X to the third minus, and then 54 divided by 2 is 27. Y to the third. Oh, look at that. It magically makes a perfect cube, right? 8 is a perfect cube because that gives us 2 times 2 times 2. And 27 is a perfect cube because that's 3 times 3 times 3. So we can now use difference of cubes on this problem. So we need to figure out what A and B are, right? Well, here we already figured out that 8 is 2 times 2 times 2. But A isn't just going to equal 2 because we also have an x to the third here. And remember that x to the third is x times x times x. So that's also going to be attached to the A. So A is 2x. And if you weren't sure of that, you could test it out like this. 2 times 2 times 2 is 8. And x times x times x is x to the third. So that would give you 8x to the third. And now what is B? We're going to get B from this, right? We already figured out that 27 you get by doing 3 times 3 times 3. So we're going to have 3. But we also have a y cubed here. And you get that by doing y times y times y. So we're also going to have y here. So that's going to be b equals 3y. So now all we need to do is replace a and b in this formula. And remember, we're using difference of cubes this time because we have a minus sign. So we're going to replace a and b with 2x and 3y. And don't forget this 2 right here. This 2 is still in the equation. So we're going to have 2. And then we're going to do all of our replacements. So we're going to have a minus b, that is now 2x minus 3y. A squared, that's 2x times 2x. So let's go ahead and write this out. Remember, we multiplied the numbers and the letters separately. So 2 times 2 is 4. and x times x is x to the 2, or x squared. So we're going to get 4x squared. Now a times b, we have 2x times 3y. 2 times 3 is 6. And x times y, well, you can't multiply those, right? So it's just going to stay as xy. And then b squared, that's 3y times 3y. 3 times 3 is 9. And then y times y is y squared. So this is our final answer. This is the factored form of what we have up here. Here are all 5 main ways to factor explained in just one video. So here's our first example. We need to factor this polynomial. So we're taking this thing that's already simplified and we're trying to turn it into multiple things being multiplied together. And for this case, we're going to be using something called the GCF. GCF stands for greatest common factor. You probably have heard that phrase in like elementary school or something, but here's how it applies to algebra. Basically, we need to figure out a factor that's in common with this first part here and the second part here. And a factor is basically like, for example, if you had the number 8, 8 can be broken down into 2 times 4. And these are factors of 8. So let's go ahead and look at the numbers first. I'm seeing 4 here and I'm seeing 6 here. Well, I'm noticing that these can both be divided by 2. 4 is 2 times 2, and 6 is 2 times 3. So 2 is a common factor between both of these. So let's go ahead and put a 2 on the outside of our polynomial, and on the inside, we're just going to put the same thing, but we divide everything by 2. So 4 is now going to become 2, because 4 divided by 2 is 2. And we're going to leave everything else the same. And then 6 divided by 2 is 3. B to the third. So we've just factored out a 2. And if you're not sure if you did it right, you can just do distributive property, multiply the 2 to both of these, and you should end up with this top part again. Remember, we're basically just doing the opposite of simplifying. So we're done with the numbers here, right? Because 2 and 3, they don't have a common factor. But actually, we can do the same thing with letters. I'm noticing that both of these, this first part and the second part, they both have a b to the third. So we can factor that b to the third out. So we're going to have 2b to the third. And then we're going to take the b to the third out from both of these. So it's just going to become 2a squared plus 3. And this can't be factored anymore. There's nothing to divide out. So this is our final factorization of what's on the top. All right, here's our second example. We need to factor x squared minus 16. Now, there's no common factor here, right? Only one of them has numbers and only one of them has letters. So we're not going to be able to do it that way. But I am noticing that these are both perfect squares. 16 is a perfect square because 4 times 4 is 16. A perfect square is basically any number where you can multiply 2 of the same number to get it. So 16 is 4 times 4. And x squared is also a perfect square because x squared literally just means x times x. So because these are both perfect squares, and because there's a minus sign in between, we can use the creatively named rule, difference of squares. So difference of squares basically says that if you have a squared minus b squared, this is basically just saying we need to have a perfect square on the left and a perfect square on the right with a minus sign in between. If we have this, then we can replace it with a plus b times a minus b. So what are a and b in this case? Remember that because this is a squared, not just a is not going to be x squared. It's going to be whatever we multiplied twice to get to it. So we'll actually look at the 16 first because I think that'll be easier to understand. Remember that 16 is 4 times 4. We multiplied 4 twice to get 16. So b is going to be 4. And in this case, to get x squared, we multiplied x times x. So a is going to be x. So a is x and b is 4. So in this thing that we're replacing it with, all we need to do is replace a with x and b with 4. So instead of a plus b, we're going to have x plus 4. And instead of a minus b, we're going to have x minus 4. And this is our final factorization. This is us factoring x squared minus 16. All right, here's our third example. We need to factor x cubed, that's the word for x to the third, x cubed plus 27. Just like before, there's no GCF because this just has letters and this just has numbers, so we're not going to find something to divide out of both of them. And these are not perfect squares because 27, there's no way to get 27 from like multiplying 2 of the same number unless you use decimals, but no one cares about decimals. But 27 is a special number because it is a cube number. It's not a square number, but it's a cube number because you can multiply 3 of the same number to get to it. You can actually multiply 3 times 3 times 3 to get 27. And x to the 3 is also a cube because you can multiply x times x times x to get to it. So we can use another rule that's just as creatively named as the last one. It's called sum of cubes. Now, I actually have an entire video on sum of cubes and difference of cubes. So if you're not familiar with this, you can actually watch that video that's on the card on the screen. But I'll go over sum of cubes because that's what we're going to be using. You would use difference of cubes if you had a minus sign, but we have a plus sign. And because of that, we're going to use this rule. Just like before, we're going to have that format of a cubed plus b cubed. But this time, it's going to turn into something a little more complicated. It's going to turn into a plus b times a squared minus ab plus b squared. So we need to figure out a and b just like before. In this case, b is not going to be 27. It's going to be what we multiply 3 times to get 27. So 3 times 3 times 3 is 27. B is equal to 3. And in this case, we multiplied x times x times x. That means that a is x. So whenever we see a, we're going to replace it with x. And whenever we see b, we're going to replace it with 3. So a plus b is now x plus 3. And now a squared, that's now x squared, minus ab. There's no sign. That means multiplication. So this is actually a times b. So that's x times 3. You can't multiply a number and a letter, so it's just going to say is x times 3. Or we'll put 3 times x, because numbers usually come before letters. And now plus b squared, that's plus 3 squared. 3 times 3 is 9. And that's it. We have now factored x cubed plus 27. All right, here's another example. We have x squared plus 5x plus 6. No, there's no GCFs we can get out of this, and we can't use the rules from before because those were only when you had something plus something or something minus something. But in this case, we have 3 different parts here. But this may look familiar to you, and that's because if you have 3 parts, one of them has x squared, one of them is x, and one of them is by itself, this is actually in quadratic form. Now, this is another form that I actually already have a video on as well. So if you want to watch that video, it's on the card on the screen, but I'm also going to go over it here. So to factor a quadratic, because we don't have a number in front of x squared, we're going to use the easier version. If you had a number in front of this, you would have to use the x method, and in that video that I put on the card like 10 seconds ago, I go over the x method in that video, but we're going to be using the easier version here. And all you have to do is figure out 2 numbers that add up to the number that's in front of x, so they add up to this, and multiply to get the number that's by itself. So I usually think of numbers that multiply first and then see if they add. So numbers that multiply to 6, well, we have 1 and 6, right? Because 1 times 6 is 6. But if we add these together, we get 7. And that's not what we're looking for. We want 5, right? But 2 and 3 also multiply to get 6. And if we add these together, 2 plus 3, we get 5. And 5 is the number we're looking for. So 2 and 3 are our final numbers. So this is going to look very similar to the other things we factored. We're going to have things in parentheses. We want it to be in this format, x plus something or x minus something in parentheses. And we're going to put in those numbers we just found. Those were 2 and 3, so that's going to be plus 2 and plus 3. And if they were negative numbers, you would put minus instead. And there we go. We have factored this quadratic. So here's the final thing we're going to be factoring in this video. And wow, that is a long one. For this one, we're going to be bringing back some of the things that we did earlier in this video. But you might be thinking, how are we going to figure out anything to do with all 6 of these? Well, for this, we can actually break this into smaller chunks that we can factor. And this is called grouping. Now, grouping is one of these things that you might be asking yourself, like, how did you even figure this out? How did you know how to do this? And honestly, it's just a lot of trial and error. Just experiment with the numbers and see what you can figure out. But the thing that a lot of textbooks do is they'll have something that looks like this. The problem itself will have 4x squared plus 3x squared. And you might be saying, well, can't you just combine these? Because they both have x squared. This is just 7x squared. But normally, if the problem has something like this, if it splits it up, it's probably splitting it up for a reason. So what I'm going to do is I'm going to group this up into this section and this section. And the reason I'm grouping these up is because these all have GCFs that we can factor out. So in this case, we don't have a number we can factor out because this doesn't even have a number in the first place. But we actually have 2 x's in each of these. So we can factor out 2 x's out of each part. So we're going to have x squared times, and then we're going to rewrite this, but we're going to take out 2 x's. So here we had 4 of them, now we're only going to have 2. Here we had 3x to the third. Now we're just going to have 3x to the 1. And then here we had 4x squared. We're taking out an x squared, so we're only going to have 4. Now we're going to put a plus sign because there's a plus sign here. And what GCF can we take out of this group? Well, we can't take out any amount of x's because this doesn't even have an x over here. But we can take out a number. These can all be divided by 3. 3 is 3 times 1. 9 is 3 times 3. And 12 is 3 times 4. So we can take out a 3 out of each of these. So we're going to put a 3 on the outside. And then we had 3x squared. We're taking out the 3. Now we only have x squared. Minus 9x. 9 divided by 3 is 3. So that's 3x. And then plus 12. 12 divided by 3 is 4. And you'll see that now we magically have the same thing in parentheses on both sides. If you're wondering how that magically happened, it's because the textbook writers wanted it to happen. But the problem might not already be in this order. You might have to move a couple of things around to get the perfect groups. So it's going to take a lot of experimenting, but just try to group together parts that can have a GCF that you can take out. So because we have the same thing in both of these parentheses, we can actually combine these. And this is basically the same thing as doing combine-like terms. So if we imagine x squared minus 3x plus 4 all is just one letter, we can combine these by doing x squared plus 3. So we have x squared plus 3 times x squared minus 3x plus 4. I know it seems confusing why you're able to do that, but let me just illustrate with, for example, if you had 4x plus 5x. If you have two of the same variable, you add together what's on the outsides. So 4 plus 5 is 9, you would get 9x. And this is just a more complicated way of saying the same thing. We have the same variable, which is just one big long thing. But because we have the same ones on both sides, we add up x squared plus 3. And then the variable, in this case, this big long thing, stays the same. So this is our final factored form of what's up here. How do you solve quadratic equations that don't look like quadratic equations? Well, you can use a method called substitution. All right, here's the example that we'll be doing in this video. We need to solve for x in this equation, and we need to do it by putting this equation into quadratic form. Now, if you remember solving for x in quadratic equations, you might know that a quadratic equation looks like ax squared plus bx plus c equals 0. Now, if you're not quite familiar with solving quadratic equations, I do have a video on it that you can watch on the card on the screen right now. So you can go watch that and then come back here. But just as a quick review, a quadratic equation always has an x squared part, a regular just x part, and then some number by itself. And then that equals 0. But in this equation, we don't have that. We have an x to the 4th, an x squared, and then a number by itself. So it's kind of similar, but we have bigger exponents. So the only way for us to be able to solve this is to somehow turn this equation into this format. How would we do that? Well, what we're going to do is we're going to create a new variable. And just to make sure we understand, this does say x here, but it doesn't technically have to be the letter x. It can be any letter of the alphabet. It doesn't matter. So what we're going to do is we're going to create a new letter instead of x, and we're going to try to get it into this format. And we're going to use the letter U. If you're not sure why we're using the letter U, I don't know either. It's like a calculus thing or something. You don't have to worry about that. But you could use any letter you want. If you wanted to use Z or F, I don't know. You can use what you want. So what we're going to do is we're going to replace these x's with U, and we're going to set U equal to something. But if you want a fast way to figure out what we need to make U, all you have to do is take the x part that's in the middle of our equation. Obviously, this is assuming that your equation is in order. So like if you had the 12 by itself at the beginning and the x to the 4th in the middle and so on, you'd have to rearrange the equation around from biggest exponent all the way down to smallest exponent. So let me show you what happens when we set u equal to x squared. This means that whenever we have x squared, it turns into u. So for example, here we have minus 4x squared. We're now going to have minus 4 times u. This minus 12 is going to stay the same, and so is the equal 0. But what is this x to the 4th going to become? Well, x to the 4th is the same thing as x squared squared, because x squared is x times x, and then you do another 2 x's, you have 4 x's. And x squared in this case is u. So this is going to become u squared. And if you weren't sure if you did it right, you could always reverse it. So you can turn u into x squared, that's x times x, which is x to the fourth. So you'll see now that we've replaced everything with u's, it looks like a quadratic equation now. We have a squared part, we have just the letter by itself part, and then we have a number by itself with no letter. So we can solve this just like a normal quadratic equation. You can solve this basically using whatever method you want. What I usually do is I try to see if I can solve it using factoring, because that's the easiest and the quickest. And if I can't solve it using factoring, then I use the quadratic formula because it works every time. So let's see if we can factor this. We need to find two numbers that add up to -4 and multiply to get -12. So let's go ahead and figure out what numbers multiply to -12. Well, first of all, if we're ignoring the minus sign for now, we have 12 times 1. That makes 12. And because it's negative, we have to figure out which one of these is negative. It's going to add up to a negative number, which means the bigger number is the one that needs to be negative. Because if we had put the negative sign on the smaller number, then if we add these up, we're going to get a positive number, and we're trying to get -4. So -12 times 1 make -12, and if we add them together, we get -11. We're looking for -4. That's not what we're looking for, so that's out the window. But you can also get 12 by multiplying 6 and 2. And remember, we're trying to add up to a negative number, so we're going to make the 6 negative because it's bigger than 2. And if we add these together, then we get -6 plus 2, which is -4. And that is the number we're looking for. See, -4. So our two numbers are -6 and 2. So what we're going to do is we're going to put it into our factored format, which is two sets of parentheses equals 0. And normally we put x plus something or x minus something, but remember, we're not using x in this case, we're using u. So we're going to put u on both of these, and then we're going to insert our numbers. So -6 was one of them we got, and we also got +2, so +2. And now we're just going to solve this just like normal. So we can split this up into two equations because it equals 0, and if either of these are 0, the whole thing is 0, because anything times 0 is 0. So this is going to become u minus 6 equals 0, and u plus 2 equals 0. And now we just need to solve for u. So on this side, we're going to have u minus 6. We need to do the opposite of minus, which is plus, to get u by itself. And we'll just be left with u equals 0 plus 6, which is 6. And now we do the same thing over here, but we have a +2. We have to do the opposite of plus, which is minus. So we'll subtract 2 from both sides. These cancel, and we'll just be left with u equals 0 minus 2, which is -2. So we've solved for u, but remember that the goal of the problem was to solve for x. Because u wasn't actually a letter in this problem, saying what u equals isn't very helpful. So because we needed to solve for x, we need to turn the u's back into x. And remember that u is equal to x squared. So our u's are going to turn into x squared. So instead of u equals 6, we're now going to have x squared equals 6. And over here we had u equals -2. Now we have x squared equals -2. And now we just need to solve for x. So over here on this side, we have x squared. To get x by itself, we have to get rid of the squared. So we'll do the opposite of squared, which is square rooting. But remember that when you square root both sides of an equation, what you're really doing is plus or minus square rooting. So the squared and the square root cancel, and you're just left with x equals plus or minus the square root of 6. Well, the square root of 6 is not a nice even number, so you can actually just leave it as that, plus or minus the square root of 6. So this is your final answer on this side. And remember, this is actually two answers. It's the positive the square root of 6 and minus the square root of 6. And we're also going to get two answers over here. So there's going to be 4 total answers, which makes sense because the biggest exponent here is 4. And over here, we'll do the same thing. We get rid of the squared by square rooting both sides. And remember that it's plus or minus square rooting. The squared and the square root cancel, and we just have plus or minus the square root of -2. Well, you can't take the square root of a negative number, right? But we can use imaginary numbers to do this. So we'll split this up into the square root of -1 times the square root of 2. Because -1 times 2 is -2. The square root of 2 is a real number, and that'll just stay as it is. And the square root of -1 is the letter I. So we're going to be left with plus or minus I times the square root of 2. Or you could have written that the other way around, plus or minus the square root of 2i. Either one is fine. How do we prove polynomial identities? What even is a polynomial identity? What's a polynomial? So here's our first example. We need to prove this polynomial identity. So first of all, what's a polynomial? Well, our official definition for polynomials is stuff with multiple things in it. So for example, here's stuff, and it has multiple things. So it's a polynomial. Now, what is a polynomial identity? Well, a polynomial identity basically is just telling you that two polynomials, two different things, are equal to each other. So this thing right here is a polynomial identity. It's saying that a plus b squared is the same as a squared plus 2ab plus b squared. And this would also mean that if you came across these in some algebra problem or whatever, you could replace them with each other because they're equal. But we need to prove this polynomial identity, which seems kind of weird because it seems like what's the answer? What are we looking for? Well, actually, there is no answer. The answer basically is the problem. It's telling you what this is equal to. So proving it basically just means do the work, show your work that shows that these are equal. And the way that we do that is we change one of the sides, or sometimes both of the sides, to make both sides exactly the same. That'll show that they're equal to each other. So which of these sides do you think we could change the easiest? Well, this side, I don't really know what we would do to change this. It seems kind of complicated. But this side, whenever I see this, something plus something or something minus something in parentheses and it's squared, I can use FOIL. So remember that when something is squared, that means you're just multiplying it by itself. So a plus b being squared just means that you're doing a plus b times a plus b. And the other side is just going to stay the same throughout all of this. So the first step of FOIL is f, which is first. So we need to multiply the first parts of both of these. A times a is just a squared. Now we need to do outer for o. So the outer parts, in this case, that's a times b, which is just a times b. You can't really multiply those. Then we have I for inner, so we multiply the inner parts. That's b times a, which is BA, or in this case, we'll call it AB because it's similar to this. And then L for last. So we multiply the last parts. In that case, that's the B and the B, which is B squared. And the other side stays the same. And now over here on this side, I'm noticing we have AB plus AB. We are adding like terms. We're adding two parts that have exactly the same letters. So this would be like the same thing if you had X plus X. X plus X is 2X. So we can do the same thing with this, even though we have two letters. So we're going to have a squared plus ab plus ab is now 2ab, and then b squared. And now you'll notice that this side and this side look exactly the same. So because both sides are exactly the same, that means we have proven this identity. And remember that there's no answer you're looking for. You're just looking to make both sides exactly the same. So once you have, that's it. The problem's done and you've proven it. All right, here's another example of a polynomial identity that we need to prove. And yes, it looks a lot more complicated than the last one, but you'll actually be using pretty much the same methods. So if you want to try this one for yourself, go ahead and pause the video and do it, and then unpause and see how you did. All right, so for this one, we're just going to expand and simplify what we're able to. So this part here and this part here, there's not much we can do with those. I mean, we could probably factor them, but I feel like instead of factoring them, it would be easier and faster if we just did FOIL on these parts. So for example, this part here, x plus 2 squared, that's just x plus 2 times x plus 2. And this will stay the same. And I won't rewrite the other side yet. We're just going to leave that for a little bit. We're going to do this side first. So we need to follow the steps of FOIL. So we're going to have first for f, so that's x times x, which is x squared. Then we have O for outer, so that's x and 2. X times 2 is, well, x times 2. And normally you put the number before the letter, so that'll be 2x. Then we have I, which is inner. So another 2 times x, which is 2x. And then we have 2 times 2 for last, which is 4. So this part still stays. And I'm going to move this over because it's getting in the way. So here I'm seeing that we can combine like terms. So you see we have 2x plus 2x. These both have x here, and they have the same exponent, which is just 1 because there is no exponent. So we can add 2x's and 2x's together to make 4x's. So we're going to have x squared plus 4x, because 2 plus 2 is 4, plus 4. And then, like before, this part will stay the same. And you'll notice that this part here looks exactly like this part here. So this means that we're making progress, but this part is still not the same as this part. So what we're going to need to do is do the same thing, FOIL, with this here. So we're going to work on the other side now. and hopefully it will become this. So remember, we're doing FOIL with this, and we need to follow the steps of FOIL. So remember that we're splitting this up because a squared just means you're multiplying it by itself. So this part is going to stay the same. And then x minus 1 squared just means x minus 1 times x minus 1. So we have first for f, x times x is x squared. Then we have outer, so that's the outer ones, x and minus 1. Don't forget the minus signs, right? So minus 1 times x, well, anything times 1 is itself. So we have just x, and then the minus sign stays. So minus x. Then inner, that's going to be the same thing, minus 1 times x, so that's just minus x. And then last, minus 1 times minus 1. 1 times 1 is 1, and then two negatives make a positive. This part is going to stay the same, just like before. And then we have like terms here. We're subtracting an x and then subtracting another x. So in total, we're subtracting two x's. So we're going to have minus 2x plus 1. And now both the left side and the right side look exactly the same, as you can see here. So that means we have successfully proven this polynomial identity. And remember, there's no answer, it's just showing that they're equal. Are you tired of solving f of x problems? Do you want to solve f of x problems in a different way that basically takes just as much work? Well, I present to you synthetic substitution using the remainder theorem. So here's the first example we'll be doing in this video. We need to solve for f of 3 when f of x is this. Now, the normal way to solve an f of x problem is to plug in what's in the parentheses, which is 3, into x and see what you get. And I do also have a video on that you can watch on the card up there. But let's say you were lazy and you were like, I don't want to do all of that. Or, let's say you had like something to the 6th power and you were just like, that's a lot of work. Well, it's a good thing that we have a rule called the remainder theorem. And the remainder theorem basically says that if you use synthetic division on this polynomial right here, then you will get the answer as the remainder. So you would do synthetic division, but with 3 inside the box. And once you do it, you will do all of the work and whatever, and then whatever number you have as your remainder is going to be the same as if you had just plugged in 3 for x. And doing all of this weird stuff, this is called synthetic substitution. So for this video, it would help if you already knew how to do synthetic division. So if you don't already know that, I have a video on it that you can watch on the card on the screen right now. But I'm also going to go over it here so you can understand it from here. So what we need to do is we need to lay out our synthetic division problem. So in the box, because we're not dividing by anything, what we're technically dividing by is x minus 3. But you don't even need to know that. You just need to know that this number here goes in the box. So 3. Then we're going to lay out the beginning numbers of each of these. So x to the 3rd, there's no number in front, which means it's 1. So we're going to put 1. Then we have minus 2, because remember the minus signs stay. Then positive 5, and then negative 7. Then we're going to draw a line underneath, and another line here, and this is going to be where our remainder is. Remember, we don't care what goes here. We're only going to care about our remainder, because that's going to give us our answer, according to the remainder theorem. I know, creatively named. So we're just going to bring down this 1, and we're going to multiply it by what's in the box. So 1 times 3 is 3. Then, to bring down our next number, we have to add these two numbers together. So negative 2 plus 3, that's the same thing as 3 minus 2, which is 1. And then we repeat the process. So we have 1 here, we multiply it by what's in the box. So 1 times 3 is 3. And then we add them together. 5 plus 3 is 8. Then we multiply by what's in the box. 8 times 3 is 24. And then we add them together. 9 is 7 plus 24. That's the same thing as 24 minus 7, which is 17. So in a normal synthetic division problem, you would lay this out like, oh, this is x squared, this is x, this is by itself, whatever. We don't care about any of that, right? Because this is the remainder theorem. And the remainder theorem says that our remainder is our answer. So our final answer is that f of 3 is equal to 17. And there you go. And if you weren't sure if you were right, you could also plug in 3 into x and see if you get 17. All right, here's another example. Go ahead and pause the video, try to solve this one for yourself, and then unpause and see how you did. All right, so normally what we would do is we would take this minus 2, plug it in for x, and see what we get. But instead, we're going to use the remainder theorem and synthetic substitution. So we're going to take this minus 2 and put it in our synthetic division box. And then we're going to lay out the beginning numbers of each of these. So we're going to have minus 2, 5, And then don't be quick to do minus 1, because you might notice that we went from x to the fourth, x to the third, and then we just went straight to x. We missed x to the 2, or x squared. So because we missed something here, we have to put a 0 in its place. Then we go on to x, which is minus x. There's no number in front, so that makes it 1. And there's a minus sign, so it's minus 1. And then finally 3. Then we're going to draw our fancy line underneath and a line here to show where the remainder is going to be. So we're going to do it the same way. We're going to bring down our first number, which is minus 2, and we're going to multiply it by what's in the box. So minus 2 times minus 2. 2 times 2 is 4, and 2 negative signs make a positive, so it's positive. Then we add these together, so 5 plus 4 is 9, and we repeat the process. So 9 times a negative 2, 9 times 2 is 18, and there's one minus sign, so the minus sign carries over. 0 minus 18, this 0 is not doing anything, so it's just minus 18. Then we multiply by what's in the box. 18 times 2 is 36, and of course, if you weren't sure of that, you could put it in your calculator. And 2 negatives make a positive, so it's positive. Then we have minus 1 plus 36. That's the same thing as saying 36 minus 1, which is 35. And then one more time, we multiply by what's in the box. So 35 times 2 is 70, and we have one minus sign, so the minus sign stays. And then we have 3 minus 70. You could put this in your calculator, you'll get minus 67. So our final remainder is minus 67. And remember that the remainder theorem says that whatever you have as your remainder is the answer. So f of negative 2 is equal to minus 67, and that's our final answer. Here's how to use the factor theorem to find, well, factors. All right, here's the example problem that we'll be doing in this video, and I know this is a lot to look at, but let's break it down. First, we need to determine if x minus 2 is a factor of this polynomial here. Remember, a polynomial is just an equation, but without an equal sign. So we first need to figure out if x minus 2 is a factor, and then we have to find the rest of the factors if it is a factor. So to figure out if x minus 2 is a factor, we can use something called the factor theorem, which is basically just a fancy name for the rule that if you use synthetic division on this equation, so if you divide it by x minus 2, and your remainder is 0, then this is a factor. So if you don't quite remember how to do synthetic division, I have a video on it that you can watch on the card on the screen right now, but I'll also quickly go over it here. So the first thing that we need to do synthetic division is we need to take this factor, this smaller part that we're dividing by, take the number that's right here, including its sign, and then switch the sign and put it in a box. So because this is minus 2, we're going to take positive 2 and put it in a little box here. If this was x plus 2, we'd put minus 2 in the box. Then we're going to lay out the rest of the numbers, the beginning numbers in front of x, right next to the box. So this first one here, there's no number in front, which means it's 1. So we're going to put 1 here. Then we're going to put 3. Then we put not 4, negative 4, because the minus signs stay. And then negative 12. Then we're going to draw another line underneath and a line right here. And this is going to be where our remainder is. And this is the important number, because remember, this needs to be 0 according to the factor theorem. This needs to be 0 for x minus 2 to be a factor. And then I'll show you what we do next. But if this is not 0, then x minus 2 is not a factor, and we can't do anything else. The problem's over. So we're going to take this first number here, 1, and we're going to drop it down. And then we multiply and add, and multiply and add, and multiply and add. So first multiply. We multiply by what's in the box. 1 times 2 is 2. And then we add these up. So 3 plus 2 is 5. And then multiply and add. So multiply, 5 times 2 is 10. And then add minus 4 plus 10. That's the same thing as 10 minus 4, which is 6. 6 times 2 is 12. And negative 12 plus 12, again, that's the same thing as 12 minus 12, which is 0. So we have 0 here as our remainder, which means that x minus 2 is a factor. So that means that we can write this equation here, or this polynomial, we can write this as x minus 2 times something. How do we figure out what this something is? Well, actually, our clue to it is right here. If you know from doing regular synthetic division, when you're writing out your answer, this number is going to be by itself, and then you add an x, each one to the left. So 6 is by itself, 5 is going to be our x term, 1 is going to be x squared, And if you had more numbers, it would be x to the third, x to the fourth, and so on. So this is going to be 1 times x squared, or you don't have to include the 1 when it's 1. So it's just going to be x squared. Then we're going to have plus 5x plus 6. So we have successfully factored x minus 2 out. So yes, x minus 2 is a factor. So we've successfully done the first part of this problem, which is to determine if x minus 2 is a factor. It is. It's right here. But it says we also need to find the remaining factors. Now, sometimes that's just going to be it. The other factor here is x squared plus 5x plus 6. But sometimes you can actually factor this part as well. So you always need to check to see if you can factor it first. And sometimes you won't be able to, but sometimes you can. So how do we see if we can factor this? Well, if you're not familiar with factoring, I also have a video on that you can watch on the card on the screen if you want. But I'll also go over it here. Remember, you need to find two numbers that add up to the number for an x, in this case that's 5, and then you need to multiply to the number that's by itself. In this case, that's 6. So what are two numbers that multiply to 6? Well, first of all, 1 times 6 is 6, but if you add them together, you get 1 plus 6 is 7. And 7 is not the number we're looking for. We're looking for 5. So what other numbers multiply to 6? Well, 2 times 3 is 6, and if you add them together, you get 5. Which is the number we're looking for. So 2 and 3 are our numbers. And remember that your two numbers that you get from factoring, you put them in parentheses with x. And if these were negative numbers, we would put x minus the numbers. But since they're both positive, we're going to put plus 2 and plus 3. So this is the factored form of x squared plus 5x plus 6. But remember that this x minus 2 is still here. That hasn't changed. So we're going to put that at the beginning still. And there we go. We have found the remaining factors of x to the third plus 3x squared minus 4x minus 12. And if you weren't sure if you were right, you can check your work by multiplying these together, and you should end up coming back to this big long thing. Here's how to use Descartes' rule of signs and how to make those big scary tables you've probably seen. So here's the example that we'll be doing in this video. We need to use Descartes' rule of signs on this big long thing. So what is Descartes' rule of signs? Well, it's basically just a way of predicting the kinds of answers that we would get if we solved for x. And if you're wondering how we would even solve for x, because it's not even an equation, we're talking about if it equaled 0. This is why your homework probably talks about finding the types of zeros. Zeros are just a fancy way of saying the answers. So they're called zeros because it's where it equals 0. So we could graph this and find all the zeros, but that would take forever. So instead we can use Descartes' rule of signs to determine the possible list of positive answers, negative answers, and imaginary answers that we could have. So like I just said, there's 3 types of answers we can get. So there's positive real answers, there's negative real answers, and then there's imaginary answers. Now the important thing to note here is that the amount of answers we're going to have is always the biggest exponent. So what's the biggest exponent here? Well, it looks like it's right here, right? 6 is our biggest exponent, which means that in total, we have to have 6 answers, or in this case, we're going to call them zeros. So when we're talking about our different combinations of zeros, they have to equal 6. So we could have 4 positive real ones, 2 negative real ones, and no imaginary, or they could all be imaginary. Who knows? So how do we figure out how many of each we have? Well, we're not going to figure out exactly, but we can figure out a list of the different possibilities. So to find out how many positive answers we have, or positive real answers, we need to figure out how many times the sign changes. So first of all, remember that this first term here is positive because there's no negative sign on it, so that means it's positive. So we're going to see how many times it changes. Does it change here? Nope, no change, right? What about here? Yes, it changes from positive to negative. So we have our first change. What about here? Nope, doesn't change, right? Here, it does change. It goes from negative to positive. So that's another change. What about to here? Yes, it changes here as well. And then finally, what about here? Yep, it changes here as well. So here's the important part of Descartes' rule of signs. Descartes' rule of signs says that for every time the sign changes, that's how many positive real answers you can have. Or you can decrease that by an even number. I know that doesn't make much sense, but here, I'll explain it. So we had 4 sign changes, which means it's possible that we have 4 positive real zeros. Or in this case, that just means positive answers, like 3 or 7. But we might not have 4 of them. We can decrease this number by 2 and still have a possible amount of zeros. So we could have 4. We could also have 2. Or we could also subtract this by 2 again and have 0. So we could have 4 positive answers, we could have 2 positive answers, or we could have 0 positive answers. You always keep subtracting the number by 2 for your different possibilities. So, for example, we're not going to have 3 positive real zeros. That's not possible because you would have to subtract 4 by 1. You have to keep subtracting by 2. So, like, for example, if the sign changed 5 times, then you could have 5 positive real zeros. You could also have, if you subtract this by 2, 3 positive real zeros, and you could also have 1 positive real zero, but you cannot have like 2 or 4. Now that's just for positive real zeros. How about for negative real zeros? That's just a fancy way of saying negative answers. So like -2 or -400. So to figure out negative real zeros, we need to figure out how many times the sign changes, just like before, but with negative x in place of x. So I'm going to show you the technical way to do this and then kind of a shortcut that you can use that's basically the same thing. So we need to replace x with negative x. So instead of x to the 6th, we're going to have negative x to the 6th. Instead of plus 4x to the 5th, we're going to have plus 4 times negative x to the 5th. And we're just going to repeat this all the way down. So how on earth do we know what negative x to the 6th is? Well, let's go ahead and write it out, right? We're going to have negative x 6 times. So it's going to be negative x times 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 negative. So remember that 2 negatives make a positive. So we're going to have negative x times negative x. Well, x times x is x squared. And 2 negatives make a positive. So that means this is x squared, and this is x squared. And now we just have all positive numbers. So 2x's times another 2x's times another 2x's, that's going to be a total of 6. So it just didn't change from before. So this is x to the 6th, just like it was before. But what if we had x to the 5th? Well, in that case, we're taking away one of the minus x's, right? We're only going to have 5 of them now. And remember, minus x times minus x, that's x squared, positive x squared, because 2 negatives make a positive. And same over here. But this minus x is going to stay. So we end up having 5 x's, so that's x to the 5th, but 1 minus sign, so the minus sign stays. So in this case, we're actually going to have negative x to the 5th. And this would be the same thing as if we just moved the sign out to the front, because remember, these are being multiplied together. And 1 negative stays when you multiply. So this is going to be negative 4 times x to the 5th. And you'll notice that this looks exactly the same as this, except we switched the sign. So here's the shortcut that I was talking about. Whenever you have an even exponent like this, the negative signs are all going to cancel out and it's just going to stay exactly the same. But if you have an odd numbered exponent, then it's all going to stay the same, except you're going to be left with a negative sign. So what that means is whenever you have an even exponent, like this one, negative 2x to the 4th, it just stays the same. So that's going to be negative 2x to the 4th. And whenever you have an odd exponent, you know it's going to leave a negative sign. So you're going to have to change the sign. So negative 3x to the 3rd becomes positive 3x to the 3rd. So technically, you don't even actually need to do any of this stuff here. I just showed you that because it's helpful to know what it is you're doing. But this is a shortcut that will basically do the exact same thing. So plus 7x squared, 2 is an even number, so it's going to stay the same. Minus x, remember this is technically x to the 1. And 1 is an odd number, so this is going to change the sign to positive x. And then plus 1, there's no x here, so that means it's to the 0, and 0 is an even number, so plus 1 stays the same. So now that we have our new polynomial here, now that x has been changed to negative x, we can now figure out how many times the sign changes and get our negative real zeros. So does it change here? Well, yes, it does actually, because this is a positive number here in the front, and it turns into a negative number. So yes, it does change. What about here? Nope, it was negative here, and it's still negative, right? What about here? Yes, it does, right? It was negative, and now it's positive, so that is a yes. What about here? Nope. It's a plus, and it's still a plus. So, nope. What about here? Nope, it's still a plus, right? And then what about here? It's still a plus, so no. So we have 2 sign changes, which means we can have 2 negative real zeros, or remember, you can subtract the number by 2 and get another possibility. So 2 minus 2 is 0, so we could also have 0 negative real zeros. And these are our only two possibilities. We can only have either 2 or 0. We're not going to have 4. You can't add 2 to it to get other possibilities because we only change the sign twice. So now our last possibility that I was talking about is imaginary zeros. But there's actually no rule of changing signs to figure it out. Imaginary zeros are just going to be whatever zeros are left over when we're done with our positive and negative ones. Because remember that we know we have to have 6 zeros or 6 answers. So for example, if we found out that there are 2 positive real zeros and no negative real zeros, well, that only adds up to 2. We know we have to have 6 of them, so the other 4 must be imaginary. So here's what we're going to do. Using this information that we just found out about here, we're going to make a table. It's going to be a list of all the different possibilities of answers that we can have. So we're going to have positive answers, we're going to have negative answers, we're going to have imaginary answers, which I'll put I for imaginary, and then we're going to have our total amounts. Now remember, for every possibility, we're always going to have a total of 6 answers every time. That's not going to change. Now we can have either 4, 2, or 0 positive zeros. So we're going to write 4, 2, and 0 on our table. But you might be wondering why I'm spacing these out, and that's because we also need to write our negative real zeros, because we can have 2 of them or we can have 0 of them. So for every single one of our possibilities for positive, we need to write our possibilities for negative. So we can have 4 and 2. We could also have 4 and 0. We can have 2 and 2. We could also have 2 and 0. We could have 0 and 2. We can also have 0 and 0. If you're not sure if you have the right amount of rows, a good way to check is to see that there are 3 possibilities here and 2 possibilities here. And if you multiply them together, 3 times 2 is 6. So we have 6 rows here. We need to have 6 rows for our table. So these are all the different possibilities for our positive and negative answers. And remember that they're always going to total to 6. So every row is going to have 6. So our last step here is to figure out how many imaginary zeros we're going to have in each case. So here we have 4 positive and 2 negative. 4 plus 2 is 6. So that's all of our 6 answers. So if we had any imaginary answers, that would put us over 6, which is, we only have 6. We know that. Which means in this case, we have no imaginary answers. What about here? This row here, we have 4 positive and 0 negative. That only totals up to 4. We need 6 in total, which means 2 of them must be imaginary so that we can have a total of 6. Now what about here? We have 2 positive and 2 negative. 2 plus 2 is 4, so we only have 4 answers. We need to have a total of 6. So 2 of them must be imaginary. Now here we have 2 positive and 0 negative. That's only 2 answers. We need to have 6. So how many must be imaginary? 4. We need to have 4 imaginary ones to make up for the lack of answers. And it's the same thing here. Here we have no positive and 2 negative. We need to have 4 imaginary answers to have a total of 6. And finally, our last possibility is that we literally have no positive or negative answers. We just have no real answers, which means all 6 of them would have to be imaginary. So, what's our answer? This whole thing is. This whole table is our answer. This is our table of possibilities. If you wanted to find out which one it actually is, well, you would have to graph this and figure out all the zeros yourself. But Descartes' rule of signs is basically just a way of figuring out the different possibilities. So what this tells you is that, for example, you would never have 3 positive, 1 negative, and 2 imaginary. You would not get these answers from this equation because it's not in the list of possibilities according to Descartes' rule of signs. So this table is our final answer. Here's how to use the complex conjugates theorem to write a polynomial function of least degree with integral coefficients having the given zeros. What? Well, here we go. We're going to do exactly that. But let's go ahead and break down what it is we're even looking at. So first of all, it says write a polynomial function. Well, that just means to write any polynomial. So, x squared plus 2x plus 5. That's a polynomial. Then it says of least degree. So basically, we need to write the least complicated polynomial we can. Degree in this case means the biggest exponent. So for example, if we were to write an equation with x to the 72 plus da 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 da, but we could write the same thing with x to the any lower number, then we did it wrong. We have to get the lowest number possible. Then it says with integer coefficients, which basically just means we can't have decimals or fractions, which honestly makes our lives easier. And then finally, it says it needs to have the given zeros, which are these. Now, how do we use these zeros to our advantage? Well, for that, we're basically going to think of something like factoring, but the opposite way. If you know about factoring, you may know that when you factor an equation, like for example, if we had x squared plus 5x plus 6, if you were to factor this, and I won't go through the whole thing, but if you were to factor it, you would factor it into x plus 2 times x plus 3. And then you would split these up, and from there, you would get two zeros. Zeros are basically just a fancy way of saying your answers. But we can actually think of this the opposite way. If we have our zeros, we can turn them back into these little equation things here, these little polynomials. But I did talk about something called the complex conjugates theorem, which is just my favorite rule to say. The complex conjugates theorem says that if you have any zero that's part real and part imaginary, that's where the word complex comes from. Complex means part real, part imaginary. Like this one here. This one has a real part, which is 3, and it has an imaginary part, which is I. It says that if you have a part real, part imaginary zero, then it's going to have the same zero, but with the sign changed. So if it has 3 plus I as a zero, it must also have 3 minus I as a zero. This is required. You can't have one and not the other. So we know that these are the three zeros that our polynomial function of least degree with integer coefficients must have. So we're going to work backwards and take these zeros that we already have and turn them into those little factored parenthesis things. So for example, we have 4 here. We always do the opposite sign. So this is going to be x minus 4. And the reason for that is if you were to split these up and turn this into x minus 4 equals 0, then if you added 4 to both sides, you would get x equals positive 4. So we can do the same things for these. Even though they're a little bit complicated, we can have x minus 3 plus I. And it's important that we put this in parentheses because the minus sign applies to both of them. Well, you'll see why in a second. And then this is going to be times x minus 3 minus I. So what I'm going to do is I'm going to distribute the minus sign to both the 3 and the positive I in this case, and then to the 3 and the negative I in this case. Because remember, a minus and then something in parentheses means distributive property. We have to distribute to both. So we're going to have minus to the 3 and minus to the I. So we're going to have x minus 3 minus I. And then over here, we're going to distribute the minus sign as well. So x minus 3 and minus negative I. So we're going to have x minus 3 and then minus minus I. Two negatives make a positive, so that's going to be plus I. And now here's where a lot of people get stuck. It seems like what am I going to do here? And you could just multiply all this out, and it would take a really long time. But I'm going to show you a little shortcut. So for this, you're just going to kind of have to trust the process and see why I'm doing this in a second. But I'm going to put parentheses around x minus 3 on both of these. We're going to leave x minus 4, and we're going to do FOIL on this first. So remember that for FOIL, you have to follow the steps of FOIL. So the first step of FOIL is f, which is first. So we need to multiply the first parts of both of the parentheses. In this case, x minus 3, I put parentheses around it because we're treating it as one thing. So we have x minus 3 times x minus 3. We don't have to multiply that right now, actually. We can just leave it as x minus 3 squared, because squared just means multiplying it twice. Next, we have outer, which is O. So we need to multiply the outer parts. So we're going to have x minus 3 times I. I don't really feel like multiplying x minus 3 times I, so I'm just going to leave it as I times x minus 3. And you'll see why I'm doing that in a second. Then we need to multiply the inner, which is I. So that's going to be minus I times x minus 3. Remember that minus signs always stay. So this is going to be minus I times x minus 3. I'm not going to bother multiplying it just like before. And then finally we have L, which is for last. So we have minus I times plus I. I times I is I squared. And then we have one minus sign. So the minus sign stays. So you might think that we've made this more complicated than before. But I'm going to show you why we put parentheses around x minus 3. It's so that we could get this. Do you see what's special about this? We're adding I times x minus 3. And then we're just subtracting the same thing again. If you add something and then just subtract it again, you've done absolutely nothing. So this actually all cancels out. We don't even have to multiply this together. So the x minus 4 is going to stay just like before. And then we're going to have x minus 3 squared minus I squared. And see, this is now simpler than before. Now, this may still be a little bit confusing because we do still have i's in here. But remember that I squared is actually special. Now, if you're not quite familiar with imaginary numbers, I do have a full video on it that you can watch on the card on the screen right now. But the thing you need to know is that I is the same thing as the square root of -1. But this is I squared. So we have the square root of -1 squared. But you may also realize that a square root and a squared do the exact opposite things. So these actually cancel out, and all we have left with is -1, which is a real number. So everything else is going to stay the same. And then we're going to have negative I squared is now -1. So -1, we have two negatives here, that makes positive. So we're going to have +1. So now we've gotten rid of all the i's. We don't have any more imaginary stuff. It's all real, so we can just simplify this. So the first thing to simplify is probably the x minus 3 squared. Remember that squared means you're multiplying it by itself. So x minus 3 squared is the same as x minus 3 times x minus 3. And for this, we can use FOIL again. So we're going to do first. The first step means to multiply the first parts. So x times x is x squared. Then outer, so we need to multiply the outer parts. So that's x times, not 3, -3. Remember, minus signs stay. We can't multiply a number and a letter, so we're just going to leave it as 3 times x. Then we have inner, so we multiply the inside parts. That's -3 times x, which just like before is just -3x. And then finally we have last, so we're multiplying the last parts. That's -3 times a -3. 3 times 3 is 9. And then we have two negatives. Two negatives make a positive. And then these we can just combine, because you can combine like terms. That's the fancy name for this. So we have x squared minus 3x minus another 3x. That's a total of minus 6x. And then plus 9. So instead of x minus 3 squared, we're going to put what we just solved here. X squared minus 6x plus 9. But then don't forget this plus 1 here. We also have a plus 1 here. And we can combine these. This is just 9 plus 1, which is 10. So we're going to replace that with 10. So there you go. We've done FOIL on this, and all we have left to do is multiply these two together. So the way I like to do this is to do them as two individual problems and stack them. So we need to do distributive property with the x. So we need to multiply the x to all three of these. And then we need to do the same thing with the -4. We need to multiply the -4 to all three of these. So let's do it with the x first. X times x squared, well, that's 2x's times another one. That's a total of 3. So we're going to have x to the third. Then we're multiplying x times minus 6x. That's just adding on another x. So it's going to be minus 6x squared. And then we're multiplying the x to the 10. You can't multiply a number and a letter, so it just stays by itself. 10 times x. Now we're going to multiply the, remember, not the 4, the minus 4 to all three of these. And I'm going to do it on the line below. So -4 times x squared, you can't multiply those, so it just stays the same. -4 times x squared. And I'm going to lay it under this other x squared. Then we do the -4 times the minus 6x. 4 times 6 is 24. We have two negatives. Two negatives make a positive. And then we have an x, so the x stays. And then finally, -4 times 10. 4 times 10 is 40, and one negative sign, so the negative sign stays. So now all we have to do is add these two together to get our final answer. So x to the third, that's just by itself, so x to the third. Then we have minus 6x squared minus 4x squared. We can think of this as dollars. We lost $6, then lost another $4, so we're down $10. Then we have 10x plus 24x, 10 plus 24. You could put in your calculator if you wanted to, 34x. And then this minus 40 is by itself, so it stays as minus 40. So this right here is our polynomial function of least degree with integer coefficients and the given zeros. So this is our final answer. Here's how to add, subtract, multiply, and divide functions explained in just one video. So here's the first example we'll be doing in this video. We have to find f plus g of x. So you've probably heard of f of x before and g of x. They mean the same thing. They're both just functions. So they're like an equation here. So whenever you see f plus g of x, that just means that you need to add the functions together. So what is f of x? Well, f of x is 3x minus 2. So we're going to put 3x minus 2. and we'll put it in parentheses. When we do later problems, you'll see why. And then we need to add g because it's f plus g. Well, g in this case is 5x plus 1. So we're going to add 5x plus 1. So when you're adding these together, the parentheses don't really matter because you can add in any order. So we can actually just ignore these parentheses and add together the parts with x and add together the numbers by themselves. First, let's look at the x's. We have 3x plus 5x. 3 plus 5 is 8, and the x stays. And then here we have not 2, minus 2. The minuses always stay. We have minus 2 plus 1. Well, think of this as dollars. You lost $2 and you got 1 back, but you're still down $1. So minus 1. And that's it. We have added together the functions. So we've just found f plus g of x. Now here's another example. This time we need to subtract functions, and this time we're doing g minus f. So we're going to set this up the same exact way as before, but with a minus sign. But instead of putting f first, we're going to put g first, because g is first in this, g minus f. So we have 5x plus 1 for g, and then minus, because we're subtracting, f, which is 3x minus 2. Now here's why we had to put these in parentheses earlier, because with subtracting, the order matters. And if you want to think of this like distributive property, the minus is being distributed to both parts in parentheses. So we can rewrite this without the parentheses, but we need to distribute the minus sign. So the 5x minus 1 is going to stay like normal, and then we're going to apply the minus sign. So minus 3x, that's minus 3x. And then we have minus 2. Because this already has a minus, adding another minus turns it back into a plus. So we're going to have plus 2. Now we can just add the parts with x and add the parts by themselves. So we have 5x, not 5x plus 3x. This minus sign here is here, right? So 5x minus 3x. 5 minus 3 is 2, and the x stays. And then we have minus 1 plus 2. That's the same thing as 2 minus 1. 2 minus 1 is 1. So that's plus 1. And there we go. G minus f of x is 2x plus 1. All right, now we need to multiply these functions. And it's going to get a little bit harder, but it's going to be kind of the same principles. So to multiply these, we need to take f, which is 3x minus 2, and it's being multiplied by 5x plus 1, which is g. And remember that to multiply two binomials, just the fancy way of saying something in parentheses with two parts, we need to use something called FOIL. So the first step of FOIL is f, which stands for first. So we need to multiply the first parts here. 3x times 5x. Well, 3 times 5 is 15. And then it's x times x, which is x squared. Now we need to do outer, which means we're multiplying the outer parts. So we have 3x times 1. Well, anything times 1 is itself, so that's just 3x. Then we have I, which stands for inner, so we need to multiply the inner parts. So we have negative 2 times 5x. Well, 2 times 5 is 10, and then the x stays. And then we have 1 minus sign, so the minus sign stays as well. And then finally we have L for last, so we need to multiply the last parts. So we have negative 2 times 1. Anything times 1 is itself, so that's just going to be negative 2, or minus 2. And now I'm noticing that we have two parts here that have an x. That means we can combine them, which is called combining like terms. We can't also combine the one with x squared because x squared is different from just x by itself. So we have plus 3x minus 10x. If you want to think of this as dollars, we had 3, and then we lost 10, so we're down 7. So minus 7x, and then minus 2 stays. So here we go. This is our final function for f times g of x. And now finally, we need to divide functions. So we need to find g over f of x. And remember that fractions are the same thing as division. So you could also say this as g divided by f. So we're going to write this the same exact way. We're going to write it like this, except instead of g, we're going to put 5x plus 1. And instead of f, we're going to put 3x minus 2. Now, there's actually nothing else we can do to simplify this, because if you were to divide something out, you'd have to factor something out of the top and the bottom. It would have to come out of all these parts, and you can't do that with this. Now, if you had some like x squared or x to the third thing in the top, then there's a chance you could actually divide them using long division. But in this case, we can't do that. But there's one more thing we need to do. With all the other ones, we could put in any number for x. It doesn't matter what we put in. But there's actually one number that we can't put in for x in this. Can you figure out what it is? We'll look at the bottom here. If we put in a certain number for x that made the bottom of the fraction 0, we would be dividing by 0. And we can't divide by 0. So let's go ahead and figure out what number we can't put in for x. Remember, we can't put it in for x if it makes the whole bottom 0. So if 3x minus 2 is equal to 0, then the bottom is 0. So let's go ahead and solve for x here and see what we get for x. So to get x by itself, we have a minus 2 here. We'll do the opposite of minus, which is plus. We'll add 2 to both sides. These cancel out, and we're just left with 3x equals 0 plus 2, which is 2. And now we're just left with multiplication. So we need to do the opposite of multiplication, which is division. So we'll divide both sides by 3. These cancel out, and we just have x equals 2 divided by 3, which is, well, 2 over 3. Nothing you can really do about that, right? So if we put in 2 over 3 for x, then we're going to get 0 on the bottom, and we're going to have an impossible equation. So even though this right here is our final answer, because there's nothing we can do, we also have to add that we can't have x equal 2 over 3. So we're going to put this little not equal to sign. But yeah, there's nothing else we can do. So this is our final answer for g over f of x. Have you ever had a dream where you're just dreaming, but then you wake up from the dream, but then it turns out that was all just part of the dream and you were dreaming inside a dream? Well, that's basically what composite functions are. So here's our first example. We need to solve for whatever this is. What is this, like fog of 3? Like, what is that? Well, this symbol here, this is an open circle, right? It's a circle that's not filled in. This actually means composite. What is a composite? Well, you may already know how to solve for just f of x, right? Like if this was f of 3, for example, this would mean that we just plug in 3 into x plus 2 for f of x, and then we get 3 plus 2, which is 5. But in this case, we have a composite. And what that means is we need to put functions inside of functions. So in this case, how you would read this is actually f of g of 3. So instead of just having a number inside of the parentheses for f of x, we now have an entire function inside of the function. So how are we going to solve this? Well, all we need to do is figure out what g of 3 is, just like normal. Then we will have a number that we can put in for f of x, and we will get our final answer. And you can tell that we're supposed to do g of 3 first before f, because g of 3 is inside the parentheses. And remember, things in parentheses always come first in any kind of math. So remember that here it says g of x, but here it says g of 3. We replaced x with 3. So on this side of the equation, we have to do the same thing. So instead of x, we're going to put 3 minus 1. And 3 minus 1 is 2. So in this case, g of 3 is equal to 2. So let's go back to here. Remember we said that f composite g means f of g of 3. So let's go ahead and write that. But we just found out that g of 3 is 2. So we can change this to f of 2, because g of 3 is 2. So in this case, we're going to use this top equation because this is f, not g. We are replacing x with 2. So we're going to do the same thing on the other side. Instead of x, we're going to put 2 plus 2. And 2 plus 2 is 4. So in this case, f composite g of 3 is equal to 4. So that's our final answer. Here's another example. What I'd like you to do is go ahead and pause the video, try to solve this one for yourself, and then unpause and see how you did. All right, so in this case, we have a little bit more complicated functions, but it's fine. We're going to do it the same way. But also the thing that's different is instead of fog, we now have goff. So remember, we're going to read this as g of f of negative 2. And f of negative 2 is going to be what's inside our g function. So to be able to solve this, what we need to do is figure out f of negative 2 first, and then whatever we get from that, we will plug back into g and get our final answer. So let's go ahead and figure out f of negative 2. We have replaced x with negative 2. So on this side of the equation, we need to do the same thing. So instead of x, we're going to put negative 2. And notice how I'm putting it in parentheses. The reason for that is because if we didn't put parentheses, then we would have 2 squared, and then we'd be applying the negative sign. Basically, we need to put it in parentheses to show that all of x is being squared, not just part of it. And then plus 1. So let's go ahead and solve this. Negative 2 squared, well, 2 times 2 is 4, and 2 negatives make a positive. So it's going to be positive 4, and 4 plus 1 is 5. So in this case, f of negative 2 is 5. But remember, that's not our final answer. That's just what's going to be inside of g, because now we need to figure out g of f of negative 2. But in this case, we just found out that f of negative 2 is 5. So instead of f of negative 2, we're just going to put 5. So now we can solve for g of 5. And in this case, we're going to use this bottom equation because this is g. We used f last time. So g of 5 means we're going to be replacing x with 5. So in this case, we have 2 times 5 and then minus 3. 2 times 5 is 10 minus 3, and 10 minus 3 is 7. So there we go. We found our final answer. G composite f of negative 2 is 7. Here's how to find the inverse of a function. So here's our first example. We need to find the inverse of this function, or f of x. Now, the important thing to note before we start finding the inverse is that f of x is basically the same thing as y. Like if you were to graph this, you would have an x and a y value, right? So f of x is basically just the same thing as y. So we're going to rewrite this as y equals 2x plus 2. And the reason we're doing that is because the next step of finding the inverse is to switch the letters. So y is going to become x, and x is going to become y. So instead of y, we're going to put x equals 2 times y plus 2. Now, technically, this is already an inverse equation, but we need to write it as a function, which means that we're putting y by itself, just like it was up here. So we need to get y by itself using algebra. So we can get rid of either this 2 next to y or this 2. I usually get rid of the 2 that's less attached to y. So we have addition here, so we need to do the opposite of addition, which is subtraction. So we'll subtract 2 from both sides. These cancel out. And on this side, we just have 2y equals, and then we just have x minus 2. You can't subtract a number and a letter, so it's just going to stay as x minus 2. And now to get y by itself, all we have is multiplication, because there's no sign in between. So we need to do the opposite of multiplication, which is division. So we'll divide both sides by 2. These cancel out, and on this side, we just have y. And now on the other side, this might be a little complicated, but remember we need to divide out from the x and from the 2. So first x divided by 2, well, you can't divide those, so it's just going to be x over 2. Or another way to write that is actually 1 over 2 times x. But you could also just put x over 2. That's fine as well. And then we have minus 2 divided by 2. 2 divided by 2 is 1. So we now have y by itself, and this is what y equals. So the final step of writing this as an inverse is to change y back to f of x. But because this is an inverse, we actually have a special format for that. You're going to write f to the negative 1 of x. This is our symbol for an inverse. And then we just write what it's equal to. So that's 1/2 x minus 1. And you'll notice that we moved y over to the left and this stuff over to the right side of the equal sign. That's fine. Usually we put f of x to the left. So this is our final answer. This is the inverse of f of x equals 2x plus 2. All right, here's another example. If you want to try this one out for yourself, go ahead and pause the video and do it, and then unpause and see how you did. So just like before, we need to swap out f of x for y so that we can swap the letters around. So we're going to have y equals x squared plus 1. Then we need to swap x and y. So y is going to turn into x equals x squared is going to turn into y squared plus 1. And now this is our inverse. But to write it in this format, we need to get y, or f of x, by itself. So first, to get y by itself, we need to get rid of this plus 1 that's hanging next to y. So we'll do the opposite of plus, which is minus. We'll subtract 1 from both sides. These cancel out. And on this side, we're just left with y squared. And on the other side, we have x minus 1. You can't do a letter minus a number, so it's just going to stay x minus 1. And now we need to get rid of this squared that's on y. The opposite of squaring is square rooting. So we need to square root both sides. So the squared and the square root cancel out, and we're just left with y. But on the other side, the important thing to note here is that whenever you square root both sides of an equation, what you're really doing is plus or minus square rooting. And the reason for that is, for example, let's say we had the square root of 9. The square root of 9 is 3. But technically, minus 3 times minus 3 is also 9. So when we square root both sides of an equation, we need to do the plus and the minus version. So there's nothing we can do to this. There's nothing we can simplify here, right? So it's going to stay as plus or minus the square root of x minus 1. And now the last thing to do is to change this into the function format. So we need to change y back into f of x. Or in this case, we're actually doing the inverse version, which is f to the -1 of x. And that's going to be equal to what we have here, plus or minus the square root of x minus 1. So there you go. This is the inverse of f of x equals x squared plus 1. Here's how to take an f of x and a g of x and find out if they're inverses. So here's the example that we'll be doing in this video. We have an f of x here, that's 3x minus 6, and we have a g of x, that's 1/3 x plus 2. And we need to verify that these are inverses. To find out if f of x and g of x are inverses, we need to find the composite functions. So we need to find f composite g of x, and we also need to find g composite f of x. Basically, f composite g means that we're putting g inside of f, and the other way around. So if we do both of these, and both of them are equal to x, like just x, then we can safely say that these are inverses. But if even one of these does not equal x, then these are not inverses. So first let's find f composite g of x. Another way to write f composite g of x is f of, instead of x, g of x. So we have an entire function as x in a function. So if you remember from solving functions, let's say we had f of 3, for example, right? We replaced x in f of x with 3. So over here, we would have to replace x with 3 as well. But in this case, we're replacing x with an entire function, which in this case is 1/3 x plus 2. So whenever we see x, we need to replace it with 1/3 x plus 2. So we have 3, and now instead of x, we're going to have g, which is 1/3 x plus 2. And then we just have minus 6. Now we need to simplify this down and see if we just get x by itself. So in this case, I'm seeing that we have a number in front of parentheses. That means we can do the distributive property. So we need to multiply the 3 out to both of these parts. So here we have 3 times 1/3x. We have to do 3 times 1/3. I'll write that out for you. 3 is the same as 3/1, and we're multiplying it by 1/3. So 3 times 1 is 3, and 1 times 3 is 3. And 3 divided by 3 is 1. So these two turn into 1. So we just have 1x, or in this case, that's just x. You don't have to write the 1 in front of a letter. And then here we have 3 times 2. 3 times 2 is 6. So we have plus 6. And then this minus 6 on the outside is going to stay the same. And now here you might notice that plus 6 and minus 6 are just canceling each other out, right? They're doing the opposite of each other. So 6 minus 6 is just 0, so they cancel out. And all we're left with is x. So we've completed the first step of verifying if these are inverses. But remember, for these to be inverses, g composite f of x also needs to be x. So let's go ahead and test that out next. So this is going to be exactly the same, except instead of f with g of x inside, we have g with f of x inside. So we are replacing the x in g of x with the entirety of f of x, which is 3x minus 6. So we're going to write out g, which is 1/3 x plus 2, but instead of x, we're going to put f of x, which is 3x minus 6. So we're going to write out g, 1/3, and instead of x, we're going to have the entirety of f, which is 3x minus 6. And then the plus 2 is here as well. So we're going to do the same thing as before. We can do distributive property, right? So we're going to multiply the 1/3 out to both of these parts. The 1/3 times 3, we did that earlier, but those cancel out. They turn into 1, right? So we have 1x, which is just x. And then next we have 1/3 times -6. Let's go ahead and write that out. We have 1/3 times -6, or in this case, we can write that over 1, because any number that's not a fraction is just over 1. So we have 1 times -6. Anything times 1 is itself, so that's just -6. And then 3 times 1 is 3. And 6 divided by 3 is 2. So the minus sign is going to stay, because it's negative. And 6 divided by 3 is 2, so we have a 2 here. And then this plus 2 is still hanging out here, so we have to leave that. And now you may notice that we have the same thing as before, right? We have an x, and then we have two numbers that cancel each other out. You subtract 2, and then you add the 2 back, you've done absolutely nothing. So those cancel each other out. And all we're left with is x, which means that g composite f of x is also x. So f composite g of x was x, and g composite f of x is also x. So we can say that these are inverses. So there we go. We have now verified that these two are inverses. Here's how to graph a square root equation and how to find its domain and range. So let's start by graphing just the basic square root equation, y equals the square root of x. Basically, any other square root equation is going to come from this. So if you know how to graph this, then you're basically already halfway there. So remember that for graphing anything, what we can do is we can plug in numbers in for x, see what we get out for y, and then plot that on our graph. And if we just do that a few times, then it's going to give us our graph. But square roots are a little bit weird because we can put in things for x, but like let's say we put in 2 and we needed to find the square root of 2 or the square root of 3. Those are going to give us big decimal numbers, and we don't want to deal with decimals. So I know this is a little weird, but I think it'll actually make more sense to put in numbers for y and see what we get for x. That does basically the same exact thing. So let's just think about this logically, right? What if we put in 0 for y? What do we have to put in for x to get 0 for y? Well, to get 0 from a square root, we need to take the square root of 0, because 0 times 0 is 0. So we have 0 for x and 0 for y. That's just right in the middle of the graph, so that'll go right here. Now to get 1 for y, to get 1 is our answer here, what do we have to take the square root of? Well, to get 1, we can do 1 times 1. So the square root of 1 is 1. Now remember that x is the left and right line here, and then y is the up and down line. So when x is 1, that means we need to go to the right 1. If it was negative, we would go to the left. So we need to go to the right 1, and also y is 1, and y is up and down. So when y is positive 1, that means we need to go up on the graph, up 1 square. And this is going to be our second point. Now, what do we have to do to get 2 for y? What do we have to take the square root of to get 2? Well, to get 2, we need to take the square root of 4. The square root of 4 is 2, because 2 times 2 is 4. So x is 4. Remember, x is to the right. So we need to go to the right 4 squares. So 1, 2, 3, 4. But we only have to go up 2, because y is 2. So we're going to go up 1, 2. And we're also going to have a point right here. And now this isn't going to get plotted on our graph because it's going to go off the graph, but to get 3, we would have to take the square root of 9. The square root of 9 is 3. But to get 9, we're going to have to go like all the way over here, and there would be a point like out here somewhere. So if we connect these up, you'll realize that a square root equation is kind of just like a parabola, but on its side. And it also only has one part. You may be asking yourself, well, if you took the square root of 4, for example, that's 2, but isn't it also negative 2, like 2 and negative 2? And yes, that's true. If you take negative 2 times negative 2, you'll also get 4. But when we have a square root sign, that usually just means the positive answer. And also, if you don't remember this, that's fine, but you might remember from functions that if we had this part here as well, and we did the vertical line test, which is basically how you find out if it's a function, you hit it more than once, which means this wouldn't be a function. For it to be a function, we have to only take the positive amounts. So there we go. We have already graphed y equals the square root of x. But what about its domain and range? How do we find those? Well, if you're not sure what domain and range are at all, I do have a video on it, so that'll be on the card on the screen if you want. But essentially, domain just means all the numbers that you can put in for x. And range just means all the numbers that you can put in for y. So a lot of the time, the domain is just all real numbers, because it's like, well, what's stopping you from putting in any number for x, right? But in this case, it actually is stopping us. Remember, x is left and right. You'll see that the graph only starts once we get to 0 for x. So if we were to put in any negative number for x, it would be over here, which there is no graph here, right? So that means you can only put in a number for x if it's 0 or higher. So the way we write this is we have our first number, the lowest number we can put is 0, and we can keep putting numbers on into infinity, because remember, this arrow means the graph goes on forever. So we're going to put 0, infinity. And then we're going to surround it by either a bracket if the number is included in the answer, or a parenthesis or whatever if it's not included. So in this case, can we put in exactly 0? Yes, we can, right? If we put in exactly 0, we'll be right here. So yes, 0 is included, so we're going to put a bracket. But even though this goes on forever, infinity itself is not a number. You can't actually put in infinity. So we're going to put a parenthesis around infinity. Now, what about for range? What numbers can we put in for y? Well, it's actually going to be the same thing, right? We start here at 0, because y is up and down. And if you go anything above that, you can actually keep putting in numbers here. And I know it looks like you can't put in numbers like around here, because there's no graph here, but eventually there will be graph here. This goes up infinitely, just pretty slow. But you can't put numbers in down here because there's no graph here, it just stopped. So anything above 0 we can put, just like for x. So we're gonna put the same thing as x. You can put 0 all the way up to infinity. So this is the final graph of y equals the square root of x, and this is our final domain and range. So now let's look at what happens when we get a little bit more complicated square root equations. All right, how do we graph this? We need to graph y equals the square root of x minus 2. That's all in the square root. And then we have plus 3, which is outside of the square root. So there's a couple ways that we could go about this. The first way is that we can just do the normal thing of plugging in numbers for x, see what we get for y. You'll probably run into decimals and stuff, but eventually you'll get the right graph. But there's actually a faster way that we can do this that's based on what we did before, just finding y equals the square root of x. Because it turns out that graphing this is actually exactly the same as when you're doing normal transformations. If you don't remember what transformations are, it's basically like when you had y equals x squared, and that's like a parabola, it looks like this. And then when you attach plus 1 to the end, the whole thing moves up 1. Or when you had x minus 1 squared, the minus 1 is on the inside, you move it all to the right. If you don't quite remember how transformations work, or if this just doesn't sound familiar to you, I do have a video on it, so you can go ahead and watch that because these rules are going to be very similar. So basically, we're going to start with what's called our parent graph, which in this case is what we graphed earlier, which is just y equals the square root of x. The parent graph is basically just the original graph that we're then changing by adding numbers to. So our graph from before, remember, was at 0, 0, and then the square root of 1 is 1, and then the square root of 4 is 2. And let's go ahead and graph that. So this was our original graph, but now we need to figure out how this minus 2 changes the graph and how this plus 3 changes the graph. So first, let's look at this minus 2 here. This minus 2 is inside of the square root. So this would be like if you were transforming the parabola and you had the minus 2 inside of parentheses. Well, the rule for this is if the number is outside of parentheses, it means you're going up and down. But if it's on the inside, it means you're going left and right because you're changing x here. We are subtracting x by 2. And x is left and right values. But the weird rule that applies to when you're doing parabolas or anything like that is the same weird rule here. And that is when it's inside of the parentheses or inside of the square root, it's going to be the opposite of what you think. Normally, you're used to minus 2, meaning that you got to go to the left 2. But for left and right, it actually means you're going to the right 2. In the transformations video, I kind of have an explanation of why that is. But just for now, just remember that left and right is the opposite of what's normal. But up and down, that doesn't change. So this is going to move us to the right too. But what about this plus 3 here? Well, this plus 3 is outside the parentheses, or in this case, just outside the square root. And when it's outside, what you're doing is you're taking what we had before, right? This part here. And then you're adding 3. You're actually adding 3 to y. So when we're outside of the parentheses, that means we're going either up or down. And in this case, there's no weird rule here. Positive means you're going up and negative means you're going down. So in this case, this is going to move the graph up 3. So what we're going to do is we're going to take this middle point here, the point that's kind of holding this graph in place, and we're going to move it according to what we just found out. So first we need to move it to the right 2. So we're going to go 1, 2. And then we need to go up 3. So we're going to go 1, 2, 3. And this is going to be where our point is. This is where our middle point was, and now this is our new middle point. And now we don't have to plug in any more numbers, right? We know what our square root graph looks like, so we just need to regraph it, but starting here. So this is our 0, 0, and we also have a point over here, and we have a point over here. All we're doing is just replicating what's over here. We're just basically copying and pasting, but in a different place. So we're going to draw the line through it as well. And this is going to be our final graph of y equals the square root of x minus 2 plus 3. And this green part's not actually part of our graph, so we can just go ahead and erase this. Now, what about our domain and range? How do we find those? Well, remember that domain just means x, the x values that you can put in, and range means y. So what x values can we put into our graph? Well, before we could only put anything that was 0 or higher, right? But in this case, we actually can't put 0. because if you put in 0, there's nothing, there's no graph there, right? The lowest number we can put is actually 2, because here is 2, right? It's 2 to the right, 1, 2. Once you go 2 to the right, that's where the graph starts. And then after that, it just goes on infinitely, and you can put in any number. So you can put in any numbers from 2, starting at 2, all the way on forever to infinity. And like before, we can put a bracket on the 2 because the 2 is included. We can put exactly 2, but we can't actually put in infinity. Infinity always gets a parenthesis. Now, what about our range? What numbers can we put in for y? Well, looks like you can't put in any number right here. You can't put in any numbers for y until you get to here, and then it just goes up infinitely, and you can put whatever you want. So it looks like you have to go up 1, 2, 3. You have to go up 3 boxes before you get any graph. So we have to put in 3 for y or higher, and you can put in any number that's bigger than 3. And exactly 3 does work, so we're going to put a bracket and then in parentheses for the infinity. So there you go. This is our final graph, and this is our domain and range. Now here's one last rule that I want you to be aware of. There are other kinds of transformations you can do, but those are all explained in the transformations video if you want to watch that. But there's one special case that has to do with square root equations. And this special case happens when we put a negative sign next to x on the inside of the square root. So for transformations, you might remember that if we put a minus sign on the outside, like for example, minus x squared, whenever you put a minus sign, everything gets flipped upside down. So if you had a parabola like this, then it would turn into this. And the same thing is true for square root equations. If you have a minus sign on the outside of the square root of x, then everything gets flipped upside down. So all the points, like this point here, gets flipped upside down. It's like a mirror here. It's just flipped to the other side of the mirror. And then this point here was 2 up, now it's going to be 2 down. And then we'll graph our new upside down equation. So this would be if the minus sign is on the outside of the square root. But in this case, it's actually on the inside, because before we're taking what we had, which is y, and then attaching a minus to it. So things are being flipped in the y direction. But in this case, we're actually attaching the minus sign to the x. So we have to flip everything in the x direction, which is left and right. So we're going to do another mirror image thing, but it's going to be from the right to the left instead of from the top to the bottom. This big line here is going to be our mirror, and this point here is going to get flipped over to the left, and this point here is going to get flipped over to the left as well. I'm noticing it's 4 away from the mirror, so it's going to be 4 away from the mirror on this side. And then we're going to graph our new mirrored equation. So this is the graph of y equals the square root of negative x. And if you're wondering why this is not a thing with parabolas, it's because they're already symmetrical. If you have a graph like this, if you were to flip it around, it's already flipped, right? It's going to do absolutely nothing. So yeah, that's the only special rule for square roots. Everything else is the same. You may have learned how to graph square root equations, but how do we graph cube root equations? So let's first go over how to graph just the basic cube root equation, y equals the cube root of x. So to graph anything, really all you have to do is plug in numbers for x, see what you get out for y, and then put it on the graph. And remember that y is up and down, and x is left and right. But in this case, I think it'll actually be easier, and I did the same thing in the square root video, is that if we plug in numbers for y and then see what we get for x, then that'll make things easier, because trying to put in numbers for x into a square root can give us decimals. So first, let's just plug in 0 for y and see what we get. And to do this, we just need to think what number, if we take the cube root of it, will give us 0. Well, remember that the cube root means multiplying it 3 times to get to that number. And 0 times 0 times 0 is still 0. So the cube root of 0 is 0. So we can plot a point right here in the middle of our graph, because it's 0 to the left or right and 0 up and down. Now, what about 1? What number do we need to put in the cube root to get 1? Well, 1 times 1 times 1 is 1. So that means x equals 1 and y equals 1. So we can put a point there as well. So x equals 1 means we need to go 1 space to the right. So that'll be right here. And then y equals 1 means we need to go 1 space upward. So we need to go up here. And there will be another point on our graph right here. And now finally, what number do we need to put in for x to get 2 for y? Well, to figure out what number to put in here, we would need to do 2 times 2 times 2, which 2 times 2 is 4, times 2 is 8. So you have to put in 8 for x just to get out 2 for y. And that's like going off of our graph here. We're like almost off of the screen right here. So x equals 8. That means we need to go 1, 2, 3, 4, 5, 6, 7, 8 spaces to the right, only to go 2 up because y is 2. So 1, 2. And there will be a point right here, almost off the screen. So now we can draw a line connecting these, right? So we're going to go ahead and draw, it's going to be a curved line, right? It's going to be a line going here, and I'll just stop it here because it's going off of the graph. Now, for square roots, this would be the end of the graph because you can't put in a negative number for x. If you put a negative number inside the square root, then that's going to get you imaginary numbers. So the graph would just stop here, anything to the left of 0. But I want you to think about how this would work for cube roots. Can we put negative numbers inside a cube root? Well, like for example, what if we put in -1? Is there any way that we can get -1 by multiplying the same number 3 times? Well, if we did -1 times -1 times -1, well, -1 times -1, 2 negatives make a positive, so that becomes +1, but times another negative makes it negative again. So actually, yes, with cube roots, we can put in negative numbers. So we're going to have a whole nother part of the graph on this left side. So if we put in -1 for x, we get out -1 for y, which means negative numbers are to the left. So we go 1 to the left, and then y equals -1. That means we go 1 squared down. And we have another point right here. And we can also put in a number to get out -2. Well, to get -2, we would need to put in for x, -2 times -2 times -2. -2 times -2 is +4, times another -2 is 4 times 2 is 8, and there's 1 minus sign. So we have to put in -8 for x to get out -2 for y. So we need to go to the left 8 squares. So that's going to be all the way over here. And then we need to go down 1, 2. And we'll have a point right here. So let's go ahead and draw another line connecting these. So this is the final graph of y equals the cube root of x. But how do we use this to graph any other sort of cube root equation? So here's the second equation that we'll be graphing in this video. It's a little bit more complicated. It's just the cube root equation, but we have an extra +1 here on the inside, and then we have a 2 here on the outside. And remember, that's multiplication because there's no sign. So we could just do it the same way, plug in numbers for x and see what we get for y, but that would be really time consuming. But because we know how to graph a regular cube root equation, what we can do is we can graph the regular cube root equation and then figure out what this +1 and this 2 are doing to it, and then just make those changes. And that's called transformations. Now, there are multiple different types of transformations that you can have. I do have a full video just on transformations if you want to go watch that and see all the different things that can happen to a graph. But in this case, I'm just going to show you how to use transformations on cube root equations. So we need to start by graphing the parent graph, which is just y equals the cube root of x, which is what we just graphed. I'm going to go ahead and just graph it the same way we did before. So here's our cube root equation, and it's already graphed. So all we have to do is figure out what this +1 is doing to our parent graph, and what this 2 is doing, and then make those changes. So let's take a look at this +1 first. What would the +1 be doing here? Well, if this was on the outside of the square root, like if it was right here, then it would be moving the graph upward because positive is up. And if it was a minus sign, it would be moving it down. But when it's on the inside, that means it's moving left or right. And usually when it's left or right, it's the opposite of what you think, because right usually means positive and left usually means negative. But for transformations, left and right are switched. So this +1 on the inside is going to be moving it to the left. So instead of plugging in a bunch of numbers, all we have to do is take this graph that we already have and just move it 1 square to the left. So our little middle point is now going to be right here. And everything else is just going to be regraphed, but 1 square to the left. So there used to be a point right here. It's now going to move right here. And there used to be a point right here. It's now going to move right here. So there we go. We have now graphed our same graph, except now it's 1 to the left. And if the problem was asking you to describe the transformation, then you would just say it moves to the left 1. But now we need to figure out what this 2 is doing. And remember that this is multiplication. So this 2 is multiplying all of our numbers by 2. Whenever we're multiplying by a number on the outside, we call that stretching. Or if the number is less than 1, it's actually compressing, which is just the opposite of stretching because it's making the numbers lower than they were before. So we need to take all of our points on the graph and multiply them by 2. So our middle point is going to stay exactly the same. It's just going to stay right here at 0. But for example, this point is 1 square above the middle point, but we're multiplying everything by 2. So it's now going to become 2 squares above the middle point. And now what about this point here? This one is 1 square below our middle. Now it's going to become 2 squares below. And just for the sake of example, let me show you the point that would have been all the way out here. So 1, 2, 3, 4, 5, 6, 7, 8. So there would have been a point all the way out here, right? This point, if it was actually on our graph, would be 2 squares above the middle. But because we're multiplying by 2, it would become 4 squares above the middle, because 2 times 2 is 4. So there would be a point right here as well. So let's go ahead and draw the new stretched version of our graph. And I'm going to graph it in purple just so that you can see it. So you can see that this version of the graph is a lot taller than the graph before. And that's why it's called stretching. We're stretching out the graph. If this was a fraction, like for example, 1 over 3, then we would actually be squishing it. We would be compressing it. And to describe this transformation, you would just say that it's stretched by a factor of 2. Now, this graph is looking like a huge mess, but remember that only the final graph is actually part of the graph. All this other stuff was just our work. So we can go ahead and erase all this now. And with that, we now have our final graph of this equation. Now, one more thing I wanted to address. For these kinds of problems, you might need to name the domain and range. Now remember that domain is just the numbers that you're allowed to put in for x, and the range are the numbers that you're allowed to put in for y. But you may notice that with this cube root equation, there's like no restrictions. We can put in any number for x because it goes infinitely to the left and infinitely to the right. And it's also going infinitely down and infinitely up, so we can put any number for y. So our domain and range are both all real numbers. So as opposed to our square root graph, which looked something like this, and we couldn't put any numbers to the left here or below here, and there were different restrictions, for cube roots, they're always going to be all real numbers for both domain and range. How do we solve for x in a square root equation? Well, it's pretty similar to what you've already done, but it's a little bit different. So here's the first example that we'll be doing in this video. We need to solve for x. Now to solve for x, you just need to get x by itself on one of the sides of the equation. But that's a little bit difficult here because it's trapped inside this square root. So to get x by itself, what we need to do is take this square root and treat it as if it was just a variable, and we're trying to get the square root by itself. Because eventually when the square root is by itself, we're going to square both sides to get rid of the square root. But just remember that if we were to square both sides right now, then we would be squaring this, and we would have to use FOIL. We couldn't just square the left and then square the plus 4. But we don't have to even worry about that, because we can solve that problem by just getting rid of this plus 4. And to get rid of this plus 4, we'll do the opposite, which is minus 4. So we'll subtract 4 from both sides. The 4's cancel out. And on the left side, we just have the square root of x minus 3. And on the other side, we have 6 minus 4, which is 2. And now we have our square root by itself. So to get rid of the square root, we can do the opposite of square rooting, which is squaring. So we'll square both sides. So the square root and the square cancel, and all we're left with is x minus 3 on this side. And on the other side, we have 2 squared. Remember, squaring just means multiplying by itself. So this is 2 times 2, which is 4. And now we just have a one-step equation. So all we have to do to get x by itself is get rid of this minus 3. So we'll do the opposite of minus 3, which is plus 3. We'll add 3 to both sides. These cancel out. And on the left side, we just have x. And on the other side, we have 4 plus 3, which is 7. So x is equal to 7. Maybe. What do you mean maybe? We literally just solved the problem, right? Well, x is probably 7, but just to make sure, we need to check our work. Now, in my other videos, I've always said that, checking your work after is a good idea. You should plug in the number back into x to see if it's right, just to make sure you did the problem correctly. But for square roots, you actually have to check your work at the end, because there's a chance that this is actually a fake answer, that it's not actually x equals 7. So let's go ahead and plug in 7 for x and make sure that this is an answer. So let's just rewrite this equation. We had the square root of x minus 3. That will now become the square root of 7 minus 3. And then plus 4 equals 6. And now let's just go ahead and simplify this down. So 7 minus 3 is 4. So we have the square root of 4 plus 4 equals 6. And now remember that technically 2 times 2 is 4, and also negative 2 times negative 2 also makes 4. But whenever we have a square root sign, that just means you take the positive answer. So this is positive 2 plus 4 is equal to 6. And yes, this is true. 2 plus 4 is 6. So our answer checks out, and our answer is x is equal to 7. All right, here's another example. We need to solve for x just like before, but it's trapped in our square root. So we need to get the square root by itself so that we can square both sides and then get x by itself. So the only thing in the way of getting the square root by itself is this 2 on the outside. And there is no sign, which means that it's a multiplication. So we need to do the opposite of multiplication, which is division. We'll divide both sides by 2. The 2's cancel out. And on the left side, we just have the square root of x minus 5. And on the other side, we have negative 6 divided by 2. 6 divided by 2 is 3. And we have one minus sign, so the minus sign stays. And now we have our square root by itself, so we can square both sides. The square root and the squared cancel, and on the left we just have x minus 5. And on the right side we have negative 3 squared. Remember, that's multiplying by itself, so negative 3 times negative 3. 3 times 3 is 9, and we have two minus signs. The two minus signs make a positive, so we have positive 9. And now we can just get x by itself with this one-step equation. We have a minus 5, so we can do the opposite of minus, which is plus. The 5's cancel out, and on the left side we just have x. And on the right side we have 9 plus 5, which is 14. So x is equal to 14. Maybe. Always remember that we need to check our work. So we need to put the number back into x to see if the equation is true. So let's go ahead and do that. We have 2 times the square root of x minus 5. That's now going to become 2 times the square root of 14 minus 5. And that's going to be equal to minus 6. So let's go ahead and solve this. We have 14 minus 5. That's going to turn into 9. And the square root of 9 is 3. So we have 2 times 3 equals negative 6. But this isn't actually true. 2 times 3 is positive 6. And negative 6 and positive 6 are not the same. So this means that 14 is actually a fake answer. It's not a real answer because we have to always check our work when we solve square root equations. So what is the answer then if it's not 14? Well, there is no answer. So in this case, we're actually going to say that our answer has no real solution because we only got one answer and it's not even a real answer. So there is no answer to this problem. How do we solve for x when there's a square root in the equation and there's also a less than or greater than sign? Well, I guess that wouldn't make it an equation. That would make it an inequality, but math terms, who cares? So here's the inequality that we'll be going over in this video. We need to solve for x. Now we're going to start by solving this just like a normal equation. And if you need help with that, then I do have a video on solving square root equations that you can watch on the card. But I'll also go over it here. Remember that when x is trapped inside of a square root, our goal is to get the square root by itself so that we can square both sides and cancel it out. And the only thing in its way is this minus 4 here. So let's get rid of the minus 4. It's being multiplied to the square root because there's no sign. So we'll do the opposite of multiplying, which is dividing. We'll divide both sides by negative 4. The negative 4's cancel out. And on the left side, we just have the square root of x minus 3. And on the other side, we have 8 divided by 4, which is 2. And 2 minus signs, 2 negatives make a positive. So it's going to be positive 2. But remember that when we're solving any sort of inequality with a less than or greater than sign, whenever we divide or multiply by a negative number, which we did in this case, we need to flip the sign around. So the sign was greater than, now it's going to become less than. So now we can square both sides of our equation, right? So we're going to square both sides. The square root and the squared cancel. And on the left side, we just have x minus 3. And on the right side, we have 2 squared. That's 2 times 2, which is 4. So now we can get x by itself by getting rid of this minus 3. And the opposite of minus is plus. So we'll add 3 to both sides. The minus 3 and plus 3 cancel out. And on the left side, we just have x. And on the right side, we have 4 plus 3, which is 7. So x is less than 7. Now this tells us that this inequality is only going to be true for numbers that are less than 7. So if we put something greater than 7, like 8, then this isn't going to be true. But we're not actually done yet with this problem. Can you figure out why some numbers less than 7 might not work? Why they might cause a problem? Well, what if we put in a number less than 7 like 2? Let's go ahead and plug in 2 into this square root. Do you see where this is going? So we would have the square root of 2 minus 3, which is the square root of negative 1. and now we're already causing problems. We can't take the square roots of a negative number except when doing imaginary numbers, and, well, how are we supposed to compare imaginary numbers with real numbers? So to solve this issue, we need to set up another restriction, something else that will stop us from putting in numbers that will give us a negative square root. So to avoid having a negative square root, what's inside x minus 3 needs to be either exactly 0 or bigger than 0. If it's not, then it's going to become negative. So the way that we say exactly 0 or bigger than 0 is by putting a greater than or equal to sign. It needs to be bigger than 0, or this line underneath means that it can be exactly 0 as well. We can take the square root of 0. So let's go ahead and solve this for x and see what we get. So to get x by itself, we need to do the opposite of minus, which is plus. We'll add 3 to both sides. These cancel out, and on the left side we just have x, and on the right side we have 0 plus 3, which is 3. So you'll see here that x needs to be less than 7, but it also needs to be bigger or exactly 3. So how do we write this as just one answer? Well, the way that we do that is by putting our two numbers that x needs to be between and putting x in the middle. And then we just need to figure out what signs to put here. So over here, we had x is greater than or equal to 3, but here 3 is on the left, so we just need to flip the sign to show that. So it's going to be less than or equal to, because x is bigger than 3. The alligator is eating x. And then here we have x is less than 7. Here we have x and 7, so we'll just carry over the sign. And this is how we write our final answer. 3 is less than or equal to x, which is less than 7. Now, if you wanted to check your work, you would just check 3 numbers. You would check to make sure that a number less than 3 is not going to work. So for example, you could plug in 2 and make sure it doesn't work. Then you put in a number between 3 and 7, so for example 5, and make sure it does work. And then you can put in a number bigger than 7, like 8, and make sure it doesn't work again. And then that's how you know that your answer is correct. Here's how to graph both exponential growth and exponential decay functions. So for this video, I'm first going to show you how to graph some of the basic exponential equations, and then I'll show you how to graph more complicated ones using transformations. So let's start by graphing y equals 2 to the power of x. Well, to graph any sort of function, we can just keep plugging in numbers for x, see what we get for y, and plot those on our graph. And remember that y is up and down, and x is left and right. So I usually like to start by plugging in 0 for x. So what do we get when we plug in 0 for x? Well, you would get 2 to the power of 0, and anything to the power of 0 is 1. So we're going to plot, we have 0 for x, so we're not going left or right, and we get 1 out for y. So that means we need to go 1 square upward, and we're going to plot a point right here. And as long as you're not doing any transformations and stuff, which I'll talk about later, you're always going to have a point right here, because anything to the power of 0 is 1. So now let's go ahead and plot some points over here on this side. So let's move over 1 square to the right and plug in 1 for x. When we plug in 1 for x, we're doing 2 to the power of 1. And anything to the power of 1 is itself. So when we plug in 1 for x, we're getting out 2 for y. So when we move 1 to the right, we move 2 squares upward, and we're going to have a point right here. What if we plug in 2 for x? Well, now we have 2 squared, 2 to the power of 2. And remember that when you're doing exponents, you're just multiplying multiple times. So we're multiplying 2 twice. So that's 2 times 2, which is 4. So when we plug in 2 for x, we get out 4 for y. So we're going to go ahead and move 2 squares to the right, and then we're going to move 4 squares upward, and we're going to plot a point right here. Now, just to demonstrate, in case we had like a bigger graph, it won't fit on this graph, but if we plugged in 3 for x, then that would be 2 to the power of 3, or 2 times 2 times 2, which is 8. So we would have to go 3 squares to the right, and 8 squares upward, but we don't have that much room on the graph, so we're just going to stop here. But remember that our graph is going to go infinitely in both directions. So it's going to kind of go up like this, right? But it's also going to go this way as well. So we need to plot points on the left side as well. So what if we put in -1? That would be the same thing as going 1 to the left on our graph. When we plug this in, we get 2 to the power of -1. And a negative exponent is just the same thing as a positive exponent, except we need to flip the fraction around, or basically put it 1 over what we would normally get. 2 to the power of 1 is 2, so 2 to the power of -1 is 1 over 2. or 1/2. So when we move one square to the left, that's a -1 for x. We only move half a square upward, and we're going to have a point right here. Now, what if we plug in -2? That will be the same as moving 2 squares to the left. And if we plug in -2, we get 2 to the power of -2. And 2 times 2 is 4. So it's going to be 1/4 because it's a negative exponent. So when we move 2 squares to the left, we only move up a quarter of a square. So as you can see, we are getting very close to this line here. But you may notice, and I'll show you to the power of -3 as an example. When we go to the power of -3, we're going to get 1/8, which means we're going to be even closer to 0. But you may notice that we're never actually going to reach 0. We're just going to keep making the fraction smaller and smaller. So now we can go ahead and connect these points. And as you can see, it's going to kind of make this curve. It's like half of a bowl shape. So we're going to go ahead and connect these up. So yeah, I mean, this was the best I could do. But yeah, this is my graph here of y equals 2 to the power of x. And you can see that I have arrows on both ends because they go on infinitely. You can keep putting in more numbers this direction and this direction. There's no limit to the numbers you can put in. What about this graph here? Is this one going to grow just like the last one? Well, let's find out by plugging in numbers, right? So let's go ahead and plug in 0 like before. And remember that anything to the power of 0 is just 1. So we're going to put a 1 here, just like the last graph. Now, what if we plug in 1 for x? Well, anything to the power of 1 is itself, so it's going to stay as 1/3. So when you plug in 1 for x, that's the same as going 1 square to the right, because so the right is positive numbers. When you go to the right 1 square, you only go up 1/3 of a square. So we're only going to go up like right here. So this is pretty disappointing already. And the disappointment continues even more when you plug in 2 for x, and that means you're multiplying it twice. So you're going to have 1/3 times 1/3. And remember that when you're multiplying fractions, you multiply the tops and bottoms. So 1 times 1 is 1, and 3 times 3 is 9. So we're only going 1/9 of a square when we go 2 to the right. We're only going up like right here. It's like literally nothing. But what happens if we go the other way? What happens if we go to our negative numbers? Well, let's plug in -1 for x. Now remember that when we plugged in +1, we just got 1/3, because anything to the power of 1 is itself. So we got 1/3, but because we have a negative exponent, you have to flip the fraction. So 1/3 becomes 3/1, or just 3. So when we move 1 square to the left, we actually move up 3 squares, and we're going to have a point right here. And if we plug in -2, then we're going to act like this is +2, right? We're going to multiply 1/3 twice. And like we said before, 1/3 times 1/3 is 1/9. But because it's a negative exponent, we flip the fraction around, and it becomes 9/1, or 9. So when we move 2 squares to the left, we move 9 upward, and there's just not enough room here to do that. So this is basically as much as we're able to graph with our limited size here. So let's go ahead and connect these up with a curve. So here's my totally perfect curve with no flaws at all. And this is our graph of 1/3 to the power of x. And as you can see, unlike the last one where it was growing, this one is not growing. It's getting worse the farther we go along for x. So we would call this an exponential decay function. So now you know how to graph the basic exponential functions, but how do you graph something a little more like this? This is a little bit more complicated. Well, we could do this the same way by plugging in numbers into x, like for example 0, and then go ahead and solve this and see what we get and plot it on our graph. But that would take a little bit longer than last time. So instead, we can use something called transformations, which is what we use to graph all sorts of other kinds of graphs. If you want to see all the different kinds of transformations and how they can change a graph, then I do have a full video on it that you can watch on the card on the screen right now. But for this, I'm just going to show you how you would apply them to exponential graphs. So first, we need to know what our parent graph is. And in this case, that's just going to be a number to the power of x. Right here, we have our parent part right here, which is 2 to the power of x. So our parent graph is just y equals 2 to the x. So remember that our goal is to take this graph of y equals 2 to the power of x, and then figure out what this +1 is doing to it, and what this 1/2 is doing to it, and then just make those changes. So I'm going to start by graphing y equals 2 to the power of x, and I'm going to do this the exact same way I did before. So if you need a refresher, just go back to the beginning of this video. So this was the graph of y equals 2 to the x, and now we can figure out what our little extra parts are doing here. So let's go ahead and look at this plus 1 first, because I think this is going to be a little easier than the 1/2. So this plus 1, what is it going to do to the graph? Well, you may notice that this plus 1 is written really small because it's attached to this x. It's actually part of the exponent. If this plus 1 was on the outside of our equation, like this, then this would mean that you're adding 1 to y. And that would mean you're moving the entire graph up 1 square. Or if this was a minus 1, then you would be moving the entire graph down 1 square. But when there's a plus or minus 1 inside of the exponent, that means we're moving it left or right. And just like with all the other kinds of transformations, left and right is the opposite of what you think. So normally plus 1 would mean positive numbers go to the right, but it actually means going to the left. So when you have a positive number in the exponent, you go to the left. And if this was a minus 1, you would go to the right. So we're just going to take every point on this graph and move it 1 square to the left. So this point right here is going to move right here. And this point here is going to move right here. So I'm going to regraph this graph, except everything's going to move 1 square to the right. So there you go. This is what the plus 1 does to our graph. But this is not the final graph because we still have to look at what our 1/2 does. Now remember that this dot here means multiplication, and we are multiplying everything by 1/2. So this means that we're either going to be stretching or compressing. And if you watch the transformations video, you would know that anything less than 1 means we're compressing it. But what does compressing a graph even mean? Well, what this means is we're going to take all of our points, and however high up they are, which is our y value, we're going to multiply them by 1/2, or that's the same thing as dividing by 2. So this point here, I think this point will be a good example. This point is 2 squares above 0, which means that its y is 2. But now we're only going to be taking half of that. So it was 2 squares above, now it's only going to be 1 square above. And I'm going to graph this in purple. This is going to be our final graph. So now what about this point here? This point is 4 squares above 0, but we're multiplying it by a half. And half of 4 is 2. So our new graph is only going to be 2 squares above. And wait, so I've just realized that, do you see something familiar here that we're doing? Anyway, let's just continue on. We had this point here, this was 1 square above, right? Now, if we move it down, it's only going to be half a square above 0. So you'll notice that all of our points are landing on our green part here, our parent graph. And I didn't even intend for this to happen. This was unintentional, but there's actually a decent lesson here. So sometimes these transformations that seem completely unrelated, like adding a plus 1 to the exponent and multiplying everything by 1/2, end up like canceling each other out. They can do basically the same thing. So yeah, this purple line here is our final graph. So we can go ahead and erase everything else. And yeah, this was completely unintentional, but this is the final graph of this equation. It just ended up being the same as our parent graph. How do we solve an equation like this one, where x is trapped inside of an exponent? So here's the first example that we'll be doing in this video, and for this one we need to solve for x. So we have x here, but it's inside of an exponent. So remember that the goal of solving for x is to get x by itself on one side of the equation. And we do things to both sides of the equation to get it by itself. But there's not really anything we can do here. We can't do things to both sides of the equation that are inside the exponent, or else we're going to mess things up. Now, this problem is a little bit easier than the one that we're going to do next, and that's because these two numbers are the same. And that makes it a lot easier. So to understand what we're doing, we can use a little bit of logic here. So I want you to imagine that we have 5 to the some exponent equals 5 to the some exponent. The only way that these two numbers can be equal, if these are both 5, is that the exponents also have to be equal, because 5 to the 2 is not the same as 5 to the 3. Those will never be equal. The only way that these two numbers can be the same is if the exponents are also the same. So for example, 5 to the 4 is the same thing as 5 to the 4. So if we think about this the same way, if these are both 3, then for these two numbers to be the same, the exponents also need to be equal to each other. They need to be the same. So what we can do is we can just ignore these big 3's, which are called the bases, by the way. And we can just set the exponents equal to each other because we know that the exponents need to be the same number. So we can rewrite this as just 3x plus 1 which is this exponent, is equal to 7, which is the other exponent, because we know they have to be the same. And now all we have left is a one-step problem without any exponent. So to get x by itself, we can get rid of this 3 or the plus 1. I'm going to get rid of the plus 1 first because it's less attached to x. So to do the opposite of plus 1, we need to do minus 1 to both sides. These cancel out, and on the left side, we just have 3x. And on the right side, we have 7 minus 1, which is 6. And now we have a one-step equation. So there's no sign here between the number and the letter, which means that it's multiplication. So we need to do the opposite of multiplication, which is division, and divide both sides by 3. So these cancel out, and on the left side, we just have x, and on the right side, we have 6 divided by 3, which is 2. So our final answer is x is equal to 2. So that wasn't that bad because we had our special rule where if the bases are the same, the exponents also need to be the same. But not every problem is going to give you bases that are exactly the same. So what do we do if the bases are different? So here's another example, and for this one, the bases are different. Here we have an 8, and here we have a 2. So we can't use that special rule where we just ignore the bases and set the exponents equal to each other. But how else are we going to get rid of these exponents? Well, we're going to get rid of them the same way. But because the bases are different, we need to make the bases the same. So what we need to do is we need to turn one of these bases into another exponent. So like, for example, 9 can turn into 3 to the 2 because 3 times 3 is 9. So what we can do is we can take 8 and turn it into a base of 2. But we need to figure out what exponent needs to go here. Well, to get to 8, you have to multiply 2 3 times because 2 times 2 is 4, times 2 is 8. So because we have to multiply 2 3 times, this means that we need to put an exponent of 3 on 2 to get 8. So 8 is the same thing as 2 to the 3. So we're just going to replace 8 with that, and we're going to leave everything else the same. Now both sides have the same exact base. They both have a base of 2. But we have something a little wonky going on the left here, right? We have an exponent inside an exponent. Well, we have a special rule in math that says that if you have something to the power of something to the power of something, if you have a power inside a power, then you can multiply the exponents together. So we're doing 3 times x minus 2. So we're going to write that out here so that it looks a little bit more familiar. And you'll notice that this looks a lot like the distributive property, where we have to take the number on the outside and multiply it to both parts inside the parentheses. So 3 times x, well, that's just 3x. And then 3 times 2 is 6. And then the minus sign stays. So when we multiply these two together, when we multiply 3 and x minus 2, we get 3x minus 6. And now on the right side, this is just going to stay the same. And you'll see that we now have a problem where the bases are the same. So we can do it exactly the same as last time, and we can ignore the bases and just set the exponents equal to each other. So 3x minus 6 is going to be equal to negative 3. And now we can just solve for x like normal. So I'm going to get rid of the minus 6 first because it's less attached to x. So we need to do the opposite of minus, which is plus, to get rid of it. So these cancel out. And on the left side, we just have 3x. And on the right side, we have negative 3 plus 6. That's the same thing as 6 minus 3, which is 3. And now I'm running out of room here, but this is multiplication, just like last time. So we need to do the opposite of multiplication, which is division, and divide both sides by 3. So these cancel out. And on the left side, I'll write it over here, we just have x. And on the right side, we have 3 divided by 3, which is 1. So our final answer is x is equal to 1. Now, for some problems, you can't just do an exponent on one side and get the bases to be the same. Sometimes you have to do it to both sides, but it'll work exactly the same way. What on earth is a geometric sequence, and how do you write the equation of one? So here's the first example in this video. Here we have a geometric sequence, and our goal is to write the equation of this geometric sequence. So a geometric sequence is kind of like an arithmetic sequence, which you maybe have not heard of either. An arithmetic sequence is basically like if you have something like 5, 10, 15, 20, right? You're adding a number each time. So each time you're adding 5. So adding 5 to 5 gives you 10, plus 5 is 15, plus 5 is 20. That's an arithmetic sequence. So a geometric sequence is the same exact thing, except you're multiplying every time. So for example, this is a geometric sequence because here to get to 8, you're multiplying by 4. And then to get to here, you're multiplying by 4 again. And then you're multiplying by 4 again. Now, knowing what number that you have to multiply by each time is really important for a geometric sequence. And if you didn't already know that, if you couldn't tell that this is multiplying by 4, then all you have to do is take two numbers that are next to each other, like 8 and 2, and divide them. So you take the second number, 8, divided by the first number, 2, and this will give you 4. And that tells you what you're multiplying by each time. So to write the equation of a geometric sequence, we need some sort of format that we can just plug things into. And for example, like when we're writing the equation of a straight line, we use y equals mx plus b. We always use this format, and then we just plug in m and b, and then we have our equation. Now for geometric sequences, we also have a format like that where we can just plug in numbers. So the format goes a sub n equals a sub 1 times r to the n minus 1. I know this sounds really confusing, but let's go ahead and explain what each of these things mean. So a sub n is always going to mean whatever number we're on. So for example, if we had a sub 3, all that means is we're talking about the third number. So for example, a sub 3 in this case would be 32, and a sub 4 would be 128. So in that case, it makes sense that a sub 1 just means the first number. So a sub 1 in this case is 2. Now r, this is probably the most important part, r is going to be whatever number we're multiplying by. So remember we said that to get from this number to this number, we're multiplying by 4 each time. So this means that r is going to be equal to 4. We'll get to that in a bit. And then n minus 1, remember n is whatever number we're on. So for example, if we plugged in the fourth number right here, then we would plug in 4 for n, and we would get r to the 4 minus 1, or r to the third. So for writing an equation, a to the n, and then this part n minus 1, those are both going to stay the same, because the idea is you're going to plug something in for n and then see what you get, like once the equation's written. But the two things that you do need to replace in this equation are a sub 1 and r. These are the two things that you need to replace with whatever number is applicable in this situation. So let's go ahead and rewrite our equation here, except we'll replace a sub 1 and r with what we know. So a sub 1 is basically just the fancy way of saying the first number. And in this case, our first number is 2. So instead of a sub 1, we're just going to put the number 2. And then r here, what is r? Well, r is the number that you multiply by each time. And as we figured out before, each time we go to the next number, we're multiplying by 4. So for r, we're going to put 4. Now we're going to put r in parentheses, because if we didn't put it in parentheses, then this would say 24. And it's not 24. And then the n minus 1 is going to stay the same. So there you go. This is our final equation of our geometric sequence. So here's another example. We need to write the equation of this geometric sequence just like before, but this time we don't know the sequence. We only know that the fourth number in the sequence is 24, because that's what a sub 4 means. And we know that r is equal to 2, which remember that's the number we're multiplying by each time. So in a way, it almost seems like it's going to be easier, because we know that r is 2, and remember that the only things we need to replace are a sub 1 and r. So we already know that we're going to replace r with 2. But the hard part is figuring out what a sub 1 is, or our first number. So there are like two main ways that we can do this. I'm going to show you the way that I think is easier, and then I'll also show you what teachers are probably teaching you. So the way that I think is easier to understand is to just think about it logically. We know that the fourth number is 24. So we have our first number, and then our second number, and then our third number, and then our fourth number is 24. And we know that we're multiplying by 2 each time. So to get to here, we're multiplying by 2. To get to here, we're multiplying by 2. And to get to here, we're multiplying by 2. So all we need to do is just work backwards to get to our first number. And remember that we can just do that by doing the opposite of multiplying by 2. So to figure out what this number is, instead of multiplying by 2, we'll divide by 2, because we're going backwards. And if we work backwards, then we divide by 2 and we'll find our number. So if we take 24 divided by 2, you can put that in your calculator, that's going to give you 12. And then if we divide by 2 again, that's going to give you 6. And if you divide by 2 again, that's going to give you 3. So we now know that our first number is 3. Now, the other way that you could have done that, and the way that I feel like textbooks usually teach you, it's a little more complicated, but basically you just plug in what we know into this equation. So we know that a to the 4 is 24, so we'll just plug in 24, equals a to the 1, which is what we're trying to solve for. And then we have r, which we know is 2, to the n minus 1. And remember that n is going to be 4 because we plugged in the fourth number. So this is going to be 4 minus 1, or 3. And then we solve for a1 like it's a letter. So 2 to the power of 3 is 2 times 2 times 2, which is 8. And then we have multiplication here. So we divide both sides by 8. And the 8s are going to cancel out. And this is just going to give you a sub 1 equals 24 divided by 8, which is 3. Which means that our first number is 3. So you can do whichever way you think you understand more. I personally think that this way, where you just work backwards, is the easiest way to understand what it is you're actually doing. So we know that our first number is 3, and we know what r is, so we have everything we need to write our equation. So remember that a sub n is going to stay the same. A sub 1 is just our first number, which is 3. R is just what number we're multiplying by each time, which we already know is 2. And then the n minus 1 is going to stay the same. This is our final equation of our geometric sequence. A sub n is equal to 3 times 2 to the n minus 1. Here's how to use geometry to be mean to your friends. Okay, well, maybe that's not exactly what we're learning, but, close enough. So to find geometric means, you first need to know what a geometric sequence is. So if you don't already know what that is, then I recommend watching the video before this, which I have on the card on the screen right now, so you can learn what a geometric sequence is. But I'll also just quickly go over, remember that a geometric sequence is when you're multiplying something over and over. So to get from 3 to 6, we multiplied by 2, and then we multiplied by 2 again, and then we multiplied by 2 again. So as long as you keep multiplying by 2, this is a geometric sequence. Now, geometric means are basically the numbers in the middle. So for example, if we wanted to find the geometric means between 3 and 24, then those geometric means are 6 and 12. Now, this is based on how many geometric means you have. So this would be if the problem said find 2 geometric means. If it said find 4 geometric means, then you would need to find 4 numbers between 3 and 24, and those would be completely different numbers. So here's the problem that we'll be doing in this video. We need to find 3 geometric means between 2 and 512. So basically what this is saying is we have a 2 at the beginning of our sequence, and then we have a 512 at the end of our sequence, and we need to find the numbers that would be in between if there were 3 numbers in between. So there's a number here, 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 and then we get to 512. So we could just guess. We could be like, okay, what if they're multiplying by 2 each time? And then we're like, okay, 2, 4, 8. Oh, that doesn't reach 512. Okay, let's start over. Or we could solve this the more sophisticated way. And the sophisticated way to do this is by using the equation for a geometric sequence. So remember that the equation of a geometric sequence is always in this format. It's a sub n equals a sub 1 times r to the n minus 1. And just as a quick refresher, a sub whatever number always just means whatever term that is. So like, for example, a sub 3 would just mean the third number in the sequence, which means a sub 1 is the first number in the sequence. And then r is the number that we're multiplying by each time. So if we're constantly multiplying by 5, then r is going to be equal to 5. So we can just go ahead and plug in what we know. So for a sub n, we're going to put in the bigger number, the last number, because we're already going to be putting in the first number right here. So for a sub n, we're just going to put our big number, which is 512. And our goal of this, by the way, is we're trying to figure out what r is, because we can plug in everything else that we know, like we know what a sub n is, we know what a sub 1 is, and all we have to do is figure out what r is, because if we can figure out what we multiply by each time, we can just fill in all of the numbers. So a sub 1 is just the first number, which is 2. We don't know what r is. Remember, that's what we're trying to figure out. And then n minus 1. Well, remember that n is just whichever number we're on. So we just put in a sub 5, actually, because remember, we have 2, and then we have 3 numbers missing. And then we have 512. Because we have 3 numbers in the middle, 512 is the 5th number in our sequence. So this means that 512 is a sub 5. So we know that n is 5, because this is the 5th number. So 5 minus 1 is 4. So it's going to be r to the 4. And now we can just go ahead and solve this equation for r. So we have 2 here next to r, and it's being multiplied. So we can do the opposite of multiplication, which is division, and divide both sides by 2. So these cancel out. And on the right side, we just have r to the 4th. And on the left side here, we have 512 divided by 2. If you put this in your calculator, you're going to get 256. And now we just need to get rid of this power of 4. So the way that we do this is kind of like when we have like x squared. When you have x squared, to get rid of the squared, you do the opposite of squaring, which is square rooting to get rid of it, and then these cancel out. So when you have something to the power of 4, the opposite of the power of 4 is doing the fourth root. So we're going to go ahead and take the fourth root of both sides. So the fourth root and the fourth cancel out. And on the right, we just have r. And on the left, we have the fourth root of 256. So this is like, what number do you multiply 4 times to get 256? So you could write this out, or you could put it in a calculator. If you don't have like a fourth root button, then remember that taking a root is the same thing as like a fraction exponent. So doing the fourth root is the same thing as taking the number to the power of 1 over 4. And then a fifth root would be like 1 over 5. So if you put this in your calculator, you'll get 4, which means that r is equal to 4. So we've just learned that r is equal to 4. So we can use that to fill in our missing numbers. So remember that there are 3 missing numbers between 2 and 512. That's because there are 3 geometric means. And we know that we're multiplying by 4 each time. So 2 times 4 is 8. So our next number needs to be 8. Then we're multiplying by 4 again. So 8 times 4 is 32. And then we're multiplying by 4 again. So 32 times 4 is 128. And just to check your work, you can multiply by 4 one more time, and you should get 512. If you do, then you've done this correctly. So that means our 3 geometric means are 8, 32, and 128. Those are the 3 geometric means between 2 and 512. Now, there is actually one little special thing here. I want you to think about, what if r was -4? What if you were multiplying by -4 each time? So let's go ahead and see. If we multiplied by -4, then we would get 2 times 4 is 8, and 1 minus sign, so the minus sign stays. We multiply by -4 again, and we get 8 times 4 is 32. And we have a negative times a negative. 2 minuses make a positive, so it's positive 32. Then we multiply by -4 again. Then this gives you negative 128. And we multiply by -4 one more time, and this gives you 2 minuses make a positive, and we end up with positive 512 again. So this is actually another valid answer. -8, 32, and negative 128 can also be the geometric means. So what this means is r could have been +4 or -4. And this is actually because of when we took the fourth root. When you take the fourth root, what you're really doing is plus or minus fourth rooting. And this is only true if this number here is an even number. So if you're cube rooting, which is to the third, or if you're fifth rooting, which is another odd number, then it's actually not plus or minus. But yeah, these are your 2 possible answers for the 3 geometric means. What on earth is a logarithm? Well, I'm going to go ahead and explain what logs even are, how to solve them on pencil and paper, and then how you can solve any log on a calculator. So here's the first example in this video. We need to solve log base 2 of 8. That's how you read it. The small number is called the base, so you say it's log base 2 of 8. So what even is a log? Well, a logarithm is basically the opposite of an exponent. So what a log is asking for, or the answer to the log, is an exponent. And it's asking, what exponent do you need to put on the small number to get the big number? So in other words, if we were to use the letter x, for example, because we use that for numbers we don't know, basically what it's asking is, if you had the number 2, our small number, what exponent do you need to put here to end up getting 8? And if you ever had a problem that said you need to convert from logarithmic to exponential form or something, that's basically all that that's saying. It's saying that you turn the log into this format where you have x as an exponent. So how do we solve this now? Well, this one has simple enough numbers that we can probably just do it in our head, or like think about it logically. So if we're trying to figure out the exponent that we need to put on 2, an exponent is just how many times do you have to multiply. So we're going to keep multiplying by 2. So 2 times 2 is 4, times 2 is 8. So you have to multiply 2 3 times to get 8, which means that the exponent that needs to go here is 3. And that also means that the answer to our logarithm is 3. So that's all it's asking. It's, what exponent do you need to put on the small number to get the big number? All right, here's our second example. How would we solve this logarithm? We have log base 9 of 3. Well, first we're going to turn it into our exponent form like we did last time. So remember, it's asking, what exponent do you need to put on the small number to get the big number? So we're taking our small number, which is 9, and we're putting some exponent on it to end up with the big number, which is 3. So we just need to figure out what this exponent is right here. But this one's a little bit harder to just do in our heads because, I mean, you multiply 9 once, you're already bigger than 3, and it's just going to keep getting bigger. So to figure this one out, we're going to have to do a little bit of algebra. So first of all, remember that whenever you just have a number by itself and there's no exponent, that's the same thing as an exponent of 1, because anything to the power of 1 is itself. And the reason that we're imagining an exponent here is because we can solve this just like a normal exponential equation where we have x trapped inside of an exponent. So if you don't already know how to solve equations where x is inside of an exponent, then I do have a video on that you can watch on the card on the screen right now. So if you want, you can go watch that and then come back here. But just as a review, your goal to solve for x when it's in an exponent is to make both bases the same, to make the big numbers the same. So to do that, we can recognize that 9 is the same thing as 3 squared, because 3 times 3 is 9. So we're going to change 9 into 3 squared. And then we have a math rule that if you have an exponent inside of an exponent, then you can multiply the exponents together. So we had 3 to the 2 to the x. The 2 and the x get multiplied together, and you can't multiply a number and a letter, so it's just going to stay as 2x. And now both sides have the same base. And when both sides have the same base, you can just ignore the bases and set the exponents equal to each other. So we know that 2x is equal to 1. So now we can just solve for x. So we have 2 and x being multiplied. So to get rid of the 2, we need to do the opposite of multiplication, which is division, and divide both sides by 2. So the 2's cancel, and I'm running out of room here, but on the left side, we just have x, and on the right side, we have 1 over 2, which means that our final answer to our logarithm is 1 over 2. And if you wanted to test that in your calculator to make sure you did it right, remember that it's what exponent do you need to put on 9 to get 3. So you would just take 9, put it to the power of 1/2, and you should end up getting 3. So we were able to solve that one too using algebra, but the numbers were still lined up so that the answer could be exactly 1/2. But sometimes you're going to get logs like this, where it's base 7 of 20, and that's not going to give you a nice even number. So in these scenarios, you can actually use your calculator to solve any logarithm. Now, if you have a scientific calculator, you may have noticed that it actually has a log button on it. And you might think that that's just the easy way to solve any logarithm. But unfortunately, the log button actually only solves logs with a base of 10. It assumes that the small number in your logarithm is 10. And depending on your calculator, it might even say log base 10 on the button. I know that iPhone calculators do that. It says log 10. So like if you wanted to solve log base 10 of 20, all you have to do is just put log of 20, or sometimes on some calculators you have to put the number 20 and then press the log button. But even though the log button only solves logs with base 10, you can still solve any logarithm with the log button. So all you have to do is assume that this log is base 10. So we have log base 10 of 20, so I'm just going to put the log of 20. But if your base is not 10, then what you have to do is take whatever you get and divide it by the log of the small number. So we have log of 20, and then we're dividing it by log of 7. And if you put this in your calculator, you should get about 1.54. So this would be your answer for log base 7 of 20. And if you wanted to check your work, you can just take 7 and put it to the power of 1.54, and it should give you an answer that's close to 20. It won't be exact because we're rounding, but it should be really close. Here's how to graph any logarithmic function. So here's the first example that we'll be doing. We need to graph f of x equals log base 4 of x. So if you don't quite know what a logarithm is yet, then I do have a video on it that you can watch on the card on the screen right now. But I'll also quickly go over it here. Remember that a log is basically just the opposite of an exponent. What it's asking is what exponent do you need to put on the small number to get the big number? So because that would be if we're solving a logarithm, then that means our answer is actually f of x. So that's basically acting as our exponent. So f of x, or in this case, we could also call that y, is the exponent that you have to put on 4 to get x. So if we were to write this as an exponential equation, this is what it would look like. And as always, remember that up and down is y and left and right is x. So to graph anything, you can always just plug in numbers into x, see what you get out for y, and put them on the graph. So for example, if you put in 2 and then got out 3, then you would go 2 to the right because x is to the right, and then 3 upward because y is up, and then plot a point here, and then you would connect them up with a line. But just putting in any numbers all willy-nilly isn't going to be that useful because, like, for example, if you were to put in 3 for x, well, how are you supposed to know what exponent to put on 4 to get 3 without doing some calculator shenanigans? Well, with logarithms, there's actually a really nice trick that you can use to know what points that you should put in every single time. So here are the 3 points that you should always put in to graph a logarithmic equation. So first of all, you need to know what our base is. Our base is 4. So you should always plug in the base, you should always plug in 1, and you should always plug in 1 over the base. So in that case, that would be 1 over 4. And there's a reason for that, and I'll show you why. So first of all, let's go ahead and plug in 4 first, because I think it'll be the easiest to understand. So if we're plugging in the point 4 for x, remember that in parentheses it goes x, then y. So we need to figure out what number we're getting for y. Well, if we were to plug in 4 for x, then what that's saying is, what exponent do you have to put on 4 to get 4? Well, anything to the power of 1 is itself. So that means we would need to put an exponent of 1 here, because 4 to the 1 is 4. So when we plug in 4 for x, we get out 1 for y. So we can now plot this on our graph. So 4 for x, that means we need to go 4 squares to the right, and then 1 for y, which means we need to go 1 square upward. And we will plot a point right here. So the second point that you should always plug into a logarithm is 1. And the reason for that is very simple. If we plugged in 1 for x, then what exponent do we have to put? Well, anything to the power of 0 is 1. So literally, no matter what number we have here for our base, then when you plug in 1, you will always get 0, because anything to the power of 0 is 1, which means our second point that we'll be plotting is 1, 0. So we go 1 to the right and 0 up or down. So our point is going to be right here. And now the third point that you should always plot is 1 over 4. So we're going to plug in 1 over 4 for x. Now, why are we plugging in 1 over 4? Well, there's another exponent rule that we can use here to make this really easy. Remember that anything to the power of 1 is itself, but also remember that a negative exponent flips the fraction around. So for example, if you had 3 over 2, and you put it to the power of negative 1, then you just flip the fraction. It becomes 2 over 3. So if we start with 4 over 1, because remember anything that's just a number, it's over 1. If we put it to the power of negative 1, then we just flip the fraction around and it becomes 1 over 4. So when we plug in 1 over 4 for x, we get negative 1 for y, because our exponent here is negative 1. So if we were to graph this, we would have to go x is 1 over 4, so we're just going a fourth of a box to the right, so not that much. And then we're going 1 down, because we have negative 1 for y. So 1 square downward, and we get a point right here. So really, that's all we need to graph it. You'll see that we have a curved line here. So the important thing to know for logarithms is that you're never going to go past this line. You're never going to touch this line. So it's just going to stay right like rubbing up against this line, and then it's going to go like this off into the distance. So there you go. This is the final graph of f of x equals log base 4 of x. All right, so here's our second example. We need to graph this logarithm, but what do we do if the base is a fraction? Well, we're going to do it the same way, but the points might end up looking a little bit different. You'll see. So first of all, we need to write this like our exponential equation. We just need to know what a logarithm is. Remember that it's asking what exponent do you need to put on the small number to get the big number. So we're taking our small number, and then we're putting some exponent, and remember that's f of x or y. F of x and y are like the same thing. And when we put this exponent on the small number, we get the big number, which is x. So now we need to know what 3 points we're supposed to plot, our little magic 3 points. So remember, we always plot our base, which is 1 over 3. We always plot 1, and then we plot 1 over our base, which in this case is actually 1 over 3. Now, whenever you have 1 over a fraction, it just flips the fraction around. So that means that this would be 3 over 1, or just 3. So let's just go ahead and plug in these for x and see what we get. So remember, when we plug in 1 over 3 for x, whenever you put something to the power of 1, it stays the same. 1 over 3 to the power of 1 is staying as 1 over 3. So our first point is going to be 1 over 3, 1. And if we were to plot that, we have 1 over 3 for x, so we're only going a third of a box to the right, and then we're going 1 box upward, so right here. Next, let's plug in 1 for x. remember that anything to the power of 0 is 1. So 1, 0 is going to be our next point. This is always going to be a point. So we go 1 square to the right because it's 1 for x, and then 0 for y. So we're not going up or down. And that means we're going to have a point right here, like always. And then finally, we plug in 3 for x. And remember that this is actually the same as 3 over 1. And we flip the fraction around. And the way you flip a fraction around with an exponent is by putting it to the power of -1. So that means that our last point is going to be 3 for x. And then when we put in 3 for x, we get -1 for y. So we have to go 3 squares to the right, and then we have to go 1 square downward. So it's going to be right here. So our difference from last time is because last time when we graphed it, it was going infinitely downward this way, and then it went upward, and then eventually went infinitely to the right. But this time, instead of coming from the bottom, we're coming from the top. So it's going to stay infinitely close to 0 at the top, and then it's going to keep sloping downward like this until we go infinitely to the right, just like last time. So this is our horribly drawn graph of log base 1 over 3 of x. So now you know how to graph just a basic logarithmic equation where you have log base something of x. But what if you have these extra things attached to it? Well, these are called transformations, where we basically have what we were graphing earlier, which is just a basic log base something of x. And then we have these extra things added on that are going to do something to the graph. So these transformation things are done with like basically every type of graph, with parabolas, with exponential graphs, with square root graphs. So I have a full video on transformations if you want to watch that to see all the different things that can change a graph. But I'll just go over here how to use them with a log equation. So basically the point of transformations is that it would take a long time to keep plugging in numbers for x and then see what you get for y when the equation's more complicated. So instead, what we can do is we can just figure out what our parent graph is. So our parent graph is just the basic equation. In this case, our basic equation is log base 4 of x, because that's the kind of graph we were doing before. So our parent graph is f of x is equal to log base 4 of x. So we're going to take our parent graph, we're going to graph it on our graph like we did before. And then we just need to figure out what this 2 is doing and what this plus 1 is doing to the graph, and then just make those changes. So I'm going to graph log base 4 of x just the same way we did before. So if you don't quite remember how to do that, you can go back to the beginning of this video. So now our goal is to just figure out what the 2 is doing and what the plus 1 is doing. So I'm going to show you what the plus 1 is doing first because that'll be easier. So whenever you're adding on a plus or minus number at the end of the graph, what you're really doing is just taking what you got for y, or f of x, and then adding 1. So when you add 1 to y, remember y is up and down, so you're just moving the whole graph up by adding numbers, or you'd be moving it down by subtracting numbers. And if you watch the transformations video, you'll see that there is a difference if there were parentheses around here. If there's parentheses, you'll move left and right. And so if it was positive, you would move to the left. And if it was negative, you move to the right. But in this case, we're moving up. So what you would do is you would take each of these points and move them up 1. So you would take this point and move it up here. You would take this point and move it up here. You would also take this point and move it up here. And then you would just redraw your graph. So there we go. We've now increased everything by 1. So the graph has been moved up 1 square. And now we can figure out what our 2 is doing. So this just says 2 log. There's no sign in between the 2 and the log. And remember that when there's no sign and things are next to each other, that means multiplication. So we're taking what we got and we're multiplying it by 2. So basically the way that we do this is we multiply everything how high up it is by 2. And for how high up it is, we're actually going to be using this right here as like our floor, because that's where it was originally before we moved it up. So this point here that's already on the floor, that's just going to stay the same because it's 0 spaces up and 0 times 2 is 0. But this point here is going to change because it's 1 square above the floor, as we're calling it. And when you are multiplying it by 2, 1 times 2 is 2. So this little point here was 1 square above the floor. Now it's going to be 2 squares above the floor. Now remember that this point was staying the same. And then we have this point here. This one, it was 1 square below. So now it's going to be 2 squares below. And so we're going to put a point right here. So we're just going to take all of these black points that I've drawn here and we're going to connect them up. So I know this is looking a little complicated, but remember that the green part was just our parent graph that we started with, and the purple was just us doing our work in the middle. So everything except for this black line we can actually erase. And there you go. This is the final graph of f of x equals 2 times log base 4 of x plus 1. There's one other transformation I didn't talk about in this video, but it's in the transformations video if you want to watch that. It's if you have a negative sign in front of the number you're multiplying by. In that case, you would just go ahead and flip everything upside down. Here's how to add logarithms, subtract logarithms, and what to do if you have an exponent inside of a logarithm. So let's go over the first property of logarithms, which is what you do when you're adding logarithms together. So for these first two properties, it's really important to know that these bases need to be the same for this to work. So if you're adding a log base 5 of something with a log base 7 of something, then you can't do this. Now, the rule is that when you're adding two logarithms with the same base, the same small number, then what you can do is you can combine them into one log with the same small number, and you multiply the big numbers together. So in this case, 4 times 9 is 36. So just remember that when you're adding logs, you multiply the insides. Now this was kind of hard to solve before because log base 6 of 4 and 6 of 9, those are going to give you completely random numbers if you put them in a calculator. But now that we've combined them, we see we have log base 6 of 36. Now if you don't exactly remember what a logarithm is, I do have a video on that you can watch on the card on the screen right now. But just remember that a log is the opposite of an exponent. It's what exponent do you need to put on the small number to get the big number. So in this case, we would need to put an exponent of 2 on a 6 because 6 squared makes 36. So that means that our logarithm is equal to 2. And 2 is our final answer. So all of these properties that I'm going to show you also work the other way around. So we can combine two logs into one log by using that property. But we can also split up one log into two different ones. So we could solve this by multiplying 16 times 8 and then finding log base 2 of whatever big number we get. But that might be kind of hard. So instead, we can see that because these are being multiplied together, we can just do the opposite of the rule we just did. Remember that you multiply the insides when you add two logs. So we can split this up into log base 2 of 16 plus the log base 2 of 8. And remember that these logs are not being multiplied with each other, they're being added, because when you add two logs, you multiply what's inside. And now these are simpler logs that we can solve on our own. So what exponent do you need to put on 2 to get 16? Well, you need to put an exponent of 4, because 2 to the power of 4 is 16. So this log right here is equal to 4. And now this log over here, log base 2 of 8, well, you have to put an exponent of 3 on 2 to get 8, because 2 times 2 times 2 is 8. So this log is equal to 3. And if we just add these together, we get 4 plus 3, which is equal to 7. So this log right here is equal to 7. So that's what you do when you need to add logs together. When you add logs, you multiply the insides. But what do we do when we're subtracting logs? Well, as long as both bases are the same, just like before, we can do a different special rule. When we're subtracting logs, we can divide what's inside. So when you add, you multiply the insides, and when you subtract, you divide the insides. So we can combine this into one log with the same small number, which is 3. And on the inside, we're going to divide 243 divided by 81. And if you put this in your calculator, you'll get 3. So we've combined these two logs into one log, which is log base 3 of 3. So now to solve this, we just need to ask ourselves the question. What number or what exponent do we need to put on the small number to get the big number? Well, if we have 3 and we want to turn it into 3, well, we just need to put an exponent of 1, because anything to the power of 1 is itself. So that means that our log here is equal to 1, because that's the exponent that you have to put on it. So the answer to this problem is 1. And just like before, you can do this the other way, where if you have one log, you can split it up into two different logs. So you could turn log base 3 of 3 into this if you wanted to. All right, our final log property has to do with this exponent here. So if you wanted to solve this log normally, you could put in your calculator 16 to the power of 5. That's going to give you some huge number. And then you have to figure out what exponent needs to go on 4 to get the huge number. And that would be kind of hard. But we have one more power rule that we can use for logs. So this power rule says that if you have an exponent on the inside of your log, then you can take it out and move it to the front. So we can take out this 5 and move it right here in front. And remember that when you have a number and some letters next to each other, that means they're being multiplied. So this log used to be log base 4 of 16 to the 5th, but now that we move the number out to the front, it is now 5 times log base 4 of 16. And log base 4 of 16 is a much simpler log that we can solve on our own. So what is the answer to this log here? Well, it's what exponent you have to put on the small number to get the big number. Well, to turn 4 into 16, you have to put an exponent of 2, because 4 times 4 is 16. So that means that this log is equal to 2. But remember that we're also multiplying it by 5, and 5 times 2 is 10, which means that this complicated log up here is equal to 10. And as always, you can do this the opposite way as well. So if you had a number in front of a log, you could move it back up as an exponent if you wanted to. Have you ever wondered what that ln button on your calculator does? Well, I'm going to show you now. So you don't have to wonder anymore. So what is a natural logarithm? Well, this ln thing means a natural logarithm. I don't know why the n comes after the L. I don't know. Okay, I just looked it up, and apparently the number one result says that nobody knows what ln is supposed to mean. Well, that's helpful. So a natural logarithm basically works exactly the same as a regular logarithm. So if you don't know what regular logarithms are, I do have a video on that you can watch on the card on the screen. So if you want, you can watch that and then come back here. So a natural logarithm is basically just a regular logarithm, except that it has a certain base, and that is base e. So what on earth is the letter e? Well, normally in math, when you have a letter, that means that you don't know what the number is. But this is actually not one of those cases. We do know exactly what e is. E works basically the same way as pi. Whenever you see pi, you know that it's equal to a specific number. It's equal to 3.14159 and so on. E is another one of those weird random numbers. E is about 2.71828, and it just goes on infinitely in infinite digits. People use E in math for the growth of populations or things like that, or at least that's according to what I just Googled. But yeah, it's not important. All you need to know is that ln is the same thing as log base e. So whenever you see ln, just translate that in your mind, or you can write it down. It's the same thing as log base e. So now that we know this, let's go ahead and do our problem, which in this case is just to turn this into exponential form. So remember that the definition of a log is just what exponent do you have to put on the small number to get the big number. So let's go ahead and write that out as an equation. It's saying what exponent do we have to put on e? We have to put some exponent here, and then we're going to end up with the big number, which is 8. And in this case, it's saying that the solution, the answer to our log is x. So the exponent that we have to put on e is x, and then that gives us 8. So if you think about it logically just like that, what a log even is, then that's how you turn it into exponential form. So ln of 8 equals x is the same thing as e to the x is equal to 8. Now we can actually do this the other way as well. We can take our exponential equation and turn it into a logarithmic one. So remember that because we have e as our base here, this is going to be our small number. That means we can write it as log base e, and this will eventually turn into ln. So it's what exponent do we have to put on the small number to get the big number? And in this case, the big number is going to be y, because that's what we have here. We have y. We don't have a number here. And the answer to the log is always the exponent that you have to put on it. And in this case, the exponent is 5. So what this is saying is you have to put an exponent of 5 on our small number e to get the big number y. So e to the 5th equals y is the same thing as log base e of y is equal to 5. Now in my last video, I talked about properties of logarithms. So if you haven't watched that, you can watch that as well. But you can actually do the same thing with natural logs because they're just the same thing as normal logs, just with base e. Remember that properties of logs you can only do, like combining logs, for example, if they're the same base. But every single ln is the same base because they're all base e. So we can do these same properties with this, and our goal here is going to be to simplify this down as much as possible. Now eventually I want to add these two logs together because if you add logs you multiply the insides, but we can't actually do that right now because we have this 2 in the way, and this 2 is being multiplied because there's no sign. But if you remember back from the power rule, we can actually do this. So let's say we had log base 3 of 5 to the 2, for example. If you have an exponent inside of the log, then you can move the exponent out to the front of the log, and it becomes 2 times this, and we get rid of the exponent. But this actually works the other way as well. If we have a number out on the front, we can move it back as an exponent. So instead of 2 ln of 4, we can turn this into ln of 4 to the power of 2. And we can actually simplify this again. 4 to the power of 2, well, that's 4 squared. And 4 times 4 is 16. So this turns into ln of 16. And now we just have 2 ln's, or log base e's, that we can add together. Now remember that when you have 2 logs and you're adding them, then that means you multiply what's on the inside of the logs. So we can combine these into one log, one ln, but we multiply the insides. So 16 times 3 is 48. And that's as much as we can really simplify it, so this is our final answer. Or if you wanted, you could put this into your calculator, but it's going to give you like a super random number. Looks like the natural log of 48 is 3.87, about that much. So this could be your answer as well. It's time to combine all of the logarithmic knowledge that you've been gaining and use it to solve log equations where you have x inside of a logarithm. So here's the first example that we'll be doing. We have log base 4 of x is equal to 2, and we need to solve for x, but it's trapped inside of this log. So just in case there's a little confusion, no, this is not multiplication. You can't just divide both sides by log 4. This isn't log base 4 times x, this is log base 4 of x. So if you don't quite remember what a logarithm is, then I have a full video on it that you can watch on the card on the screen right now. So if you want, you can go there and then come back here. But to solve this, I think it'll be easier if we turn this into exponential form, which basically is just writing down what the log means. So remember that a log is what number or what exponent do you need to put on the small number to get the big number. So what this is saying is if you have the small number, then you need to put an exponent of 2, which is the answer to our log, to get our big number, which in this case is x. And now that we've written it in exponential form, it'll be a lot easier to solve. So let's just go ahead and simplify this. We have 4 squared. 4 squared just means 4 times 4, which is 16. And that's actually all we need to do. We've already solved for x. X is equal to 16. So here's another example. This one, we have a log on both sides of the equation. And I know that this looks a little bit scary, but this one might actually be even easier than the first one we just did. So this is pretty similar to if you've ever done exponential equations. Like, for example, let's say you had 3 to the x is equal to 3 to the 5. Well, when you have x trapped in an exponent, then you can just ignore the bases and then just set the exponents equal to each other. Because if you have the same base, you know that the exponents are also going to be the same, because you can't have like 3 to the 4 equals 3 to the 5th. That doesn't even make sense. So with logs, it's actually exactly the same. We have 2 logs with the same base. That's important. They need to have the same small number. And if we have 2 logs with the same small number, then the big numbers, the parts on the inside, should also be the same, or else they're not going to be the same numbers at all, because log base 3 of 8 is not going to be the same as log base 3 of 9. So we can literally just ignore the log parts and just set the insides equal to each other, because we know that they have to be the same. So x plus 2 is equal to 7, and now we can just solve for x. So to get x by itself, we have a plus 2 in the way, so we need to do the opposite of plus 2, which is minus 2 to both sides. So these cancel out, and on the left side we just have x, and on the right side we have 7 minus 2, which is 5. So our final answer is x is equal to 5. Now here's a little bit of a harder one. I know this one looks even scarier than the last one because we have 3 logs going on, but we're actually going to combine all the things we did before, and we're also going to use properties of logarithms. So properties of logarithms is basically how we combine different logarithms, and I do have a full video on that as well. So if you're not sure how to do that, you can watch the video on the card. But basically, we're going to be using 2 different properties here. So one of the properties that we can use is called the power rule, or the power property, or I don't even know if it has a name. But basically, that power property says that if you have a power, an exponent, inside of a log, then you can get rid of it and move it to the front. So we had a power of 3, we now moved it to the front, and we have 3 times log base 2 of 8. But this actually works the other way as well. If we have a number in front of a log, we can move it to where an exponent would be inside of the log. So this is going to become, without the 3 now, log base 2 of 2 to the 3. And 2 to the 3 is 2 times 2 times 2. 2 times 2 is 4, times 2 is 8. So this is going to become log base 2 of 8, and everything else is going to stay the same. Now you might be wondering why we just randomly decided to do that. And the reason for that is because now we can combine these two logs here. Our eventual goal is to get to where we had before, where we had just one log on both sides, and then we can just ignore the logs. But to turn these two logs into one log, we need to combine them. And we couldn't combine them unless we got rid of this 3. This 3 is stopping us from combining these two logs. But now that all we have is log base 2 plus log base 2, we can combine them into one log. So this is another property. I think this is the first one I went over in that video. It's the product property, or whatever you want to call it. Basically, if you're adding two logs together, and it's important that the small numbers are the same. When the two small numbers are the same and you're adding two logs, then you multiply what's inside of them. So we're going to combine this into one log base 2. But on the inside, we're multiplying 8 and x plus 1. So let's go ahead and do that off to the side. So we're multiplying 8 times x plus 1. And this might look a little bit familiar to you. To do this over here, we need to use the distributive property. Because we have a number in front of parentheses, we need to multiply the 8 out to both parts of the parentheses. So 8 times x, you can't multiply a number and a letter, so it's just going to stay as 8x. And then that's going to be plus 8 times 1, which is 8. So log base 2 of 8 plus log base 2 of x plus 1 are going to combine and become log base 2 of 8x plus 8. And that's going to be equal to log base 2 of 5, just like what we have over here. So we've successfully whittled this down into one log on each side of the equation. And because they have the same base, that makes it even better. Because whenever we have two logs of the same base just on either side of the equation, and that's all we have, then the insides must also be equal to each other. So we can just ignore the logs and set the insides equal. So 8x plus 8 is going to be equal to 5. And now we can just solve for x like normal. So I'm going to get rid of this plus 8 first before we get rid of this 8 because it's less attached to x. So we have plus, we need to do the opposite, which is minus, and subtract 8 from both sides. So these cancel out. And on the left side, we just have 8x. And on the right side, we have 5 minus 8. Think of it as dollars. You got $5 and then lost 8, so you're down 3. So minus 3. And now I'm running out of room here, but basically this is multiplication. So we need to do the opposite of multiplication, which is division, and divide both sides by 8. So these cancel out. And I'll move this over here. On the left side, we have x. And on the right side, we have negative 3 over 8. You can't simplify that fraction, so we're just going to leave it as negative 3 over 8. And there we go. We've got an x by itself, so this is the answer to our equation. So that was every single algebra lesson. If you're at this point in algebra, then it seems like the last thing you have to do is to ace your final exam. So if you're ready to start studying for that, then you can watch this video right here. If you have any questions about literally anything in this video, go ahead and leave a comment down below, and I'll be sure to answer your question. Thanks for watching.